actually hear you, but it's okay. All right. We are back. What is my life? 6927. You are the first. Congratulations. What dog? What's up, dog? You're the second, I think. All right, remember to, on the Discord, on the Tumblr, let people know good to go to /watch. We'll bring everyone back. We're doing this together. It's great. Taiwai. Hello. We are back. Hey. I've got my cup of tea. I am getting caffeinated. And you are here at 7 a.m. Eastern time, not 7 a.m. in other places. I'm not going to do math this time of morning. Empress Arianna, good morning. Tyree, welcome back. Welcome back, everyone. All right. We're starting to get the crowd back in. I love this. I love this. And yes, so we have another great speaker. Who's gonna kick off this next round of the live stream. Oh, my little lantern just died. Oh no, it's okay. So our next speaker is Dr. Jacquelyn Veatch. So Jacquelyn is an early career ocean scientist who specializes in polar climates. Welcome, Jacquelyn.
Awesome.
And she's going to be talking about the West Antarctic Peninsula. So take it away.
Great. Thank you so much, Andrew. And it's awesome to be here tuning into all of these great talks. We just finished an awesome talk on vegetation. And right now I'm going to be taking you to a place with very little vegetation, just a taste of the wide breadth of science we'll be talking about in the live stream. Super cool. So today I'll be talking about the Western Antarctic Peninsula, and specifically about how this region has been transitioning from a polar to a subpolar climate. This title slide picture I'm showing here was taken at Rothera, which is the British research base on the peninsula, where in a very rare sunny day, we saw a group of seals sunbathing on an ice floe. It is not usually this sunny in Antarctica, but when it is, you gotta snap a picture because it is beautiful to see. Oh, my video was working earlier. It might not be working now. That's okay. We are traveling to the vast continent of Antarctica for this talk. It is the continent on the bottom of the globe. And this is a place that undergoes a huge seasonal change every year, where the sea ice extends far offshore and then shrinks in the summer. And this large seasonal change is what sets the backdrop to the ecology that lives on this continent. Now, this most vast wilderness in the world is actually home to a lot of different creatures, especially on the coasts, in the marine creatures, and especially on the Western Antarctic Peninsula, which is where my mouse is circling right here. This arm of the Antarctic is just south of South America. So this is the tip of South America here. The stretch of ocean, we call it the Drake's Passage, and then the Antarctic Peninsula is this white arm right here. Now, as the sea ice undergoes these large changes over 1 year, expanding in the winter and contracting in the summer. There has also been a large loss in sea ice due to rising temperatures, especially on the peninsula, where it is warming faster than the global average. So here is a zoomed in map of that arm of ice I was pointing to earlier, the Antarctic Peninsula, and below that ice is pieces of continent, which is shown here in the gray in this map I have. And again, the Antarctic Peninsula is a rapidly warming ecosystem. It still hosts a large variety of life, which is detailed in this graphic here on the right. At the start of that food web are phytoplankton, like many ocean ecosystems. These are small photosynthetic plants that drift in the water. Next up on the food chain are krill, which are these small shrimp-like creatures. I'm circling my mouse here. And then these krill are the main food source for lots of different marine creatures such as whales, seals, and penguins, as well as seabirds of flight. And the context at which this ecosystem lives is quite harsh. The winters here are very cold with very high winds, lots of storms coming in, and the ocean is covered by sea ice for parts of the year. So the life that lives in Antarctica is specifically adapted to these environmental cues and these environmental conditions. And so it is important when we study what lives in Antarctica, how they relate to their natural surroundings, such as ocean movements, is very important to contextualize how they are able to live in such an extreme climate. And we do this by heading down to the Antarctic and in deploying our ocean observing systems. As a US scientist, I do most of my work out of Palmer Station. Palmer Station is the US research base on the Antarctic Peninsula, and the picture shown here is the entire station. It is not very large. At the capacity, it can hold 40 people, and that includes scientists as well as support staff such as carpenters, electricians, doctors, cooks, marine technicians that all support the research science that happens out of this station. Now, it is a long way to get down to Palmer Station. To arrive at Palmer, your journey begins in Punta Arenas, Chile, where you board a research vessel. Here I'm showing the Lawrence M. Gould, which has been the research platform I have worked off the most. Aboard this research vessel, you then cross the Drake's Passage, which is the piece of ocean I pointed out earlier. And this is a notoriously rough patch of ocean. After 2 or 3 days of pretty high seas, the research vessel arrives at the Antarctic Peninsula, and then a few days later, steaming down the peninsula, the research vessel arrives at Palmer Station. And upon arrival at Palmer Station, scientists are greeted by a host of marine animals and marine life, especially in the summer. Here's a picture I took of a humpback whale and her calf. There are also several species of penguins that nest near Palmer Station. Here I'm showing a Gen 2 penguin in the upper right, a chinstrap penguin on the lower right, which you might be able to guess where it gets its name from. And then to the left of the chinstrap penguin are some Adelie fledglings that are very fuzzy and cute. Also on the peninsula, we see the Antarctic krill. These are 2 different species of Antarctic krill that I pointed out in the graphic a few slides ago. And these are what we call a keystone species. So they're a very crucial step of the food chain that transfers energy from photosynthetic organisms like phytoplankton up to larger creatures like penguins and whales that feed on the krill as their main source of prey. And if you have a microscope, you may also be greeted by some creepy crawly looking phytoplankton and other microscopic organisms that live in the ocean. Now, I mentioned that Palmer Station is right near a persistent penguin rookery or persistent penguin nest. And the hypothesis is that these persistent penguin rookeries are co-located with submarine canyons, not by happenstance. So Palmer Station is right next to Palmer Deep Canyon, which we think has influenced the local oceanography in order to supply a consistent amount of food to that region. So here's another map of the Western Antarctic Peninsula. So we're on the western coast of the Antarctic Peninsula. In Oscar Schofield's paper. And the red boxes show places where we have concurrent measurements of the oceanography and also penguin rookeries, or how many penguin nests are in the area. And these penguin nests seem to co-locate with deep submarine canyons, so very deep trenches in the ocean floor. And we don't think this is a coincidence. So Palmer Station is shown up here on the map where my mouse is circling, where we have a deep submarine canyon and a persistent penguin rookery or penguin nest. And so on the backdrop of these penguin rookeries is a warming climate and warming peninsula. So the two most populated penguin species in the area are the gentoo penguin and the Adelie penguin. Now, as the peninsula warms, it shifts from what we would consider a polar climate to a subpolar climate. Now, the gentoo penguin are adapted to these subpolar climates. They are historically found pretty much north of Palmer Station, whereas the Adelie penguin is a polar species, meaning it's adapted to what we would consider a polar environment. And they have been at Palmer Station for as long as our records can show. So the shift from polar to subpolar climates, especially at Palmer Station, has been shown in the shift of distributions from Adelie to gentoo penguins. So as the Adelie population seems to decline, the gentoo population seems to be expanding in the area. So this is showing the direct link between the ecology in the area and the environment. Now, down at Palmer Station, we have an opportunity to take a lot of ocean observing data around these penguin rookeries, these penguin nests. And so that is where a lot of my work comes in. Shown here is a very picturesque view of a submersible called a glider. And we can use ocean observing instruments and marine technology such as the glider and some radars I'll talk about later to understand what the physical oceanography, or the motion of the ocean, if you will, in the area, to really map penguin behavior onto their dynamic ocean environment. So I'm a radar nerd, so I'm going to be talking about radars today. And specifically can I say my favorite? Yeah, I'm going to say my favorite ocean observing instrument, which is the high frequency radar. So these high frequency radars are a wonderful feat of engineering in that we can take them apart and ship them down to the Antarctic and put them back together in about 5 days is our record of building one of these radars. So this picture on the right here shows the radar. And then here to the left is the remote power module, which supplies power and computer space to the radar that takes its measurements. Here is a picture of a radar in several feet of snow and ice with the remote power module in the background. And so again, this radar is no easy feat to build, but we can do it with the platforms provided by the U.S. Antarctic Program, which is funded by the National Science Foundation. And so here on the left, you see a crane lifting pieces of equipment onto this small black boat, which is a Zodiac. The Zodiac then ferries this equipment to the island where scientists and other so scientists are waiting for the boat to come. We then lift all that equipment onto the island and organize them into these piles, and then that's me in the middle carrying some poles. So, and then we hand carry the poles to where we build the radar station. And it's takes a lot of time, but it's a lot of fun. I think it's a lot of fun to do, to be on these really remote places. Here is a finished product. So the radar is in the background and the remote power module is in the foreground. And why would you build an entire radar in the Antarctic? Well, it's because we get data like these. So when we have multiple radars in the area, we can use the radio waves collected from the radar to map which way the ocean currents are moving. And this here is what I would call a vector map of the currents. So this is the surface current velocity in the area around Palmer Deep Canyon. And what this does is it tells us the magnitude and direction of the ocean flow, much like you might see a weather map from your daily weather channel that shows the velocity of winds. This is the velocity of the ocean currents. And so the hypothesis here is that these ocean currents are aggregating the prey that penguins are relying on. So they're pushing together those krill into these patches where penguins can reliably find them. To test this hypothesis, in that observed surface current velocities, I've released thousands of virtual particles. So this is something that I do in my computer code with that observed data. And you can see those particles that are kind of coming together in these clouds, these large black clouds. That is an area where the ocean is aggregating or pushing things together. And those red dots in the video there are foraging penguins. And you might be able to see, if you watch this video as much as I've had, that those foraging penguins seem to be targeting these particle clouds or these places where the ocean is pushing their prey together. So we have these foraging locations by tagging penguins here. So this is an Adelie penguin with a tag on this, and this is all done. It's heavily guidelined to make sure that there's no harm to the penguins. But what this suggests is that the penguins are actually using the local oceanography to forage more efficiently. So there, again, this really tight connection between the ocean environment and the penguin. In conclusion, the Western Antarctic Peninsula is warming rapidly, catalyzing change from the environment up through the food web. Penguin populations are moving farther south, with subpolar gentoo populations growing, where Adelie populations are shrinking. And lastly, penguin foraging behavior is closely tied to the coastal currents and canyon regions, indicating this tight biological physical coupling. Now, this research is very important in that it is, we're kind of at the front lines of climate change here, where we see rapid ice decline. And all of this research is made possible by the research vessels from the U.S. Antarctic program. Currently, we have the U.S. Antarctic program has recently decommissioned both of its research vessels. And so this is making this monitoring project harder to continue. But lastly, I would like to thank all of my collaborators, and I'll take any questions.
That was amazing. Thank you, Jacquelyn. It also looks like what an amazing crew you guys have. I love it. A human pyramid in Antarctica. Is which part of the pyramid are you in? Are you in the photo?
Oh, I'm the top of this one. Yeah.
Oh, nice. Okay.
Look like I'm about to fall.
Yeah. Yeah, you look scared.
Yeah, well, you got to make your own fun when you're down there. There's no, arcade or movie theater to go to. So
that's, I mean, yeah, I don't imagine that there's like a Five Guys or anything either. No. Okay, we got some quick fire questions. Silly question: what is your favorite penguin species?
My favorite is the Adelie, and it's because they're one of the smallest, so they're very cute and are also very curious creatures.
Oh, they do look so cute. Another quick fire from what dog? How many radars are you putting up, or did you put up?
3. Good question. Yeah, 3. So we need the radars to overlap in the area that they measure, because they only get a radial component, so like a forward and backwards. But if we have 2 or 3, even better, 3 radial components, we can use some vector calculus to make them into a current map, so like magnitude and direction. But we had 3 up there. Mm-hmm.
And so all those penguin, like, so that like swarm of penguin of like black dots and then the penguin dots and stuff, you're getting all of that from the radar, basically?
Yeah, we're getting the surface currents that are moving those black dots from the radars, mm-hmm. and then we're getting the penguin locations from the GPS tag that is glued to their back.
Does that hurt? That doesn't hurt them, penguins? No. Okay, good. Because there's a lot of penguin love in the chat. I'd hate for you to be doing
a lot of penguin love here too. Mm-hmm.
Let me see. So here's a quick one. Are penguin predators following the krill that you're seeing?
Yeah, good question. So each step we go up the food web, the connection between the krill and the predator gets a little bit more muddled. But so the penguin predators would be the leopard seals in the area, and they are definitely adapted to the penguin behavior, and they know kind of when to catch the penguin. But the connection between the leopard seal and the krill is a little more hard to determine, because you're missing that step of the penguin. So that's a long way of saying a little bit, but yeah, the predator is attuned to the penguin foraging strategies.
Mm-hmm. Yeah. There's something here as well. So I don't know what the ocean conveyor is. You can maybe explain that to me as well. But how does the ocean conveyor play into food source accumulation?
Yeah, so the ocean conveyor is the large overturning circulation, like in the global ocean. So we have water that's in the pole, gets cold and is subducted, and then travels along. Some gets upwelled in the equator, and some gets upwelled down on the coast of Antarctica, where it is then in contact with the atmosphere again, gets cold, becomes more dense, and sinks. So it's this large, like, overturning globally from pole to pole. And how that affects the supply of food? Well, so when we have water that is upwelled on the coast of Antarctica, that water has a lot of nutrients in it because a lot of respiration has happened. So while it's underwater, it's basically accumulating nutrients. And so when that water upwells on the coast of Antarctica, it has all of these yummy nutrients in it. And so the phytoplankton love that. And so when we have this upwelling event, the phytoplankton will start to bloom. And when the phytoplankton are growing a lot, then the krill come in and they feed on the phytoplankton that is feeding on the nutrients. And then the predators that are eating the krill come in and feed on the krill. So it is the upwelling of nutrient-rich deep water kind of jumpstarts the food web in that way. And so these coastal areas where there might be these upwelling events are areas, or what we call a biological hotspot, partially because of ocean currents, but also this mechanism that of the ocean conveyor belt where we have upwelling of nutrient-rich deep water.
That's awesome, because it's, just, I don't know. I feel like it's crazy that, like, the conveyor belt feels like a physical thing that's just like math and water moving around and stuff, but then it kickstarts the tiny little critters who feed the bigger critters and everything. It's crazy.
Yeah, and I'm a physics nerd by training. I'm a physical oceanographer is what my degree says. But I've been my current research is working on these biophysical coupling, which is really cool to contextualize the physical movements of the ocean and explain why it's so important to understand the physical environment.
One final thing before you go. This has been so much fun. What's the weirdest thing about living in Antarctica?
What's the weirdest thing? Sorry, my lights just went out. My power just went out. That was weird timing. So the weirdest thing is that it is almost like an adult summer camp, and that you're like living and working and communing with a very limited amount of people. So again, we make our own fun. I think the most fun I've had is in our open mic nights where we all put together a skit. I am not musically inclined. A lot of people down there are musically inclined, but me and my fellow less musically inclined folks made a sea shanty about our journey, and we sang the sea shanty to everyone, and that was very fun and weird.
I want that sea shanty on Spotify. All right, thank you, Jacquelyn. There are some more questions in the chat as well. If you are able to stick around on the YouTube, people would love to know more about Antarctica and penguins, I think. But thank you so much for being here.
Thank you so much for having me.
All right. And without further ado, we will bring on our next speaker. So our next speaker is Sunny Wescott. She is Executive Director of Geospatial Intelligence at ISAC. And Sunny is going to be talking to us about weather misconceptions and messaging mistakes. So the floor is yours, Sunny. Take it away.
Okay, good morning and/or later morning, I guess, for everybody else out there. I'm Sunny Wescott. I'm a prior Air Force forecaster. I've done quite a bit of work in the forecasting realm. So that's everything from operational forecasting to communicating to different critical infrastructure stakeholders. So I wanted to take the time to just touch on a couple of kind of more interesting ways that we can make weather, when we're talking weather, to our industry, to our leads, to our operators, how we can make it a little bit more impactful for them. Often we end up speaking solely on the technical side of the house, and that can end up leaving them a little bit more in the dust. So within my field specifically, what I specialize in is a different way of communicating, and that's kind of taking on a multitude of different jobs and adding them into my scientific field. So what I do is I go out of my way to learn other people's industry backgrounds. So I learn a little bit of engineering. I learn a little bit of the built infrastructure do's and don'ts. I learn what temperature concrete becomes more malleable. I learn some of the Spalding characteristics of geology. I learn a lot of different aspects of how we operate within the interconnected world. So that's the geospatial side of the house. And then the intelligences is making the weather more comprehensive as far as the threats on the horizon that are coming in for industry. So if temperatures are going to be over 105, this means different things to utility managers, depending on if it's energy, if it's water. This means different things for construction crews. We know that mulch is combustible. We know that coal seams are combustible, especially after 105 degrees. So this becomes a bigger conversation with each of the different industries, looking at things like propane tanks when temperatures are over 120. Being able to add that into messaging gives them a little bit more to work with and brings them back into the conversation when we're talking about the forecast. So what I do when I talk about weather and I talk about cityscapes is that I like to look at what does this mean to operate within a worsening environment. So if we're saying that temperatures are getting notably higher in the cities, what does it mean for restoration? What does it mean for new site development? It means that the concrete isn't setting right. It means that epoxy isn't setting right. It's not hardening the way it's supposed to. It's becoming more brittle. We're having to repave the roads more often. We're also annotating things like EVs are heavier than gas-powered cars in different ways, and this can cause more friction and wear and tear on the roadways, which can subsequently end up yielding some pretty significant impacts to the rest of the operation within the region. Everyone gets really bitter when they have to repave things they just paved. So being able to explain it a little bit better to them within the physics side of the house is critical. Same things with operating with bridges. When we're talking about things like the bridges getting stuck or failure points within the interconnected material, we know that direct sunlight and ambient air temperature don't melt our infrastructure, but it does cause each piece of the infrastructure to bend or breathe a little bit differently. And if we've attached them all together, they typically want to buck against one another. And that's where we get the warping and the dimpling and the cracking. It's not necessarily a single failure point as much as it is the interconnectivity is actually going to end up wearing it down. So when we're communicating to industry, breaking this down by concrete, epoxy, metals, power lines, bridges. There's a lot of different information that we can do within that spectrum. So there's other sides of the house too. I like to involve the public as much as possible when I speak. So I don't shy away from hard questions, things like social media manipulation. When other countries are coming into the fold with the conversation and they're propagating out misinformation, this can become highly problematic because it encourages general society to distrust the scientists. So if I put out a forecast and a fire kicks off and people say, I believe the government started the fire, and we say we didn't, and then all of a sudden we see social media posts with AI generated images saying that we did, it becomes a true battle uphill to be able to say as a meteorologist, what causes what kind of an ignition, why the material was so combustible, why the fire got so out of hand, really being able to highlight back to general society that there's never an intentional fire on our side of the house that ends up spreading to the rate at which we're starting to see these days. A lot of people are using the annotation of the new cityscape developments that are anticipated with smart cities and saying that these weather disasters are happening because of smart cities, when in all reality, the last thing that you want if you're going to develop a cityscape is for it to catch fire, because it ends up becoming structurally jeopardized for nearly 2 to 3 times longer than if you had just bought out the land over time and developed it, or if you had gone through the proper channels of slowly evolving the area, because now all the material has to be scrapped. There's ecological studies that have to go underway. The air quality in that region ends up plummeting. You lose a lot of the general vegetation you needed to maintain in order to build in your cityscape due to the higher levels of pollution from production. So there's a lot of conversation that can be had a little bit more openly when we're having these forecast discussions on the back end of major disasters, because unfortunately the media will continue to propagate it whether or not we address it head on. So this becomes a kind of comical side of the house for me. What I do when I'm presenting is I like to remind people that these weather movies are out there. I don't know if you guys all know, but there's more than 6 Sharknadoes. They're coming out with a 7th one. There's also obviously the multitude of Twister movies that are out there, both the popular ones and the unpopular ones. And then we have Day After Tomorrow, we have Geostorm. So you get to speak with general society who has these notions of how weather events happen based off of the movies. So I recommend to any scientist within your field to watch even the conspiracy theory movies, just so that you're ready for the types of questions that you get from general society within this vein. So this is going to be, how do they perceive that you're operating within your field? How do they perceive that the government is contributing or not contributing? So this is everything from when we look at Godzilla or we look at Stranger Things and the kids go and they save the world by not telling general adults, and the government having fallen short to the point in which a kid saves the world. While it's a feel-good story, it does actually end up sowing distrust in general society against some of the scientific community. So there's a lot to be said about making sure that we're leaning into these conversations, we're showing up into the public space, and we're willing to have the hard talks with people when it comes to things like why these weather events are getting worse and why they're perceiving it as an intentional act. So I like to highlight different weird weather events for them so that they understand that it'll only get more strange as time goes on, and that there's endless amounts of fun weather that's out there for them to be able to learn about. Things like sprites, which look like Stranger Things is coming into, the earth. And so you get to have the conversation of how long have sprites been around? What are sprites? What is a blue jet? What are elves in the concept of lightning strikes? So this brings in a better conversation of gravity waves, and gravity waves create those ripples in the clouds where everyone thinks they're man-made clouds because they have concentric rings that circle out from the thunderstorm. So really being able to have these conversations is just in a fun manner, more than anything, being able to be open and honest, being aware of the fact that they're missing information. They don't often get to interact with a scientist at a direct one-on-one level, especially in general society, but a lot of our operators as well. So I like to make sure that we're having the conversation of, if somebody brings up a question to me, I believe that gamma rays are the reason that fog is getting worse. Awesome. Let me deep dive into that for you. We'll have a good conversation about what that looks like. What is a gamma ray? What does it do to fog? Where does it sit within that upper level of the atmosphere? So I made sure to take that same general graphic I just showed you, and I pull more science and I bring it all into the table and I share it with them in a very open and engaging manner. So we talk about what other types of fog are out there, what kind of disruptive fog is out there, how dense is too dense, why do car crashes continuously happen, and then my other new favorite one, super fog and the bacteria. So this becomes the misconception, which is bacteria occurs naturally in soil. Super fog lifts everything up off of the moisture field. So this includes things like very light particulates like bacteria up and into the fog. You end up interacting with it because you're interacting with the aerosols. So this ends up becoming a conspiracy theory that we're creating fog in order to get people sick. So you have to be aware of both what kind of fog is out there, why fog is getting worse, what is super fog, that's where it mixes in with wildfire smoke and becomes twice as dense, and why the general conspiracies are out there stating things like this is an intentional act. Where did that bacteria come from? Where have we seen it before? What other countries already have this problem set as we go forward? So I like to make sure that we keep it a little bit more interesting for everybody. We talk about things in each of the industries. So this is everything from what does it mean for the built environment? What does it mean for operators? What does it mean for general society as far as trust, mistrust goes? What does it mean for tourism? Where people people are going, when they're going. Are they taking the right precautions? When they travel into an area and they don't know the weather events, they don't know the general risks and threats on the horizon, what does it look like to be able to operate there? What kind of events may take struggle or strain going forward, like the Cherry Blossom Festival, with stronger winds, more intense heat, the fluctuations between hot and cold, and the damage that that has on vegetation. And then, of course, for everyone out there who goes out and goes for Bigfoot sightings or any of the other climate and cryptid events that are out there. So I wanted to make sure that I highlight that I do presentations on the cryptids. I think it's a fun way to bring weather into everyone's wheelhouse. Everyone who likes cryptids, there's ways in which to make weather applicable to that conversation too. If they're a mammal, then they're going to be responding to certain biome shifts over time, the same thing that weather causes for any other mammal. It's going to change where you're going to be sighting these kinds of animals. It's going to be changing what kind of threats that animal and yourself are going to be going through. So it's everything from Bigfoot to the Loch Ness Monster, warmer waters, higher concerns for pollution, greater concerns for acidity within the water content. Where is all that sediment going during a flood event? Is the lake evaporating out too fast? You know, what are we going to do for Nessie as we go forward? The chupacabra when we lose the forests from major wildfire spreads? Where is this creature going to be moving to? What does it mean for sighting? Is it going to become more hostile and aggressive, bite more often? All of these conversations can really just be brought to the house anytime that you're trying to have the conversation about weather, you're trying to have the conversation about misconceptions. It's really just leaning in the science and meeting them where they are. And that can be anywhere, arguably. So again, even with Mothman in West Virginia, you know, if the forest catches fire, if there's droughts, if there's more lightning, these all become a problem for any general creature that is moth-esque in natural capability. So looking at each one of these, I've just tried to make it a little bit more fun for our different industry members to be able to understand a little bit more of that risk as we go forward, to be able to make it more playful, to encourage them to engage us as well. So I always annotate at the end of any given presentation, we know it was warmer on the planet once before, but we weren't here. Our stuff wasn't here. We weren't operating within the spectrum. We didn't have nuclear power plants, the transmission lines, the roads, my house. I also can't outrun most of the animals on this planet, so I'm not looking for them to get any more aggressive than they already are. So trying to stay in the Goldilocks era is pertinent to me specifically. I am a lifter, not a runner. So that's a real quick 10 minutes on what I do as far as weather work goes. I know it's a little bit different than our typical forecasters in and out when they're doing weather conversations, and we're doing things like 2 to 4 inches of rain or tropical cyclone landfall, lightning strikes, wildfires. It's just a different way to have that conversation and to keep it more fun for each one of our meteorologists, I think, as well.
Sunny, that was a tour de force. That was amazing. Thank you so much. There's so much love for you in the chat. There's a really good message. Someone says, Sunny, this legit sounds like you have my dream science communication job. People really leaning into the Bigfoot sightings, question mark. Some questions. One is, what are sprites?
Sprites are super cool as a conversation with lightning. So when we're talking about what does it mean for a warmer world, in some regards, there are some studies out there now that make a lot of sense that are saying that our atmosphere, the troposphere, is getting taller, which means our thunderstorm cells, which go from, if you've ever seen them, they create an anvil shape and they flatten out at the top because they're coming up to the tropopause, the top of our natural environment of weather. So what ends up happening when you have a thunderstorm with that vertical column, that updraft that creates that overshoot there, it ends up punching through the tropopause into the stratosphere. Lightning strikes shoot down, they shoot sideways, cloud to cloud, and then they shoot up and into space attemptively. And what ends up happening is that they're moving into the higher levels of the atmosphere and they create a ripple effect, a gravity wave. So sprites go up and then they rip apart a sort of, cosmic membrane, if you think of it that way. And that ripple is what the ELV is. And the ELV is essentially an EMP in the upper levels of the atmosphere, at the ionosphere to the thermosphere, mesosphere region. As these thunderstorms get taller, and they get more potent and lightning gets more potent, there is a concern for low Earth orbiting satellites going forward from things like sprites and elves, because they're very hard to predict. It depends 100% on how strong the storm is. And we frankly don't have a ton of science on them. So it's a really interesting growing scientific field, because now the storms are tall enough to really be able to see them clearly.
That's crazy. Yeah. So I think a lot about these big thunderstorms, particularly in the tropics, but I'd never thought about them effectively like setting off EMPs in the, just and then setting off an EMP and that kind of going out. That's kind
of they're some of my favorite weather phenomena. I love getting in arguments about whether or not lightning is getting worse over time, because it makes sense that it would. If the atmosphere continues to get taller, there'd be more ice available in the upper levels of your thunderstorm, which means you need ice for there to be lightning strikes within that field of the combustible nature of a thunderstorm. The more ice you have, the more dense your hail is as well, which would explain why hail is getting so much more potent, despite not always being larger than the record for that region.
I love that. Thanks for explaining that so clearly. We have to move on to the next speaker, but some people are saying, are any of your presentations open to the public? Do you have a website that people
I do. I'm very easy to find. I would have thought there would have been another Sunny the meteorologist out there. Ironically, Sunny is my real name, so I'm very easy to just Google. You'll find that there's a bunch of different YouTube recordings. I also have a link tree of a lot of different presentation decks where you can find endless amounts of research. And I run a bi-weekly extreme weather information network group, which is open to the general public, where I provide forecasts, and then I work to bring private sector into the table to be able to communicate with everybody as well. So I'm very easy to engage with. I'm on LinkedIn too.
Awesome. Well, chat, you know what to do. Go find Sunny, find Bigfoot. And thank you, Sunny, for that amazing presentation. Really appreciate it. All right. We are going to move swiftly on to our next presenter, who is Marcus Sarofim. So bring him on. So Marcus is a former EPA climate scientist, and he's going to be talking to us about certainties and uncertainties. So Marcus, take it away. The floor is yours. Ooh, sorry, Marcus, I can't hear you. Nope.
You hear me?
Oh, I hear you now.
Great.
All right.
Good morning, Andrew. Good morning, audience. My name is Marcus Sarofim. I was at the EPA for 18 years. I left in January. Since leaving, I started posting on a Substack. So I want to plug my Substack, the Sarif Report, where I talk about climate analysis and various other things. But today I'm going to be talking about certainties and uncertainties. My area of research for a long time has been reduced complexity modeling. So finding ways to take, these huge complex climate models, which take days, weeks, sometimes even months to run, and emulating them with simpler models so that we can do faster and maybe more policy relevant calculations. And in particular, I want to talk about producing probabilistic information. We all make decision making under uncertainty all the time. Pretty much everything you do, you don't know exactly what's going to happen, but you sort of have an idea. And I think that, sort of weather reports is a perfect example of this. You get up in the morning, you look at your weather app, it gives you a probability of rain, and then you make a decision as to whether or not to bring an umbrella, to cancel your picnic, whatever. So where do we get that sort of probabilistic forecast for climate predictions? So there's a number of uncertainties which need to be chained together in order to estimate probabilities for what's going to happen with future climate, whether it's at the global level or the local level. The first and hardest is that we have to have some idea about what future emissions will be. Now, future emissions are a choice. We have control through policy levers, through technology developments, through personal choices, all those things about how much we will emit in the future. But we can sort of, there are political scientists and economists and engineers who can come up with, based on sort of the historical path, sort of say, here's what we think the most likely futures might be. And they can try and put probabilities on future emissions. And you need this if you want to go probabilistic. These emissions then feed a carbon cycle so that you can see how much your CO2 emissions change CO2 concentrations. You need to also have atmospheric chemistry because methane's lifetime in the atmosphere depends on levels of the hydroxyl radical. Doing this gets you greenhouse gas concentrations in the future. You can calculate the radiative forcing from these concentrations. Once you know the radiative forcing, which is sort of the warming effect of greenhouse gases on the atmosphere, then you want to calculate the temperature. And there's a term, climate sensitivity, which is basically how much the Earth will warm per unit of this additional radiative forcing, this warming effect from greenhouse gases. Put all of that together, and then you can say what the probability of a future global temperature is. And you can chain that down to sea level rise, precipitation, and all sorts of other things. So this is a graph from a paper I wrote in 2024, but it really depends on an emissions projection developed by Resources for the Future in 2021. And the black line and the gray outline are the median future emissions based on this group's estimates, and the 5 to 95 percentile. And so we can see a couple of things here. One is that according to the RFF group, they think that the most likely future is that emissions will drop by about 50% over the next century, and that they're going to peak in the near future. So this is maybe considered an optimistic sort of future of emissions. Also overlaid on this are the SSP scenarios, which is what the climate community has used for a long time to talk about future climate, but they're not probabilistic. So the problem, again, about making emissions projections for the future, it's hard. So on the right, these emission projections came out in 2021, and I've just overlaid sort of what we've actually seen in the real world. So even in the, a few years, we already see that maybe the CO2 was a little bit too pessimistic about how fast CO2 would come down in the near term, but the methane was too optimistic. And we can see that the IEA, at least, is very optimistic about where we're going to be in 2030 compared to what this emission projection says. So the 8.5 watt per meter squared scenario has been in the news a lot. So I can use this probabilistic assessment to look at the likelihood of exceeding 8.5 watts per meter squared, along with some other scenarios. And I can see in terms of emissions, of the 10,000 RFF scenarios, only 2 of them have higher emissions than the SSP 585 scenario. So exceeding that emissions is nearly impossible, but 1% of the forcing scenarios exceed it because there's a lot of uncertainty from the emissions to the forcing. And if we think about where the planet will be in 2150, now like 8 or 10% of the scenarios might exceed that. So that's still sort of a relevant threshold to think about. I've been doing this kind of probabilistic assessment since I was a graduate student. So I collaborated with Andrei Sokolov and a number of other authors at MIT, and we published a paper in 2009. And this probability wheel on the left is what we thought temperatures would be at the end of the century based on our best estimates of future emissions and climate at the time. And you can see there's a lot of red there. We were pretty pessimistic about what the state of the world would be. And this sort of assessment kind of lined up with where the rest of the climate community was at the time. 16 years later, on the right, you can see a lot of that red has disappeared. So this is this new RFF scenario. And so this is great. We've seen the worst case outcomes have become much less likely. Where we were 90% likely to exceed 4 degrees before, we're only 13% likely to exceed it now. On the other hand, we often see 2 degrees as a global target. Exceeding 2 degrees is still highly likely. Exceeding 3 degrees Celsius is still a coin flip. And this, again, lines up with sort of what other people in the community are doing. I'm showing the climate action tracker sort of projections in 2015, 2021, and 2025. And they also say like the best estimate end of the century temperature is, close to 3 degrees. Temperature isn't the end of the story. We have a reduced complexity model which estimates impacts. And here we have a list of all the impacts that we can look at in the US using our model. Caveat, this is based on sort of the studies we were able to sort of leverage for our framework that existed at the time. None of them are perfect, so take all of the results with a grain of salt, but it is sort of our best estimate, and best estimates are important. The way we do this is we take one temperature run out to the future, and here we show degrees of temperature change in the US by year, but then we sort of ignore what year it's happening, and we just look at the temperature changes. This is called sort of the by degree approach. And then we run our impacts model at each of those degrees, and we can produce damage functions. So on the right, we have 3 damage functions that are based on air quality. Climate impacts on air quality through changes in meteorology, climate impacts on air quality through increases in dust in the Southwest, and climate impacts on air quality through increases in wildfires and wildfire smoke. And this leads to increased deaths in the US. And we can sort of estimate this per degree. I will say there's another newer wildfire smoke study out there that shows much higher damages and is maybe more consistent with the massive acceleration we've seen in wildfires in the past few years. We can also do this for sea level rise. So here we have a group of sea level rise scenarios that were developed by Sweet et al. And they basically do high resolution coastal sea level rise for a number of different scenarios into the future. And so for a given year, say 2100, we use our damage model and we estimate the damages at 30 centimeters, at 50 centimeters, at 100 centimeters, and so on. And again, we can produce damage functions. And here we show damages to coastal properties, and damages due to the fact that we're going to get a lot of roads flooded, which are going to create a lot of delays and so on and so forth. So the idea is you create sort of these damages by centimeter or by degree. You create these damage functions by interpolating, and now you profit. You have a way to calculate damages really quickly for any future scenario. And our model produces all of these estimates at the state level. So on the left, we have our sea level rise damages by state. And you can see that per capita, Louisiana, unsurprisingly, is going to be the hardest hit. On the right, we have all of the air quality effects added together. You can see that the West Coast is hit hard because of the wildfires. The Southeast is hit hard because there's sort of higher temperatures are making like a chemical stew for all of the pollution in the Southeast, and that accelerates things. But oddly, you actually get reduced particulate matter in the sort of northern Midwest because of more rainfall washing out the particles. So this sort of model can be used to look at, how do damages change over time? How do damages change over space? How do damages change over people? Environmental justice is a very important question. So to conclude, even with uncertainty, we have certainties. We are going to see warming over the next 2 decades. We're almost certain to blow past the 1.5 degree threshold. We've already seen individual years past that. Probabilistic modeling is important in order to get these odds. We still see a large chance of exceeding 3 degrees, which would be bad. These impacts are unevenly distributed, and the uncertainty blade is sharper on the bad side. So plan for worse than the median. I have some future work. I want to add some feedbacks. Our climate model, reduced complexity model, doesn't really have the full permafrost effect. It doesn't have Amazon dieback. It doesn't have like Amazon ozone methane effects. I want to look at probabilistic impacts from individual pulses, and we want to do a more full suite of sectoral impacts with our model. So thank you, and I think I have 4 minutes for questions.
Thank you, Marcus. That was a great talk. You had a lot of questions in the chat, actually, so I'm going to just start pulling them up. So one of them was, there were a couple of questions about, you talked at the beginning about how there are all these different variables that, you know, can be changing, all of these different things that go into these different probabilistic assessments. There are kind of two questions. One is, with so many of these variables, how does one specific aspect affect the outcome?
Okay. Actually, if you go and read my companion Substack post, I actually do a decomposition into how much is the climate uncertainty, how much is the emissions uncertainty, how much is the internal variability uncertainty. You care about global temperatures a couple years in the future, it's all internal variability, El Nino effects. As you go out to like 2050, it's mostly the climate uncertainty, because a lot of that sort of, like, our emissions just aren't going to turn that quickly. But the further out in the future you go, the more and more important our decisions about emissions become.
That was great. And yeah, one of the other questions was like, which is the most important of these things? And what you're highlighting there, right, is that it depends on the time scale that you're looking at.
Yes.
So another thing kind of related to that, so a lot of this has been about projecting temperature. One of the questions was, does temperature affect air quality? Hot air feels harder to breathe. I could be imagining that. And I guess the meta thing for this question is like, what other things can you learn if you're able to project temperature in the future? I guess you have sea level rise, but yeah.
Yes. So temperature directly affects air quality. The higher the temperature is, basically, the faster the chemistry works, the more pollution you produce. But other things affect air quality. So changes in precipitation wash out pollution. Actually, your response to air quality also depends on the temperature. If it's hotter out, the same level of ozone actually has a worse effect on your body than when it's colder out. And yes, you can do changes in precipitation and the effects on like infrastructure and flooding. You can do changes on sea level and coastal stuff. So all of that.
Another thing which is funny is people, if you go back a couple slides, people thought that was the periodic table for a half second. They were like, this is the weirdest periodic table I've ever seen. But it is the US map, as the chat eventually worked out. Smart chat.
Yes. I think it's a Penn State developed way of showing the US, so you can see all the states in sort of the right place-ish.
One more question was, between these different assessments that we've had of like future scenarios, have the methodologies changed substantially? Have the ways we deal with these uncertainties changed over time as well?
Yes. So emissions projections have to change every few years, because we didn't expect solar and wind prices to come down so quickly. We're always curious about, like, will there be a global policy? Will countries meet their NDCs, so on and so forth. The climate reduced complexity climate models are also continuously updated. I would say those change more subtly, because we've really known most of the key climate science for a long time. So you're sort of tweaking around the edges for that. And then the impacts models, like I said, like our wildfire model, we already know is an underestimate. So I think the impacts models also need a lot of work.
Awesome. Thank you, Marcus.
Thank you.
And yeah, we're gonna move on now, but lots of love for Marcus in the chat. Thank you for that great talk. We are turning over to is it hour 41 now? Or am I just going crazy? I don't know what hour it is. What day is it? Where am I? I think we're in hour 41. And we're gonna just take a second to remember again why we're here, why we're 41 hours into this crazy live stream. And the reason for that is because, as I've said many times before, everyone in the country, in the world, needs actionable weather and climate information. And this is something that we've known for a long time. You need to know whether it's going to rain today. You need to know whether it's going to be a drought over the next couple of months. You need to know, going forward, is your home liable for increased flooding due to climate change? This is all just crucial information that we need for our livelihoods. And as a result, the US has built up this incredible infrastructure for doing weather and climate prediction. And that is all now at risk. One thing that I'm highlighting is the National Center for Atmospheric Research in Boulder, Colorado, this beautiful crown jewel of atmospheric and weather science in the US. It's being targeted now for dismantling by the current administration for no other reason than the fact that this lab works on climate. And this is really just a taste of things to come down the pipeline. So the Office of Management and Budget last week, or only a few days ago, proposed rulings which would make this type of political interference routine and permanent. It would allow political appointees rather than scientists to decide where the funding goes. It would allow political appointees to terminate grants for no reason. And this is a really terrifying prospect for US science. It means we're going to lose scientists who would otherwise stay in the US. I know friends who are already have left to do postdocs in other countries. And so this is the time to stand up for what we've built over the last 70 years through this really concerted effort by our society. So I'm going to ask you to go to wclivestream.com/call. It's going to take you to a 5Calls website. You put in your zip code. It's really easy. It tells you who your representatives are, gives you some background information and a script which you can read to them. Their staff are very polite. They're there to listen to you. And I just encourage you to, if you like what you see here, if you think it's worth defending, to go to that website and ask them to stand up for science. And with that, I'm going to bring on our next speaker, who is really a bit of a superstar in our field. If you haven't heard of Kate Marvel, you should have. and I'm looking forward to you being able to be introduced to her now. So Kate is a senior scientist at Project Drawdown and is going to be talking to us today about the climate future. So Kate, take it away.
Great. Hi, everyone. Thank you so much. Good morning. I'm happy to be here. I apologize in advance. I am on travel. I am trying to do my best from a hotel room with very sketchy Wi-Fi, but let me know if I disappear and you can't hear me. Okay, anyway, I wanted to talk a little bit about what's happening right now in the climate and what's going to happen in the future. And I think this is a really great way to piggyback off the excellent talk that Marcus just gave. So we know that the Earth is warming because of greenhouse gases. We are more sure about this than we are that smoking causes cancer. There's really no doubt whatsoever in the scientific community what the cause of climate change is. Now, humans do many things that can change the climate. We change the way that we use land. We emit what people generally think of as pollution, what scientists call aerosols, kind of gas and dust and soot that blocks the sun, and actually makes the Earth a little bit colder. But we know that all of the global warming that we have seen to date has been caused by human emissions of greenhouse gases. Now, I want to sort of break down some of these greenhouse gases and talk a little bit about what they do. So carbon dioxide is probably the greenhouse gas that gets the most press. You've probably heard the most of it. We talk about zero carbon, low carbon. And carbon dioxide is a really important greenhouse gas. And one of the reasons it's really important is that it sticks around in the atmosphere for a really long time. If a molecule of carbon dioxide is not quickly removed by photosynthesis, essentially growing stuff on the Earth's surface, it's going to hang out in the atmosphere for hundreds or maybe even thousands of years. So the important thing about carbon dioxide is that it sticks around for a long time. And what this means is that every ton of carbon dioxide emission adds to global warming. The global surface temperature increase is essentially linear in the cumulative carbon dioxide emissions. And what that has implications when you look at a country by country breakdown of who is causing global warming. So right now, on a national basis, Chinese emissions are about double what US emissions are. But because the atmosphere doesn't necessarily care about year-to-year carbon dioxide emissions, it's that accumulated CO2 over history. The US is actually more responsible for climate change than China because of our historical emissions. So carbon dioxide warms the planet and sticks around for a really long time. But it's and carbon dioxide emissions, I think everybody on this live stream is probably aware of this. Carbon dioxide emissions from burning fossil fuels contribute to climate change. So CO2 emissions make up about 60% of the emissions from the fossil fuel industry. But it's not just carbon dioxide. Carbon dioxide is not the only greenhouse gas. It's not even the only important greenhouse gas. Methane is a pollutant that humans emit that is shorter lived in the atmosphere. It sticks around for a decade or so, about 12 years. So that's the good news about methane. The bad news about methane is that it is incredibly potent. While it's in the atmosphere, it is more than 80 times better at trapping heat from the Earth's surface than carbon dioxide. And so methane emissions from fossil fuels also contribute to climate change. So this is a pie chart of methane emissions from the fossil fuel industry. Methane, CO2, not the only greenhouse gases. Nitrous oxide and fluorinated gases from fossil fuels also contribute to climate change. So here's nitrous oxide, here's fluorinated, or what we call F gases. Now, nitrous oxide and some fluorinated gases are both long-lived and potent, but compared to CO2, compared to methane, their concentrations are small. This doesn't mean that they're not important, but it does help put those emissions into context. So it's not just fossil fuels. I think the standard narrative that we get is CO2 from the fossil fuel industry is causing climate change. And that is indeed a large part of the story, but it's not the only part of the story. Industry emits greenhouse gases. And here I am not talking about industry burning fossil fuels for energy. I am talking about industrial processes like making cement, like making plastics, like making steel, where the processes themselves are sources of emissions, the way that we currently use them. So industry emits carbon dioxide. Industry emits methane, industry emits F gases and nitrous oxide. In addition, the way we use our land, what we grow, what we eat, agriculture and our land use decisions also emit greenhouse gases. So agriculture and land use decisions emit carbon dioxide, mostly through deforestation, clearing of landscapes that absorb a lot of carbon dioxide in order to make way for pasture or cropland or built up land. Also emit methane, primarily from rice production and livestock production, and nitrous oxide mostly through fertilizer. So that's the overall story of greenhouse gases. It's not just fossil fuels, it's not just carbon dioxide. But we know that because these things are causing climate change, that means we know how to stop climate change. We know how to limit the warming. So to stay below 1.5 degrees Celsius, 2 degrees Celsius, whatever arbitrary limit that you set yourself, to stay below 1.5 degrees Celsius, the world needs to cut emissions in half extremely rapidly in about 10 years. So this is our current trajectory of emissions, and the dashed line is kind of, there's no such thing as business as usual, but a continuation of current trends. So we need to bend that curve and we need to make it go down incredibly sharply. And so the solutions that will allow us to do this, the solutions that will have an immediate impact on temperature change are what we call emergency brakes. So emergency brakes can do one of two things. They can be solutions that are incredibly easy and rapid to implement right now. So something like preventing deforestation is an emergency brake solution because it prevents the emission of large pulses of greenhouse gases. But we can also, when we're designing emergency brake solutions, look to the fact that we've got some warming agents that live in the atmosphere for a very long time, and some that, while they are short-lived in the atmosphere, are incredibly potent while they are in the atmosphere. And this is why solutions that target methane are what we call emergency brakes. They prevent a lot of short-term warming. They bend that curve. I want to be really clear here. I am not saying that we can cut methane emissions as a substitute for cutting CO2 emissions and other greenhouse gases. What I am saying is that we can leverage the fact that we've got these short-lived global warming agents that are extremely powerful while they're there. So those are what we call emergency brake solutions. We need to bend the curve, and we need to bend it down really, really quickly. But we know to stay below 1.5 degrees Celsius, the world has to reach net zero greenhouse gases by 2050. So it's not enough merely to cut emissions in half. We need to make those emissions go to zero. We need to stop putting greenhouse gases in the atmosphere. And so this is a process that's going to take time. We can pull those emergency brakes. We can prevent quite a lot of short-term warming. But in order to get to net zero, we need to simultaneously be in the business of implementing new low carbon systems, transitioning the energy sector, transitioning the electricity sector, transitioning the transportation sector. And in the long term, affecting the social change that we need to transition fully to a zero carbon, zero greenhouse gas society and economy. But most people think that even by 2050, there are still going to be some residual emissions, things that we have just not figured out how to decarbonize, emissions that are vital for development, vital for other sorts of other things that we care about. So most people think that it is possible to cut emissions a huge, huge, huge amount by 2050. But if they are not zero, we still get warming. And that's where so net zero greenhouse gases effectively means net negative carbon dioxide, which means that in addition to cutting our carbon dioxide emissions, we are also going to have to take carbon dioxide out of the atmosphere. Now, this sort of engineered carbon dioxide removal is almost zero right now. We're going to need it to greatly scale up in the future. But I want to be really clear what I mean by greatly scale up. I mean, all of the effort, all of the money that we put into carbon dioxide removal is only going to matter, is only going to work if emissions also fall. There is no way, there is no scientific way that carbon dioxide removal can allow us to not reduce our emissions and still get to net zero. So how are we going to do this? How are we going to pull those emergency brakes? How are we going to affect that social change that is going to allow us to stop putting these warming agents in the atmosphere? In order to answer that question, it's really important to look at the sources of emissions. Where are these greenhouse gas emissions coming from? What are we doing to put them in the atmosphere? And how could we do that differently? So if we look at the atmosphere, the sources of greenhouse gases that we're putting in the atmosphere, about 25% come from the way that we produce electricity, burning fossil fuels like coal, gas, oil to produce electricity. About 24% come from the way we use land, what we eat, what we grow. About 21% come from industry. So those are industrial processes beyond just using fossil fuels for energy. About 14% globally is transportation, although in the United States, that accounts for the bulk of our greenhouse gas emissions. About 6% is buildings, so the way that we heat and cool our buildings and the way that we cook our food. And the rest is leakage, things from the fossil fuel infrastructure, gas leaks, things like that, or other energy-related emissions. So once we know where these emissions are coming from, we can start to look for solutions. We can start to look for ways to shift these sectors, do things differently. At the same time, while we are reducing emissions, we can also support sinks. We can support the ecosystems on the land, on the coast, and in the ocean that are extremely effective at removing carbon dioxide from the atmosphere. So mitigating climate change is a story of reducing sources and at the same time supporting sinks. I want to stress that climate solutions in and of themselves also can have co-benefits. They can, as Marcus mentioned, lead to improved air quality. They can have economic benefits. They can have job benefits. They can have justice benefits. And so I think it's really important to talk about climate solutions in that context. I want to end with a plug for a tool that my organization has been working on. This is called the Drawdown Explorer. We call it the world's ultimate climate solutions platform. Here you can browse solutions by sector. You can click on them to see whether they're highly recommended, worthwhile, worth watching. And you can see estimates based on peer-reviewed, publicly funded science of the emissions reduction potential of all of these solutions. So I'm going to end with this QR code, which if you want to, you can scan. You can go to the Drawdown Solutions Explorer. You can play around with on your own. So thank you very much for listening, and I'm really excited to take some questions.
Hey, Kate, thank you for that awesome talk. And the internet and the hotel Wi-Fi, was valiant and didn't fail at all. Awesome. We had one question was, so how does CO2 removal in the atmosphere work? And then the follow-up was kind of like, are we talking about nature-based things? Are we talking about technical solutions?
Great question. So from an atmospheric perspective, the atmosphere kind of doesn't care how you get carbon dioxide out of it. It just sees the concentration of carbon dioxide in the atmosphere. So as I think the question is alluding to, nature is very good at taking carbon dioxide out of the atmosphere. And that's because we've got stuff growing on the surface of the earth, both on the land and in the oceans, that does photosynthesis. I have been a scientist for many years, and nobody has ever been able to convince me that photosynthesis is anything other than magic. So there are what we call nature-based solutions, which try to leverage that, which try to encourage reforestation, the regrowth of forests where there already were, or where there used to be forests, or afforestation, planting forests where there aren't any, supporting coastal blue carbon, supporting the ability of plankton to take CO2 out of the atmosphere. So that is a source of research right now. There are also what we call more engineered CO2 removal solutions, things like direct air capture, where if you've seen it, there's these giant things that look like air conditioners that suck CO2 out of the atmosphere. I think the consensus is emerging that that is not going to be very economically feasible, and you also have to figure out what you're going to do with the CO2 that you take out of the atmosphere. So there is a lot of active research going on various ways to affect carbon dioxide removal. But I think everybody working on this would agree that CDR, carbon dioxide removal, is kind of like having your stomach pumped. You want that option to be available to you, but also you really need to stop eating poison.
I think it's a great analogy to end on. There are a couple more questions in the chat which we don't have time for, but if you are able to stick around on the chat afterwards. I think people would love to engage with you on that.
Sure thing.
Great. Thanks so much, Kate. Really appreciate it. And with that, that's the end of my hosting slot. I'm gonna pass it over to Clark now. I will see you guys in the last 40 minutes of the live stream, T-minus 9 hours. Bring your friends, bring your family. We are going straight through. No more resets now. I'm going to see you guys. So I want to come back in like 8-9 hours, see a ton of people. That's my challenge to the chat. Go forth and multiply. All right, and with that like kind of zany, sleepy energy, I'm going to pass it over to Clark.
All right, thanks, Andrew. Hi, I'm Clark. Sorry it's a bit late for my segment, but I'll be with you for the next 2-ish hours. And that was an amazing talk. And thank you all again for tuning in and for engaging with us. We've got some more science coming, but let's first remember why we are here. Weather and climate forecasts are so important for policy decisions and everyday decisions for us all. I personally rely on accurate weather forecasts every day to ensure I don't get stuck biking through a thunderstorm. Luckily, U.S. scientists are world leaders in world and climate science, responsible for advancements such as the first ever computer models of carbon pollution impacts. In particular, the National Center for Atmospheric Research, NCAR, is a world-renowned laboratory which climate science around the world depends on. However, this essential source of data is at risk. The current administration is attempting to dismantle NCAR because climate change research does not align with the administration's political priorities. If this upsets you as much as it does me, please follow the link in the description and share your thoughts with your representatives. They have the power to protect NCAR and the responsibility to listen to their constituents, you guys. So show them that you care. Now, on with the science. Our next speaker is an assistant professor at Dartmouth University. She'll be speaking to us about hydroclimate variability over South America. Please welcome Dr. Arianna Varuolo-Clarke.
Good morning, world. This is so exciting. Thanks for having me. This is such a great opportunity to be sharing our science with the world, although it is, of course, a bummer that it comes out of kind of the threats to the science. But I'm here to talk about my research that I did during my Ph.D., where I was specifically looking at and trying to understand what led to these large increases in summertime rainfall over southeastern South America. This little inset here is just showing precipitation trends over South America from 1902 to 2022 over DJF, so Southern Hemisphere summer. And I just boxed this region of southeastern South America, or SISA, as you'll hear me call it, which encompasses southern Brazil, Paraguay, Uruguay, and northeastern Argentina. But before I get to the science, and in the name of this weather and climate live stream, I want to talk about how I got here. How did I come to be a professor at Dartmouth College? And it starts with and is includes a lot of great collaboration with federal science agencies and federal funding agencies. I was listening to one of Dr. Lily Dove's talks, and I loved how she talked about her career being so connected to and really having federal agencies as a collaborator. And so I wanted to take that moment as well. So I went to college at Vermont State University. It was called Lyndon State College at the time. It's this really amazing small college in Vermont. We call it the Northeast Kingdom. Jim Cantore from the Weather Channel, he and I share the same alma mater. So we both graduated from Lyndon State College in their Atmospheric Sciences and Meteorology program. It's worth noting that I had funding from the Department of Education through their Pell Grant funding. For low-income students. That's a grant that you don't have to pay back as part of your financial aid package. And then during my time at Lyndon at Vermont State University, between my second and third years, so the summer when I was a rising junior, I was accepted into the NSF SOARS program. So SOARS is the Significant Opportunities for Atmospheric Research and Science, which is housed at NCAR, the National Center for Atmospheric Research, and kind of hosted by or run by UCAR, the encompassing entity that helps to run NCAR. And this program is absolutely amazing. I truly would not be here today without that program. It exists to kind of bridge the gap between undergraduate school and graduate school for folks that have been historically marginalized in the field, whether that's gender, race, military status, disabilities, kind of bringing all of these people who maybe otherwise wouldn't have opportunities to continue their education and helping them learn what the opportunities look like within academia. So I'm truly grateful for that program, and continue to connect with it as I've grown out of and graduated the program. You can go back for up to 4 summers, which I did between my undergraduate and starting my master's at Stony Brook University. And they also supported me to do this Juneau Icefield Research Program, where I got to spend 6 weeks traversing the Juneau Icefield from Juneau, Alaska to Atlin, British Columbia, trying on my hat, checking out if I liked glaciology. Turned out I liked the atmospheric sciences better. But that was a great learning opportunity. Okay, that was undergraduate. Then I went to go get a master's at Stony Brook University, where I was looking at and trying to understand how well the North American monsoon is simulated in climate models. So lots of people are familiar with kind of the Indian monsoons and the larger monsoons across the globe, but we here on our continent have a very small monsoon that spans from across northwestern Mexico into the southwest US, where Arizona and New Mexico kind of are in that core region of it. And then after my master's, I moved to Columbia University and their climate school and the Lamont Doherty Earth Observatory, where I was working on some of the research that I'll talk about today. And I should say in both my master's and PhD, I was funded through the National Science Foundation in some capacity. And so at Columbia, there's this amazing project through the NSF PIRE program, which is Partnerships in International Research and Education. And so it was this broad partnership with folks at Columbia, folks at the University at Albany, that's where the lead PI was, and then we had colleagues at institutions in Brazil and Argentina, and the tagline was CREATE, so it's climate reconstructions across the Americas. Okay, maybe I don't have that right all the way, but we were basically trying to build reconstructions of hydroclimate across the Americas using tree rings and cave sediments, and blend that with climate modeling so that we could better understand the future by being better informed by our past. And it's worth saying that across the paleoclimate world, especially over the last 1,000 to 2,000 years, we've got really great tree ring records across much of the US, across much of Europe, across Australia, but in places like South America, our records are much more limited. So that was a huge effort of this project to try and build out our records, especially in places like the tropics. So kind of the tropical parts of South America, where we don't get as nice tree rings because we don't have as distinct seasons because we're in the tropics. And then finally, before starting here at Dartmouth, I was a NOAA Climate and Global Change postdoctoral fellow housed at the University of Colorado Boulder, and so again had this funding from the federal level. And okay, now I will really quickly talk about some of my science. So here I'm just showing these global precipitation trends from 1950 to 2020, showing that so green, it means there's been an increase. So this region of Southeastern South America really stands out as having one of these largest precipitation trends over this historical period. And so when we look now, if we take an average of that boxed region, you can see there's a lot of year-to-year variability in the precipitation trends, but overall it's been increasing from 1902, and this record ended in 1922. And it's worth noting that there has been this kind of decrease over kind of the time period in which I was working on my PhD, where we started to see these declines in rainfall in the region. And that was kind of the whole point of thinking about this question of, we have this really large increase. What is the future of hydroclimate for this region going to look like? Are we going to see the trend continue to increase? Or will we see this reversion towards drier conditions? And so we focused on the rainy season, DJF, so austral summer. And you can see here, just looking at these seasonal trends, that we look at the annual versus the kind of seasonal trends. That DJF, that austral summer period, stands out as having the largest increase. We see a large increase, or we see some increases in our shoulder seasons, and not so much during the winter time, but that makes sense given the summertime is our rainy season within this region. And then this increase has been evident across streamflow records. So this here on the left is just looking at sediment records from this lake, Laguna Marca Chiquita, which showed that 1975 to 2000 was wetter than any period in the last 200 years. And then finally, the Rio Bermejo tree ring streamflow reconstruction also shows this increase in extreme streamflow events from since 1960 compared to an earlier period. And in the interest of time, I will kind of just speed through. So this increase in precipitation has also co-occurred with this increase in demand, where we've seen this transition from kind of natural grasslands and grazing agricultural practices to this boom, this soybean boom in the region, where now this region is really one of the core bread baskets of the world, if you will. We get a lot of our soy, cereal, maize from this region. And then, so really what I wanted to know is what caused the precipitation increase. And maybe I'll just end here on the teaser of it all, which is depending on what time period you're looking at, what kind of question you have, what kind of model or what model you're looking at. Lots of different authors have come up with different ideas of what led to the precipitation trend. One, that it was just natural atmosphere-ocean variability. Another suggested that it had to do with the stratospheric ozone depletion, so the ozone hole. And another paper said that it was all just a response of greenhouse gas forcing, so anthropogenic forcing. But all of these papers, what I'm struck by is they all noted that the models kind of systemically underestimated the precipitation trend, and that has become something that I've been really interested in and showed in my research, even these latest generations of climate models. So here's just our observations compared to these different models. This is our observational range of uncertainty for kind of the observed precipitation trends, and only about 6 simulations from 5 models really fall within that trend. And so why? Maybe because the trend is just strongly driven by anthropogenic forcing, by that greenhouse gas forcing, but the models are systematically underrepresenting it, or internal variability kind of maybe, so that year-to-year natural variability dominated the observed trend, and models systemically underestimate that internal atmospheric variability. And so that leads to this kind of research that I'm picking up now, which is this meta-analysis of global precipitation trends to quantify how often Earth system models miss historical precipitation trends, and then to see if we can make the link where those models that are those simulations that are underestimating these precipitation trends, does it relate to this underestimation of atmospheric circulation variability? And the big why of this all is if the models are underestimating our past trends, how much confidence can we place in them for the future trends? So if we can better understand why they aren't getting some trends, that can hopefully help us constrain our future projections of regional precipitation. And with that, I think I'll conclude. Thank you so much.
Amazing. That was a great talk. We do have time for a few questions. So starting off, there was a commenter mentioning that they love seeing the different paths different scientists take to get here. Could you talk a little bit more about maybe how you found your current career, if your current topic is maybe personal to you, or why you study this scientific topic?
Yeah, that's a great question. I think for me, and the advice that I give to earlier career people than I is to be open to different career paths. So when I set out to go to meteorology school, I was maybe what you would call a weather weenie at the time. and really wanted to study tornadoes and help us increase our warning time for tornadoes. But then I got to college and fell in love with the climate problem. I like to joke that I grew up like kind of outdoorsy, so I think like having this interest in the atmosphere and then also being a little bit of a tree hugger, learning about the climate problem just felt like this really clear passion point for me to study. But then beyond that, like once I figured out that I really enjoyed doing climate science research and thinking about these different historical changes and future changes, I've been really open to kind of what that specific problem that I'm attacking looks like. And so I think like ending up where I did for my PhD, that opportunity presented itself, or to work in that specific group presented itself because I had done this monsoon research beforehand. And so I'd kind of just like jumped around whatever ideas and people were willing to work with me and what funding they had. But much of the work has always been kind of related to thinking about rainfall changes. So I think I just like rain. I used to be really scared of thunderstorms, and now I'm here. And then for South America specifically, my PhD advisors were on this project, and it was kind of broad, just think about hydroclimate across South America. And then I found this really unique or interesting problem of this discrepancy between models and observations and not really having a good idea of what led to the trend.
Super interesting. I also have a fear of thunderstorms, so... a more technologically driven question. Do you think that the precipitation trends will increase into the future?
That's a really good question. And so if you extend the data to include 2023 and 2024, you see that there's some real drought and dry conditions in that region over 2023 that rebounded a bit in 2024. And so I think that what I expect to see happening is like this overall background trend, but then maybe these punctuated intense droughts, which is a really then challenging thing to communicate, right? At the one hand, you need to make sure your culverts are wide enough to handle the risk of flood and things like that. But then you also need to be thinking about water resource management and being able to prepare for these like shorter term droughts. So it's a pretty, and so with precipitation, there's just so much of that year-to-year variability. And then there's this background trend that's been increasing, and then storms that do hit are becoming stronger. But then you can also have these drier phases. So it's a little bit of both, which is not a satisfying answer.
So there's another technical question. What are some factors driving the precipitation increase in the past century, and what could be behind the recent decrease?
Okay, so for driving the precipitation increase over the past, so one idea had to do with the temperatures, so cooler temperatures over the Atlantic could have promoted some increases in rainfall. Then there was the one idea of the stratospheric ozone depletion, which when you get that ozone hole, it kind of basically shifts that mid-latitude westerly belt further south and places this region under a region of ascent, so uplift, so then you would get more rainfall. And then with greenhouse gas forcing, it kind of, one of the dynamic changes is also that shifting of the mid-latitude westerly wind belt. And so one idea too that folks have talked about in the literature is whether or not having that rebound of the ozone hole, right? So our ozone hole is healing. That's a really good example of scientific and environmental solutions that have worked. So the ozone hole is healing. So as the ozone recovery occurs, and maybe pushing shifting that mid-latitude westerly belt back towards the equator, but then you still have that greenhouse gas forcing. What is the push and pull of those two responses? And so is that what we could be seeing for the recent decrease? And so beyond that, I don't have a good idea yet about what's driven the recent decrease.
Well, it sounds like you've got some more interesting research ahead of you. Thank you so much for your time. I think we are going to be moving on to the next speaker, but thank you so much. That was a very interesting talk.
Thank you. Take care.
All right, so wrapping up the hour, we have one more talk, then only 9 more hours to go. Before I introduce the next speaker, I'll briefly discuss why we're doing this stream again. U.S. scientists and science institutions are vital to weather and climate research around the world. This is due to decades of investment into this infrastructure by the American public. However, the freedom for these scientists and institutions to pick what research is needed is under attack. The Office of Management and Budget, OMB, has proposed extreme rules for research funding, allowing political appointees to make funding decisions instead of the scientists themselves, limiting the type of science that is eligible for federal funding, and restricting how scientists can share their work with each other and with the public. So if you like public science talks like this, making climate and weather research accessible to those who are actually impacted, and if you want important science, as decided by experts, not politicians, to continue being funded, please contact your representatives and tell them you oppose the OMB's proposal. Click the link in the video description, and there you'll find a call script you can follow, making it so easy to have your voice heard. Okay, our next speaker is an atmospheric science PhD student studying tropical rainfall. Let's give an enthusiastic welcome to Alex Parsells.
Hi, can you hear me? Okay, great. Yeah, thanks for introducing me, Clark. And yeah, my name is Alex Parsells. So I want to talk a little bit today about my research and also some of the tools that I use to do this research. So the tools that I'm talking about are reanalyses and climate models, and also energy budgets that come from those. And I use those to study tropical rainfall, but I'll get to that later on. And so really what I want to talk about is just how these tools are made, because I think that they can be and really should be poster children for federal funding of research, because they're incredibly complex and also incredibly useful. And then I'll give you a brief idea of like one small example of the type of research you can do with these. I called this talk Atmospheric Accounting because of a comment that my friend Aiden Ocampo made about the research that I do the other day, which I thought was funny and also true. So Aiden, I don't know if you're watching this, but thank you for inspiring this title. So I'm a PhD student in atmospheric science at Columbia University. And like I said, I work with tools like this. So Merit 2 is a reanalysis product. If you don't know what that is, I'll tell you about it. Climate models like NASA GISS Model E. And then within both of those types of products, I use what's called an energy budget approach. And so the idea is that you can trace the flow of energy through the climate system. And because of the conservation of energy, you can learn something about atmospheric processes. And in particular, the process that I want to understand better is rainfall in the tropics. And so I'm interested in using energy budgets in these products to understand why it rains, when and where, and how much it does in the tropics. And so when I talk about energy in the climate system, I feel like this is kind of an abstract concept. So I want to talk about concretely, what do I mean? And really the idea is that there's several different forms of energy within the climate system, right? So I think probably the most intuitive one is kinetic energy, right? And if you go outside and feel the breeze blowing on you, that's kinetic energy, right? I mean, every kilogram of air has kinetic energy equal to 1/2 times the square of its speed. And, this is something that can be relatively low energy in terms of a gentle breeze, or of course, it can also be high energy in terms of gust from a hurricane. And this is a picture from a hurricane that's sort of close to my heart, because this is Casino Pier from Seaside Heights, New Jersey, where I went every summer growing up. This is impacts from Hurricane Sandy in 2012. And when you look at this picture, right, this is a pier that once was a complete pier and now is a partially destroyed pier. And this roller coaster was not built in the ocean, right? Something put it there. And so you might be imagining like it takes a lot of energy to take a roller coaster and throw it into the ocean. So where did that energy actually come from, right? How did the wind get the energy that it has? And the answer is really that it comes from other reservoirs of energy within the climate system. And so those reservoirs include things like sensible energy. So this is really just the temperature of the air, right? And so, you can measure this with the thermometer. On hot days, the air has more sensible energy. There's also gravitational potential energy, right? So this is just the fact that the atmosphere is within Earth's gravitational field. And so it takes energy to raise air up to a higher height. And so you can actually store energy that way by having air at higher altitude. And then the most important one, probably for the tropics especially, is latent energy, which is the energy associated with the moisture in the air. So, air is not dry. We have water vapor in the air, and we also have solid and liquid water in the air too, in the form of clouds. And when water changes phase, it either releases or takes in energy associated with that phase change. And so, for example, when water evaporates from the ocean surface, it takes energy to do that, and that energy is then stored in what's called latent energy, where it can then be released when the water condenses, right? And if you think about water condensing, right, I mean, that sounds a lot like rain. And the cool thing about the fact that energy is in all these different forms is that energy is conserved. And so you've probably heard of energy conservation in some sense. Maybe, you're familiar with the first law of thermodynamics, which basically just says that energy is conserved. But because of that, we can write an energy budget equation, which is just a simple equation that helps us track the flow of energy through the system. And so here's a really simple one. Right here, you have basically a tendency term. You have a term that represents advection or flow of energy. And then you have a source term that represents processes like radiation and evaporation and precipitation. And so we can use simple equations like this to track the flow of energy through the climate system. And because energy is conserved and not just arbitrarily created or destroyed, we can learn something about atmospheric processes, especially processes like rainfall, right? And so this is a tropical rainfall climatology that we'll come back to later. But this is basically where it rains the most in the annual mean, right? And you can see, I think this is a pretty rich picture. And one of the most obvious features is this huge band of rainfall that goes across the tropics in the equatorial region, which is called the ITCZ, or the Intertropical Convergence Zone. And so what I'll get into later is how we can use energy budget approaches to understand the features of this rain belt. So the question, though, right, is how do we actually quantify the flow of energy through the atmosphere? I mean, hopefully the idea of a budget makes it clear that we can do this in principle, but in practice, how do we actually know where the energy is going? In weather and climate science, we are very fortunate to have what is really like the envy of observing systems in other branches of science. I mean, we've got weather stations all over the place that have been around, some of them for over 100 years. We've got satellites in orbit that have been, some of them orbiting for decades. We've got a lot of eyes on the Earth, and we've got very broad spatial coverage and very broad temporal coverage too. For studies like this, it's still not enough. And we would need to observe much more than we currently do to really be able to quantify energy flows on the scales that we want to quantify them purely observationally. So what do you do instead? You use what's called a reanalysis product. And I'm going to give you the recipe to make a reanalysis product right now. If you are going to try to follow this recipe, I would recommend gathering a few dozen of your most scientifically minded friends and maybe budgeting a few decades to create this thing, because they are really complicated products. So I don't build reanalyses at all. I just use them, but I think it's fun to talk about how they're made. And so what do you do first? You build a climate model. So you start off with the equations of fluid motion, the Navier-Stokes equations, some continuity equation to include conservation of mass, and a few others. And then you have to discretize these equations, because these equations are really meant for the continuous case. And we don't have infinite computing power. So you have to actually take your spatial domain and your temporal domain and discretize it. So you have basically a spherical grid. And then within each grid box, you've got all these processes that are too small for you to resolve directly, but are still really important, so you can't ignore them. So what do? You take those processes, and these are things like convection, things like photosynthesis, runoff, right, transport of water across the land surface, turbulence, atmospheric chemistry, and many others. And you basically take your best guess as to how you parameterize them, or in other words, represent them more efficiently than actually resolving them. And then once you've done that, congratulations, now you have a climate model. You can run it and you can do experiments with it for different forcings. And now you're not even halfway there to making a reanalysis product. So what you need to do next is gather as many observations as you can. And so these are observations that come from basically as many different sources as you can imagine. So weather balloons, right? Moored ocean buoys, radar, satellites, dropsondes. These are things that you literally just drop out of an airplane and they measure winds in the atmosphere. Even, permanent weather stations like this one on top of Belvedere Castle in Central Park. So you gather all these observations, as many as you can, and then what do you do with them? You have to assimilate them into your model. And so there's a process called data assimilation, which is really the backbone of how reanalyses are built. And the idea is you have observations that you want to assimilate, and you have your free running model and the state of the atmosphere that your model simulates without any observations. And then you want to nudge the model towards the observations using something called an analysis increment in order to minimize the difference between them. And so this is an example of the analysis increment that's applied over the entire few decades of the Era 5 reanalysis for a few different variables, so temperature and zonal wind, ozone concentration, specific humidity. And then you assimilate these observations into your model, and congratulations, you now have a reanalysis, except that you've also done something really important, which is you've broken the conservation of energy that you might expect to have in your model, because the data assimilation process and this analysis increment is a totally unphysical process that doesn't happen in real life. And so now you can no longer rely on energy being conserved, which makes energy budget approaches and applying them to reanalysis data quite interesting and not straightforward. But so congratulations, you've now got a reanalysis. Once you combine your model and your observations and the data assimilation process, you can get something like Merit 2. And so now what do we do with that? And so I'll talk really briefly actually about one research project that's just an example of what you can use a reanalysis energy budget for. And this is something that I'm wrapping up now and should be published later this year, involving understanding the seasonal cycle of the intertropical convergence zone, this tropical rain belt that I mentioned. And so if I play this precipitation climatology over the course of the year, right, you can see that as we go through the year, this rain belt isn't static, it moves, right? And it changes intensity somewhat too. There's some zonal redistribution of rainfall. There's a huge meridional distribution of rainfall where the belt is moving north and south with the seasons, but it doesn't move directly with the seasons, right? There's some offset. And so this is a somewhat complicated picture. And the question is, how can we understand it in simplest terms? And there's a well-known energetic framework, it's called, for ITCZ latitude, which I'll just give you sort of a sketch of the idea. And the idea is that the ITCZ, the intertropical convergence zone, is closely tied to the Hadley circulation, which is this dominant overturning circulation in the tropics that you see here. And if that circulation dominates the energy flux through the tropics, which is a big assumption, then the ITCZ should be very sensitive to changes in the atmospheric energy budget. And we should be able to understand even seasonal migrations of the intertropical convergence zone, including how far poleward it gets and when it gets to that poleward extent. We should be able to understand that migration through the lens of energy flux. And so what we did is basically took a bunch of different reanalysis products, so 5 of them that you can see on the left here, and compared a few different methods for computing the energy flux, because as I said, the fact that your energy budget is not closed and reanalyses don't conserve energy makes it not straightforward to actually compute the energy flux. And so we wanted to compare a few different products and a few different methods. And I'll just mention briefly that what we found is that there are seasonal changes to the structure of the Hadley circulation that cause the Hadley circulation to go from exporting energy, an energetically direct circulation, to now importing energy. So compare June on the left, where the ascending branch of the cell here is straight up and down, to December on the right, where it's got this interesting kink structure, which comes from a shallow circulation being superimposed within it. That actually changes it to an energetically indirect circulation for part of the year. There's also an interesting seasonal offset, or you might call it a lag, between the phases of the seasonal cycles of energy flux and precipitation, which I would like to understand more. And then the biggest thing we found is there's a huge amount of uncertainty in the true value of the energy flux across the equator, depending on the data set and the method that you use. And so I'll wrap up soon. I just want to conclude by saying that this type of research would not be possible without federal funding. So federal grants have funded essentially all of my graduate training. I was on a grant from the National Science Foundation for 3 years. Now I'm on a grant from NASA. But beyond funding me personally, they also funded the reanalysis products and the climate models that I use to do this research, and without which it wouldn't be possible. And this is true for many, many other scientists in this field. And I just want to emphasize at the end that, you know, these products like reanalyses and climate models, hopefully I gave you an idea of how complex they are. And because they're so complex, they require a lot of people to build and maintain. And so this is just a sample of 3 papers that describe 2 reanalysis products in a model. And you could see the sheer number of names involved with all of these efforts. And in addition to people, right, it also takes a huge amount of computational effort, which is hosted at places like NCAR, which is currently under attack. And so I just want to conclude by saying that this enterprise has paid dividends over the last few decades, and it's contributed greatly to the quality of life of the average American through improvements in forecasting. But it also requires sustained and steady investment of both dollars and effort. And so let's make sure that those dollars and the tools that people need to turn them into results are available. So I'll stop there. Thanks a lot.
Thank you. That was an amazing talk. Very clear description of the atmospheric energy balance. Everyone in the chat was loving to see your scientific perspective on some things that we see every day. So we do have a few questions about the plot you showed at the end. Specifically, there seemed to be a section where the rainfall was interrupted. What is my life 6927 was wondering if that's Africa that's causing that.
Yes, I think you're talking about the climatology here. And yeah, actually, so East Africa is basically the only longitudinal region where you don't get a clear intertropical convergence zone. So yes, good eye to spot that. You can see it sort of is interrupted here. I actually don't know too much about the dynamics of this region. I mean, I know there's some topography here, which might be relevant. There's also, at least in summer, there's winds blowing from west to east across the Arabian Sea that are contributing to the Indian monsoon. But I don't know that I could say anything super intelligent about rainfall in this region. But yes, definitely good eye, because that is the only place where you don't get a clear ITCZ.
And on the other side of that map, what's causing that large amount of precipitation in the Southeast Asian region?
Oh yeah, so this is what's called the West Pacific Warm Pool, or the Indo-Pacific Warm Pool. So it's in the Western Pacific near what's called the Maritime Continent, where you have Indonesia, Malaysia, etc. And so this is where you have the warmest sea surface temperatures on Earth. Pretty consistently, they're above 28 degrees Celsius. And so because the temperatures are so warm, you get a lot of convergence, and you get basically a huge amount of deep convection in this region. And I didn't mention it at all, but this is actually the focus of the next project that I'm working on now, because historically our idea of tropical convection in the Pacific and its contribution to energy flux has been that in the Eastern Pacific here, you have the equatorial cold tongue where you have cool SSTs, and convection there tends to be a lot shallower. And because it's shallower, that convection actually imports energy rather than exporting it from the region. And the atmosphere is actually losing energy to the ocean, so that makes sense that it's importing energy from nearby regions of the atmosphere. But we've always thought for decades that the deep convection, and we still think this, to be clear, the deep convection is exporting energy from the West Pacific. And what's interesting is we have runs from the GISS Model E climate model that I mentioned, where the energy budget has been closed by a collaborator of ours named Kuni Inoue, who works for NASA GISS. And when you look at the closed energy budget in that model, you find that actually deep convection in this region seems to be importing energy, which is confusing. And so we're trying to understand the process by which that happens. But yeah, so the warm pool is a very interesting region where you have really warm SSTs, and that produces a ton of convection.
Nice. That sounds like a super interesting future project. I think we have time for one last question. Someone was wondering if you ever factor in any terrestrial things like biology, plants, animals, and how those affect these systems.
Oh yeah, good question. So I don't think about them explicitly too much, or I don't consider them explicitly too much in my research, plants and animals, but plants for sure are very important. And from an energetic perspective, I guess what I would say is like the main way that vegetation modulates the energy flux in the atmosphere is through the surface energy budget. So you have fluxes of heat and moisture coming off of the surface. Those feed into the atmosphere. And so especially in places like the Amazon rainforest and the Congo rainforest, where you have a ton of vegetation and a ton of moisture exchange between the land and the atmosphere, that energy flux into the atmosphere in the form of latent energy can have a huge downstream impact on rainfall. And so actually the surface energy budget is one of the least quantitatively understood parts of the total energy budget, to the point where actually our best way of getting at the surface energy flux is actually not to use observational estimates of the surface energy flux, because there just aren't that many. Instead, the best way to quantify it is to take estimates of the top of atmosphere energy flux, which is much easier to get at from satellites, and then use lateral estimates of the lateral transport by the atmosphere, and back that out to get the surface energy flux. And that's actually a big reason why people are interested in quantifying the horizontal flux using reanalyses and models. But yeah, so definitely plants play a huge role through transpiration and evaporation in energy fluxes and rainfall.
Awesome. That's super interesting. Thanks again for your amazing talk.
Thank you. Yeah.
All right. So thank you all for joining us for the 42nd hour of the live stream. Very exciting. Before we get into the next speaker, I'll remind you again why we're doing this stream. The US is at the forefront of weather and climate research, from the development of the first computerized weather forecast to our extensive observational network, as the previous speaker mentioned. These accomplishments were only possible due to the financial support of the government and your taxes, but the current administration's proposed budget for 2027 cuts NSF and NASA Earth Science budgets in half, eliminates NOAA's research funding, and removes programs aimed at young scientists. I myself am currently funded by an NSF grant that terminates this next year, with future funding for myself and my lab group sort of up in the air. If you want the scientists on the stream, myself included, to continue being able to produce high quality science, we need your help. So please follow the link in the description to contact your representatives. The proposed budget is currently being discussed by the House and the Senate, so please go make your voices heard. With that, it's time for some more great science. So please give a warm welcome to Trey Alvey, a research scientist who doesn't only study hurricanes, but also flies into them, apparently. So I can't wait to learn about hurricane intensification. Welcome.
Thank you for the introduction, Clark. All right, so today I'll primarily be giving just a brief intro of some of the research that I've been working on over the past few years. I'm currently a hurricane scientist at the University of Miami with the Cooperative Institute for Marine and Atmospheric Studies. I work closely with NOAA and other federal agencies. Really looking at whether storms align or don't align, and looking at the precursors for rapid intensification in hurricanes. So starting off, what is vortex alignment? So anybody familiar with hurricanes has probably seen a satellite image that looks a little bit like this, where you have an exposed low-level circulation and a mid-level circulation farther towards the east. And this is caused by vertical wind shear that's basically pushing most of the thunderstorms to the east of where the low-level center is. So you think of it in the vertical, it actually begins to tilt. And if we look at a cross-section, it would look a little bit like this, where you have, again, that displacement or tilt between the low and the mid-level vortex. And this is usually an unfavorable configuration for intensification due to shear and dry air penetrating into the core. Now, many times storms undergo rapid evolvements where they become vertically aligned, and you get a configuration that looks more like this, where the low and mid-level centers are now overlapping. You now have an upright vertical column, and you begin to see a cloud pattern that looks a lot more symmetric and much more favorable for intensification. That dry air is no longer getting into the core, and you're able to get these runaway feedback mechanisms that allow for significant intensification. And that eventually can lead to storms, if they're not impeded by other effects from the environment, that looks something like this, where then you have a major hurricane with a well-defined eye, and you get, it's sort of, think of it like an efficient heat engine, where you get sort of this in, up, and out circulation, and it's really just being fed and driven by the warm ocean waters at that stage. So why do we care? If we look at this distribution of the vortex tilt magnitude, and on the x-axis, the TC intensity, you'll notice that, one, there's a large variability in tilt magnitudes, especially for these weaker storms here. But also you'll notice that all of the storms that are stronger, especially ones that are hurricanes or major hurricanes, they all have relatively low tilt magnitudes. So a nearly vertically aligned state is a necessary precursor for a storm to reach some of these higher intensities. Another reason why it's important, here's an example from Dorian, a storm in 2019 that had devastating impacts in the Bahamas. The black line is the best track National Hurricane Center, what the actual final track was. The red lines are the forecasts, and you can see that there was a pretty significant divergence in the forecasts until after the period of reformation or repositioning when we had that alignment occurring. So you can see that can create large forecast uncertainties. And then in terms of my own research, like Clark said, I do get to fly with the hurricane hunters from time to time. One of my first storms ever I got to fly into was Hurricane Irma back in 2017. And here are just a few pictures, the stadium effect and some video from that storm as well. So one of the other responsibilities I have is being a lead project scientist, and sometimes that involves helping to execute the flight patterns into some of these storms. This is from Fiona when it was in its early stage, and here was actually the flight pattern that we had drawn up, and that's what it was supposed to be. In reality, though, things are a lot messier and a lot harder in nature, and this is what it actually ended up being. You can see quite different. You're dealing with responsibilities of not getting too close to land and where you release dropsondes and then deviating for convection, things like that. So it makes it very complicated. And in this case, there were actually multiple centers reforming. So we were trying to fly 2 different centers at the same time. And yes, it was messy. So to look at the evolution of this storm, this was Fiona, like I said. Initially, it was very asymmetric, misaligned. You can see that exposed low-level circulation. And these are all the reconnaissance flights as well through those periods. Then during this period, you begin to see an increase in precipitation. And this is the radar data from Meteo France. And you can see an explosion of convection right near Guadeloupe here. And this actually led to a repositioning of the center farther towards the east. And this blue and green plane here and orange plane, those are actually one of the planes that I was on, helping to be a lead project scientist during this particular case. And then after it went through that alignment phase, then you can see it rapidly organizes and rapidly intensifies into a hurricane, and then eventually becomes a major hurricane once it moves off towards the northwest past Hispaniola. So just looking at that center reformation, or kind of that one center moving towards another, so you get that vertical alignment. This is from the radar data, Fiona. Once again, you can see initial center was to the west, but then you see this jump in the X towards the east, where most of the brighter oranges, yellows, and reds indicating stronger convection, the center moving towards the east, towards that stronger convection, basically pulling it in and leading to a vertical alignment of the circulation, which was more favorable for intensification. So what we can also do with some of this data, so some of the radar data, for instance, we can actually assimilate it into the models, and we can get something that is a quantitative measure. So in this case, this consistency score that lets us know how much improvements we're seeing based on inclusion of data or exclusion of data. And in this particular storm with Fiona, when we include that radar data that I was showing, you actually do see, you can think of the greens as more improvement, the reds as more degradation. You can see that improvements in track, intensity, which is Vmax, and then also R34, R50, R64. Those are all size metrics, so the radius of the 34 knot wind in this case. So indicating the value that radar data does have into these storms. So very important for us to not only incorporate ground assets, but also the airborne radar data from NOAA, and also the Air Force reconnaissance data is very critical for improving these models. So here's a quick schematic kind of summarizing some of the research that we've done in terms of differentiating between storms that eventually become aligned or storms that don't become aligned. again, being critical for determining whether a storm will be able to go on to become a major hurricane or not. And you can see in the aligning cases, first you have significantly stronger initial vortex usually. You also have more up tilt precipitation. So you can think of that as the precipitation is kind of pushing back against the vertical wind shear direction and is actually becoming more symmetric even in the face of that wind shear. Also, the vortex itself is a little bit smaller, more compact, and usually the tilt direction itself is actually in sort of more of this left of shear orientation, which kind of also aligns a little bit with that precipitation becoming more up shear. The non-aligning cases, on the other hand, they tend to have a weaker vortex. They have less precipitation. That precipitation may be farther from the low-level center. The vortex itself may be a little bit broader, and that tilt orientation tends to be more down shear or down shear right. So this next animation that I'm going to show you, this is also from Fiona once again, using the radar data like I was talking about before. You'll track the low and the mid-level centers by the L and the M's, wind and reflectivity on the left, 5 kilometer vorticity, and streamlines at 2 and 5 kilometers on the right. So starting off, you can see that initially you have the low-level circulation is moving off towards the west, but there's not very much precipitation associated with it. But then you have this M that forms pretty far away, this new mid-level vortex near this upscale growth of convection pretty far away from that low-level center. And this is actually the feature very far away from where the actual original center is that will become the dominant mechanism. You can see increases in vorticity, the darker reds increasing near that M during this period. And then this M, this mid-level vortmax or circulation, it begins to rotate within sort of this broader cyclonic gyre that it's embedded within, and precipitation and convection continues to increase within the vicinity of M. L is still continuing to move off towards the west. As deep convection and confluent flow increases near the mid-level center, you can see the vorticity amplifying, those red colors becoming even more prominent. The original low-level circulation begins to elongate as the mid-level circulation approaches it, and convergence is increasing, convection is increasing in this region. So think of it as sort of you're getting kind of this runaway feedback growth that's eventually going to lead to a relocation of this L towards the position of the M during this time frame. You can see the L jumping from here to here as the new low-level circulation is forming near that mid-level circulation. So this is just one example of the complex evolution that can happen in these early stage storms. And this actually led to the vertical alignment, like I said before, and the eventual intensification. So real quick, we can also just show trajectory analysis. We can run trajectories on this data. And for this earlier period, you'll notice that if we simulate the trajectories forward in time, that most of the trajectories actually moved away from the mid-level center. So this was kind of the very early period before the repositioning, the reformation of the center, like I was showing before. During this later stage, this is about 4 to 6 hours later. Now you can see if we run trajectories, they become much more embedded within and around the mid-level circulation. So they're sort of recirculating within the region itself. So that's essentially acting to trap the vorticity and allow for this runaway growth. So real quick, just want to kind of touch on what is the future of the science. So one of the things that we're now working on is incorporating machine learning to be able to get vortex tilt estimates and estimates of the vertical structure, even when we don't have reconnaissance. So right now, reconnaissance is the only way that we can verify the vertical structure of the storm. You can get proxies from satellite, but we don't really have a good understanding or idea of what exactly the storm looks like, because oftentimes with current satellite data, we only see the top of the storm. So that's where we're trying to use machine learning trained on a data set of the radar data from reconnaissance plus the satellite data to sort of give us synthetic analyses even when we don't have reconnaissance available. because just simply we're not able to fly every storm and we're not able to fly all the time. And then real quick, why does all this matter? I mean, I don't think I have to explain too much, why hurricanes matter. They have significant impacts to the US and to other countries. But in the broader scheme of things, most of this research was funded by federal agencies like NOAA, NASA, and the National Science Foundation. And without that funding, this research wouldn't have been possible. And this research is very critical for continuing to progress and improve hurricane forecasts, which have rapidly improved within just the last 10 to 15 years. And so, at least in my opinion, continuing the funding for these agencies is critical to both the protection of life and property here within the US and within other countries around the world. And with that, I'll open it up for any questions. Thanks.
Awesome, Trey. Thank you so much for that excellent talk. The chat was loving all of your graphics and the photos of the hurricanes. We do have a few questions. Firstly, have you ever studied a hurricane that rapidly intensified?
Yes, yeah. So I've studied a few different ones. So actually, Fiona was actually a storm that went on to rapidly intensify. So during its early stages that I was showing before, that's kind of the area my research is focusing on right now. It's kind of figuring out the precursors to that rapid intensification phase. But yeah, I mean, there's been several that both I've flown and that we've studied. I mean, the rapid intensification problem is kind of one of the biggest remaining issues in terms of hurricane intensity forecasting.
And speaking of flying through hurricanes, someone was curious what it was like the first time you ever flew through a hurricane.
It was definitely nerve-wracking. So actually the strongest storm that I've ever flown was the first storm that I flew. It was Hurricane Irma. So it was a Category 5. So several people, including my advisor at the time, have flown many times in their lives and never got to fly in a Cat 5. And that was my first flight. So it's definitely nerve-wracking. The plane itself is actually a plane from the 1960s. So it's very different from like a commercial airliner, like what you'd typically be used to. And I'm actually, I was actually nervous about regular flying even before flying with the Hurricane Hunters. But that's kind of quickly gotten me over it.
How did you get convinced to do this if you're afraid of flying?
I think I've always been drawn to kind of going towards my fears head on. And I think that's,
awesome.
Kind of a good example of that. I don't think there's a better way to get over the fear of flying than flying into a Cat 5 hurricane.
That is one way to do it for sure. Okay, switching gears to a more sciencey question. What are some of the factors that determine how strongly a hurricane will develop?
So one of the biggest and most important factors is the underlying ocean conditions. So from the ocean sea surface temperatures themselves, there's sort of a maximum potential intensity, sort of this theoretical maximum that the storms can reach. So that's kind of the primary fuel engine for these storms. However, there's other factors. Vertical wind shear is an important one, since that can disrupt the core and tilt it, and also kind of keeping the environment from intruding too much into the storm, where surrounding conditions like dry air can have impacts as well.
So since ocean temperatures seem to have a strong influence, can we expect hurricanes to become more intense as the oceans warm?
Yeah, that's a great question. Right now, most of the research suggests that yes, we should expect to see more stronger storms. However, there's kind of this interesting trade-off where a lot of the studies doing future simulations are suggesting that we'll actually see fewer overall storms, but the ones that we do see will be more intense and will have more rainfall. And that just being, there may be increases in vertical wind shear. So some of the storms may have more trouble overcoming sort of the earlier stages, like I was showing in this talk. But once they're able to do that, then they have sort of this unlimited, unimpeded fuel source with those warmer oceans, if that makes sense.
Yeah, that's super interesting. So we are at time, but there are a few more questions in the chat. So if you have time to go onto the YouTube and maybe answer those in the chat, that would be awesome. But thank you again for such a really interesting talk.
Definitely. Thank you.
Okay. So that was an amazing talk. Thank you all for tuning in and continuing to engage with us, with the speakers, and with each other. We've got some more great science coming. But first, let's remember again why we're here. Weather and climate forecasts are so important for policy decisions and everyday decisions. Luckily, U.S. scientists are world leaders in weather and climate science, responsible for advancements such as the first ever computer models of carbon pollution impacts. In particular, the National Center for Atmospheric Research, NCAR, is a world-renowned laboratory which climate science around the world depends on. However, this essential source of data is at risk. The current administration is attempting to dismantle NCAR because climate change research doesn't align with the administration's political priorities. If this upsets you as much as it does me, please follow the link in the description and share your thoughts with your representatives. They have the power to protect NCAR, and they have the responsibility to listen to what we have to say. With that, let's get right into our next speaker, Dr. Makoto Kelp, who is an assistant professor at the University of Utah. He'll be teaching us about prescribed burns in the Western U.S. So welcome, Dr. Kelp.
Great, thank you for hosting, and thanks for the introduction. Okay, let's see if I can control this. Okay, so we'll talk a little bit about prescribed burning today, which I think is a really interesting kind of socio-ecological tool that we have in kind of thinking about and tackling wildfire emissions. And so this is a nice slide that I've borrowed from my good friend Tina Liu, who's up at UBC, and that really fires are a dynamic part of our Earth system. Fires have existed long before humans, and humans have used fire to kind of change and adapt landscapes throughout our history. And so we know that fire is an essential part and component of the Earth system. We know that climate plays a large, important role in kind of influencing fire behavior, from hotter temperatures, creating drought-like conditions, which can amplify fire and emissions. But we also know kind of climatic patterns like El Nino can dampen and oscillate these patterns as well. Humans impose really strong controls on the fire system, both through igniting fires and also suppressing them as well, which I'll talk a little bit about later. But we are feeling the downwind impacts of these kind of increased fires that we're seeing throughout North America and really throughout the world as well, where smoke is starting to degrade air quality and public health way beyond the fire line. Smoke is able to travel thousands of miles from coast to coast basically now. And that we're seeing that fires are starting to transform traditional carbon sinks into sources, like what we're seeing in the Amazon and the Boreal regions in Canada. And so we know that fires are becoming, or are really right now, a inextricably linked component with our climate future. This is a nice paper led by Minghao Chu, for which I'm a co-author on, where we're looking at these different kinds of socioeconomic or emission pathways when we look at these climate trajectories and a bunch of different scenarios that wildfire smoke is present in all of them. And not only are they present, but they're also increasing under these future climate scenarios, where smoke is projected to potentially increase by 3 times in the future. And so, it's not all just doom and gloom. There's ways that we can mitigate the impacts of these future wildfire emissions. And there's a bunch of different timescales we can think of this problem. Many on this kind of live stream who are interested in climate science should always think about reducing fossil fuel and greenhouse gas emissions, right? These are the ingredients that cause a lot of these fire scenarios where we have these heightened probability of fire risk and more emissions, and it's kind of this cycling feedback loop. So we should prioritize a cleaner energy transition. There's also increasing discussion of kind of impact reduction strategies, right? If you're living in the Western US and you have these fires that are affecting your community and your homes, you want to be able to look into home hardening or creating defensible spaces around your houses and homes to protect your property and lives. And there's also an increasing discussion on insurance and reinsurance markets as ways to mitigate kind of the downfall after a wildfire event. But what I'm really interested in is this kind of midstream strategy of hazard reduction. I think it's some of the most proactive strategies that we can pursue, and prescribed burning being a fundamental technique, being that we can use these low-level, low-intensity burns that may clear off the brush of a forest floor, that when it sparks, it may travel up the canopy and create a larger wildfire. So it's this idea of using land management and this fuel reduction techniques as a proactive way of preventing future emissions. However, there's a big problem in the United States, and this is a pretty political and sociological issue as well, and that prescribed burning is basically cut down the middle here of who does it and who doesn't do it. So these circles on the map here represent the total area burned by different fire types. The green color are controlled burns, and the red color is these out of control wildfires. And we see that there's a lot of prescribed burning in the eastern United States. It's very commonly used as a land management technique in the southeast US to clear off hunting grounds, to clear off crop residue, etc. You see a lot in Kansas, Oklahoma, Texas. You know, these prescribed burns have been mentioned in like the Little House on the Prairie books. So it's almost a kind of an ingrained component of Americana. Whereas in the Western United States, it's very much still a limited application. We don't really do prescribed burns that much in the Western US, and you can see that it's dominated by these wildfire emissions. And the issue, though, is that there is not much empirical evidence that if we scale up massively the amount of prescribed burns we do in the Western US, which a lot of these states are actively proposing now as a way to prevent future wildfires, that it'll actually work in kind of reducing and preventing that future risk. And so that's this project that I kind of wanted to talk about, a couple slides, and to ask the question of, do prescribed fires really work in the Western US? And work here means, does it prevent future wildfire emissions? To do that, we look at different treatments done by the kind of US Forest Service and other land management agencies. And looking at these treatments, what happens to those areas after having treated those areas and then a wildfire comes in? And so we look at the 2020 wildfire season, we look at these different treatments, and we look at all these different kinds of high resolution satellite derived variables, including DNBR, which is the change in normalized burn ratio. It's very similar to NDVI, which is kind of this greenness metric of vegetation. This is more like a brownness metric, so how scorched an area of land becomes. We also have PM 2.5 emissions at high resolution produced by inventory and by UC Merced. And we look at other kinds of high resolution covariates as well. And we set up this kind of quasi-experimental design where we compare these different treatments to adjacent or nearby controls. And we look at this all across the Western United States and look at the kind of efficacy of these different treatments in preventing future impacts. And we also control for land cover, time of year, elevation, all these different kinds of metrics that we can kind of take into account in our calculations. And, you know, we find that they largely work, prescribed burns, that pooled estimates, so comparing all these different treatments to all these different controls across the Western United States, statistically reduced 2020 wildfire burn severity by 16%. So if you do a treatment in that area has a buffering capability of around 16% more able to resist these impacts. And looking at California, where we have smoke emissions, they have the ability to reduce wildfire smoke emissions by 101 kilograms per acre. So it's nice to see that these results are significant in a statistical way. But, you know, we found some unexpected results as well. There are different kinds of land management techniques, right? It's not just prescribed fire. There's also mechanical thinning, where you kind of physically lop off branches and kind of put them in a pile and try to take them away, we find that prescribed burns were statistically significant in reducing burn severity compared to thinning. That kind of makes sense and agrees what we see largely in the literature, although there is a lot of differences between ecoregions. But what we found is that treatments done inside the wildland-urban interface, which is an area of heightened policy consideration, and these are areas of high vegetation with people living in it, so it's kind of high-risk areas. We find that treatments done in those areas are actually less effective than those done outside, way outside of the WUI in kind of rural or remote areas. And so this was kind of an unexpected finding, and that we think that this is because when you're doing prescribed burns in an area with people, there's a lot of considerations other than kind of peeling back the fuels, right? You have to worry about smoke exposure coming and inundating that community. You have to worry about that wildfire escaping and going into the community of interest as well. So it's a lot more difficult and to manage. So potentially fire managers don't, kind of go all out when doing these treatments. And this is my last one of my last content slides here. But we wanted to look at what happens if we see these treatments, or what happens with these treatments in terms of kind of an overall budget of smoke. Because prescribed fires are fires, and fires emit smoke. And smoke really from any source is bad for human health when kind of exposed to it. And we find that smoke directly emitted by these prescribed fires make up only 23% of the averted smoke during a wildfire. So they save more smoke than they emit. However, as you can see from this kind of graph where we looked at 2 large case studies of these fires in California, that even though these treatments overall saved smoke, because we're doing so few of these treatments in the West, that it's less than even 1% of the emission of the total budget of this wildfire. So they work, but we're still not really at scale. And there's still questions of what happens if you 10x the amount of fire prescribed burns we're doing. And so what I want to leave people and I want people to think about, because I think prescribed fires are really interesting, is that, there's not much discussion or debate about out of control wildfires, right? We know that they're a problem and that they can potentially be an existential threat to humanity in many different ways, right? But prescribed burns are a problem with respect to a whole bunch of different considerations. I don't like to put a bunch of text on a slide, but I just want to kind of leave you with the idea that prescribed burning is very much a policy problem. It's an implementation problem. It's an optimization problem. It's a public health problem. There's so many different kind of angles to prescribed burns that we're still not really having scratched it. And so that's why I think it's a really interesting avenue for future work that hopefully will be funded as well. And I think it's also a nonpartisan effort because wildfires affect humanity, and prescribed burning is kind of one of our most proactive avenues for mitigation. But with that, I think my 10 minutes are up, and happy to have a little discussion.
Awesome. Thank you so much for that very interesting talk. The chat was blowing up with questions and comments. So we'll get right into it. Do you know if the health of the trees impacts the type or severity of the smoke released?
Yeah, that's a good question. That's like a ecological question. And we still don't really have much of a typology of these prescribed burning effects. So what we have is pretty basic land cover types, basically forests and savanna. We don't really get to the species level. There are a lot of kind of prescribed burning publications and case studies looking at kind of patch level or forest canopy level effects. And they kind of determine or look at species relevant emissions and behavior. But that's another problem with prescribed burning, is that the data quality is very, very low still, because all these different agencies keep records in their own way. Even though we've been doing prescribed burns kind of more actively since the turn of the century, there's no centralized database, and I think only recently, within the past decade, we started geolocating a lot of these records. So it's,
okay.
Yeah, so there's a lot of data quality issues, but yeah, I think there's a lot of ways we can improve this kind of biomass to smoke conversion pipeline.
Mm-hmm. Okay, similar question that you also might not have an answer to given that description, but someone was wondering if tree diversity, so having a mixed forest versus a single species forest, would play a role in the wildfire growth or the emissions.
Yeah, I don't think I'm the person to answer this, but I mean, there's been a lot of really bad land management practices, from clear-cut logging, and there's fuel reduction strategies that involve not burning, right? And in some ways, that's a conversation of what is the best way to prevent future wildfire emissions from a land management perspective, because trees are a valuable commodity. In the United States and the Western US, for example, our logging infrastructure has been shut down, a lot of it through environmental kind of lobbying in the 70s through the turn of the century. So we used to be kind of cutting down trees all the time. Now we are without that infrastructure. So if you cut down a tree in a national forest in Oregon, some of the closest mills are in Idaho. By the time you truck that log all the way to Idaho, it's basically worthless. We also have very underdeveloped biofuels kind of markets for the United States. So we might like the big timber from a tree, but there's also a lot of other components of that tree or biomass that we can use, but we just don't have the markets or the infrastructure to process them. And, trees are important too, right? Like just burning them, you just also create more carbon, which also kind of feeds back onto the climate change system as well. So yeah, it's still an open question as to, is prescribed burning the actual best method to use here? But it's one of the cheapest, and that's why people are a proponent of it.
Okay. Yeah, so one commenter noticed that they themselves have seen an increase in this in prescribed burns. Do you think that the perception is changing in how we treat forests, and prescribed burns are being embraced more, maybe because of the price that you mentioned?
Yeah, I mean, in the Western US, we've started doing that within, the 2020s, I guess, early 2020s, we started to scale it up. It's still not at the rate that we need it to kind of achieve potential reductions in the future. But prescribed burning, it just depends what you're thinking about, right? Like there's also cultural burning from indigenous communities who have been doing these kinds of practice for millennia, but it's not always about preventing future wildfire emissions. It's about kind of managing land, managing soil and ecosystem health. It's still an open question. Are we going to feel those effects, right? Because if you do a prescribed burn in 2024 and you do a lot of them, then the next year you don't do anything. There has to be some kind of cadence of maintaining ecosystems where it might have to be kind of a routine part of our land management practice. There are kind of older colonial records and indigenous records in California saying that the Central Valley was filled with smoke basically year round because of kind of constant cultural and prescribed burning. And so, then that's another kind of trade-off, right? Do we want to experience kind of low-level smoke intermittently throughout the year to prevent large orange sky events that may come for a week or a month, right? So another kind of trade-off, which is a pretty interesting kind of problem to think about and explore.
Yeah, speaking of those trade-offs, a commenter was wondering that with the trade-off between short and long-term impacts, do you have any insights on how to overcome this?
Yeah, I mean, I think this is more of a science, communication, and policy question, because the impacts we feel from an increase in prescribed burning or a rapid expansion is going to be negative in the short term, right? We're releasing a ton of smoke, and we might not achieve the desired effects of future wildfire emissions being dampened immediately. And so kind of the externalities or the impacts on health, economy, recreation is going to be negative within the first few years of a treatment. But then, there are some new emerging evidence and studies showing that, but within the end of like a 10-year span, that benefit is going to be, massively paid for by itself. And so, yeah, you got to communicate that, and there's going to be pushback, but you have to kind of see where the projections are going and, look at the kind of long-term outlook on these kinds of treatments.
Awesome. Thank you for that lovely response. I do think we are out of time, but that was an amazing talk. Thank you so much.
Great. Thanks so much.
All right. Wrapping up the hour, we only have one talk left and then 8 more hours to go. Before I introduce the next speaker, I'll again discuss why we're doing this stream. U.S. scientists and science institutions are vital to weather and climate research around the world. This is due to decades of investment into this infrastructure by the American public. However, the freedom for these scientists and institutions to pick what research is needed is under attack. The Office of Management and Budget has proposed extreme rules for research funding, allowing political appointees to make these funding decisions instead of the scientists, and limiting the type of science that's eligible for federal funding, and restricting how scientists can share their work with other scientists and with the public. So if you want more public science talks like this, making weather research accessible to those who actually need it, and if you want important science as decided by the scientists themselves and not external parties to continue being funded, please, please, please contact your representatives. Tell them you oppose the OMB's proposal. You can click the link in the video description and it will take you to a call script that you can follow, which makes it so easy to have your voice heard. Well, with that, let's get into the final talk of this segment, Courtney Payne, who is a postdoc at CU Boulder. Wow, Inception.
Sorry. Okay, sorry about that. Hi, everyone. I'm Courtney, and I'm presenting today about the potential impacts of marine cloud brightening on Arctic marine ecosystems. So as a consequence of climate change, increasingly we're looking at doing some more extreme climate interventions to manage and reduce some of the unwanted consequences of climate change. So one kind of branch of these different climate intervention strategies is called solar radiation modification, or solar geoengineering, whereby we would alter the reflection of shortwave radiation or the transmission of longwave radiation. And one of these strategies is called marine cloud brightening. So the way marine cloud brightening works is that we would, if we were to implement this, take boats, move them around the world's oceans, and use them to spray sea salt aerosols into the lower parts of the atmosphere. And those sea salt aerosols would act as cloud condensation nuclei. They would lead to extra cloud formation over these parts of the ocean and enhance the amount of light, that is sunlight, that is reflected out of the Earth's atmosphere. So marine cloud brightening is a strategy that we've kind of thought about employing in the Arctic as a means of increasing the amount, the kind of extent of the sea ice in the Arctic, and saving a strategy for saving the sea ice. And that's the purpose of the kind of experiments that I'll be presenting on today. So we don't, fortunately, rely on actual experiments in the real Arctic. We are using a modeling framework to assess how this could work. And we rely on the Community Earth System Model, or CESM. And this is a model that's developed at NCAR, the National Center for Atmospheric Research in Boulder. We use a particular version of this model that has quite a few different phytoplankton and zooplankton functional types, so it has a complex marine ecosystem, and it can be used as input for a fish model as well. And in this talk, I'll compare these 5 different baseline simulations, which we look at between 1920 and 2070, to 6 different marine cloud brightening perturbations for 2035 to 2070. And these different perturbations differ in both the strategy as well as in the magnitude of the perturbation. So we use 2 different strategies in these, We use two different strategies in these experiments. One is a summer strategy, whereby we seed clouds in every grid cell, every part of the Arctic north of 67 degrees north, but only for May through September. Those are the months where this is most effective. We also rely on a dynamic mask perturbation, which is maybe a more realistic or easy to implement strategy. And in this strategy, we seed clouds still for the area north of 67 degrees north, but just the ocean, and just the ocean where there's not super high sea ice concentration. So this is maybe, yeah, more realistic. We could actually get boats to the areas where we would need to seed clouds in order to make this happen. So the green parts of these plots you'll see are places where we've seeded most or all of the time in these experiments, and the white indicates places that are seeded less often. So you can see that there's some really, with the dynamic mask experiments, there's some really big shifts over the season in what parts of the Arctic we are seeding with clouds. And then I also mentioned that we look at 3 different magnitudes of perturbation. So in these experiments, we increase the cloud droplet number, which is about 50 across the Arctic normally, to either 100, 200, or 400. So we kind of double it each time to assess how the ecosystem would change as a result. So the first kind of important metric that we looked at was how the sea ice area increased as a consequence of these perturbations. That's the point of the perturbation, so we want to see if that was effective. And here I've plotted over the 21st century the change in annual sea ice area across the Arctic. And you can see that there's a pretty big decline over this whole period. When we do these perturbations, pretty immediately they typically yield an increase in sea ice area, and an increase that's well outside of the range of what we are seeing in the baseline simulations for almost all of these perturbations. So they're effective in the thing that we most want to do, which is increase the sea ice. This is typically when these sorts of experiments are done. The team is a bunch of atmospheric scientists, and this is kind of where their sea ice investigation will stop. But for this particular grant, the sea ice expert we have on hand had some other questions that he wanted to look into. So first he started looking at the annual cycle of Northern Hemisphere snow and sea ice. And here I've plotted that between 1920 and 20 in light green and 2040 in darker green. And that's for the ice area, the ice volume, and the snow volume. And as you can see, for all of these characteristics, they have a really big seasonal cycle in the Arctic. We have high ice area and ice volume and snow volume in the winter and low in the summer. And there's also a big change over time. As we move into the 21st century, the ice area gets less extensive, the snow volume gets thinner. And when we look at these different perturbations, many of these perturbations, especially the lower magnitude ones, kind of return the ice state to historical conditions. So we see ice area that maybe looks like the early 1900s rather than like the 2040s, even though we're looking at it over the same years. However, for snow volume especially, we can see that the higher magnitude perturbations shift snow and ice state to a lesser extent to conditions that are really unprecedented in recent history. So typically in the summertime, snow entirely melts on the surface of the ice in the Arctic. But as you can see here, there's in some cases almost more snow in the summertime than there would have been in the winter in the early 1900s. And perhaps not surprisingly, that huge change in snow leads to a lot less light getting into the surface ocean. And what I study is phytoplankton. These are the single-celled plants that drift in the surface ocean, and they're really important because they feed the ecosystem. They are the base of the marine food web, and also because they are an important component of the global carbon cycle, because they take up carbon in the surface ocean and they can sink down deep into the deep ocean and sequester that carbon for really long time scales. And one of the most important metrics for phytoplankton is net primary production, which is how much growth, how much carbon they fix, and that might be available to either sequestration or to the ecosystem as a whole. And between 1920 and 2070, phytoplankton have typically ended up producing 350 to 500 teragrams of carbon in the Arctic. However, there's been a big change over time. So between 2035 and 2070, they typically produced about 450 to 500 teragrams of carbon. So the kind of high end of this long-term mean. And that's just because as sea ice is reduced, there's more light in the surface ocean. Phytoplankton, which need light to grow, can grow more rapidly, and thus there's more food available for the marine ecosystem. So when we look at these different perturbations, those dynamic mass perturbations, the more realistic, weaker perturbations, kind of yield us conditions that are somewhat analogous to earlier parts of the 20th century. However, for the summer perturbations, especially the 200 and the 400, where we saw really unprecedented snow conditions on top of the sea ice, we can see that there's a huge reduction in Arctic NPP, that we're really shifting well outside of the bounds of what was observed typically in the early 1900s. And that decline is really focused in the central Arctic. Here I've plotted those summer and dynamic mass perturbations and what the resulting change in productivity is for them for each of the different magnitudes, 100, 200, and 400. And you can see that across the Arctic, for the area north of 80 degrees north, we get a 15 to 82% decline in productivity. And over this whole region, the Arctic and subarctic, we still see a 3 to 9% decline in productivity. So it has some pretty big regional consequences. I also looked at changes in fish biomass. I saw that there was a 17 to 72% decline in fish biomass north of 80 degrees north relative to unperturbed simulations. And over this whole region, who cares? No one cares that much about the area north of 80 degrees north because people don't live particularly close to there, and there aren't fisheries that are really important there. However, that's not true of this region as a whole. Within the Arctic and subarctic, some of the world's most important fisheries are located. And we can see here that there's a 4 to 12% decline in fish biomass in that region as a whole. So this could have some pretty big consequences for the fisheries of the area. So in summary, my work indicates that Arctic marine cloud brightening can result in increased sea ice area. However, higher magnitude perturbations can result in sea ice and snow states that are unprecedented in the 20th century and reduce light in the upper ocean. And those reductions in light lead to large declines in Arctic phytoplankton productivity, particularly in the central Arctic, which in turn yields large reductions in fish biomass in the Arctic and subarctic. Thank you so much, and I'd be happy to take any questions.
Amazing. Thank you so much for that talk. Super interesting. We do have a few questions in the chat. Let's start off with, how is thick snow on ice different from thick sea ice?
Yeah, so snow on ice has a really high albedo. It reflects a ton of the incoming solar radiation. I think it's pretty close to 0.9. So 90% of the light that's incident on that snow is reflected. It's close to the same for thick ice. I think values of 0.8 would not be unexpected, but that 10% difference has some big implications. And I think maybe a secondary thing is, I didn't emphasize this potentially enough, but the ice is both quite a bit thicker and the snow is thicker. So you're getting huge increases in the albedo and thus a big increase in the light that's not being retained in the system.
Okay, super interesting. Secondly, have you seen any evidence of fish species or other species migrating further north to the cooler waters? Also, sorry, my cat really wants to say hello. Enjoyed your talk as well.
Love an animal who appreciates a good talk. I think that so the fish model has some limitations. It only allows fish to increase or decrease within any given grid cell. So there's no migration in this fish model. That said, we do see changes in the relative importance of fish by different places. So the fish model has 3 different kind of functional types. It divides up fish into like the bottom feeders, the pelagic fish, and then forage fish, which are smaller kind of, and there are examples of the types of fish for each of these categories. I won't go into that. But pelagic fish are maybe like tuna, and demersal fish might be like cod.
Okay.
And with these different, especially with the more extreme perturbations, we can see that certain places that would have historically had really been cod dominated, they become more forage fish dominated. And that means that there's, they would not be an ecosystem to the same fish that have existed there for a long time. So.
Okay, super interesting. Switching gears back to the algae, is there a trade-off between having more open ocean, having that open ocean algae, and then the under sea ice algae, which is also important?
Whoever has asked this question is really, this is a feeder question for me because I am an under ice phytoplankton person. I think that so under ice phytoplankton blooms are a phenomenon that we've only started to observe in the last 15 years. I think they've probably been happening for a very long time before then. This is a very cool thing where we thought that phytoplankton in the Arctic would only grow in open ocean conditions, but increasingly we are observing them in an under ice environment with sufficiently thin ice. We didn't test under ice phytoplankton productivity in this study, but I would suspect that there would be a pretty big reduction in that because the ice is a lot thicker and because it's optically kind of impenetrable. There's not a lot of light that's getting into the under ice environment. So while this model, while these baseline simulations show that there's about a 20% of total productivities happening under the ice in the baseline simulations during this kind of time period, I anticipate that it'd be quite a lot lower in those more extreme perturbations.
Okay. Very cool. So there was also a comment just shouting out the NCAR models that you use. Could you talk maybe a little bit about how NCAR is supporting your work?
Yeah, so this project, the PIs for this project are based at NCAR. I work at NCAR a couple days a week. NCAR is an incredible working environment where you can collaborate with scientists from all different specialties, and that's kind of why projects like this are able to happen. I think atmospheric scientists working closely with sea ice scientists and phytoplankton people can ask really interesting questions about the consequences of perturbations like these that other groups might not think to act because they're not interfacing so closely with people with different disciplines. So I certainly think that work like this is one of the many reasons why NCAR is an incredible place and should continue to exist in its current form.
That is awesome. Is there any projects or current questions you're thinking about that you'd really like to look into next?
Yeah, so I have mentioned that phytoplankton have some big impacts on carbon sequestration. We see that in these simulations that the increase in sea ice leads to increase in Atlantic meridional overturning circulation. So the kind of conveyor belt of heat that moves into the Earth's interior, ocean's interior, which happens in the North Atlantic. And it seems like we also see an increase in carbon sequestration through that same process. So I'm really curious to investigate further how these perturbations might impact carbon storage in the ocean.
Oh, that sounds super interesting. All right, well, thank you so much for your talk and for answering questions so well and for filling in last minute. It did not seem like that was the case at all. That was a very great talk. So thank you again.
Thanks so much.
All right, and thank you all so much for your continued support of this stream. This does end my portion of hosting. I have to sign off and head into work, sadly. This is way more fun than work. But I will be handing the reins off to Robert Pincus, who'll take over as your host. It's been a pleasure.
This is work, Clark. This is work. This is the work.
That's true.
Thank you. Thanks for hosting. All right. We are just about to roll into hour 43 of the 2026 Weather and Climate live stream. there we just rolled in. I really hope this doesn't become a regular thing, because science is a little bit in crisis in the United States, and we are asking for your help. There's 3 topics I'm going to talk about over the course of the next 2 hours. Every time I talk, I'm trying to get you to help us. Or as Dora the Explorer says, we need your help. And we need that because we want you to apply. We're going to ask you to apply some pressure to your elected representatives. And in this case, to comment on proposed regulations by the Office of Management and Budget. So that's what I want to talk about now. Last Friday, the Office of Management and Budget, that's part of the executive branch of the United States government, proposed sweeping new changes in regulations. And our excellent directors are going to drop in 3 links into the chat. One is an article from Scientific American that gives you an overview and a sense of what these are like. One is a more detailed analysis from sort of a scientist and policy person. There's the Scientific American summary. And one is the link to the proposed regulations themselves. And let me, DNR, this is a disaster. This is a recipe. Basically, the intent here is to exert complete political control over all scientific research, not just weather and climate, all scientific research done in the United States. And it's a recipe essentially for the destruction of the American scientific enterprise. So I'm at work this morning. I'm at the Lamont Doherty Earth Observatory. There's people from the live stream are here. Adam Sobel is 2 doors down. Michaela Biasuda 3 doors down. The often mentioned Jiayang Li is through that wall. Shane Russert, who gave a great talk, is right behind me. And this institution has been in place, I think, since the 1950s. No, we're 75 years old this year, so right about 1951. And plate tectonics, the idea of plate tectonics was discovered here. This institution has been involved in all kinds of cutting edge, so biogeochemistry was an understanding of some of the Dansgaard-Oshkosh events in which big rafts of the melting Laurentide ice sheet shut down the AMOC. All that stuff was invented here. Some of it has practical use. I'll come back to that, but lots of it doesn't. And what the Office of Management and Budget is proposing to do will essentially make progress like this not possible. That's a bad thing. But the good thing is that you, every single individual person, can go comment as a member of the public on these proposed regulations. And so that is the link for comments right there in the chat. And so I would really urge you to go to read up a little bit and to explain to the Office of Management and Budget why they shouldn't do what they're proposing to do. I would so appreciate it if you would do that, because if the government could indeed exert complete political control over the American scientific enterprise, but the scientific enterprise would be a smoking ruin. And that's not good for anybody. It's not good for us in practical ways, and it's not good for us in cultural ways. All right, go do it. Do it early, do it often. And while you're doing it, we have Ellen Ellen McRae to come speak to us. Sorry. After asking you how to pronounce it, I forgot it because I'm not looking at that screen.
That's great. No, I was like, I've never had to spell out the pronunciation.
Right. So Ellen McRae is a former federal climate scientist and a service delivery expert. And now she is helping do the practical work of connecting science to industry users. So thank you for speaking to us, Ellen.
Thank you, Robert. Well, this is really exciting to be on here, and thank all of you for doing this over such a long time. Yesterday, the day before, it's just been wonderful to see so many colleagues back again. I think one of the hardest parts about leaving NOAA after I did 20 years with NOAA and another 10 years with the US Geological Survey. And I think one of the hardest parts was feeling like the band was breaking up. So it's nice to have everybody back together. So I'm super glad that you talked about the OMB issue, Robert. And I'm just going to talk about the work that my new company is doing. We're called Aeolus Climate Strategies, and really the connections that we're making between, in this particular instance, the climate science and the insurance industry. So I don't know if I have control of these. or if I just should move to, oh, I see it. Yep, I got it. Okay. So who are these people? Everybody's been talking about insurance, and we've suddenly become very popular. And I think it's because, as my old mentor used to say, Margaret Davidson, she always said that we have to look and follow the money and figure out where we can make the biggest influence and change in this, in the way we approach our changing climate. And so the insurance and reinsurance industry has been doing an incredible job with a series of scientists that are on staff of some of the larger companies, as well as some of scientists and science interested in some of the other parts of the ecosystem of insurance. So for those of you that aren't as familiar with the insurance industry, I just put up a bunch of different companies. You probably all have your own insurance company, but we have insurance companies that do your property and casualty insurance, and they insure your home, they insure your car, they do health insurance, and some people do health insurance, but this focus is on property and casualty insurance. And then we have the reinsurance companies. Those are the bigger companies that insure the insurers. So it's basically all how humans are managing risk. When we manage the vulnerability and exposure, which equals the equation of risk, it's about really transferring that risk off of the asset owner, in this case, the homeowner, and transferring that to your insurance company in case of a loss. That insurance company then transfers their loss to larger reinsurance companies, which are busy watching the markets and making sure that the pricing is appropriate. In addition to the pricing from the companies, though, we have regulators in each of the states that run the offices of insurance commissioners. And those commissioners are responsible for making sure that the insurance stays affordable for those different, for their own citizens within that state. Insurers are informed by property and casualty catastrophe modeling companies that are busy taking all of the science, ingesting climate models, ingesting anything on severe convective storms, from derecho to tornadoes and hail and high winds other than derecho. Brokers, actuaries, there's a whole group of people that are busy trying to inform what happens in the insurance arena. So, oh, it's interesting. My title's been moved a little bit here. Sorry. So in terms of how we did this within NOAA and how I continue to do this now that I'm outside of NOAA, it's really thinking about engaging with the kinds of industry sectors that have a concern about a changing climate, or where climate can impact their business models. So we worked across and still work across the different sectors of insurance. We work with transportation officials, roads, bridges, highways, all dependent on changing heat and precipitation conditions. Energy companies, electric utilities primarily, but also the corporate real estate world, the health, thinking about health impacts from air quality changes to changes in heat, and so many more. Pretty much, we used to say every sector of the U.S. economy is impacted by climate information. And so it's really about connecting with what I call the power users and the non-power users associated with these different industries, and becoming that trusted partner and the person that they can go to find the kind of information that they need. So that's really that technical assistance piece that's so valuable in climate science and climate services, is being able to help people find what they need to make their own decisions. We do this through a very deep and continuous engagement process that includes that kind of technical assistance that I'm talking about. So within the insurance industry, the concern is definitely being able to look at weather and climate risk. Many of you may be familiar with the billion-dollar disasters from my friend Adam Smith. Adam has moved this product over to Climate Central, so this is a slightly older graphic, but it really the insurance companies, and as well as the rest of us, are looking at the prevalence of billion-dollar disasters around the country and thinking, wow, we need to start thinking about what our coverage is when it comes to the risk we assume on our homes. And so the insurance companies are looking at the deployed capacity that they have to cover these losses around the world. And it's adding up to be about $500 billion worldwide. And within the United States alone, they're covering the losses annually at about a tune of $105 billion just in the last 5 years. So this is a huge business that completely depends on the science and the data ecosystem from the federal government, from the academics, from a lot of the experts in the climate and weather arena that are helping to inform those catastrophe models that the industry is using, as well as inform their actuaries, their underwriters, and so many pieces of the industry that help determine the pricing. So that insurance and so many other industries that I already mentioned depend on credible information. Credible information is really what we consider to be inherently governmental in terms of the real-time observing systems, for example. The United States is probably the most well-observed portion of the globe when it comes to our investment in buoys in the ocean, looking at El Nino and La Nina conditions, drones flying overhead, tide gauges along our coastlines, satellites around the world, ships and aircraft, just looking at hurricanes and looking at the global ocean, as well as every one of the in situ platforms, including USGS's stream gauging network and the cooperative observing systems of the weather that report daily into the Weather Service to verify and validate the observations around the country. This is a huge investment in terms of not only the ability to collect information at the very base of the triangle, which is really that observational infrastructure, in case you can't read it, but it's also that collection and transmission of the data so that all of the investments that are made in this observing structure are available to the taxpaying public. Those data need to go out in not just the raw form, but those data come in to our data centers and they get processed to make sure that we're distinguishing between a very outlying number, and we validate those numbers to make sure that it's all trusted and true. That data stewardship is really important to the quality control and the accessibility of those data. And we're working towards a cloud model for those data so that they would be more easily accessible. In addition, as you move further up the ecosystem, at least in terms of NOAA's information, we move from that collection of information to the data and the quality assurance of those data, and into the use of those data for Earth system models and Earth system inputs for all of the weather and climate models that are run within NOAA as well as around the country. So a lot of academics and so many of our scientists around the US access this information. And then where I was sitting was what they called the pointy end of the spear, I guess, which is sort of a strange term. But essentially, the top of the triangle was really that translation and that interpretation and decision support information, where I was responsible for making sure that happened across the eastern part of the United States. So there are some risks to what's happening now in terms of those observing system on which our entire weather and climate ecosystem depends. And that is the underfunding of the observing systems themselves. We have some ships and aircraft with lost days at sea with maintenance issues. We have buoys and in situ observations, including all of the weather stations, that require maintenance. If they go down, including the stream gauging network at USGS, a lot of those hydrotechs have left federal service. So there's a lot of concern, especially in the insurance industry, and I'm speaking specifically for that, about the proposed elimination of the research centers and the proposed elimination of some of the ways that we support the observing systems around the country. And really around I shouldn't just say the country, but really around the globe in terms of our observing systems in the ocean and our satellite systems. So there, as you know, and this is part of the reason why I think Robert is hoping that you guys will all take some action across the bottom of your screen, is really thinking about the workforce reductions. So there are several of us that are monitoring what's happening in terms of the loss of some of these observing structures and some of the research structures. And really it comes down to the huge loss of the federal workforce. It seemingly is skewed towards the longer career scientists. We've lost hundreds of PhDs and also that institutional memory. So there's a lot of hiring that's trying to occur right now, but that is happening at some of the more introductory levels of federal service. And so that sort of historical knowledge and the background of where to find things or what we've already tried before and maybe shouldn't bother to try again is different. So that's part of the concern. As a result, I think the ultimate concern for the science community is this potential loss of data quality. Some of those foundational data sets on which many of us depend, the forecasting and observing systems, and the concern that that there's just a backlog of humans' ability to validate and quality assure the data that is coming in. We've all been assured that the data are still coming in, that the observing systems are intact. I think the concern is actually more of a tail risk. There's a lot of concern that we just don't have enough people to keep up with the kind of cadence that people have become used to, what we call the latency, or the amount of time it takes between the observation being taken, the quality assurance being done, and the report and the access being allowed. So you can just squint your eyes and look at the decrease in the black graph and look at the decline in the staffing levels changes from prior years as reported by Nature. So that's really the concern that I think many of us are thinking about. So what's being done about it? A couple slides of what's being done about it, and then that's it. So the first is thinking about my company and the work that we do across the understanding of the different hazards that we have coming out of NOAA, USGS, Army Corps of Engineers, NASA, name your science organization, and our deep understanding of our hazard by hazard understanding, whether it's flooding or drought, hurricanes, hail, high heat, air quality, you could go on. But how those are applied to the different parts of our country, whether that's done at the state level or across the nation. We have coastal experts as well as folks that focus primarily on inland concerns. We also take this to the state level and to the local level. And that's a scaling issue, right? We have lots of counties and communities that need this information. So working at the geographic scale with partners in the philanthropies and in the industry areas is a big part of climate services. Additionally, it's those relationships at the different industry sectors. As mentioned, I did a big focus on the insurance and reinsurance industry, as well as the transportation sector, the engineering sector, and the health sector. So lots more work. And then I'll just move on to the last slide here. And that is that there are more actions being taken specifically by the insurance industry. We are keeping the industry concerns at the forefront and working with congressional members. We're talking with federal agency program managers, and we're supporting the preservation activities that are happening in the private sector to try to preserve access to data. We're also building coalitions across the different associations to make sure that we're working together to reach Congress and talk about these concerns about the observing systems and data quality. And then we just want to leave with the fact that the future system is going to have to allow for various approaches and redundancies to define what is essential public information and how it's used across the world. So I'll just leave it at that.
Thank you so much. We have a couple of questions and not a whole lot of time. So can we highlight what dogs question, which is to say, will insurance go up for everyone if forecasts get worse?
So there's a bit of a check and balance in the insurance industry in terms of the rate and how the rate is set, and then also the regulation of those rates. And so when you think about different insurance companies, say, pulling out of California and Florida, as you've heard about in the news, other people having their insurance companies change their rates, that's managed by the state insurance commissioners. And so that's one place that you can call as your representative if that becomes a concern for you. Also, states are finding that they are backing their own plans. Sometimes they're called the FAIR plan. So that's another way to access insurance if you run into problems.
So Hannah had a question that hopefully you can answer relatively quickly, which is there somewhere we can get amounts and numbers for talking points? And in particular, it sounds like she'd like to use this in her red state.
Well, I guess you can email me. There are, I'm thinking about, like, you're thinking about sources for this kind of information. There are some companies that have their own platforms that are available. So you can look on, some of the reinsurance sites to find their platforms and how they track these data. And then you can find, there's if you look back, I don't know if they have access to the slides, Robert, but you can look back on my first slide where you can see the concentrated losses. The New York Times also reported on concentrated losses and have maps that might be helpful for the vulnerable. Oh, thank you. The second slide, third. Yeah, there you go. So you can see that there's actually a Dun and Bradstreet analysis. So several financial sector places where you can find that information.
Just as a reminder to folks, these live streams are recorded, and so you can go back and page through and find slides and so on. There is another question. I think we have to move on, though, but that question, just for you, maybe you can respond to it in the chat, is about the transition from public to private. And it seems super interesting.
Yeah.
All right. We are
Go back and check out the NOAA panel on this site yesterday. And we talked all about how we all loved our jobs, and, so it's great.
Thank you so much.
Thank you.
I am here to remind you of why it is that we are staying up all night and taking time out of our work days and spending time preparing things. But you know what? You already know that. So instead of listening to me yammer at you about why you should call your folks, call your folks, you should do that too. But what you should do is call your representatives and explain to them why cutting the scientific research budget is also a terrible idea. So you can do that and not listen to me, and that's okay with me. But let me explain to you why that is. So this year, like last year, the president's budget has enormous cuts, roughly 50% for geoscience in NASA's budget, roughly 50% for geoscience in the National Science Foundation's budget. And the agency that Ellen was describing, NOAA, which if you can imagine an agency more in service to the nation, it's hard for me to do. That agency has its Office of Research just eliminated. That doesn't seem to me like a particularly great idea, like it's going to engender the health and welfare of our country. And if it doesn't seem to you like it's a good idea, why don't you call your representatives and tell them that? And I want to just stress how effective this can be, because last year, the president's budget looked a lot like it does this year, including all of the budget cuts and the very large reductions. And Congress said, no, we won't do that. We will instead fund our agencies at roughly flat levels, which is less than ideal in a world with large inflation, but is nonetheless an acknowledgement of how important the American scientific enterprise is. So please call them. We tried to make that easy. The call thing, call URL in the crawl down there has a couple of things, including a script. I read last night in the chat that someone was worried about retaliation. They would like to do this anonymously. I don't know that that's possible, but I want to stress that, like, your representatives are beholden. They have to listen to you as a constituent. You have no reason to be afraid of retaliation. This is their job. They are there to represent you. So please tell them what you think. Make some noise in the House and the Senate. That'd be terrific. All right, we will move on to our next speaker, who is Maria Galuchkina, who's an early career scientist, and is going to talk to us about animals in the ocean.
Hi, Robert. Thank you so much for that beautiful introduction. And yes, like Robert said, please call your representatives. It is your right as a constituent. Bother them. Tell them exactly how you feel about science and science funding. My PhD, which I'll talk to you a little bit about, as an early career scientist, I spent a lot of time funded by the NSF, and also like a lot of the data sets that I use and that I'll describe are publicly funded and are critical to so many people around the world. And I want them to continue to exist. So I'm Maria. I'm an early career scientist. I recently defended my PhD, and I wanted to talk to you a bit about coral reefs in a warming world and how we could possibly forecast coral bleaching months in advance. And I want everyone to leave this talk caring about coral reefs, not only because of their incredible biodiversity, they are the world's most biodiverse ecosystem, but also because corals confer so much economic value and ecological value to nearly 1 billion people around the world. They protect countless low-lying island nations from storm surges. Nearly 500 million people worldwide rely on coral reef fisheries for their food and their income, so it's a matter of food security as well. And a lot of nations, particularly around the Caribbean, rely heavily on coral reef tourism for their GDPs. And despite the fact that coral reefs are super duper valuable, as you can imagine, as we all know from being on this live stream, not only have air temperatures gone up over the last century, but so have ocean temperatures. Everywhere in orange and red shows warming over the last century. And in particular, I spent a lot of my PhD thinking about the Caribbean, which over the last 50 years alone has warmed from 1 to 2 degrees Celsius. And this has led to an increase in marine heat waves, both in their frequency and in severity. And coral reefs, out of all the ecosystems that exist, perhaps have the most unambiguous response to marine heat waves via coral bleaching. Typically, when corals are healthy, they're full of color and structure, as in the image on the top right. However, when corals are faced by extreme heat, they expel their algal symbionts, so they lose their color and they lose what gives them 90% of their food. So they're essentially starving to death and they have this pale white color. It's important to note that this is a temporary state. Corals often do recover from bleaching if the heat wave recedes quickly enough. But in this particular case in the Central Pacific in 2015, 2016, that did not happen. All of these corals died. It takes a really long time, if ever, for a reef to recover after such a mass mortality event. And in response to these devastating bleaching and mortality events across the globe, numerous organizations have invested both millions of dollars and countless man-hours into reef restoration projects. On the left is an image of a coral tree, I believe offshore Florida, and on the right is a photo from Belize. But essentially what people are doing here is they're growing baby corals out on these trees. They're monitoring them, and then when they're big and healthy enough, they outplant them onto existing reefs to try to grow out. But even these efforts are not immune to marine heat waves. I'm not sure if any of you guys remember the news from around September 2023, when ocean temperatures offshore Florida hit nearly 100 degrees Fahrenheit. I think they might have actually hit 100 degrees Fahrenheit, which is crazy warm. And during this heat wave, every single one of the coral outplants on these trees bleached. And restoration practitioners scrambled to get the survivors out of the sea and onto land-based tanks, which you can imagine is very physically and logistically challenging. And in the end, nearly all of these restoration fragments died. So millions of dollars and years of effort were obliterated in the span of a few weeks. And with an event as devastating as this, the question remains, can we provide enough warning so that rescues like this can be successful? Specifically, can we provide warning on the order of multiple months in advance? So I want to argue that we need accurate forecasts for successful responses. And what I mean by accurate, I not only mean correct, but I also mean early, so far enough in advance for people to take action, and localized, meaning relevant to the particular area that you're focused on. And we do have an early warning system. It's called the NOAA Coral Reef Watch. If you want, you can play around on this website. It's free. It's available to everybody. Every coral reef manager, practitioner, scientist, whatever that I've talked to, both in the US and internationally, use this product because it's free and it's publicly available, and it's kind of the only thing we have. It uses satellite temperature data and computes a metric, which we call the degree heating weeks, which is essentially an accumulated heat anomaly over the last 12 weeks. This is both a really great product, but there are a few caveats, one being that it's not locally calibrated to local coral reef response. And it's also not enough of an advance lead time for people to take action. So typically in between 4 to 8 degree heating weeks, so anywhere in like yellow to orange, we expect bleaching to occur. And anything above 8 degree heating weeks, we expect to see mass bleaching and mortality. But say I'm a coral reef manager in the Southern Caribbean, where this white arrow is pointing to. At this moment, no bleaching is predicted to occur, and I'm not entirely sure what's going to happen with this heat wave. I'm not sure if it's going to expand, if it's going to contract. So at this point in time, in August of 2024, I'm not sure what's going to happen in October of 2024. So this motivated a lot of the work that I thought about of how we can build a better bleaching forecast. And in order to do so, I want to argue that we need to know when coral bleaching has and hasn't occurred in the past. And we also need to know what both the ocean and the atmosphere are doing during bleaching, see if there's any patterns in that, and see if we can use these patterns to leverage it for predictability. So let's travel to the Southern Caribbean island of Curacao to find out. In Curacao, like pretty much most coral reefs across the globe, we don't actually have good records of coral bleaching. But the good thing is the corals themselves record when they have and haven't bleached. Here is an image of me taking a coral core sample from a massive coral colony. I then extract the skeletal core. It's also important to note that only the top of the coral is alive, and then we patch it back up, and it tends to grow over that little patch. So this is kind of like taking a biopsy. It's relatively minimally invasive and doesn't really harm the coral that much. We take these coral skeletons back onto land, and then we CT scan them like you would in a hospital. And when we look at these CT scans, we can see annual density variations. And much like trees, these massive stony corals form these annual bands. And what's really cool is that when corals, well, cool in a scientific sense, when corals bleach, they severely slow their growth, and they form these super high density bands. So I guess you can't see my pointer, but you can see these really like bright white bands in that middle image. So we collected 45 corals, we CT scanned all of them, and we identified stress bands in all of them. And this plot on the right is a little bit confusing, but what I wanted to show you here is that we identified 9 total bleaching years. And what I really want to drive home is that bleaching is a relatively recent phenomenon. Like we don't really start to see mass bleaching events until 1990. And even then, even though temperatures have warmed pretty steadily over the last 100 years, especially over the last 40 years, we're still not seeing coral bleaching every single year. So there's clearly some sense of pattern in that. And I'm going to jump a little bit ahead and give a little spoiler alert. What's ultimately responsible for these patterns are what we call climate modes. Modes of variability. These are well-studied climate patterns that typically occur in a particular ocean basin or section of the atmosphere. You might have heard of the El Nino Southern Oscillation, but we hypothesize that these 2 other modes also impact the Southern Caribbean. And I'm going to jump through these little dynamics a little bit quickly, but typically in the Southern Caribbean, it's a lot cooler than the rest of the Caribbean because you have these prevailing easterly winds that are essentially like, imagine a bowl of soup. You have a hot bowl of soup, you're blowing on that bowl of soup. Those winds are cooling the hot bowl of soup down, but they're also bringing cold water from the deep ocean to the surface. So you have multiple mechanisms of cooling on the coral reefs there. However, during bleaching years, we find that on average, the North Atlantic is already much warmer. But on top of that, you have a weakening of those winds. So not only do you not have that, bowl of soup is no longer cooling down, and you also don't have that cold water coming from the deep ocean to the surface to cool down those corals. So that's what leads to those marine heat waves that cause bleaching. And we hypothesized that these 3 climate modes are what's driving that. I'm not going to go into the nitty-gritty details here, but you might have heard that we're expected to see a strong El Nino event in this upcoming year. All of these climate modes, including El Nino, are described by indices. So they have a relative value of how strong or how weak they are. And we expect that, El Nino, which occurs in the Pacific, will have some lag between it occurring in the Pacific and it affecting the Southern Caribbean. So we test different month combinations of 1, 2, and all 3 of these climate modes. And we call this BEEP, the Bleaching Event Early Predictor. And this is an oversimplified version of it, but essentially what this means is we take, for the best predictor that we found, we take the NAO index, the AMB index, and the ONI index. So those 3 climate patterns for every single one of those years from 1985 to the present. All of the 9 bleaching years that I identified are plotted in red. And BEEP is essentially a decision boundary. Anything above that decision boundary is predicted as bleaching having occurred, and anything below that is predicted as bleaching not having occurred. And over this almost 50-year time period, we have those 9 total bleaching events. 8 of those total events are correctly predicted by BEEP. There's only 1 missed prediction and 1 false alarm. However, the NOAA degree heating weeks, there are a ton more false alarms, which is not particularly useful for reef practitioners. The other thing to note is that coral bleaching in Curacao typically begins in the late fall, so around October and November. But the last month used in this predictor is June. So what I want to argue with BEEP is that, particularly here for Curacao, by the time June is over, we can use BEEP to predict whether bleaching is going to occur later on in the year. The other cool thing that I found was BEEP is able to predict subsequent years correctly as well. We know that in 2023 and 2024, we had a lot of bleaching at Curacao, but in 2025, there was no bleaching. And BEEP is correctly able to predict those events as well. So what does this actually mean for coral reef managers? So going back to that whole idea of coral reef restoration, with this improved 5 to 6 months lead time, reef managers are able, have enough time to potentially move those coral nurseries from a colder location or onto land, as well as reduce tourism and other local stressors, and prepare other appropriate mitigation strategies. I wanted to leave some time for questions. I really wanted to drive home that federal funding is super important. And on top of that, the only thing that will really solve the issue of coral bleaching and coral decline is if we reduce our emissions. But until then, there are a ton of fantastic people doing fantastic work. Yeah, I'm happy to answer any questions.
Oh, yay. I'm channeling Roadrunner right now with Beep Beep, but I'm so rooting for the corals and I'm so rooting for you. Thank you for that terrific talk. So there's a whole bunch of interesting questions. Stu Weiss asks if there's any evidence for evolution or natural selection and changes in species composition after that short-term recovery.
Yeah, for sure, which does make things challenging in studying coral reef histories. But yeah, we've seen a ton of reefs change their composition to from being more diverse to less diverse. It seems like there are particular species that win out in these marine heat wave events, which is devastating because we are losing biodiversity through that. But there are pretty clear signals of natural selection across species in coral reefs.
Can we get this question from Empress Arianna? So are there varieties of coral that are more sensitive to heat? If there are, now I'm gonna have to sneeze too. If there are varieties of coral that are more sensitive to heat, does reef construction efforts have to worry about a lack of biodiversity? Yes, that is.
Yeah, that's a great question. The answer is yes. In these reconstructions that I used a particular I used one species of coral because it's pretty abundant in the Caribbean, and it's relatively hardy. So if we're seeing bleaching in this particular species, that means that a lot of the rest of the reef is probably bleaching. In the Pacific, we've tried to in different places we've tried to use different species. It does complicate things a little bit. But I think that like as long as you use a relatively hardy species, that's a really good indicator of whether other like quote unquote weaker species are also bleaching at the same time.
Sydney Lindquist, one of our frequent commenters, asks if you can introduce the algae to the skeletal remains as a way to sort of revive them or reanimate them.
Yeah, I know a little bit less about that. I know that people have tried to do work along those lines. Off the top of my head, I don't feel like I can accurately describe it, but I know that people have attempted to do that kind of work. In general, like they do hold on to a tiny bit and then it like reproduces. But that is a potential strategy. It's just difficult to do on like an actual like in reef situation as opposed to like in tanks. So that's not a typical way of like trying to prevent corals from dying when they're bleaching.
Okay, and finally, Jacob asks if there are other indirect proxies for coral bleaching that go further back in time.
This is the only, as far as I know, the coral stress bands are really the only way. Sometimes we have tried to look at geochemical signatures, so looking at the geochemistry of coral skeletons. That's been less studied, and I think that is an actual potential cool avenue for studying this. If you look at trace elements such as uranium to calcium, I think that does actually spike during bleaching events, but it hasn't been commonly used. As far as I know, the stress band reconstructions is kind of the main method that people use for looking at coral bleaching in the past.
Super cool. All right, Maria, thank you so much. Enjoy the rest of your day.
Thank you. Bye, everyone.
You want to make Maria happy, right? So you should call your representatives. There's a third big thing that we're worried about and that motivates the Weather and Climate Livestream 2026 edition. And that's the administration's proposal to dismantle the National Center for Atmospheric Research. So one thing you might have gotten out of Ellen's talk is how much of the scientific enterprise is devoted to reaching users and making commerce and life and property safer in the United States. And one place that's been at the forefront of that for weather and climate historically in the United States has been the National Center for Atmospheric Research. That's an establishment in Boulder, Colorado. It sits on the top of this, well, the main lab sits on top of this hill. It was in the movie Sleeper from the 1970s. It's kind of a futuristic building, but it's full of people looking to the future in terms of weather and climate research. And that involves all kinds of things. It involves, so the administration has said, well, we're going to shut this down because it's a hotbed of climate alarmism. And it is true that NCAR works on climate problems, but they work on many, many other things as well. Yeah, well, we can talk about whether it's alarmism or not, but they do many, many other things. They provide infrastructure that enables academics at smaller institutions to do their work. That means they provide airplanes. That means they provide enormous supercomputers. That means they provide other kinds of observing facilities, radars and so on, to look at clouds. That means they provide expertise, data sources, centralized data sources. And the administration, because they're annoyed with the state of Colorado, has said, well, we're going to dismantle that. We're going to take the big supercomputer and give it to somebody else. Who will we give it to? Oh, I don't know, the University of Wyoming. It turns out that that particular act was stopped by a judge's order earlier this week, but the threat in general to NCAR remains. And this would really be, shooting ourselves in the foot as a country to dismantle this thing that has existed since 1960 and has provided the underpinning for so much science. One of the things that Jennifer Kay pointed out early on in the live stream was how much efforts at NCAR had helped to promote aviation safety, because NCAR's got a bunch of weather weenies in it, and they're interested in like super strong downdrafts that make planes smack into the ground. And that doesn't happen anymore the way that it did in the 1970s and the 1980s. So another thing that you should call your representatives to complain about is the administration's plans to dismantle NCAR. Please do that. Really, please do that. It's why we are here. And so the example scripts and ways to contact your legislators are in the crawl at wclivestream.com/call. All right. This is WCLS broadcasting to you live. Our next speaker is Haley Krim, who, for those of you who've been in the chat, has been doing this job, the hosting job. And now we get to hear about what she does for a living. She is a climate social scientist at MIT.
Thank you so much. And great to be back here and great to be seeing all the familiar names in the chat. Good morning, everyone. Yeah, so I will talk a little bit about what I do. So I work at MIT Open Learning, as he said, which is the division of MIT that focuses on public education. So we take all of the amazing work that's going on at MIT and try to make it as useful as possible for the public. And that's a little bit of what I want to talk about today is climate education and climate literacy. And actually, I will start talking about something that I did before I came to MIT and then also talk to why that happened. But first of all, I just want to talk really quickly about my background and how I got here in terms of federal funding, because I think it's a little bit different to how many other people have been supported by federal funding in the past. And that is, after I came out of college, I went into AmeriCorps, which is a national service program where you get sent somewhere around the country and you spend a year doing whatever you signed up to do. So I worked in a local government on their climate and sustainability office. I was the only full-time staffer there. It was the best time ever. It was the government of Park Forest, Illinois. I had a great time. And after you complete your service in AmeriCorps, you get something called an education award. And this is all, federally funded and organized by states. So my education award is that top arrow, which supported me to go to do my master's degree at the Columbia Climate School in climate science and policy. And also after AmeriCorps, I went into the federal government as a contractor for NOAA and the U.S. Global Change Research Program. So that, obviously supported my work because I was working for these agencies. And so that is an important reason that we need to protect government funding more broadly. So it's not necessarily just NCAR and grants and everything, even though that is absolutely important, but all of these other pathways that people use to get into federal service and into federal science work is incredibly important as well. So just wanted to shout out AmeriCorps really quickly. So if we're talking about climate literacy for action, first we have to look at what is actually holding back that climate action. So I'm going to go really quickly through a selection of factors that have been found to impede the implementation of climate action at different stages across the US context, because there are a ton of different ways this happens. So first of all, we have some companies, subnational governments, organizations, and individuals who just have no intent to take climate action, and this could be due to mis or disinformation. It could be a perceived lack of will from the people they care about, constituents or stakeholders. And it also could be from competing interests like economic or health pressures, or there's just the inertia of the status quo. There are people who are many, many more who are intending to act, they would like to act, but they can't because, for example, they're paralyzed by the scope of the problem or the scope of the solutions because they don't know what would be best or the most appropriate action for them to take. And also, we see that they don't have the resources a lot of the time to implement the plans that they would like to do. And then lastly, really a couple of the things that stop plans in implementation from reaching their full effect are the duplication of effort, which I'm sure everyone's familiar with, and reinventing the wheel. Can be a lack of shared visions and goals amongst all of the people working on a project or amongst, individuals participating in a sector or companies in a trade group or something like that. We also have fracturing, and actions are siloed by geography or communications, and then also an overall lack of feeling of collective progress, which keeps morale up and galvanizes people to continue taking action. So what do we do about that? We look at something called climate literacy, and this term was coined by NOAA at an organization or at a workshop organized by NOAA and the AAAS in 2007. And it basically asks the question of what do people need to know in order to actually do something about this and make these actions more effective and actually continue and have sustained climate action. So the official definition is that it is an understanding of how the climate system works, how human actions influence the climate, and how climate influences people and other parts of the Earth system. So in 2023, and hopefully all these logos load, there are, well, there they go. So there are 31 different departments, agencies, and national labs all came together as part of the Climate Engagement and Capacity Building Working Group of the U.S. Global Change Research Program, with the intention to look at this question again for 2023, the 2020s, because things had changed a little bit since 2007 in the realm of climate action, as you might assume. I also want to point out that some of these agencies aren't traditionally climate or science agencies. It was a super interdisciplinary group, which reflects the importance of climate literacy to all of these different types of industries and interests. And I actually was the coordinator of this group. So the rest of my talk will be about the work that we did. So we set out to answer these two questions. In order to address the climate crisis, what do people need to know? And what do people need to be able to do? So we talked to 750 experts from around the world, and we had different listening sessions for different groups of people. So we had scientists and students and workforce development experts, indigenous knowledge holders, business people, educators, and other types of groups. And what we found, every single time, no matter who we were talking to, we got similar distributions. So first, we found that there are a ton of different things that people need to know in order to address climate change. And science, the climate science, is essential, but it's not sufficient in order to support action in the 2020s. So some of the biggest things that came up were communication, hope, justice, social science, indigenous knowledge, empathy, and systems thinking. And again, no matter who we talked to, these were the same things that came up the most. When you code those answers, you group them together, there is a clear focus. Every single group wanted to know, or said that people need to know, about the solutions, then about the impacts, and then everything else was pretty much tied in terms of climate science, psychology, ethics, and hope, the causes of climate change, and climate justice. So when we asked what do people need to be able to do, this was kind of a new question, and we were really expecting things like electrical engineering or, be able to install solar panels or something like that. But what we got was this really interesting sort of soft skills array of answers, again, across, including from scientists and, business people and everything like that. Things like just being able to take action, obviously, is the most important, but communication, finding and understanding what information is trustworthy and accessible, emotional intelligence, critical analysis, systems thinking, community building, all of these incredibly important, life skills that aren't necessarily climate skills, but they are the sticking points for action a lot of the time. And so these were identified, again, across almost 1,000 responses from 25 different countries. Lastly, of my graphs, we also asked who should use this information. The 2007 guide was really aimed at educators and students. So educators were very highly represented here, but also this 2023 work shows that it's no longer just a question of education or of, young people learning about climate change. Decision makers came up the second most. So, our Congress people, our, mayors, our CEOs, anyone who has power to make decisions needs to know what they, climate needs to be climate literate. And then everyone also is a great one. So this work is essential for more than just teaching in schools, and we have to get it out of just schools in order to reach everyone in the time period that we need in order to actually take action and have an impact on climate change. So what did we do with this? We combined all of these listening sessions results with all of the expertise of these 31 agencies and all of the people that were in the group, the results of the 5th National Climate Assessment, which had just come out, and of course the IPCC AR6 findings to make these two guides. So they ended up being two separate pieces. First that came out was Climate Literacy Guide, and that was published by USGCRP in 2024. And then the second was the Transformative Skills Guide, which expands the definition of climate literacy and covers that skills aspect. And that was published last year in 2025. I'll talk a little bit more about that at the end. So what does it cover? So climate literacy now expands far beyond just the climate science. So of course we include how we know and the, scientific method, observations, how we understand the climate. It has the basics of the greenhouse gas effect and, different atmospheric chemistry, bullet points, not the whole thing. And then we go into causes and specifically name fossil fuels as a major cause of climate change. We go into impacts, and then there's a whole section on equity. It's built in all of the other bullets as well. And then there's sections on adaptation and mitigation solutions and actions that need to be taken collectively, not individually, or yes, individually, but there's a focus on the collective action. And then the last one is hope and urgency and the psychological aspect. So that was, published by the USGCRP and put out at Climate Week in 2024. And then last year, unfortunately, after everything went down, so this was not published by USGCRP or the government, but we have still been able to save and publish the work that we are doing on transformative skills. So this builds off of an international framework that was put together by social scientists in the sustainable development space that is called the Inner Development Goals. And so we took those goals and the framework that they had created and applied it to the climate context. And so this guide covers things around how to develop and how to look at skills from the relationship to yourself, the way you think, the way you relate to others and for the world, the way you communicate, and also the way that you act and behave in the world. And you don't have to take my word for it. The IPCC AR6 did find, using the 2007 definition, that improving climate literacy promotes enhanced societal responses, behavior change, and reductions in emissions. And this impact increases when you include things like, information provision, indigenous knowledge, and civic engagement as well, are things that really help increase the impact and the potential of your climate action. So how does that work? Increasing climate literacy at a community scale, including the skill building aspect, increases the strength of social mandates for climate action as people understand the importance of that action and they exercise their power to demand it. It also increases the strength of policies and plans with respect to climate change, as more people who are creating and giving input to those policies and plans have the context and the skills that they need to effectively create more climate informed policies and plans. What do we call it when those things all work together? And the policies and plans and social mandates drive sectoral advances on climate targets. That is climate action. And then really quickly, I just want to say, as I have alluded to throughout the talk, that both the Climate Literacy Guide and the National Climate Assessment that it is built on were taken down after in the summer of last year, and then the Transformative Skills Guide was never able to be published. But all of these things are back up. There's a new website called climatelitteracy.earth that holds the Climate Literacy Guide and Transformative Skills Guide and a bunch of other resources related to this for increasing climate literacy in policy and workforce and education. And then there's a whole another website called climate.us, which actually is a bunch of people from my old office at NOAA have basically taken it upon themselves to put climate.gov back up independently, and that holds a full working copy of the National Climate Assessment. So I just want to say thank you all so much, and if there's any questions, I would love to hear them.
There's one, which is good. And I mean, there's probably more than one, but there's one that we're going to ask because you didn't leave yourself much time.
Yes.
Stu brings up this sort of interesting, Stu Weiss brings up this interesting thing, which is the tension between personal action and responsibility versus systematic change. And so how can you speak to that?
Absolutely. And that is one of the, as you're alluding to here, a huge target of misinformation as well, and ways that people try to divide or distract. So it is sort of a complicated question to answer because obviously personal action completely matters. And the fact that, you turning your lights off or taking less flights or something doesn't have, the tons and gigaton impact on climate change causing emissions doesn't mean that it's not worth it. But we do need to, and you see it in the responses, focus on the systems thinking aspect and this collective action aspect, the ways that we can work together so that we're not, or the default isn't to think about how can I impact this by myself, and then when it doesn't have an impact, maybe get discouraged, but look and think in a collective way. How can I mobilize my community? How can I call my representatives? How can I, get all of my coworkers at work to push ourselves and push the institutions that we, exist within to take action that'll be much, much bigger of an impact than we could do at an individual scale. So both are definitely important, but we really need to think more collectively and more, on a social level scale than just at an individual scale.
And so one of the question that I had real quick, is the extent to which the communication strategies, this interest in how do you enable people to make decisions, how much is that specific to climate, and how much of it is sort of general for any societal issue?
Yeah, it really depends. Although, especially with the transformative skills, you see that it's really quite general. We had a funny conversation one time with a scientist where he was like, well, isn't this just a list of how to be a good person? And fundamentally it is. We're talking about the things that allow people to work together to make those collective impacts. So it's not necessarily just, the information that you need to know is more climate specific, but the skills are very broad. And the benefits of developing those skills at a societal level go far beyond just the ability to make stronger climate action.
Super cool. Thank you so much. Been great to see you all these hours, many hours on the live stream. So it's nice to hear what you specifically are up to. We are at the top of the hour. We are at the top of hour 44. Syl is probably right outside of Washington, D.C., or maybe inside right now. Who can wait? I can't wait for Syl to get to Washington and deliver all those letters that he's been carrying. There it is, hour 44. 6 hours from now, we will wind this thing up. What I want you to do between now and then is to call your Congress critters, write them letters, tell them that dismantling the American scientific enterprise is a bad idea and you don't like it, and that they should, use the authority vested in them by the power of being your representative to change. Maybe let me speak to the one thing. Let's talk about the OMB restrictions, right? The idea, and maybe the director could drop these back in the chat. The idea that political appointees would have the last word on every single grant made in every single scientific subject through the entire grant-making machinery. So that we're not just talking weather and climate science here. We're talking all of it, medicine, every other thing. That a political, that you would have to write it. Basically, they would like to upend the whole way the scientific structure does. If paying for publications would no longer be allowed, and just so that that's clear to you, the way it works now is we pay to have our stuff published, which my spouse, the journalist, thinks is nutty. We pay to have our stuff published because it costs money to publish papers. We pay actually private publishers like Wiley in some cases. So we pay to have that stuff published, and we don't pay that out of our pocket. We pay that out of the grants that did the research. And the OMB wants to make that not an allowable expense. The OMB wants to tell you 4 years before you actually have to go to the conference what conference you're going to go to. You know what? I don't know, because I don't know what conferences will be available to me. They want to restrict our international collaborations. And maybe there's an argument to be made about, how you'd like to invest money in your own country. But one of the things that scientists do is they ask questions and they talk and they learn from other people. And so why don't you help your representatives learn from you? In science, we argue with one another, but we are arguing with one another to try and come to a greater truth, to some truth that maybe none of us can see and on our own. And so let's help our representatives see the truth of how important the scientific enterprise is to the American experiment. Call your Congress critters, get in touch with them, write letters, and tell them to keep the politics out of the scientific process and to let the scientists do their job, and let the politicians do theirs. All right, I'm super excited for our next speaker, only because I know the work a little bit. It's Catherine Skiro, who's an assistant professor at the University of Virginia. I can't wait. Yeah. What you got?
Hi, Robert. Hi, everyone. Great to be here. Indebted to all of you guys who are hosting and doing the organizing behind the scenes. This is really quite an amazing event. Happy to be here. Yes, I'm Kathleen Skiro. I'm an assistant professor at the University of Virginia. My primary research focus is deep convection. And so I'll tell you about the different ways that we study deep convection in my lab group. We are supported entirely by federal grants and the university. So this work is largely funded by NASA and the Department of Energy and NSF, and hopefully continued to be funded by those agencies and other federal agencies in the future. My work that I'll talk about today is focused on deep convection organization and its implication for extreme weather, extreme hazards like flooding, and also its implications for climate. So extreme precipitation events are increasing in frequency and intensity. This is a really nice visual from Climate Central taken by the 5th National Climate Assessment. This is showing in observations that heavier downpours are increasing, especially in the eastern part of the country where we already experience a lot of these downpours, and even in the West. So extremes are increasing across the United States and also across the world. So that's what's shown in the right here. This is from the IPCC, the Intergovernmental Panel on Climate Change. We see the increase in frequency and intensity of precipitation extremes nearly everywhere, except for maybe in a couple of small regions in what we call subtropics, where it's already rather dry. Just a note on extremes versus climate average. So on the left, you see this is what is supposed to be happening on average to precipitation. And so you see a little bit of a different pattern where you have in our drier regions what we call the wet get wetter or dry get drier pattern. But something a little bit different is happening with precipitation extremes, and it's worth noting that they're especially over the continental regions where we're having the greatest impact on humans and ecosystems that are interacting with humans. That's increasing in frequency and intensity. Why is that? Well, there's a thermodynamic and a dynamic component to that. So the thermodynamic component, which I am certain you've already heard of, is called the Clausius-Clapeyron relationship, where the moisture capacity of the atmosphere increases 7% per 1 degree Celsius of warming. And what does that mean? It means that you have storms that are becoming more intense in a warmer climate. Add to that dynamic changes. What does that mean? Changes in winds, changes in the way that air comes together, converges or diverges, individual systems, storm systems.
Hey, Kathleen's frozen for us. Hopefully she's, well, I don't know, hopefully, not hopefully she's frozen for you, but we're gonna ask her, we're gonna work behind the scenes and try and get her to come back. That's a bummer, because that's super interesting, what she's talking about. All right, so it's time for me to rant some more. I'm just free. All of the hosts are just completely freestyling. That's probably very obvious to you. I have really been thinking about this distinction, though, between the way that science works and the way that policy works, and maybe especially policy in this day and age. In science, I just can't even tell you how much it's important to have questions. And I think if you have a question and if you acknowledge that there are things you don't understand about the world, internet issues. If you acknowledge things you don't understand about the world, that means that there's something left to learn. And so when we have arguments about, amongst ourselves, I mean, these are not personal arguments typically, but they're arguments about how we should interpret the signals of the world, of the world around us, how we should understand what's going on. And that's a very different feeling than politics, because it isn't personal. And when we argue with one another, when we say, well, I think the world works like this, it doesn't have this, it doesn't have this compulsory nature to it. And so in a world where there's increasingly more and more some groups of people telling other groups of people how they ought to behave, maybe we can show them and stress for them a different way of working, a way in which when we argue with one another and we disagree with one another, we do it with sort of respect. So this is one of the reasons I hope that you will call your Congress folks and talk to your friends and neighbors as well and explain what it is you've seen. I mean, I know, or it seems to me, that there are these lovely online communities. Some of you have other communities offline in Tumblr or Discord or whatever your place of meeting is, but reach out to the folks around you in real life and help them understand just exactly what is at risk here, which is the possibility of taking a whole culture and edifice that is in service to the rest of society, and dismantling that because you don't like hearing a different opinion. And the other thing to say about science is that when we are honest with ourselves, and all of us are, of course, human beings. All of us scientists are human beings. But when we are doing our science, we don't think necessarily that it implies a particular impact. So this attack on the climate science is to confuse what the science tells us about the way the world works. Sorry, I'm trying to figure out what we're going to do next. If Richard is ready, maybe we would just put him on. The point is that science doesn't tell us what we should do. It doesn't tell us how the politics should work. It just tells us the way the world works. And we can make, as a community, as a society, we could make decisions that don't necessarily say, that might, for example, privilege economic activity over environmental regulation. That's a reasonable policy position, but it's not what the science says. All right, hang on just one second. The amazing backstage team is trying to figure out what they're going to do. You know what you should do while you're waiting? Why don't you go pick up the phone and call your Congress folks and tell them, maybe I'll ask you specifically this time, to resist to oppose and somebody's asking me to talk about my science journey. All right, fine. Yeah, I didn't do that when I spoke. So here's what happened to me. I went to high school. I grew up in San Francisco. And when I left high school, I took the high in high school, maybe a little too seriously. And I went to work as a machinist in the Exploratorium, which is a science museum in San Francisco. And so I, was working with my hands, building things out of wood and metal. And I had astonishing mentors there. And they got me interested in science and in explaining things and learning things about the world. So I went to, eventually, after a few years, I went to a small college in the Midwest, and then I went to the University of Washington. Oh, yeah, I did a detour, actually, to work in one of the federal labs doing energy conservation work. And then I got my physics degree at the University of Washington in the late 1980s. And physics at that time seemed like super cool, but very abstract. that by the time you get to atomic and nuclear and quantum mechanics, it's not about the world you live in anymore. And the husband of one of my professors, the wife of one of my professors worked in the geophysics and atmospheric sciences department. And he said, you should just go find out what she's doing. And so for those of you who saw Jennifer Kay's talk, that was Marcia Baker. And she was kind of an amazing mentor. And she brought me on as a PhD student. And I studied low clouds over the ocean. I flew around in airplanes off the Azores, and I did computer modeling at a time when that was still just coming out. And I did some pencil and paper modeling as well. From there, I went to work at NASA, where I measured clouds from space, wrote software to understand clouds from space before the rockets were even launched. I spent some time at the University of Wisconsin, and then I went to work in a joint lab of the NOAA and the University of Colorado. And if you want to know more, you'll have to wait, because Catherine is back. Right? Yes, Kathleen, excuse me. 1 second. She's much more interesting than hearing me rant about my sordid career.
I am still trying to get sorted here, though.
I'm so happy to see you.
I don't know what happened. Am I live? Oh, I'm live. Okay.
You're live. Yeah, you're here.
That's great. I don't know what happened, and I don't know how much you heard of me. I was giving myself my presentation.
You were at the 7% per Kelvin.
Oh, okay. Okay.
That's where you were.
All right. Let me try and revive this.
This is how you know it's live, because we make mistakes.
Yeah, that's right.
All right.
Okay. Can you see my screen?
Can we bleed the time 5 minutes, push everything back? Richard can start later. All right, cool.
Can you see my screen?
No, I cannot see your screen.
Darn. Okay. Let me stop and try again. Share window.
We can see your share of the live stream.
Oh, yep. Okay.
The window.
Can you see my screen now with the presentation?
Yes, we can.
Okay, great. I really hope I don't get cut off again, but if I do, I will come back. I will persist.
Yeah, you were in the thermodynamic part. There you go.
Okay. All right. So I was talking to myself for a while. Okay. Dynamic versus thermodynamic changes to extremes. We have an increase in moisture content in the atmosphere that's increasing 7% per 1 degree Celsius. We also have dynamic changes that are occurring in the atmosphere that can substantially enhance this 7% and make it much more intense in other places. This may be where I stopped, where this is from the Intergovernmental Panel on Climate Change. This is the change in annual maximum daily precipitation. So on the left is sort of what I already showed, hopefully you saw, where this is an increase in extreme precipitation nearly everywhere. Now it's just showing that there's some hatching where there's low model agreement. And then where there's high model agreement, it's just the color. The thermodynamic contribution is showing this nearly uniform increase everywhere. And the dynamic contribution, where you see the hatching and the different patterns, is largely contributing to the uncertainty. And you have the same sort of overall pattern, but there's much more uncertainty, meaning like the difference among climate models is larger. So studying this dynamic contribution and its uncertainty is a critical aspect of better understanding predictions to extreme precipitation. I don't need to probably motivate why we are studying precipitation extremes. It is everywhere. We see flooding and catastrophic impacts everywhere. In fact, Mexico and South China recently really saw some catastrophic impacts. So kind of back to who am I and what do I do? So my lab group studies deep convection, and I study it in 3 different ways. The basic convective physics, so understanding the fundamental mechanisms of intense thunderstorms at the individual storm scale. how that translates to our understanding and better prediction of extreme convective precipitation and the impact of extreme convective precipitation, and the role of deep convection in climate. So understanding how changes to deep convection across scales relate to changes in the tropical overturning circulation, or the overturning circulation in general. I study largely in the tropics, and its relationship to how clouds change and how that affects our predictions of future warming, global warming. So what do we do in terms of convective physics? So I was saying that I am highly motivated to study organized deep convection and what organizes deep convection, because those are the systems that are largely contributing to extreme precipitation. What does that mean? Well, let's just think about what an organized convective system would be, like an individual cloud or cell. These are short-lived. I don't know, I'm saying 30 to 60 minutes here, at most a couple of hours, and produce localized intense rainfall, but really lack the scale for catastrophic regional flooding. Not all the time, but sometimes. Organized convection is the clustering together of multiple cells into what we call mesoscale convective systems. And these are systems that extend over hundreds of kilometers and persist for hours and can even persist for days. This is not the greatest example, but this is an example that there happened to be severe weather in Charlottesville a few days ago, and I was chatting with my lab group in Slack about it. So this is a screenshot I took of different convective systems in the area. This was, you can see some things are organized in lines and some are isolated by themselves. And how do we get these lines versus these individual cells? And why does it matter? Well, it matters because the lines are larger in area, can persist for longer, and can be more intense in convecting and their resulting precipitation. So in terms of flood frequency, this is the additional motivation from Who et al. This is flood frequency in each month of the year. This is the United States. The main thing to pay attention to is that these like tighter hatching bars are showing the MCS related flooding events, and the non-MCS related, so organized tight hatching, disorganized less tight hatching, for different types of flooding events. And you can see that most of the bar is tight hatching, so it's largely driven by organized convective systems.
Kathleen, I'm here to
Okay, so
tell
what
you
organizes deep
Wait,
convection?
Kathleen.
What is our definition of organization? Well, it kind of depends on who you ask in the field and what part of the field they're in. For those that are like me, who are studying convection from radars and spaceborne platforms, and trying to understand the evolution of convective systems from growth to decay. That's how my group defines organization. So we define organization as the clustering of individual cells together and its upscale growth from isolated cells to mature mesoscale convective systems. I'm sure a lot of people would define it this way, but there's also a whole literature that studies convective organization in the context of idealized simulations, and we call that convective self-aggregation, and that's a little bit, you can define organization in a number of different ways with a number of different metrics, both in observations and in modeling studies. So I wish I had 3 hours to tell you all the things that we're doing in our group currently. I'm just highlighting a few recent works for those in the field who might want to keep up with us. We study environmental conditions supporting the growth, maturation, and decay of convective systems, as well as how they grow from isolated to organized. We've found that moisture is critical to organizing deep convection. It's not just critical to the amount of precipitation that falls or the initiation of deep convection, but it's also critical to organizing deep convection in the real world. We look at land surface heterogeneities, and so we've done some convection permitting modeling recently to illustrate that larger soil moisture gradients are supportive of organization, not just in terms of convective initiation, which is the literature has suggested, but also the upscale growth and organization of convection. I've also done some work understanding cloud radiation interactions. That's a little bit more complicated, but for those that are atmospheric scientists, we are trying to understand the role of cloud radiation interactions by disabling certain interactions in convection permitting models. And we've found recently, like shortwave heating is in fact quite important in suppressing organized convection during the daytime. How do we study these things? I already mentioned a couple of things like convection permitting modeling and how we look at cloud radiation interactions. We use and take our own field campaign observations. So we have, for instance, an upcoming field campaign in Alabama that's coincident with the Department of Energy atmospheric radiation measurement site, longstanding critical measurement sites in the United States and throughout the world. we're going to be going down and launching weather balloons like it's shown here to try and better understand the environment surrounding deep convection. We use convective system tracking databases, which are generated from spaceborne instrumentation, infrared and precipitation radar that and microwave that illustrates, it's kind of illustrated here on the right. You can see convective systems. We identify them and their shields and how they propagate in time, and then tag different measurements to that to try and understand what factors are influencing their evolution, etc. So on to how this relates to extreme convective precipitation and things that we're doing in our group currently to try and understand extreme precipitation. This is an example from a recent postdoc who is looking at synoptic conditions or large-scale conditions, patterns in the jet stream that relate to extreme precipitation. So identifying dominant patterns, which dominant patterns equal predictability. These are 4 dominant patterns in one season, December, January, and February. You can see, I'm just showing an example here of this one pattern where you have a high pressure that sits over the Pacific, and there's a wave pattern that's associated with that. And this particular synoptic pattern happens to be related to extreme precipitation in like the Mississippi and Ohio River valleys in the United States. So this is just an example of some of the stuff that we're doing in our lab group, and also understanding deep convection and its role in climate. I probably have to mention that there's, in order to do that and understand deep convection and climate, there's something that we need to consider, which is that standard climate models are operating on grids of 50 to 100 kilometers, but individual deep convective cores are much smaller than that. And so there's a resolution gap that forces models to rely on parameterization. What is that? It's an approximation. Parameterizations are based on our incomplete knowledge and how deep convection relates to the large scale environment, or however, whatever you're parameterizing is that relates to the large scale environment. So this can lead to significant issues in predicting extreme rainfall, as well as generally being a major source of structural uncertainty in climate models. What do I mean by uncertainty in climate models? Well, there's irreducible uncertainty. So this is projections of global average temperature change. There's irreducible uncertainty due to natural variability. That's what's in orange here. There's different emission scenarios. So whether we're emitting more or less, and how the economy and social impacts are changing. And what I'm talking about, though, is the uncertainty due to varied and incomplete physical representation of the climate system among different climate models, such as we like to point fingers at deep convection, and I think it's for good reason. By the way, one of the things I do also in my lab group is I try and reduce this uncertainty by using my observational work to create model diagnostics that are rooted in empirical relationships that we understand, like this relationship. There's a well-known relationship between column moisture and precipitation, where you have a sharp increase in precipitation at higher values of column moisture. In other words, moisture is very important for deep convection initiation, organization, and onset. And you can see how climate models are doing in comparison to observations, and use this as an observational benchmark to try and reduce some of that structural uncertainty among models and improve parameterization of deep convection. Okay, so uncertainty and changes to clouds are also a major part here in terms of understanding the difference among climate models and their projection of future temperature changes. So what I try and do in our lab group is understand systematic differences among climate models in their representation of deep convection and its interaction with the circulation, and how that impacts how clouds are changing in the future. So just a couple of examples, and actually these are preliminary, but the flavors of this have been published in recent.
All right, live streamers, the technology is not perfect. We will acknowledge that. Sorry about that. I think Kathleen lost her share and lost her ability to hear us. It's too bad, because I can imagine the stuff she's talking about. I've seen her work in the past, and it's super cool. So I'm sorry you missed that. Maybe we'll get another chance. Because we ran over a little bit, I'm not going to rant at you, but I saw in the chat that some of you are calling, so thank you so much. Instead, I'm going to introduce my colleague, Richard Seeger. He's down there and about 20 meters that way. He is, I didn't even look at how you described yourself, Richard, but he is, let's see, a climate scientist at the same Lamont Doherty Earth Observatory where I work. I'll probably see him at lunchtime. Richard, I think if you, talk for about 10 minutes and then I'll come back on and we'll get some questions for you, okay?
Okay, can everyone hear me?
Yay, I can.
Good. So I'm going to talk for a little while about the tropical Pacific Ocean and how it's changing in the real world over the past decades and how climate models are getting it wrong and why it matters. And the first thing to know about the tropical Pacific Ocean is it has very rich spatial structure. The map you're looking at here is of the sea surface temperature in colors, the precipitation in contours, and the surface winds in vectors. And you see the winds, the trade winds sweeping from the east to the west. That's piling up warm water in the west because of the rotation of the Earth. It causes upwelling along the equator, which gives us the cold tongue, and the precipitation nicely arranges itself over the warmest water. So it's a coupled dynamical interaction between the ocean and the atmosphere that sets up this spatial structure. But that interaction is not, that state is not stable over time, and it oscillates back and forth in the well-known El Nino Southern Oscillation, which is shown in this famous schematic here. If the trade winds weaken, then the upwelling weakens. That causes warming in the cold tongue. That warming pulls the convection from the West Pacific further into the east, which weakens the trade winds, which weakens the upwelling further. It also brings the weaker trade wind, relaxes the slope of the equatorial thermocline, which again brings warm water from the west to the east. So it's a couple positive Bjerknes feedback. And it, of course, can run the other way to strengthen the gradient. And right now, we are expecting a strong El Nino this winter, which is getting a tremendous amount of attention because and when this gradient changes, it causes climate impacts all over the world. The moves in the locations of convection drive waves in the atmosphere that create climate anomalies, temperature anomalies, precipitation anomalies all over the world, including wet conditions in the southern United States during El Ninos, for example, but also the same thing, dry conditions over Australasia. The gradient changes matter, and we know this from just the year-to-year variability. But it's also going to matter, therefore, how this gradient changes over time. And this is where we come to this huge discrepancy between what the real world has done and what models show. On the left here, I'm showing you a trend from 1958 to 2022 in observed sea surface temperature using multiple data sets. And you can see that there's warming almost everywhere, but right along the equator there's a region where the waters have not warmed up, or in fact, they might even have cooled in some regions. And that is in stark contrast to what models do, which is warm up everywhere. And in fact, they warm up more at the equator than in other regions of the tropical Pacific Ocean. So in the real world, the gradient between east and west has been strengthening. Models say that the gradient should be weakening as a consequence of rising greenhouse gases. So we've looked at this, looking at all possible start times and end times from when sea surface temperature data began in 1870, and that's what's shown in this triangle plot. The trend start year is on the x-axis, the trend end year is on the y-axis, and the color is the trend in the east-west gradient that occurred for that combination of start year and end year. So you see it's purple mostly, especially towards the end. That's saying that this gradient has been strengthening. And as you go further on in time to end years later on, the more this has been, the strengthening appears. The hatching there shows where the observed strengthening actually sits somewhere within one or more members of 14 large ensembles. So this is looking at hundreds of different climate model simulations. And what you see is that for end dates in the last decade or so, the observed strengthening is outside the range of what hundreds of climate model simulations can do. So it can't be captured as a result of the force change in those models or the internal variability in those models. So that's a big failure of what the models are doing. They're simply not being able to capture how the equatorial Pacific Ocean is changing over the past decades. I'd like to make clear that what we're talking about here, this very long-term trend with this equatorial cooling, is distinct from the shorter timescale variability that's known as the Pacific Decadal Oscillation. So if you look at the trend from 1980 to 2022, for example, at the top, you have that very broad cooling, but this is a pattern that oscillates back and forth, as you can see in the figure at the top right. Sometimes we've had patterns of SST trend that have been the opposite of that. That's in contrast to this long-term climate change pattern, which we call the Pacific climate change pattern, which has this narrow equatorial cooling, and that has just simply been emerging over time, very consistent with what you would expect as a response to a steadily increasing greenhouse gases over time. But this is not just at the sea surface temperature. This has an expression in the entire upper ocean thermal structure and in the circulation. This is in a section along the equator of depth and longitude, and you can see how the surface cooling or lack of warming is connected to this big region below in the thermocline of where the waters have actually been cooling. The picture on the right is a north-south section of an equatorial section, and you can see that that cooling, it's narrowly confined to 10 north, 10 south, and it's near strongest on the equator. So this is the cooling at the surface is connected to what is going on below. So let's think through how this is happening. In the mean, we have, this is an equatorial section again. In the mean, we have the winds going from the east to the west. They drive upwelling in the central and eastern equatorial Pacific. They drive a current from the east to the west of the surface and the equatorial undercurrent flowing down the pressure gradient from the west to the east below. And there's mixing going on between those as well. In response to rising greenhouse gases, we tend to have initially we'll have less warming in the upwelling regions. So we have cooler waters there, warmer waters in the west, which is going to drive winds from the east to the west, and that's going to increase upwelling. In the east, the winds will tend to reduce the trade winds, and that would actually put downwelling in there, but it also weakens the vertical shear between the south equatorial current at the surface and the undercurrent below, and that's going to reduce the amount of vertical mixing of heat down from the surface to below. The net effect is we get this cooling of the thermocline waters from the east to the west. The mean upwelling is then going to bring that cool water from the surface to the top, and you'll get a pattern of warming in the west, cooling in the middle, and warming in the east. And then that's the actual observed trend pattern. So we can see how that's an adjustment of the equatorial ocean to the changing patterns of winds. So in the models, we do see that they actually also have some cooling below the surface as well, but it tends to be muted, and it tends to be focused further towards the west than in the observations. So what's happening in the schematic in the models on the right here is that even if they had the right wind response to begin with, they will get the cooling in the central equatorial Pacific, but then they have this strong warming in the west, which suppresses mixing, and then that's cooling below the surface remains there. So what we believe is going on is that the parameterized vertical mixing in these models doesn't realistically respond to the shear change, but it disproportionately responds to the increased stratification, and which decreases the mixing everywhere, and the surface and the subsurface become decoupled in the models. Whereas in the real world, the mixing is continuing, and it's able to bring the subsurface cooling to the surface. Okay, so what are the implications of the wrong tropical Pacific SST trends in models? So here we have a picture of the trend from 1981 to 2020 in observations in the left and models on the right. And then the lower picture is what's happened in the track density of tropical cyclones from observations. And what you would get from a model on the right, if it was driven by that change in the model change in tropical SSTs. So in the real world, there's been an increase in the Atlantic basin and a reduction in the western part of the Pacific basin. But had the sea surface temperature changed the way models predicted it should have done over the last 4 decades, we would actually have seen an increase in the western part of the Pacific basin, and we would not seen a large increase in the Atlantic basin. So if we'd been sitting a few decades ago believing our climate models, we would have had completely incorrect projections of how tropical cyclones across the tropical oceans would have behaved over the coming decades. Another example where this really matters is East Africa, which is sensitive to tropical Pacific sea surface temperatures. In the real world, this region in the spring rains has been drying, which is consistent with the strengthening equatorial zonal SST gradient in the Pacific Ocean. But in models where that gradient weakens, they predict that this region is going to be wetter. So we feel again that this is a region where there's a significant problem with model projections. By getting the SSTs wrong, they're getting precipitation projections wrong in a critical area of the world. The United States is another one of these. These are looking out into the future now, where the simulations on the left are atmosphere model simulations that are driven by an extrapolated sea surface temperature pattern that continues the observed strengthening of the gradient. The one in the middle is the same atmosphere model, but forced by the CMIP6 model change in sea surface temperature, which has a reducing gradient. And on the right, we have the difference. So the story here is that the gradient continues to strengthen out into the future, as I believe it will. Then the southern United States, including the Southwest, is going to be drier than the drying that the CMIP6 models are already predicting. There are other examples around the world, but I'll finish it here and say, what can we do to make the tropical Pacific dependent climate and weather projections more reliable? The first thing to do is believe reality. If models and reality disagree, we need to question the models, not the observations. And believe it or not, that is not what's been happening up until now. We need to have some very honest skepticism about existing projections. It could well be that because of these biases, that future reality might be outside the vast ensembles of model projections that we have, and they could be better or worse as a result of that. And we need to find ways to work around that. And now we need to improve physics-based models through confronting them with reality. Often that is talked about correcting model biases, which is a rather boring way of presenting it. I think it should instead be framed as using physics-based models to understand why the world is the way it is. And by doing that, it becomes an interesting problem to study. And last of all, we need more observations, and especially in situ measurements of surface fluxes, mixing currents, and how they move heat in the tropical oceans and how they couple to the winds. An example of that is the NOAA-led TPEX International Field Campaign, which is scheduled for 2027, which with aircraft, ships, moored platforms will be studying what I just said, all the relations between the currents and the mixing and the SST and the atmospheric boundary layer in the equatorial Pacific. Hopefully that can still go ahead, because that will enable us, that data will enable us to improve how we represent this in models and improve our projections of the future. Thank you.
Thanks, Richard. Everything I've heard you talking about the last year condensed into 15 minutes. Well done. We had some questions in the chat. We're a little bit sort of behind the ball here. Climate Brad, I'm not sure this will pop up on your screen, but Climate Brad asks, oh, there we go. Can Seeger talk about the decoupling of the Ocean Observations Initiative?
I'm not sure what he's referring to there, actually.
All right, Climate Brad, you can make that more explicit in the chat, and we'll give it back to Richard. Hannah has a question. How can we guard against creating or believing in incomplete projections?
Yeah, well, that's a good point, because in fact, the CMIP6 projections are all based on models that have been unable to reproduce the observed changes in the tropical Pacific. So I do feel that they have all been compromised to some extent. And I mean, by doing this work, by talking about it here and all sorts of other places, we're trying to make clear that people who are using these forecasts in adaptation need to be very aware that what might happen could be outside what the range of what the models available they have. So they should always be thinking of ways to try to come up with alternative scenarios that are plausible but not contained within the model. So I think it's a lot of education about the models don't necessarily have all the answers, and adding just more models into the mix, if they have the same biases, isn't going to improve matters. I'm happy to get out now, Robert, if you want to try to catch up, because I realize you're behind time. And
we are a little bit. Sadly, I'll pester you about this downstairs, but we will say goodbye to Richard Seeger. Thank you so much. And in the interest of trying to get back on schedule, I think I will skip the periodic rant, because you know what I'm going to ask you to do, which is to call your Congress people down there. And to address one of three questions. One is the dismantling of NCAR. One is the devastating budget, potentially devastating budget cuts in the president's budget, where we've had success in the past in pushing back. And the third is in the exertion of complete political control over the scientific grant-making process. So you know all that. So go do it, please. Do it again. Tell your friends to do it. Get your cats to do it. That would be great. But instead of hearing me encourage you, we'll hear instead from Rebecca Neumann, who's a professor at the University of Washington and is going to talk about rice.
Great. Thank you. Perfect. Yes, I'm excited to be here to talk today about my work looking at arsenic contamination of rice and how that might be impacted by our warming world. So arsenic is a global carcinogenic contaminant. It's found naturally in soils and sediments all around the world. When it gets ingested, it can cause arsenicosis, which manifests itself externally with these lesions I'm showing on palms and bottoms of feet. This is visually gruesome, but what really ends up causing the problems is when all the damage that arsenic does inside of the body. So this slide is showing all the various different systems that arsenic can impact. And chronic arsenic exposure has been showed to increase rates of death pretty significantly. So arsenic, when it's in soils and sediments, we don't tend to worry about it in terms of human exposure. The main thing is that children can sometimes directly ingest that soil and sediment when they're playing outside. The main thing, though, that we worry about is when arsenic moves off of soils and sediments and into the surrounding water. Because once we have arsenic in water, it can enter our drinking water systems. It can be taken up by our agricultural crops. It can move through our aquatic ecosystems, including up into organisms that we consume, such as fish. So the way in which arsenic moves off of soils and sediments and into water is through a process called microbial respiration. And so I know for many people, it's been a long time since you took chemistry, and this maybe looks intimidating, but the slides didn't quite work out quite right. But what I want to ensure you is that this is a process that you are actually quite familiar with, because it's happening inside of your own bodies right now. So respiration is the way in which organisms get energy to live. We do this by taking organic carbon in the food that we eat and oxidizing that carbon into CO2. We couple this oxidation reaction with a reduction reaction. We take oxygen and we reduce that to water. So oxygen as an electron acceptor is quite energetically favorable. So it's often the preferred electron acceptor. But there are lots of places in the world where oxygen is not available. So for example, within flooded soils where we grow rice. So what can happen is when oxygen is not available, microbes turn to other electron acceptors in order to generate the energy that they need to live. And a very common electron acceptor is iron. It's present in soils and sediments. So iron 3 is a solid form of iron. It's a mineral. And microbes will reduce that down to iron 2. Iron 2 is a dissolved form of iron. So when microbes take iron 3 and they reduce it down to iron 2, they end up dissolving that mineral. It turns out that elements like arsenic tend to associate to the surface of these iron minerals. And so when these iron minerals dissolve, what ends up happening is that arsenic moves off of the soils and the sediments, and it gets dissolved and mobilized into the surrounding soil water. So it's through this microbial process that we end up mobilizing arsenic into the water. Because we grow rice in these flooded soils where oxygen is not available and we have this microbial respiration reaction occurring, we tend to find arsenic in the rice grains that we grow. So this here I'm showing is a study from 2009 where researchers went around and they looked at arsenic in rice that they bought from the marketplace. So the top is showing what they estimated to be the global distribution of rice, arsenic in rice available in the global marketplace. The middle is just showing the distribution in Bangladesh, a country in Southeast Asia, and then I'm showing here in the United States. So these levels of arsenic by themselves don't tell us a lot, so we need to be able to anchor them to something that tells us if they are of a concern. So in 2016, the FDA passed a guideline that said we should try to keep arsenic levels in the food that we feed to babies below this threshold. And then the second line is a threshold that a study found in 2013 that began to cause genotoxic effects. So this basically means this is the level at which DNA gets damaged. That damaged DNA can cause mutations, which can eventually lead to cancer. So what this is showing us is that arsenic in rice is a global concern and that the levels that we're seeing in the rice are not negligible. The question I had was, what might happen to the levels of arsenic that we're finding in rice as we move into a warmer world? The reason why I thought that warmer temperatures might have an impact on arsenic in rice is because microbial reactions tend to speed up when we have warmer temperatures. And so this whole reaction that I stepped you through, I thought could be happening faster, which would mean we would have more mobilization of arsenic off of the soils and into the surrounding water, which would mean we would have more arsenic available to be taken up by the plant, and thus more arsenic that can move into the tissue of the rice plants that we grow. To test this, me and a graduate student and a number of undergraduate researchers conducted an experiment where we grew rice at 4 different temperatures. And indeed, what we found, sorry, none of the slides really converted quite right. So what we found is that, unfortunately, our hypothesis was correct. We were seeing more arsenic mobilization under warmer temperatures, which resulted to more arsenic moving up into the tissues of the rice plant. So this bottom panel is showing arsenic levels in the stems of rice plants. And you can see they're steadily increasing as we had warmer growth temperatures. And then the top is showing the levels of arsenic in the rice grain. You'll notice that the warmest temperature treatment didn't have any grain data, and that's because the plants were so temperature stressed, they actually didn't produce any grain. So this is kind of an additional impact that warmer temperatures can have on our agricultural system beyond just arsenic levels. But in general, we did see increasing levels of arsenic in the grains that we were growing. Again, put these levels into context. I'm showing, again, the FDA guideline for baby food and the genotoxic threshold. We were working in a relatively low arsenic system, but what we were seeing is that as temperatures warmed, we took a system where arsenic really wasn't much of a concern and kind of bumped it up into a regime where we began to worry about the levels of arsenic. So what this study indicated is that we are anticipating that this problem of arsenic contamination of rice can be exacerbated as we move into a warmer world. Often when I present this work, people get a little anxious about arsenic in the food that they are consuming. So I like to point people to a Consumer Reports. That this organization did 2 different studies in 2012 and 2014, where they went around and really looked at levels of arsenic in a wide range of products, rice as well as other grains. And kind of the high level take home message from their work was they identified rice, which tended to be the lowest in arsenic. So this was basmati rice grown in India, Pakistan, and California, and sushi rice grown in the United States. And then they highlighted products. They highlighted products that were kind of the worst in terms of arsenic exposure. And so there's supposed to be a nice map back here showing rice production in the United States. So it turns out that the rice grown in Texas, Louisiana, and Arkansas tend to be the highest in arsenic. And so these are products that I, in my own personal life, tend to avoid. And this is because these part of the country where we grow rice is where we used to have former cotton fields, and we use arsenic-based herbicides and pesticides. So I personally try to avoid rice grown in Texas, Louisiana, Arkansas. And then the other thing I avoid actually is brown rice. And that's because a lot of the arsenic accumulates in this outer hull, which is what makes rice brown. And so when they polish the rice and make it into white rice, that hull gets removed. And so you lose all of the arsenic that had accumulated in that outer part of the rice. And so people tend to think brown rice is healthier. It is from a fiber perspective, but not from an arsenic perspective. So I tend to focus on eating white rice. And then the reality is that most of us here in the United States, our diet is not very rice heavy. But if you are concerned, I point you back to this Consumer Report. They created a nice table and a point system where you can try to keep your points below a certain threshold in a given week. And they outline, kind of what different products will contribute to your diet in terms of points. Okay, so with that, I'd like to say thank you to my funding sources, including a study from the National Science Foundation, where we kind of expanded this greenhouse study and looked at arsenic throughout the lower Mekong. Well, actually, it was a bigger project, but our personal piece, we looked at rice and arsenic levels in the lower Mekong Basin. And I'm happy to take questions.
Yay, that is super cool. Thank you so much. We have a couple of questions in the chat. Some of them, I think, at some level you addressed, but maybe we'll dispose of them quick. There's the one from Sydney, which says it's interesting that rice grown in California and India has the lowest levels, even though they both have extreme heat. That's kind of related. I won't be able to say this name, but NII. Similar question, why are there higher levels of arsenic in rice grown in the US? So these seem like related questions. So maybe you want to expand on that.
Yeah, so the temperature is just like one variable. So there's like the soil that the rice is grown in. So in the United States, California tends to have pretty low levels of arsenic in the soils versus, as I pointed out, in kind of Texas, Louisiana, they're growing rice basically on soils which have legacy arsenic contamination from the past use of arsenic-based herbicides and pesticides. But there's then also kind of the species of rice that was grown. So different types of rice, they're different in terms of the levels of arsenic that they will take up out of the soil. And so that's a combination of a whole bunch of, plant physiology pieces. And so it just turns out that like the types of rice that get grown like in California just tend to be low in arsenic.
Super cool. Another question that we have from What Dog is, can we easily remove arsenic from either soils or rice?
So the levels of arsenic, again, I started the talk that it's naturally occurring, it's existing all over the world in soils and sediments. And so it's, it's impossible to remove it. And the levels that we're seeing in the water are actually quite low compared to what's in the soil. So, you know, it's like you have this huge reservoir in the soil, and then you have small amounts of it moving into the water. And that small amount is then what moves up into the plant. So there's not really a way to kind of remove it. It's a naturally occurring thing found all around the world. In terms of removing it from rice, so like that polishing, the converting of brown rice to white rice is kind of a straightforward way to remove the arsenic. But again, there's like there's research being done to identify, like, are there certain cultivars, are there certain species of rice that we can grow that tend to accumulate less arsenic? So there's ways to manage it kind of through agricultural choices.
And Sydney, who's got a lot of questions, has this one for you. What got you interested in this topic? And I would maybe ask, in addition to whatever general stuff you wanted to say, to talk about how you came to this topic scientifically.
Sure.
Yeah, and I have another question if we have time.
So when I started my PhD, arsenic in Bangladesh was the groundwater in Bangladesh, they figured out was severely contaminated with arsenic. And so there's this whole story about how aid organizations came in the 70s, and the idea was to move the country off of contaminated surface water from microbial contaminated surface water. And they moved them over to groundwater, and that helped in terms of waterborne diseases. But what started happening is that people started showing up with those lesions that are showing on the hands and the feet. And so people were, you know, wondering what was going on. And eventually they figured out, oh my gosh, this groundwater that we moved everyone over to has a bunch of arsenic in it. And so basically it was this mass poisoning of billions of people. And so there was this kind of big concerted international effort to try to understand arsenic, like why is there arsenic in the groundwater? You know, what's happening? And so there is this kind of big push to advance our understanding of arsenic biogeochemistry. And my PhD kind of coincided with that point in scientific progress. And so my PhD was based in Bangladesh, and I was studying and trying to understand how things that were happening at the land surface could be impacting what was happening in the groundwater system. And so I was working around all of these rice fields, and people started also then looking not just at arsenic in groundwater, but then like we're using this groundwater to irrigate these rice fields. And so what could be happening to arsenic into the rice? And so then people started doing these studies like I showed, where they went around and it turns out like, oh my gosh, arsenic is in rice, not just in Bangladesh, but everywhere in the world. And so then, and then you just start connecting the dots, and it's, so then when I launched my own career as a kind of an independent scientist, no longer a PhD student, started to pull those pieces together, like what might happen with climate change and kind of arsenic in rice. And so that's, I think, kind of how science happens. Piece by piece.
Yeah, right. Curious people embedded in a social context working on problems that matter. Thank you so much, Becca. It is the top of hour 45 on station WCLS, the weather and climate live stream. My time with you is done. Syl, somebody was asking in the chat, Syl is going to meet with legislators directly outside the Capitol as part of the closing of the live stream this afternoon between 5 and 6 p.m. So as I have understood it, he's going to hand over those letters to some of our congressional representatives. I now hand the stage over to my colleague, Duncan Watson-Paris, who's at UC San Diego. Good morning, Duncan. Somebody commented that Richard Seeger sounded like John Oliver's cousin. I can hardly wait to find out who you are, who you sound like. Oh, you're a more handsome John Oliver. Well done. Have fun. Get them to call. Get them to apply. See you later.
Fantastic. Thank you, Rob. Good morning, everyone, and welcome to the last 5 hours of the live stream. It's been a fantastic effort. I'm excited to kick us off this morning. I'll keep us on track. We've had a couple of great calls to arms, but I will hand straight over in the meantime to our next speaker, Yutian Wu, who's a research professor at Lamont Doherty Earth Observatory at Columbia. And I'm excited to hear about your work on sea ice loss.
All right, you hear me okay? Okay, so yeah, thank you for having me. My name is Yutian Wu, and I'm a Lamont Associate Research Professor working at the Lamont Doherty Earth Observatory of Columbia University. And in the next 10 minutes or so, I'll be happy to share with you some of our recent work in focusing on the polar sea ice, especially the Arctic. So I'd like to start by showing you this nice animation made by NASA, showing the NASA remote sensing measurements of the Arctic sea ice concentration. And as many of us here know, that the remote sensing is a wonderful tool and reliable tool for allowing us to continually monitor the changes at the two poles. And the time series plot showing you here is the annual Arctic sea ice minimum area from 1979 to 2024. So as you can see here, it started from about 6.5 million square kilometers in 1979 and ended at about like 3.7 million square kilometers in 2024. So this definitely is a dramatic decline in terms of the Arctic sea ice concentration. So in some of our recent studies, we zoomed in to focus on a region over the Arctic, and that's the Barents-Kara Sea region, and that's located north of Norway. And that's the place where the sea ice has melted the most dramatic over the past 4 decades or so. And we take a box average here, and you can plot the concentration over the Barents-Kara Sea in a unit of percentage from 1979 to 2021, something like that. And this is time series similar to what I just showed you before. But I think apart from a just overall decline of the sea ice concentration, I think what's more interesting to us is that this decline is not a constant. And there are definitely like a decade or 2 decades where the sea ice decline were much faster than some other decades. So we're curious to know why. And it turns out this question of how much of sea ice decline is caused by anthropogenic versus internal variability components is a fundamental question in climate science. And you can ask the same question, but for, say, temperature increase, right? How much of the temperature increase is caused by anthropogenic versus internal components? So first, we know that what we observe in terms of temperature or sea ice change is really a combination of 2 factors. The first one is what we call the externally forced component, as highlighted by the purple footprint. And the other is the internal unforced component, okay? And that's, giving rise to a lot of the wiggles in, the track. So for the forced component, it exists due to the external forcing. It can be due to either anthropogenic increase in atmospheric greenhouse gas concentrations or changes in the atmospheric aerosols. And sometimes we call that the signal. On the other hand, the unforced component exists due to the internal variability of the atmosphere-ocean system or due to the chaotic nature of the Earth's climate system. And they could exist in the absence of external forcing, and sometimes we call this the noise. So the question is, how can we isolate the forced versus the unforced component. So first, for the forced component, we, as many of us do, we make use of climate models. We take an average across multiple models, multiple ensembles, to smooth out those wiggles and to isolate the forced component. But for the unforced component, we wanted to take, a new approach, and we want to explicitly estimate that by using machine learning methods. So how do we do that? So first, machine learning methods, we don't want to use it simply as a black box. We want to start from something physical, right? And we know what is changing the sea ice in various timescales. From decades of research, we know it's driven by the wind that blows on top of it. So based on that, first we train the neural networks to establish the relationship between the winds or the atmospheric circulation and the sea ice trends using detrended climate model outputs. Okay, and after this is trained and validated, what do we do next? Is to fit in the observed circulation trends. In this case, is largely the unforced component to the trained model to estimate the unforced component of the sea ice trends or the internal variability of sea ice trends. Okay, so how does the result look like? So here we are showing the sea ice trends for 20-year slicing window from starting from 1980, ending 2022. Black is observations. Red is the anthropogenic or forced component, and blue is the unforced component that we explicitly estimate by using the machine learning method that I just talked about. So first of all, it's amazing that the blue bar and the red bar can add up nicely to the black curve, which is observations. And remember, we didn't tell machine learning to do that, and the fact that it can reproduce observations is something fascinating. And it probably reveals something fundamental, something physical about the climate models. And then because of this linear additivity, and this allows us to explicitly quantify the contribution from the two components that we just talked about. So maybe we can start from entire 43-year time periods, and they are shown by the two bars on the right-hand side. They are estimated by using slightly different methodology, but the conclusion is the same. You see the dominance of the red bar or the anthropogenic component. However, if we look at shorter timescales, right, this 2 decades timescale, what do we see is that the anthropogenic contribution is relatively constant throughout the years. And what is varying is the internal variability component. And specifically during this a 20-year time period, 1997 to 2017, you can see the internal variability actually contributed to a significant amount to the observed trend. And we can look at what was exactly going on in this 20-year time period. What we plot here is the sea level pressure, and you do see this circulation dipole pattern that sits over the North Atlantic Europe sector. And we know that what this is, right? Through decades of research in the area, we know this is a very effective atmospheric circulation pattern that is effectively steering the atmospheric flow from the lower latitudes towards the higher latitudes and melt the polar sea ice both thermodynamically and dynamically. And finally, for most of us who don't really live in the Arctic, why does it matter? And the fact is that the effect of Arctic sea ice melting or Arctic amplification in general is not limited to the Arctic, but it can be felt by the rest of the planet via changes in the atmospheric circulation as well as the ocean circulation. And this is a topic that has stimulated, active research in the past decade or so, especially the polar amplification multi-model intercomparison project, PA-MIP, which is really international effort that led to coordinated modeling experiments trying to address the causes and consequences of polar sea ice change. Here, I just wanted to quickly show you, two of our recent studies focusing on this topic and specifically on the heat extremes. So our focus is the Northern Hemisphere mid-latitude heat extremes. And the first study we focused on the summertime heat extremes, and we found a non-negligible but small contribution from the polar sea ice melting. On the other hand, for the wintertime cold extremes in the mid-latitude continents, we found a large contribution from the melting of the Arctic sea ice in terms of in reducing those cold extremes, both in the current climate as well as into the future climate. So I'll stop here. I'd be happy to take questions and discuss more.
Amazing. Thank you so much, Yu-Tian. I find it really interesting. I think it's a really nice use of machine learning, not to directly try and model the whole thing, but regress out the bits that maybe we don't want. And I think it's a nice sign that the forced response looks pretty constant, right? But the internal variability is the thing that's varying. So a couple of questions coming through on the chat. You obviously hit getting a lot of interest. So What Dog asks, is there more sea ice in the North Pole or the South Pole?
That's a good question. I think, that's really, I should have known the answer. For sea ice, I think I don't want to say anything wrong, but I think you can certainly find that answer in some of the NOAA website where they have the plots for the sea ice concentration over the Antarctica, as well as sea ice concentration over the Arctic, and how they change from one year to another. But I don't want to say something wrong. Yeah.
No problem. No worries. So, okay, a couple of other questions. So, sorry, have we lost enough sea ice? The sea route above Russia has become safe to traverse. This is obviously something that people, have talked a lot about in geopolitics and.
Right. I think there's definitely lots of research studies focusing on what's the tipping point, right, for the Arctic sea ice, and this is something that I haven't really looked at that myself, but my understanding is that when you reverse the forcing, right, when you mitigate the greenhouse gas emissions, there's hope that the Arctic sea ice can grow back, within a certain time frame. So it is probably reversible.
I wanted to actually touch on that because one of the things that we saw, obviously there was this precipitous decline through the early noughties in sea ice, and then it seemed to kind of flatten out. And I guess people were pretty worried that we would end up with a much sooner kind of ice-free summers in the Arctic, but it seems to have plateaued out. Which of those is noise, which of those is signal, and where do we expect the next decade to take
Oh
us?
yeah, that's a great question. This is something that it wasn't the focus of this study, but if you look carefully, right, into the most recent decade, like 2002 to 2022, you do see the reversing sign of the internal variability component, which is actually acting to grow more sea ice and counteracting the reduction of sea ice from the anthropogenic component. So we do see the signal, the signal of that from our machine learning exercise here as well. But as you talked about, I'm aware of other studies led by people like Mark England, Lorenzo Pavani, and they've looked into this in more detail and trying to explain why the CI sort of decline, sort of flattened over the past decade or so. And I think their conclusion is kind of similar. It's because of internal variability.
Right. Let's hope it stays small for a while longer. Yeah, there's a good topic a good question came in, sorry, about how you got interested in this topic. So this was an interesting question to hear people's backgrounds and hear about how they got curious about the topic.
Yeah, sure. When I was in undergrad, I was interested in physics and mathematics. And then wasn't exactly sure what I wanted to do for graduate school, excuse me. And after I came to the United States for graduate school, I got to know more in terms of climate science, right, which is fundamental to physics. And it is a topic that allowed me to sort of practice my skills in physics and mathematics, but also apply the skills in something that we can see and feel on a day-to-day basis. So that's why I got interested in the topic, climate science, climate modeling.
I can relate to that.
Yep.
All right. Thank you so much, Yujin. Appreciate you taking the time. So welcome to those of you who may be joining us this morning, West Coast time or lunchtime East Coast, or indeed anywhere around the world. So we've seen a lot of talk so far. The next speaker is no exception. I just thought I'd take this moment to kind of remind us why we're here. So weather and forecasts and the work that Yujin just presented on trying to understand and decompose the changes in critical Earth system components like sea ice are important for everyone. And US scientists have become world leaders in many of these aspects. And so we developed the first computerized weather forecasts and climate models. And that success is only possible because of decades of investment by you, the American public. And there are a number of ways in which these efforts have come, being undermined. Particularly egregious at the moment is the political interference from the proposed by the Office of Management and Budget, OMB, and they've proposed a number of changes to the way that scientific funding is allocated, which would let political appointees make funding decisions about specific grants instead of scientists. One of the cornerstones of our science is the peer review process, which is very rigorous and make sure that the questions we're asking are, pertinent and interesting and advance the science. And so these changes would limit the types of science that can receive support and restrict how we can share our public with each other and with the public. So if you please take the moment and take an opportunity to call or write to your representatives at wclivestream.com/call. It seems, frivolous. It seems like, it's just another voice, but it really can make a difference. These representatives have a lot obviously going on, and the more they hear about these specific issues, the more inclined they are to do something about it and find out about it. Okay, so without further ado, I'm delighted to invite our next speaker, Adam Sokol, who's a postdoc at Princeton University, and he will discuss zeroing in on clouds and climate. Hey, Adam, good to see you.
Hey, good to see you too, Duncan. How's it going?
Excellent.
Good.
Over to you.
Yeah, so I'm Adam. I'm a postdoc now at Princeton University. Before that, I was a PhD student at the University of Washington, and my whole research career has been predicated on public support for science. Now I had a NASA fellowship that funded my graduate studies, and now at Princeton, I work for a cooperative institute between the university and the Geophysical Fluid Dynamics Lab, which is a NOAA lab in New Jersey. So really, without that kind of public support for science that Duncan's talking about, my research career would have looked very different. So I'm going to tell you a little bit about my work and also just in general about how we observe clouds and model them, and especially thinking about their role that they play in global climate and climate change. So what you're seeing here is an image taken from the International Space Station of some convective clouds in the tropics. So these are really deep thunderstorm clouds, and you can see that they're producing these really expansive kind of disks of thinner clouds in the upper troposphere. So that's around 13 kilometers or so of altitude. And the fact that these clouds look really white to us means that they're reflecting a lot of sunlight. And in this case, the sunlight goes right back out to space. So this is a pretty large local perturbation to the energy balance of the planet. And if we add these up over all the clouds we have in the atmosphere, this is a pretty significant player when it comes to the radiation budget of the Earth. And that's what I'll talk mostly about and what my work focuses mostly on. But the radiation impacts of clouds is kind of just one part of the story when it comes to the importance of clouds and weather and climate. So I think you don't have to be a scientist to know that clouds are obviously really important when it comes to weather, right? That's where rain comes from, and pretty much all of our weather except a sunny day is defined by the presence of clouds. So because they bring rain, they matter for all sorts of things that depend on precipitation, such as ecosystems and agriculture, as well as a lot of severe weather, hurricanes, monsoons, and flooding, all these different things. And over the last few decades, really our understanding of the role of clouds in climate has matured quite a bit. So we no longer see them as kind of just a passive marker of where we have rising air in the atmosphere and where we have rain and stuff like that. We now kind of appreciate the fact that they're much more of an active player in the dynamics, both of individual weather events and also the kind of global dynamics of the atmosphere and of the climate system. They are very tightly coupled with the circulation of the atmosphere and with many other components of the climate system. And we can't really just mark them as a passive marker of what air is doing. They really play a very active role in shaping weather and climate really across the globe. So in the top right here is this little cartoon we have of a cloud reflecting sunlight back to space. And that's what I said my work focuses mostly on. So we call these cloud radiative effects. And they generally fall into two different categories. So the one on the right is the one I already mentioned. We call this a shortwave radiative effect because it occurs in the shortwave part of the electromagnetic spectrum. This is visible light. And these clouds are just acting as an umbrella. Basically, they're reflecting sunlight back out to space and shading the surface. So that cools the climate, just like an umbrella may cool a person during a hot day. And then on the left-hand side, you have this other category of radiative effect. We call these long wave radiative effects. This is in the infrared part of the spectrum. And this is the opposite effect of the shortwave. It actually warms the climate. And that's because it's trapping infrared radiation that would otherwise escape out to space. So you can kind of think of this as wrapping a blanket around the planet and keeping the Earth warmer than it would be otherwise. So you have these compensating effects here. And the net radiative effect of any cloud in the atmosphere is just the sum of these two parts, and different types of clouds will have very different net radiative effects. For example, low clouds in the atmosphere, clouds near the surface, the shortwave effect tends to win out. So they have a cooling effect on climate, but these higher kind of wispier cirrus clouds higher in the atmosphere have a much stronger long wave radiative effect. So they tend to warm the climate on average. So if we average over many years, we can get a sense for the climatology of how these clouds affect the radiation budget of the planet. So these are long-term averages. On the top, you see the shortwave and the long wave components of the radiative effect. And those darker colors really are just tracing where clouds exert the largest radiative perturbation. So this is just where clouds are. And that's generally the same place as where we find a lot of rainfall on the planet, right? So these darker colors in the shortwave and long wave are compensating. So when we look at the total, we see that the colors are much brighter and the net radiative effect is actually much closer to zero. And that's especially true in parts of the tropical atmosphere, like over Southeast Asia, near Australia, the Indian Ocean, and across the Pacific as well. So there's this balance, almost exact balance between the shortwave and the long wave in this region of the tropics. And that's something that we've been interested in for a long time, something we've also thought about in my own research. How does that balance kind of arise? What are the exact forms of clouds that we need to see that balance? And is something that's kind of fixed, or is that something that could change in the future? So we can get maps like this and understand the climatology of clouds because we have these great satellites that can fly around in space and take pictures of cloud systems over many years. And when it does that, we can get a good sense for how clouds exist and interact with different parts of the atmosphere. So this is what's called the A train. This refers to this constellation of satellites that are NASA satellites that fly very closely together so that they're basically taking pictures of the same cloud systems at more or less the same time. So two that I have used a lot in my work are CloudSat and Calypso. These are what we call active sensors, meaning they're flying, and as they fly, they shoot down basically a laser beam, and they get the backscatter from that beam, and that tells us something about the clouds underneath. We also have these passive sensors like these ones you see on the right with these large red fans, and these aren't shooting their own laser, they're just kind of taking a picture of whatever is already coming up from the surface of the planet. So when we have all these different instruments together, they're each telling us something different about the same cloud. We can piece those together, and that ends up being a really powerful combination of measurements that we can learn all sorts of things about these systems. So this is just an example of some things we've learned in my own work. So on the left here is just the climatology of specifically higher ice clouds in the atmosphere. So these are everything from the tops of thunderstorms to the very thin cirrus clouds that become barely visible to the naked eye. And you can see that in that Southeast Asia region, almost 80% of the time or so, you have some sort of ice cloud overhead. That could be a thunderstorm, or it could be something you can't even see. But it tells us that these clouds are going to be really important in that region for not only the radiation budget, but for also things like how is water vapor transported into the stratosphere, many different aspects of climate that depend on this cloud climatology. We can also learn a lot by looking at individual events. So this is an example on the right of some new data that I just was downloading the other day from the EarthCare satellite. So this is actually from the European Space Agency. This satellite was launched in 2024 as kind of a successor to CloudSat and Calypso. It contains some of the similar instruments. And on the top, you can just see the types of particles we're looking at, basically if it's ice or liquid. And on the bottom is kind of the amount of condensed liquid or ice in the clouds. And you can see that varies a lot within these systems. And you can see these lighter white colors are at the center of these convective storms where the cloud is very deep. And that's where we have kind of the center of our thunderstorm action and where you'd expect to find the most rainfall. What's really new and exciting about EarthCare is that we can also estimate the vertical velocity within clouds. That's what I'm showing on the bottom. The red color means that the air is rising vertically. That's what we expect within clouds. That's why we have clouds in the first place. But this isn't something that we can easily measure from space. So it's really exciting to have these measurements now because they're going to allow us to answer all sorts of questions about the dynamics of these systems. What's the kind of timing of these updrafts within thunderstorms? How do these systems evolve over much longer periods of time? Questions like this that are really important for understanding the full role of these cloud systems in global climate. So these satellites help us observe clouds in the present day. We're obviously taking pictures of things that are already in the atmosphere. If we want to understand the role of clouds in a future climate, if it's warmer, we have to rely on modeling tools, right? And modeling clouds and their role in global climate has been this kind of decades-long grand challenge in the climate modeling community. It's something that's very difficult, and that's because there's important things happening at a really wide range of scales here, all the way on the left from the different shapes of ice crystals that we find in the atmosphere. We need to model and account for those shapes because they have a big impact on the amount of sunlight that might be reflected by a cloud. In the middle, we're talking about processes that occur at both microphysical scales, but also the scale maybe of an individual cloud, things like mixing with the environment, the formation of new particles, things like that. And on the right-hand side, we're talking about these scales maybe from 10 to 100 kilometers, where we tend to find these storms kind of clustered together at those sorts of scales, like you can see in this image on the right. That gives us things like supercell thunderstorms, squall lines, and stuff like that. So all of these processes are what gives us clouds in the real atmosphere, but all of these are occurring on scales much smaller than what we can resolve in our models. So that means we have to parameterize clouds in our global climate models, and that's been long been a role of uncertainty in our simulation of future climates. Another approach we can take is to simulate the atmosphere at much finer scales, but to not do so over the entire globe, just to kind of do so over a generic box or a specific region. And we can use something called a cloud resolving model to do that, which you can see an example of here. So you can see at this horizontal resolution of 1 kilometer now, we're able to actually see individual clouds form and watch them evolve over time. So in my own work, I've used models like this to answer a few different questions we have about clouds and climate, such as the radiative feedbacks associated with deep convection, how warming affects spatial patterns of rainfall, and the influence of aerosols on clouds, and how that goes on to impact the large-scale circulation of the atmosphere. So this last project about aerosols is something I've been doing more recently, and I'll just mention a few brief slides about some cool results we have from that work. So I'm not the first one on the live stream to talk about aerosol and clouds and how they interact with one another. I know Rob Wood was talking yesterday about marine cloud brightening. So this picture, I think, really sums it up. These are ship tracks in the North Pacific where container ships are combusting fuel and emitting small aerosol particles. And you can see that that obviously has a huge impact on the clouds that form in this particular region by brightening the clouds and also leading to enhanced cloudiness where we have those aerosol particles. So we did some simple experiments to try to understand how this brightening of clouds by aerosols impacts the larger scale circulations of the atmosphere. So we used one of these cloud resolving models to simulate a very basic circulation where we have some warm region where we have a lot of rainfall and thunderstorms, and then some cooler region where we have subsidence and it tends to be very dry, and some large scale circulation between them. So we did a simulation like that, and then we basically pollute the model domain tremendously. We just add a ton of aerosol into the atmosphere. That's going to brighten all the clouds. And we were interested in what happens to that larger scale circulation when we do that. The results ended up being pretty cool. So on the top is an animation of that clean experiment, and the white here is just showing where the clouds are. And on the bottom is this experiment that was polluted. And you can see we just completely changed the texture of the storm activity that's happening mostly on the right-hand side of this model domain here, where we have the warmer surface and where we have most of the rainfall. So when we add pollution, we tend to find more storm activity overall. You can see all these kind of white spots popping up in the right half. And we just get a more turbulent convective region. There's a lot more air being transported upward in the atmosphere in these storms, but we actually find basically no change at all in the large scale mean circulation that we were interested in. And this is quite fascinating because usually we think of the storm activity as being pretty tightly coupled to the large scale circulation. And this result is showing that we actually break that link when we add aerosols because we change the spatial distribution of where those storms are occurring. So we have enhanced storm activity, but we have kind of compensating subsidence happening right there, exactly where the storms are. So we have more turbulent mixing on the right, but not necessarily more net ascent out of that region. So we find quite different results if we add aerosols just to one half of the domain instead of uniformly. So this is one example of the type of mechanistic understanding we can gain from these high resolution experiments. And we found that if we add aerosols only to the drier, cooler region, we actually get a big strengthening of the large scale circulation because we actually contract the region where convection occurs. So by simulating these different scales with a model like this, we can see how these smaller scale cloud processes actually lead to these kind of remote effects on the larger scale organization of convection several thousands of kilometers away. So lastly, I'll just wrap up here by saying if we want to continue answering interesting and important questions about clouds and climate, public support is obviously critical for that. So on the left is a global cloud resolving model developed by the Geophysical Fluid Dynamics Lab that I work closely with at Princeton. This is called XShield. These models are incredibly exciting because we can simulate the whole globe. We're starting to do so at several year timescales, so starting to get closer to those climate timescales. And this is obviously revolutionary for climate modeling because you can see just the great amount of detail we're able to simulate with individual weather systems in a model like this. Also, continued satellite observations into the future are going to be really important, not just for understanding these basic science questions we still have, but also understanding trends in cloudiness as we start to observe clouds responding to changes in the climate. So these are just two missions, INCUS and AOS, from NASA that are targeted to be launched within the next few years. And I really hope those go through because those will be really incredibly valuable for a lot of the questions we still have about clouds. So I'll wrap it up there, and hopefully there's some time for some questions.
Fantastic. Thanks so much, Adam. A lot of great visualizations and really nice explanations. I have lots of questions myself because I find this super interesting, this question of how the aerosol effects in one region are communicated to another. Do you have a good kind of physical explanation for what's causing that suppression in convection from the physical changes in the shallow cloud regions?
Yeah, so basically when we add aerosols just to these shallow cloud regions, it seems like the boundary layer, basically you have enhanced mixing at the top of the boundary layer with the free troposphere. And that's something that has also been kind of noted in these much higher resolution LES experiments, just looking at low clouds, is that when you have a lot of particles, you just get more turbulent mixing at cloud edges. So that basically dries out the boundary layer, which means that as air is traveling from that dry region over to the warm pool, it has to go just a little bit further to pick up enough moisture to convect. And that's why we have this kind of shrinking of the convective region and this kind of strengthening of the overturning circulation.
That's cool.
Yeah.
What would happen if the aerosol were absorbing? If this was a smoke layer or something, how would that change the picture?
Yeah, that's a really fantastic question. So yeah, in these simulations, there were no direct interactions between the aerosols and the radiation. We were just looking at the cloud part. So if the aerosol is absorbing, obviously where that aerosol is in the atmosphere is going to have a huge effect, right? If it's in the stratosphere, that's going to warm the stratosphere, and that will stabilize the upper troposphere. And we think that would slow down these circulations in the tropics, because convection basically has to puncture through a more stable atmosphere. So in general, I think as we warm the upper atmosphere, these circulations should probably slow down. But of course, if you have a smoke layer lower towards the surface, that would be completely different, right?
Yeah, right. Interesting. Cool. We'll have to chat another time. Some other questions are coming through on the YouTube. Could we use vertical velocity to help diagnose and track tornado formations? So I guess this is in reference to some of the satellite observations.
Yeah, that's a great question. So that's something we do to some degree, not always vertical velocity, but basically how we detect tornadoes from afar is with Doppler radar, right? That's what can tell us a little bit about how the air is moving within these cloud systems. And we look for this particular pattern that's associated with like a very small scale spiral that you would see in a tornado. So that Doppler radar instrument is exactly what we have aboard EarthCare for the last year and a half. So that's exactly the same satellite technology, basically, is how we're measuring. We're trying to measure vertical velocity within clouds, but now from space instead of pretty locally on the ground.
Brilliant. And just lastly, I quite like this question of, how you became interested in studying clouds. What got you excited? What sparked that initial curiosity?
Yeah. When I was little, I kind of always had some interest in weather, but nothing ever really came of it. I remember just when being very little, just kind of watching the Weather Channel on TV for fun. Nothing really came of it. And then I was in college trying to figure out what I wanted to do with my life. And I kind of got interested in environmental things and thinking about climate change. And I knew I was definitely more interested in the science part of it. And that's where I thought I could contribute. And then I kind of just kept finding myself fascinated in this question of the role that clouds play in climate. I think clouds are something that have been captivating the imagination for probably thousands of years, I'm sure, right? So I'm far from the first one to just find them innately interesting for some reason. And it just so happens that they were such a big question mark in climate science. And a lot of the areas and the questions we had that were interesting related to clouds and their role in climate in some ways. So that's kind of how my trajectory went and how I found myself here.
Yeah, I often reflect that we're in this lucky position of being able to study a really interesting, complex phenomena that happens to also be really important for the world. So yeah, we're very fortunate. Thanks, Adam. Appreciate it.
Yeah, thanks. Yeah.
All right. So next up, I'm delighted to introduce Scott Weaver. Hi, Scott, the former White House Executive Director for Meteorology, has a fantastic perspective on the role of the federal government in supporting these endeavors. And I think they're going to talk about kind of interdisciplinary challenges in kind of climate adaptation. And we're not without challenges, Scott.
Oh, believe me, I know. Thank you so much for the introduction. We're not sure if my slides are going to move, so hopefully the folks on the tech side will have to move them if they don't. But I list my three previous affiliations, my current one in consulting now, but really the one that's important is the third one away. So I'm a climate scientist who was doing research, publishing papers, etc. And I started job hopping, which at first felt very scary, to be quite honest with you. It was my career path might be a little bit untraditional. And I found myself taking some chances, and I ended up as the director for an interagency disaster program for windstorms. And that at first was challenging, but it really exploded my view. And it's actually how I came into this topic. I was not searching for this topic. I was working on like seasonal climate at NOAA's Climate Prediction Center. So very different than how I started. But what's cool is by interacting with people in a highly interdisciplinary environment, it really changed my thinking. So the first thing I want to show you, I'm going to go through some slides very quickly because this is really a 40-minute talk. So think of this as like a trailer for a movie. I want to start with the engineers. This is a design wind speed map. Engineers have different categories of risk. So this is for risk category 2, which is like your home or like common construction. And so basically what this map tells you is this is what wind speed, what gust wind speed you should build your home or business to withstand. So we're going to see this map later. I just wanted to throw it out there as the initial tool of the example we're going to be using. We're going to be using winds, which are very hard to garner from climate change models, but in any event. And I wanted to point out the engineering community is really going out front on this. The engineering community that I experienced was highly interdisciplinary, working with social scientists, et cetera. So they're very out front in looking for other ways to engage. They also have accountability. These are engineers designing buildings, et cetera, and also setting the national design standards upon which building codes are made. And so they've started, and this is just one of many examples, they've started, trying to get comfortable with the climate science community. But as we find when climate scientists and structural engineers meet, it could be very challenging. We have different points of view, very different points of view. Our training is very different, et cetera. Well, if you're an engineer and you start thinking about climate change, you might see this as one of the first metrics of climate change. This is our metric, right? This is our globally and annually averaged temperature. Sorry, I guess the slides are not advancing. Okay, that's not good. Okay, so we're on the globally average temperature. And so you could see you have wiggles here, and you could see the red smooth lines with showing the trends, and what you can really see is an acceleration. So if you're an engineer, you may be wondering, what does this mean? What do I do with this? And so please, next slide. And you would be right, because society doesn't feel the globally and annually average temperature. Society feels this, right? The tracking metric doesn't really tell you much about what's happening on the ground, obviously. And so going from just a large scale metric like globally average temperature to this is a significant scientific leap, if you will. Next slide, please. Okay, so what we really want to do is quantitatively link these two. Well, that's essentially an attribution problem. So for those of you who might not be climate scientists, I wanted to discuss that a little bit. But before we do that, this is all in the past already. So if we can go to the next slide, if you're an engineer, you might have been reading about the Paris goals over the last 10 years in the New York Times or the Wall Street Journal or whatever media you consume. And by the way, I know these scenarios are old. The scenarios are not the point. It's more about the overall discussion. So I didn't hunt down the new figure, but anyway, if you're an engineer, you're looking at this and you're going, but when I talk to the climate scientists, they're really not bullish on 2 degrees. It's probably going to be higher. So if you can please hit and so engineers need to be thinking about higher levels of global warming, because as I mentioned, they're literally accountable to what they do. If something fails, sometimes that could cause problems. And so that community is starting to think about climate change as much more of a risk factor for their designs that need to last 100 to 150 years. So one of the big questions we had at first was, do we follow scenarios or do we go with global temperature levels? And I can't get into why the science, I don't have time to get into why they're different, but defining global temperature levels is difficult. I mean, there's swings and, decadal variability. And when are you actually at 1 degree, 2 degree, 3 degree? It's difficult. But generally the community seems to be landing on temperature levels to do this work, which for many reasons makes pretty decent sense. Next slide, please. So as I mentioned, this is kind of an attribution problem. Now, this is literally one of my favorite graphics in all of climate science history, because again, I'm not going to do this, but you could probably spend 20 minutes, if not longer, exploring this graph. The more you look at it and the more you try to rationalize where the scientists put these different events, the further down the rabbit hole you can go with theory. And it's very interesting if you really think about it. But I'm concentrating on tropical cyclones here because we're time limited here. The only thing you need to know about this graph is the further to the right or the further up an event lies on this graph, the more confidence climate scientists have in being able to attribute these events to climate change or not, being able to find out essentially. And it makes sense, right? Temperature upon temperature, global warming and our temperature metric. So obviously the temperature events are easiest. But what if you're interested in winds along the coast and you're thinking about tropical cyclones? Well, then you might have an issue. But I do want to point out that the tropical cyclones, and actually all the events, but maybe more so for the TCs, are much further to the right than they are up. So what that means is we have more confidence in being able to understand how climate change may be affecting a group of events or its distribution. Is it variability getting more? Is intensity getting more? Things like that. So next slide, please. So just to give some an example, like what do you mean by attribution writ large? So I'm going to be this is like poor person's we call poor person's attribution. This is not real attribution, but just trying to give someone insight. So hurricanes feed off warm water. So if you look on the left panel, these are the trends for the years 1900 to 2015. It's a little old, but the trends are still there, obviously. And you see increasing trends in the main development regions for tropical cyclones near the United States, near North America. And it's not surprising. If you look over on the right, look at the red distribution. You can't get a Category 5 hurricane according to this. Essentially, I don't know, below, you have to extend the line, but below 82 Fahrenheit. And so if the trends in ocean temperatures are increasing, it's not far-fetched to think, hey, well, we could have more Category 5s. It's pretty simple. Next slide, please. There's also single event climate attribution. And so this is Hurricane Michael. You could still start to use the ocean temperature patterns for this. And so you can see that the difference between when Michael was way down here in the Caribbean Sea and came up through the Gulf of Mexico, the difference in the ocean temperature anomalies there. And so basically Hurricane Michael came through, picked up all that potential energy stored in the ocean and just deposited on the coast as winds and rain. And so that may be like the first step into thinking, does climate change even have an effect on this storm? To the extent that you could attribute the sea surface temperature anomalies, you could start to say, yeah, it may have, or it did some portion of the storm. And then you would go through all of your modeling and other data sources and methods to try to confirm that. Next slide, please. So remember, I told you we would be back here again. So we're back here at the wind design map, which you probably didn't see the first time because my slides weren't advancing. So as I mentioned before, wherever you live on this map, this is suggesting you should build your home or your business, build whatever building you're building or infrastructure to withstand this wind speed in this part of the country. So you may notice in South Florida, it's very high. And then as you move along the west coast of Florida into the Big Bend region, it drops by about 50 miles per hour. And then as you go west along the coast, the design wind speed increases. Well, that's because this is all based off of, the past climate. There's no climate change involved here. And so what originally, if I had control of my slides, you wouldn't have seen all this at one time. So I would have brought in the storms later, but we've had 3 above design level storms in 3 years in a row, 2018, 2019, 2020. Now, Dorian didn't make landfall, so I'm sort of cheating here, but Dorian was predicted to make landfall like 3 days before and suddenly made a right turn due to a cold front coming across the southern US. Had it made landfall where it was predicted, it would have definitely been above category. So in sort of the final the final slide here, I want to show you, please advance the slides. I want to show you how the engineers view these above design level events. So imagine if we're doing some kind of attribution, Hurricane Michael. Imagine someone did an attribution study. They determined that Hurricane Michael's winds were, 20 miles per hour more than they would have been if the storm occurred 200 years ago. Well, I think that's very important information to tell the story. Now, you might not be able to connect scientifically all the way through from the climate science to the disaster, but I think it'd be interesting to look at what the engineers find post-disaster. So what these figures are showing, we've zoomed in on those boxes I showed in the previous slide. So this is zoomed in on the panhandle of Florida, if you couldn't tell. The design wind speeds are in gray, so you can see those cutting along. And then the contours are the estimated wind speeds from engineering models and other data sources. People go out ahead of the storm and place wind measuring devices, all kinds of different data sources, and some modeling. You can't avoid it. And this is what they come up with for the storm. Anywhere you see warm shading, it means that Hurricane Michael's winds exceeded the design level. Okay, so this goes right from the coast. Hurricane Michael came in as a category 5. It exceeded the design level winds all the way into southwestern Georgia. I know I'm at time. I just want to explain one more thing. So That went right from the coast all the way into southwestern Georgia. Hurricane Laura, on the other hand, a little bit different. The engineering community decided to color the winds that are the below design level, but almost there. That's what the blue is. But you'll see the red and the orange or whatever shade they are, pink again. And you'll notice it doesn't become, Laura didn't become above design level till it already was pretty far inland. So that's really a case of where the hurricane kind of held itself together close to its maximum intensity and moved inland across the gradient of decreasing design wind speed. So it became above design level. So anyway, I'm finished here. I know it's sort of like picking things out of a tornado. There's some climate science, there's some engineering, and that's kind of what it's like. So when you're dealing with the two communities of having conversations, we're still trying to find kind of like, how do we link these things together? And like I said, there's more here that I would love to talk about, but if anyone has any questions, I'm happy to answer them, or comments too, please. Comments are great also. So thank you.
Amazing. Thank you, Scott. I really appreciate that perspective. I think it's really interesting to kind of, it links the research we do to that really human aspect. And like you say, right, the storms that people feel and the damage that is done on the ground and the very visceral impacts. I wonder, I mean, in the face of the political, let's call them headwinds, right, that we face in the research in the climate and weather community, right? How do we, I think this is a great way of doing that, but like, can we better communicate the impact of this research through your engineering, through these kind of questions where we're like, look, if you want to have infrastructure that can withstand the changes we're going to feel over the next 10, 20, 50 years, like we need to know what these things are.
So this is an excellent question. And I might say things here that might get me in trouble. Look, I'm not, everybody, we're all humans and we come, it's not going to get me in trouble, but I mean, we're all humans and we come to this from our own perspective. So I was not a climate change scientist in the early parts of my career. I was working more on like interannual variability. So the politics of climate change science were sort of like to the side. I was adjacent to it. But I will tell you, I could swear that I remember adaptation being like a 4-letter word at one point when I was in graduate school.
Right.
And I'm not 100% sure of that. And that's the reason I bring this up is because I wasn't in the climate change science community. I was coming from sort of the weather climate community, right? And so I wasn't really in on that. I just kind of remember that being a thing and not really thinking much of it at the time. But as I became I did become a climate change scientist at one point. And, I would bring things up like, we're not paying enough attention to adaptation. And sometimes I would get some looks like, we don't talk about that. It's mitigation. And don't get me wrong. Of course, mitigation is like that's where we need to be. But it's also, important that, in my personal opinion, and like I said, I don't really care what anybody thinks about what I say. My personal opinion is that we missed the boat on adaptation. We're too far behind. We should have been trying to link structural engineering and climate science 25 years ago. I mean, this is something, we are late to the party. And now you have two fields where highly technical people that are brilliant. I'm just a communicator. I'm not one of those brilliant people, but who are brilliant. And it's like we lock heads. I had someone in a meeting one time, an engineer, like not being serious, but kind of banging on the table. Like, I just need a number at this location in 2100. And, my head wanted to explode over that. I was like, we don't do that. We give you PDFs if we give you anything, which,
Right.
So,
right.
There's, even with these highly technical people, we've been trained completely differently. And I'm not saying that engineers don't understand uncertainty. They deal with it all the time. In fact, it's constant in their calculations. But I just think in terms of the way people are brought to think about weather models, climate model, they think in weather model terms, not really climate model terms. It's a very different thing, as you know. So
I wonder, I mean, what role does, insurance, reinsurance, there are big capital, infrastructure investments, right, at risk, right, and surely someone is
okay, so you just brought up something very interesting. Again, like I said, this is really a 40-minute talk, so if it seems a little scattered, I just did what I could, but I really wanted to get this out there. I think this is really important. I mean, I think we need to be, call me crazy, but linking climate science and engineering departments at universities and maybe having some kind of major in that, or that's where I want to go with it. But you're talking about the reinsurance company. So they do catastrophe modeling, right? And that is wholly interdisciplinary. Like you have the hazard piece that climate scientists and meteorologists work on is just one part of that. They're constantly studying disasters and looking at engineering failures afterward to update what are called fragility curves, which are essentially, if you get this level of hazard, here's your probability of failure. And so every disaster that happens, they're out there learning and then updating their empirical catastrophe models. So what's interesting to me is, even though that's mostly the purview of reinsurance companies, that lab, the catastrophe model lab, is very interdisciplinary. There's social scientists involved in that, structural engineers, other kinds of civil engineers, you name it, right? And I mean, I worked on a team once for disasters, and we had an epidemiologist because they were trying to understand, secondary impacts after a major disaster, et cetera. So the catastrophe modeling enterprise, to me, is kind of where that all happens. And I'm involved in a project now between Lehigh University and Rice University. They're the kind of academic leads, and then industry comes in and sort of funds the projects, but all the companies share the results, so to speak. Yep. And that is like a microcosm of what I'm talking about, because they're working on developing better catastrophe models, essentially, or at least the components of them. And it's super interesting, but it also just goes to show you how it needs to be interdisciplinarity is hard, because we all come from our background, and then it's very difficult to put those together, but people are doing it and doing it successfully. I just think we need to do it on a bigger scale. And I think if the federal government's going to support science, which we're not sure, then they need to be more into this situation too. I'm not necessarily developing a catastrophe model.
Actually, just to pin you on that a little bit. So Stephanie asks a really nice question. So as an outsider, seems like a no-brainer, getting everyone together. What stops you all from breaking down these silos, right? To put a fine point on it.
It's what stops us from breaking them. Right now I feel like nothing should stop us. I mean, sometimes when there's ashes, you can change that. I mean, I haven't thought deeply. I really like the question because it comes from like the other perspective. It's like why can't we break this? And I agree. Maybe it's time we do. I'm already in my 50s, so I'm a little set in my ways. So I would love for some people that are coming up that are seeing the world from like younger eyes and like getting exposed to all these different things, because that has changed. I can get into that too. I don't know if you've ever been to an undergraduate research symposium these days in meteorology, but the work they're doing is what I was doing for my master's degree. You know what I mean? Like things have changed. The students now are so much more brilliant than we were back then, and the younger scientists too. And so not to punt the ball. I hadn't really thought about it.
No, I think I agree. Actually, I think science is becoming more interdisciplinary, and I think that there is a level of bureaucracy, and just the way we organize our institutions has traditionally been fairly siloed. But I think with data science, machine learning, and other engineering, disciplines coming in there that are inherently interdisciplinary, I think that's starting to change.
If I can just say one more, there is a program that exists, but it sits on a shelf. There's a law, a congressional law, the National Windstorm Impact Reduction Act, which stands up the National Windstorm Impact Reduction Program. That's the program I was the director of. It's, in theory, the strategic plan, everything you would want to see to begin to solve the problem of what I'm talking about. Everything. But nobody funds it. It's a coordination program, and that's it. So if you want to have this happen, fund NWIRP, or what we call NWIRP. And that's all I'll say. Thank you.
Call your representatives.
Yeah. Thanks, guys.
Amazing. Thank you, Scott. Okay. Well, that was a really great, perspective from the engineering point of view, and I think a really interesting set of questions around interdisciplinarity, and really speaks to the role of federal government in funding and supporting those, all the way from that felt impact at the community level back through the engineering and back to the fundamental science that many of our talks have been about. And so we switch gears now slightly, and I'm welcome to the stage Professor Spencer Hill, who's a faculty at City College of New York, who will introduce and discuss the weather drivers of smoke events in the northern US. Hey, Spencer.
Hi, Duncan. Thank you for hosting. Pleasure to be here. Are my slides looking okay?
Looks good to me.
Wonderful. All right, let's jump in. So I'm coming to you from Harlem, New York, the City College of New York, where I am an assistant professor. And we're going to be talking about this infamous smoke event that hit this city among many others in the Northeast US in June, just under 3 years ago now. This is work that was led by Greg Randazzo. This was his master's thesis, working with myself and Jimmy Booth in the Department of Earth and Atmospheric Sciences here. And Robert Field from NASA GISS was a key collaborator. And Greg is continuing follow-up work, working with the same team of folks via a PhD through the CUNY Graduate Center. The thesis work, what we're showing today, is all published earlier this year in JGR Atmospheres. Okay, so starting a talk on fires with an obligatory shot of an intense fire going on in a forest. The point here is just to remind ourselves, we're not talking about a campfire, right? We're talking about massive blazes, incredibly intense fire, thousands of acres burned, incredible amounts of smoke produced. So 2023 was a horrific year for Canada in wildfires. This is showing you over each individual calendar year, January through December in the x-axis, the amount of PM 2.5, that's particulate matter with diameter less than 2.5 microns. We care about that because they get into our lungs and are extremely damaging. So it's the amount of PM 2.5 emitted for each individual year up to that point in the year. So each of those gray curves is a different year other than 2023. And then the red is that year for Canada as a whole. And you see it started early and it just never let up. It was a record shattering year for wildfires in Canada. Of our particular interest are the ones that happened in the very beginning of June in Quebec. So that's the red circled region of this map. So almost certainly caused by lightning. And the lightning then triggered this whole complex of fires in Quebec. A few days later, the smoke generated from those fires, as you can see, this is from the MODIS satellite, a true color image from June 6, 2023. Quebec up here, hopefully you can see my mouse, we're in the area labeled fires. But then a few days later, that smoke had traveled down such that the bulk of the heaviest plume of smoke was over New York State, and shortly thereafter, New York City. This is a picture taken from Coney Island by Greg himself, actually, on that same day, June 6th. And this is no filter, right? This was this truly apocalyptic event. It was the most commonly used phrase for describing it. It really sort of seared into the psyche of the city, I think, and the rest of the country to some extent. And I was reminded throughout, as were many others, of that movie Blade Runner 2049 that came out just a few years ago. Sort of brought that sort of dystopian future to mind. Okay, so, and that was sort of in the qualitative terms, in the psyche of the city, it was this intense event. Quantitatively, scientifically, it was also a record-shattering event. So there's many ways of quantifying that. One is shown here. There's a site in Queens that's an AirNow site for collecting air quality data, specifically this PM 2.5 metric in micrograms per cubic meter. And this is a histogram of the hourly measurements of PM 2.5 concentrations at that site, spanning the whole record, which is about 11 years plotted here. So the gray bars are all of the years, the counts of events, from almost no PM 2.5 to the highest values on the right. And the reds are only from these 3 days of this smoke event. And you can see that the not just the one single max, but the most of the top 10 or so measurements were all from this single event. So the question we were interested in was, how did that smoke get to New York City, and how did it end up at the surface where it could damage public health, right? Instead of, say, being higher up in the atmosphere. Why did that smoke that was in Quebec to the north, 1,000 kilometers or so more, why didn't it stay local or go some other direction? Why did it come to the Northeast US at the surface? So what Greg did was a heroic effort of scraping, collating data from a huge array of free, publicly available data sets of observations, in situ and satellite, as well as model-based data sets, to sort of paint a complete portrait of the meteorology of this event, the weather patterns that enabled the smoke to come from Quebec to New York City. This is deliberately a wall of text, sort of just to impress you. He really looked at a ton of stuff, and all of this is data supported by local, state, federal governments in the U.S. and otherwise. So one of those tools was called trajectory modeling. So what Greg did was, using the satellite identified fire locations, he created forward trajectory calculations, which is where you say, okay, start a parcel of air at this location at this time, and given how the winds and other things evolved over the next few days, where would that air go from there? And so all of these curves here, each one was started up here at one of those point sources of the fires. And then the rest of the curve is where it went after that. And the punchline is that virtually all of them sort of went straight south. And the mean trajectory, which is the black curve, the average over all of them, was a straight shot to essentially the 5 boroughs, right? And then all of them do this thing where they curve to the east, right? In fact, there's this like almost perfect oval that they've created. So why did that happen? Why did those trajectories all go this way in this curved pattern? Well, it turns out that there was an extratropical cyclone, a weather system that is not uncommon in the Northeast in summer. And this wasn't a particularly strong or weak one, but it was located in sort of the perfect spot just off Nova Scotia, such that the winds that flow counterclockwise around it were in the region between Quebec and the Northeast US, sort of oriented straight from north to south. So these contours are of the mean sea level pressure. And the way the atmosphere works, you can think of the near surface low level winds as mostly coming along these contours and in a counterclockwise orientation. So again, hopefully you can see my mouse, but I'm curving out the path where these contours would go straight down from Quebec to the Northeast US. So it was the presence of this cyclone sitting there in just the right spot that gave us that transport. Not only that, but the cyclone itself was weirdly slow in moving around. It was weirdly stationary. And if anything, it actually moved slightly to the west over the period of this event, rather than most of the cases, the storms moved to the east. So this left panel here is, the colors are sort of a track density. So on average, how many of these extratropical cyclones do you get each summer? And you can see we're in, like, this isn't an area where this is rare. We get a decent amount of these per year. The green arrows are showing like a typical track of cyclones in that location. Which direction do they go and how fast? And you can see that throughout the domain, they're mostly going to the east, right? They're heading pretty clearly to the east throughout the domain, the green arrows. What this cyclone did is the blue with the overlaid red arrows. This cyclone didn't do that. It went first a little bit north and then actually eventually went to the west. So that was a very unusual track. And then you can think about that. You can quantify that in another way here via this histogram of the speed of these events, just how fast they went. And the upshot is this was one of the 13th slowest out of 642 events in this data set. So that's the story of the horizontal transport. Then there's this question of why it was at the surface rather than aloft. It turns out that the emitted smoke, rather than going high into the troposphere, as sometimes these fires do, it mostly was emitted into the lowest 3 kilometers or so, and then it stayed there. And so this is why the paper was called a wall of smoke. And this graph is maybe a little complicated, but the point is that all of these curves, which are different days of this event, show that the values are highest below 700 hectopascals or so. That's the y-axis, and that corresponds to the lowest couple miles or so of the atmosphere. So prior events that were analogs here of this one had smoke go up and then sink back down later on, but not the case with this one. And this one, the smoke was emitted low and stayed low. It just came as a wedge straight to New York City. So to summarize, the record-shattering June 23 smoke event was due to this unusual combination of very strong smoke emissions from wildfires in Quebec and an unusually stationary weather pattern, this extratropical cyclone, parked just in the spot that brought the smoke straight to New York City for days on end. I'll skip that because I'm a little longer on time. And I just want to say, where are we going next with this? Well, what we're starting via Greg's PhD and where we're hoping to get funding to go in the future is to better quantify the unusualness of those factors, right? When you have a record-breaking event, it's hard to quantify just how record-breaking it was, so to speak, or just how likely events like that or even stronger are, and how those likelihoods might change year to year and on longer time scales. So that's where we're digging into next. Thank you.
Fascinating. Thank you, Spencer. Appreciate the nice overview. I hadn't realized just how bad that smoke was over New York. And I completely agree. My mind went to that Blade Runner movie too. Like it just, we had something vaguely similar in the UK about 7 or 8 years ago, I guess. There were fires in Portugal that came up and around, and it's pretty creepy. But obviously the health impacts are more than that, and it's great that that we're doing the work to understand where these come from and how they travel. So we have a few questions in the chat. Just went up. Oh yeah. Is lightning typical for that location at that time of year, or is that something that in itself is changing with climate change?
Lightning is not infrequent in the summer in Quebec, right? We get these convective storms, these strong thunderstorms, and how exactly lightning works is, I think, sort of an outstanding scientific mystery. It certainly is to me, but you can think of these thunderstorms being pretty common in this part of the world. And so many wildfires in the Northeast US and Canada are not from cigarette butts, although some are, right? Things like that, they're from lightning. In terms of how it's modified by climate change, I think that is an open, outstanding, and important question. I recall work now, better part of 10 years ago, by David Romps looking into this question. But the literature there might have advanced quite a bit. So that's a key part of the question of the smoke risk moving forward. That's a key ingredient, right? Is the ignition of these fires in the first place.
Yeah. So it's a confluence of the events, I guess, right? It's a confluence of the drying, I guess, in the background material. Then you have the lightning just happens occasionally, but then you also have this unusual cyclone, I guess, that brought it back around. So you were looking to take this forward in kind of future directions. Are there any other aspects that do these, I guess, kind of questions and findings relate to some of the fires that we have here in California or other parts of the world?
Yeah, so for one, for the Northeast US and including New York, no small fraction of the wildfire smoke events we get actually are from fires emanating in the Western US and Canada. So these are events where you have that vertical transport pathway I alluded to was not the case in this one. So for them to get all the way across the continent, you need them to be ejected high into the upper troposphere and then sort of ride the jet stream and then eventually make their way down to the surface over here. So for us East Coasters, it's the Western wildfires are not nearly the same severity of its concern, but they matter to us as well. In general, the framework for thinking about smoke risk from fires is broadly applicable, throughout the domain, West Coast and East Coast, right? You have to, there's the issue of, there's a very stochastic or sort of hard to predict component coming from the ignition, right? Does the lightning strike a dry patch or a wet patch? Does the cigarette butt hit a dry litter or, make it into the trash can that the car was driving past? But irrespective of those random sort of aspect, as it were, there's the fire weather, right? So hotter, drier, all else equal, more likely for things to burn.
Sure.
Right. And then the smoke then what the smoke does is then, of course, the weather, how the winds are blowing, right? The smoke is evolving chemically. If there's rain, it gets rained out if that happens along its path. But otherwise, we can think of it as mostly a passive tracer. It's sort of getting blown as the winds blow. And they're moving something very loudly outside my door, sorry. And so where the smoke goes once it's emitted is basically just, what the weather is doing.
So actually to that, sorry to interrupt, but to that point, there was a question from in the audience about that specific extratropical cyclone, and they rightly point out, right, we might expect them to head east, and what made this one move westward was there some other kind of synoptic or large scale system that redirected it like a blocking.
I recognize this person. Yes, so it's a great question. There was upstream a sort of blocking high. So sort of in the central Canada, a high pressure system, sort of like the opposite phase, as it were, of the low pressure system that was off Nova Scotia. What role that had in this sort of unusual trajectory of this particular cyclone is a legitimate question. I would, if I could, I would pass it on to Jimmy Booth, my collaborator, who's the resident extratropical cyclone expert here. But yeah, I mean, and maybe I'll just sort of pivot there, though, to say, as we think about the risk of smoke events like these moving forward, the statistics, the behavior of those cyclones is as important as anything else, arguably, right? Like with mean warming, we have some evidence, some confidence in sort of more fire weather conditions overall, uncertainties for sure. But whether these cyclones, whether they become stronger or weaker, whether they they tend to have more of these unusual stationary tracks, or the opposite, maybe they start going even more quickly offshore. The Northeast sort of smoke risk is highly contingent on those, and those are questions that we feel like are really outstanding, need to be addressed more cleanly, and we're hoping to do so. I'll close on theme with this event. We have a pending proposal to a program at one of the major funding agencies that we submitted last year as well, and the program then was the entire program, not our proposal. The budget was cut for it. Yeah. So this year it's come back around, we hope, and we'll see how it goes.
No, but these are the real impacts that I think this live stream is hoping to highlight, right? This is important research affecting millions of people, and these questions are certainly of the public interest. So thank you very much for your time, Spencer.
My pleasure. Thank you, Duncan.
Delighted to introduce our next speaker, Anna Vaz. I hope I pronounced that correctly. Who will be talking about fish and changing oceans.
Yes, thank you so much, Duncan. I'm Anna Vaz. I'm a system scientist. I'm a physical oceanographer by education, but by trade, I'm a fisheries oceanographer. So I study how changing ocean conditions can affect our fisheries. I was a NOAA Fisheries employee that got terminated with the probationary terminations. And I'm going to talk a little bit of the work I was doing, correlating ocean variability with fisheries and how we can use that for management and why it's important to have both weather and climate research on that. So fisheries, they can be affected. Of course, they live in the ocean, so any number of ocean phenomena is going to affect our fisheries productivity. You can vary conditions, you can shift species distributions, and so where you can find species, the amount of fish you can find in a place, the timing of their reproduction for protections, it all can vary according to ocean and weather conditions. And here we have a graph that similar to many we have seen already in this live stream, but showing this time different management tools and regulations we can have, what's the spatial temporal scales they operate, comparing to different spatial temporal scale of weather phenomena. So you can see the like weather changes. We also have changes in how we can regulate different things with fisheries. So industry operations are going to have short spatial and time scales, while if we move the long-term resource capitalization or rebuilding plans are going to operate in very large time scales. Resilience sustainability, the authors chose to put at the very high spatial temporal scales to highlight the importance of climate change prediction for this, but we actually work with resilience sustainability over all the spatial temporal scales. And that is what is also a bit of a very challenging, because many different phenomena can compound, and we can have multiple stressors into an ecosystem. You can also have human activity that are going to change the outcomes of our fishing resources. So we need to undergo all these different spatial temporal scales. So I'm going to talk a little bit about a case in the U.S. South Atlantic. So where we are talking about is exactly the U.S. South Atlantic Bight that is located between Cape Hatteras in Florida and Cape Canaveral in Florida, and Cape Hatteras in North Carolina. So the area of we show here with a yellow square in the map. This map comes from the Ecosystem Status Report of the South Atlantic. That is the citation, Craig et al. That is a report that shows all the trend, the health, the conditions of the ecosystem, including socioeconomic conditions. So it's really a snapshot to managers can use to understand what's happening, what is the major drives, both economic and of the ecosystem in general. So we can see here in our region that the Gulf Stream is a major current happening in the region. We also have the Charleston bump, and can generate this warm core ring that is almost persistent in the region. And we also, the interaction of the Gulf Stream winds and the bathymetry cause a lot of upwelling and downwelling in that region. And the region is highly productive because of all these interactions. Here is a summary from the South Atlantic Fisheries Management Council. Drives a lot of jobs and is a big economic resources, and both commercial and recreational fishery in the region are very important, both economically and culturally. So what is our problem? We've seen that in recent years, there is a decay in recruitment of different species. And recruitment is the amount of fish that is entering an adult population. So fish spawn a large amount of eggs in the ocean, and they need to be transported to suitable places for their survival. And some of them are going to survive and grow into juveniles and then come back and enter the adult population, where they can spawn and have more babies. So here we are looking at graphs of a stock assessment model. That is a model we use to look at estimate the number of fish that we have. So using that, we can estimate limits for fishing. But this model in particular does not take into account any environment effect directly. It's just looking at the status of the population, the size, composition, the length, composition, the amount of fishing that is happening, and many parameters related to the populations itself. But we can see that is a group of groupers and snappers, especially with a bass there, the Black Sea bass. And we see that there is decaying in lots of them, those inbred in recent years. And there is a stable or increasing populations, those in green. And that puzzled us, like what could be driving that? We did meta-analysis. We excluded a lot of things related to fishing, overfishing, anything related to the population itself or the models. And these trends are also seen on our sampling. So we did some analysis that showed us that environment could be behind the changes we see in the species that are trending downwards. Another clue come from the peak spawning. That's the only striking difference we see in these species, because they occupy about the same place, they live in the shelf at the same depths, they have very similar life cycles, but the species that are decreasing, they spawn the winter, while the species that are increasing, they spawn in the summer. And another clue comes from the ecosystem status report that I mentioned before, because then we looking at several ocean conditions, we see that we have an increasing trend in sea surface temperature in the region, while we have decreasing coastal upwelling, and the Gulf Stream appears to be more onshore during this time period. This can change our nutrient dynamics, especially impacting the chlorophyll A production, which we see here in the time graph that is highly variable. But if we look at the spatial temporal trends over this time period, we can see that the increase is really localized into nearshore positions, while the large part of the shelf where this population lives, it shows a decrease in this surface chlorophyll. The Gulf Stream position, here we have from model that captures 30 years of ocean conditions. We see that both at surface, there's a lot of variability, but at subsurface, at 200 meters depth, we can see that is really onshore on recent years. So we decided to explore this a little further. We look at all these different variables: sea surface height, sea surface temperature, bottom temperature, chlorophyll A, the position of the Gulf Stream, all by seasons. So here we just look at the winter anomalies, the time our species they spawn. We can see that there is a trend upwards for sea surface height and bottom surface temperature, an increase while a decrease in the productivity of the chlorophyll A. And then when we do correlations between all these different components, we see that the strongest correlations were with the sea surface height, the Gulf Stream position at surface and at depth, and that the species spawning in the winter and the summer, they are behaving in opposite trends. While we don't have the full picture, the full mechanistic explanation, what we are suspecting is that a decrease of this proximity of the Gulf Stream is lowering primary productivity and impacting the winter spawners. Now, we see that this is happening. Just like a short summary is that these intrusions of the Gulf Stream at depth, they're being more frequent, and is significantly correlated with several species recruitment deviations. And the intrusions itself are also correlated with chlorophyll wave at the shelf break. But we don't have the full picture of the chlorophyll wave productivity. While we're using model outputs for the other variables, we are using outputs of chlorophyll wave from satellites, which we need to exclude also the very near shore region, because we might have problems with resolution of the chlorophyll wave productivity. So we don't have also the depth profile of this primary productivity. So our next step is to investigate the 3D changes of productivity with new NOAA models, the MON6 Northwest Atlantic model that is incorporating BCG biogeochemical variables. And we can really look at the variability of chlorophyll at depth, because our hypothesis is while these changes are lowering productivity for the winter spawners, they are increasing somehow for the summer spawners, which are benefiting from this changing ecosystem. So thank you so much. I hope I could show a little bit of why all these models and our understanding of the physical environment can also help with our fisheries questions and management issues.
Thank you so much, Anna. That was that was fascinating. I don't think a lot about the creatures that live in the oceans that we model, but that was a really nice talk. I'm sorry to hear you were part of this wave of cuts in the initial set of firings a year ago. It's a whole mess. So next steps, we want to investigate the changes in productivity with these NOAA models. What exactly would that look like, and what kind of models are you using?
So the whole project to investigate changes in ecosystem conditions is doing high resolution MON6 model for the Northwest Atlantic Ocean, and we have a hindcast looking back. I forgot exactly how many years now. I think more than 30 years, but it has is the cobalt is implemented together with the MON6, so we can look at all the changes in nutrients and primary productivity, which can help us untangle a little more the mechanisms by which we see this difference, because we are imagining that these intrusions of the Gulf Stream are somehow blocking upwelling in that region for the winter spawners, but they might be helping other phenomena, other mixing phenomena, and increasing productivity for the summer spawners, but we don't have that resolved yet. There's a new paper coming out showing these changes in sea surface height. So while like the recruitment deviation itself also were not correlated with the MOO, the NOO, or ENSO, we see that all our physical variables are correlated. So they might have a signal of these changes in there too. So we need to understand with the models, we'll be able to look at how it's changing, because just the surface is not giving us the full picture of the changes that are happening in the whole ecosystem.
Right. Yeah, of course. And these are all, deeply interconnected systems, I imagine, right? So you have changes in the around the Gulf of Mexico, and those get communicated all the way through.
Yes.
I imagine up to the North Sea and the UK fisheries and
yes, because the Gulf Stream transport has a play too there. Like it seems when we have a increased transport is when we are going to have less of this effect. When the transport decreases is when we have more of we seen this decay in recruitment too, and the blockage of the upwelling. So it's a very interesting correlation there. We need to explore this further. There's people looking at different parts, and we can start putting out the puzzle together. So Yeah.
I can imagine. What would it mean if I mean, obviously there are huge impacts to agriculture and Northern Europe, and Europe in particular, if the AMOC were to slow down or collapse. What would it mean for the fisheries?
Yeah, that is a good question. It's part of the whole project I was working on with Noah too. We had different people in different regions of the country, because while some fisheries might suffer a decline and other species could be benefited from these changes. So
Right.
it's not a simple, straight answer. We need to understand who are, we were saying winners and losers, but it's very important for us to understand that, because then the industry itself can prepare for the future, because it's like, where are they going to invest? Are they going to invest on making their ports more weather resilient, or in new boats for the new fisheries that is coming for the regions? For example, shrimp is something that used to stop around North Carolina, and now shrimp is found up to New York. So is shrimp something that might expand and might be a good winner of these changes, and something that can be exploited? So it's things that we need to understand, how these distributions are shifting or expanding, or which species are going to suffer a decline and others that are going to benefit.
Yeah, no, that makes sense. And again, is it, is a excellent reason why we need this research and why it's vital.
Yes, and
economy, for the science. And for
yes, and it's all interconnected. It's like there's no way to separate the human actions and the weather and the ocean from our biology. So
okay. All right. Well, thank you very much, Anna. I appreciate you taking the time and sharing your great talk.
Yeah, thank you so much for the opportunity. Yes.
Absolutely. Well, thanks for joining us. Some of you may be joining, in and out. I appreciate you just dropping in and joining us for this. We've had some great talks so far. Our next speaker is no exception. But before they join us, maybe take a minute just to kind of remind everyone why we're here. So, these forecasts that we've been talking about, whether that's for the weather, for the climate, for the air quality that we just heard from Spencer, or indeed for the fisheries, right, that large parts of the economy and agriculture rely on, come from and paid for by, a lot of that research is paid for by the federal government, and that feeds through large parts of the economy. We heard from oh my gosh, I've forgotten his name now, but there was a great talk just a couple of talks ago discussing, the engineering aspect of this, Scott Weaver, on, the hazards and the destructive capabilities of storms. And so, US scientists have been world leaders in weather and climate. We developed the first computerized weather forecasts. We used the first computer models of the climate impact of carbon pollution, and have developed really unparalleled networks of observations, weather stations, floats, boats, Argo, as well as a fleet of Earth-observing satellites. And this really was only possible because of decades of investment by you, the American public, and that has had outsized impacts in the economy. Like those investments get multiplied by this research and downstream innovations. And unfortunately, the current administration is really destroying the foundations of this success through direct budget cuts to NSF and NASA, swathing cuts to NOAA. So we just heard from Anna, who was cut from the NOAA Fisheries Program. Those questions are still there. They're not going to go away, and we just won't have the information or the data to be able to respond and deal with those. On top of that, the administration is trying many different approaches to dismantle the National Center for Atmospheric Research in Boulder. So NCAR is a world-renowned laboratory for weather and climate science. It's really a kind of mecca, if you like, for climate scientists. And this isn't because of any kind of legitimate scientific disagreement. Let's be honest, this is really just a ideological opposition to the climate research that they do, the vital climate research that they do. I work with many of the research scientists at NCAR, and they're some of the best scientists in the world. They develop one of the best climate models in the world that is used broadly. It's open source, it's publicly available. You know, this isn't a silo, it's really a source of fantastic innovation and science that is being put at risk, people's, you know, lives and livelihoods being threatened and dangled for political point scoring. So call your representative, advocate for the fantastic science that you're hearing about here and the science that we do in order to support these initiatives. Okay, so with that being said, I am delighted to welcome our next speaker, Hannah Joy Warren, who's a polar oceanographer and is here to talk more about the creatures that live in the ocean, and this time particularly small creatures, the phytoplankton and the carbon that they live off in the Southern Ocean. Thank you, Hannah.
Yes. Oh, thank you so much, Duncan, and huge thanks to the organizers of this. I did this last year and I had so much fun, and I'm really glad to be back. So Duncan mentioned Argo floats. We're going to dive into that. We were just in the ocean. We're going to stay there. I am finishing up my postdoc at the University of Washington's Applied Physics Lab. I'm also jointly at NOAA's Pacific Marine Environmental Lab in Seattle, Washington, and I'm a polar oceanographer. I focus on the Southern Ocean, which might seem really far away. I'm hopefully going to convince you today that it is still extremely important for the weather and climate we're experiencing here in the US. So to start off, the Southern Ocean, what is it? Why is it important? And what are phytoplankton doing there? But before I talk science, I just want to point out that none of this, I would not be here today without all of these funding agencies. My PhD was partially funded by the Environmental Protection Agency. My first postdoc was funded by NOAA, my second by the National Science Foundation. And in a few weeks, I'm starting as a senior oceanographer at the Applied Physics Lab at University of Washington, thanks to a NASA grant. So without all these federal funding agencies, I wouldn't be here today. This would not be my career. And hopefully you can tell that I love this so much. And I'm really grateful to get to do this really important work. So welcome to the Southern Ocean. We're going to dive to the south. This is a view of the Southern Ocean. We can see South America on the lower right, Africa on the lower left, Australia is there on the upper left. And this ocean that surrounds Antarctica is the Southern Ocean, and it's where the Pacific Ocean, the Atlantic Ocean, and the Indian Ocean all get to meet. So what you saw on the left here is maybe the stereotypical view. Southern Ocean oceanographers really like this diagram that I've just added on the right, which looks totally bonkers. It's called the Spillhouse diagram. And here you can see that, and this is the way that we think about this, the Southern Ocean is the central connective point of all these other oceans. The red arrows you're seeing on top is surface ocean flow. The blue arrows is deep ocean flow. So this is really the connection point between all of our world's oceans, which is partly why the Southern Ocean is a really key component of global climate. So we're going to dive in. I'm going to start simple here, taking us back to biology high school basics, just to get everybody on the same page. We've got water in our oceans. We have carbon in the atmosphere. This is atmospheric carbon. You might have heard people talk about PCO2. This is what we're measuring that's increasing. That can also dissolve into the surface ocean, and that goes back and forth and depends on some factors like temperature, salinity, how windy it is. And if we add sunlight, water, and carbon, we get photosynthesis. We can grow up photosynthetic organisms. These are very similar to plants on land. In the ocean, we have phytoplankton. And just a side note here, because I'm going to be talking in terms of carbon for this whole talk. So to put this in carbon, photosynthesis is growth. So phytoplankton are incorporated carbon into their bodies. We can also get particulate organic carbon. So if phytoplankton die and sink, they're forming these amalgamations. That's particulate organic carbon that can sink to depth and remove that carbon. And this particulate organic carbon, you can just think about the amount of carbon in particles in the water. So essentially what you can see, some of them are very tiny, but essentially like parts of carbon that you can see. Phytoplankton also is included in particulate organic carbon because it's in a particle. So in this process, we also get remineralization, which you can think of as death and decomposition. And this is where phytoplankton are releasing carbon from their bodies. Microbes can chew them up. So carbon is going back into the water in this process. and that converts back into dissolved inorganic carbon, DIC, which is where we started. And this one, you can think about the amount of carbon that is dissolved in the water. So this is water that carbon that we cannot see, that would pass right through a filter if we tried to filter it out. So the two big pools of carbon in the ocean that we think about are particulate organic carbon, POC, in particles, dissolved inorganic carbon, dissolved in the water. So there's our primer on our phytoplankton and how they're impacting carbon. Now, here's your primer on the Southern Ocean. And just to orient you to my diagram, this lighter blue, middle blue color is the surface ocean. The lightest blue is the atmosphere. These little lightest blue spots are the sea ice covering the surface ocean. Then the darker blue is the deep ocean. So that's where that water is not going to come back up to the atmosphere for about 1,000 years. And then we have the ocean floor here, and then on the far left in the brown, continental shelf, so the shallower parts of the ocean. So taking away the labels now, hopefully that was long enough of them up there. In the Southern Ocean, we get high but episodic phytoplankton production on the shelf. So phytoplankton blooms, get this big, it looks green sometimes, can be a huge bloom. It's episodic because this is a very seasonal environment here. And then that phytoplankton can produce organic carbon, particulate organic carbon, and that can sink down. And 30% of global organic carbon export, so export to the deep, is happening in the Southern Ocean. Another cool and very important factor here is that we get deep water mass formation in the Southern Ocean. I'll walk you through this. As we get ice forming, that is only taking in H2O. We're not taking in the salt. So as we get that, we get brine rejection. So all the salty water that's being rejected from the ice gets really, really heavy. It's rejected as brine, and that causes downwelling because the saltier the water, the heavier, so that sinks to the bottom. And with this, we're getting our water that is high in organic carbon sinking to the depths. And as I said earlier, this water stays out of the atmosphere surface ocean system for about 1,000 years. So this process together creates a potentially very large carbon dioxide sink where phytoplankton are using carbon to grow, producing organic carbon and sinking to depth, and thereby influencing global climate. So we're really taking carbon from the atmosphere and moving it to the bottom of the ocean in the Southern Ocean. This is now a slightly more complex diagram, the same idea, mode waters in the surface. So that's kind of water that is interacting with the atmosphere. We have intermediate water forming, so that's going to sink down a little bit, not all the way to depth. We have deep water that comes up and then downwells again as bottom water. And so all of these different water masses are also really impacting where the carbon is in the Southern Ocean. And the shallowest water up there, the mode water, is taking up a lot of carbon. It's moving from the north to the south here. It's getting colder. That can take up more carbon. But as some deep waters come up, as I said, the deep waters can have a lot of organic carbon, so that can cause some outgassing. And overall, these two systems are pretty much on the outgassing and uptake from the deep waters on balance. The CO2 uptake is positive, so we're getting generally net uptake here. And those factors are influenced a lot by physical processes. I mentioned this earlier: mixing, salinity, temperature, wind, ice cover, all affect how much carbon can move in and out of the surface. And we actually know those fairly well. There's also the biology here. I'm popping in the phytoplankton, and this side of things we don't know nearly as well. And this is where my interest really, really lies, in trying to tease apart what the phytoplankton are doing. So here's a diagram walking through my project. It's sort of how I mentally organize what I work on. So in the middle there, we have our CO2 going in and out of the ocean. On the left side, we have the physical processes that I don't really dive into because those are fairly well understood at this point. On the right side, we have phytoplankton, the biological processes, and this is where my research goal comes in. So my overall goal is to determine the relationship between phytoplankton community composition and air-sea CO2 flux. I'll explain community composition in just a minute. So the first step of this piece would be to characterize the community composition, see who is living there, not just phytoplankton, but who is there. The second piece is then to estimate Southern Ocean air-sea CO2 fluxes. So where is that carbon? We have to measure the carbon. And I put up the little yellow funny looking thing. That is an Argo flow, and that is where we get our carbon measurements from. And just for reference, this is a biogeochemical Argo float, so we're able to measure carbon parameters. This is me on the deck of my building where these floats are built. Some of these floats are built all over the world. And this is just, I'm 5'4", so if I put my hand above my head, that's about how big they are. So a brief overview, some of you may have heard this or may know this. This is how floats work. They descend to depth, drift for about 10 days, and then they descend down to 2,000 to 6,000 meters, depending on the type of float. And then they do a profile through the surface ocean. And that on the right, you can see that's the profile they take in temperature and salinity, for example. And then they have an antenna that they stick out of the surface of the ocean, satellite back the data right to our computers, and we can download it. So it's a really great way to get data. And here's my Argo float picture. So I'll put that on the slide where I'm using this data. So let's dive into what I'm doing, the science that I've done so far, for focusing first on Southern Ocean phytoplankton community composition. And this is a diagram to show you how important the community really is. The two dominant taxa, you don't really need to remember these. I'll always have their pictures next to them. Diatoms on the left, they're very pretty. Phaeocystis on the right, it is a mucus matrix with tiny little cells in it. That mucus is made out of carbon, which is very important. Diatoms are grazed upon by zooplankton, krill, and copepods. They feed the food web, the big, beautiful things that we think about when we think about Antarctica. Phaeocystis is only grazed by salps, these kind of like jellyfish. They're sort of a dead end in the food web. So a lot of that carbon is potentially then available for carbon export. So I'm gonna look into this. And just a note, this is a paper from my PhD advisor from 1999, which I read early in my PhD and has really influenced everything I've been interested since then. And so just to break this down for you, on the x-axis, we have phosphate. You can just think of that kind of as a normalizing. That's another nutrient that we're normalizing to. And then DIC on the y. So dissolved inorganic carbon. So we have more carbon, a steeper slope in Phaeocystis means we have more carbon used per phosphate in Phaeocystis. And so this is what I really want to see if I can show this on a full Southern Ocean scale. Okay, so to characterize the community, I have these in situ observations. These are ship-based, a database. I did not collect this data. This is from over a century of data of points. And then you'll notice that it's not coincident in space or time with BGC Argo float locations. So I used a machine learning model. I used these modeled fields of biogeochemical data, so temperature, salinity, sea ice, nitrate, which is another nutrient, oxygen, and chlorophyll, paired it with our observations. And then using this maximum entropy species distribution model, I was able to predict where we are likely to find diatoms and Phaeocystis, our two primary taxa. So that is how we characterize our community composition. Now we're diving into the carbon piece of this. I've got my float up there, and we'll get much more into this data. So this is just a quick picture of where we have the float data and dissolved inorganic carbon measured there in the blue dots. Closer to the continent, it's higher, which is where we're quite interested in. And just remember, this is just how much carbon is dissolved in the water. So now, to put these pieces all together, we're going to try to trace this carbon from the atmosphere through the phytoplankton and see what we find. So here are the two maps that I showed you previously, diatoms on the left, Phaeocystis on the right, and I'm going to reorganize these very slightly. I'm going to say, where do we have high diatoms and low Phaeocystis? So you'll see that the green bubble pops up there. Here, if you can see my mouse, there we have high diatoms and low Phaeocystis, and then vice versa. Down here, the bottom of the map, we have high Phaeocystis and low diatoms. So that's how we can really look at who's impacting things here. So now I've taken these two high diatoms, high Phaeocystis, and I'm remapping them together. So in the red, we have high diatoms. In the blues, we have high Phaeocystis. And then I'm just going to close these into closed polygons so I can compare two regions. And diatoms will always be in red, Phaeocystis will always be in the blues. And now I'm adding the float data, and you can see we actually have quite a bit of float data in each of those two locations, and that's what we can compare. And here is the carbon data that we're comparing that I showed you previously. So first, we can get chlorophyll from these floats, and this part is very important. In both the winter and the summer, the chlorophyll is the same between those two regions. So in the red and in the blue, we have 0.03 in the winter and we go up to 1.1 in the summer. Phytoplankton are growing in the summer. We expect this, but it's the same amount that we have there, which is important. And I should have done this first. Chlorophyll is a proxy for how much phytoplankton there is. So we can just think it's about the same amount of these two. And now this is the really important part also. In the winter, we have the same amount of DIC, so amount of carbon dissolved in the water. In the summer, when we have growth, there's higher phascistus. You can see the blue, you can at least read the blue number is higher, 2192, and the red number is 2186. And these are significantly different. It's a little hard to tell. So this is giving us a good idea that we probably really do have something here. And this is another way of looking at, I'm going to break this down. This is carbon export per unit of nitrogen. So the change in carbon divided by the change in nitrogen, how much is there? And it's divided by nitrogen, really just we're normalizing it here. So we can just really think about it. We can compare them equally. And then this is mixed layer depth to mixed layer depth plus 50. So this is kind of below where the phytoplankton are growing. You can just think of this as like slightly deeper waters. We're not at the surface anymore. And the phascistus in blue there is higher. So we're having more dissolved carbon that's moving below the surface of the ocean where we have phascistus dominating. So we potentially have more carbon export in the phascistus region. This is the first time this has been shown at any kind of large scale merging a lot of different data products. I'm pretty excited about this, and we have achieved our research goal now. And I will just wrap up. There is my overall project. And I will also acknowledge my funding sources for this specific work. The other ones earlier were for my entire career. And with that, I will take any questions that you might have.
Fantastic. Thank you so much. I was kind of engrossed in that because it's learning a lot about the ocean and the carbon cycle. I was curious. So you have all the downwelling in the the freezing areas where the ice, the brine, that whole thing. That was cool. And it occurred to me, so, a lot of the more optimistic climate scenarios assume we will be doing a lot of carbon dioxide removal into the future, yes, right, to draw down some of the carbon that maybe we can't abate or mitigate. And so that seems a good place to dump the carbon, but you have to get the phytoplankton is more efficient, presumably in the tropics, because that's where all the sunlight is. And so how do you think about that? Is that something
that kind of is a nod to iron fertilization, which is, right, so the phytoplankton here in this region, yes, we don't get that much sun, primarily limited by iron, which is a nutrient that they need to live and grow. And so in the 90s, there were huge experiments where ships would go out and scientific experiments, dump iron into the ocean off of ships, see the phytoplankton grow, and then you think, okay, then we're going to get that carbon down. And through experiments and models, it looked mostly like it was just offset regionally. So if you add iron in one place, right, you're going to use up something else, your manganese, your cobalt. These are other metals that are really important. Maybe even your nitrate, which is very high here. And then downstream, that water is limited by something else. So the phytoplankton that would have grown over here, you just may grow here. And then in some, we have no change. So overall, it doesn't seem very likely. You might think, well, why don't we fertilize with a little bit of everything? And then we're getting into problems of upper trophic levels. So the zooplankton get decoupled from the phytoplankton. Then what are our penguins and our fish eating? And it's a massive fishery in the Southern Ocean. We get a lot of krill, huge krill fishery, but there are other Antarctic toothfish, Chilean sea bass. There's a big fishery down there as well that the US uses. And then we're starving ourselves of the food that we would have otherwise been able to catch and eat.
Right.
So
yeah,
it's a giant puzzle, big puzzle.
There's a great question as well on the chat, a lot of interest. Do things like tsunami cause a lot of outgassing on top of everything else, obviously, that they do?
That's an excellent question. I would say probably not a huge amount, because if you think about the size of the global oceans versus the size of a tsunami, yes, a tsunami is large, but they're pretty infrequent, and relative to the entire ocean, they're pretty small. So I think in the localized spot, they probably are causing extra outgassing, extra churning. But on the global scale, it's probably not making a very big difference. Great question.
answer.
Really integrating the topics there. I love it.
Yeah, I love it. It's a great forum. Okay, well, we're at the top of the hour, so I'm going to hand over now. But thank you so much, Hannah.
Thanks, Duncan.
Great talk. So yeah, I'm delighted to hand the baton over to Mackenzie. I think we're nearly on the home straight now. 4 hours left, so we're in good hands. Thank you, Mackenzie.
Yeah, thank you. Thank you so much for helping host. It's been great. All right. Well, welcome everyone to hour 47, I believe. I'm Mackenzie Larson. I am a fifth-year PhD candidate at the University of Colorado Boulder in the Department of Atmospheric and Oceanic Sciences. And my research focuses on Colorado Front Range high-impact weather like snowstorms and downslope windstorms. So before we move on to our next grouping of keynote speakers and panels, I want to remind everyone why we are all here. And that is because U.S. scientists have been world leaders in weather and climate prediction. We have had the first computerized weather forecasts. We have organizations that develop complex models of the weather and climate. We also have a very vast observation network ranging from space with satellites, with airborne measurements, all the way down to boats and floats and land measurements as well. And all this amazing research and science that's done is thanks to you, the public, because your taxpayer dollars is what allows for U.S. federal funding of this research, and it's absolutely essential. However, currently, the administration's proposed budget for the fiscal year 2027 is currently jeopardizing this research and the scientists that conduct our amazing research. Currently, there are proposals to cut the NSF and NASA's Earth science budgets in half. And a big question I, as well as others here on the stream, as we've talked about, are really concerned about how can we train the next generation of young scientists to better inform our weather forecasts and just our general climate understanding if this happens. For example, my graduate research is fully funded by federal funding, which I'm extremely thankful for. And that funding is what allows us to pursue our passions of improving our weather and climate knowledge and prediction. We've already seen negative impacts from funding cuts, such as short-staffed weather forecast offices, shrinking or elimination of research labs, and we've also seen different summer internship programs, such as NSF research experience for undergraduate programs being cut as well. So we urge you all to please visit the link that's shown here at the banner. Visit our website at wclivestream.com/call to contact your representatives and senators to help protect our weather and climate research. So now we are very excited to start with an AGU President's panel. So I'm going to welcome everyone to the stage here. I'm going to welcome Haley, who's going to be moderating this discussion, as well as Ben and Brandon. So welcome all, and please take it away.
Thank you so much. It is great to be back on the stream, and welcome Ben and Brandon. First of all, this is how the panel is going to work. I'll go through and introduce you really quick. We'll go through some questions and discussion, and then we'll take questions from the audience. So if you have any questions about the American Geophysical Union or anything we talk about, put them in the chat, and we will get to them towards the end of this session. This also is the beginning of our last section of keynotes, so it talks from here on out will be 40 minutes for the next until 6 p.m. for the next 4 hours until 6 p.m. Eastern time. So with that, I will introduce our amazing panelists. Brandon Jones is the president of the American Geophysical Union. He's a former federal scientist who's dedicated more than 20 years to expanding access to STEM education and fostering a more inclusive scientific community. He serves as assistant director for ecosystems research at the EPA and a program director in the Earth and Space Sciences at the National Science Foundation, where he worked to advance undergraduate and graduate education programs in the geosciences. We also have Ben Zaitchik, who is the president-elect of the American Geophysical Union, and he's a professor and department chair of Earth and Planetary Sciences at Johns Hopkins, where he studies fundamental climate processes and their application to social challenges. Before joining Johns Hopkins, he was served as a AAAS fellow at the Department of State and as a research associate at NASA. So we have strong academic and federal connections, and now to talk about work in a professional society. So welcome again to you both. And to start off, I would just like to ask, for viewers who may not be familiar with AGU, how would you describe your work and the role that AGU plays in advancing science?
Sure, I'll jump in on this. Thank you, Haley, and I'm looking forward to the conversation. I'm glad to be here with my partner, Ben. I'll just start with the description of AGU. If folks aren't familiar, it's the world's largest professional society for Earth and space scientists. We have close to 60,000 members connected across the world, right? Over 200 countries and regions, et cetera. And that scale and that scope of the organization allows us to mobilize in a unique way all of those voices as it relates to the Earth and space system, right? So as a professional society, and the U in AGU, which is that union piece, I think is important to highlight because we can serve within the research ecosystem as the connective tissue for members in different sectors at different career stages, again, from different countries and cultures and disciplines, et cetera. So one of the ways, or a couple of ways that AGU shows up in that particular space is through our convenings. Obviously, we have a big annual meeting, and this year's meeting will be in December in San Francisco. We would love to see you there, but we also host meetings throughout the year and even co-host meetings with other organizations. I just returned from Japan last week where we co-convened a meeting with the Japan Geophysical Union. We co-convened the Ocean Sciences meeting this past February in Scotland with 2 other professional societies. So the convenings obviously are a huge part of what we do. We also provide platforms for communication from our digital news outlet, which is EOS, which has lots of mechanisms and opportunities for members and others to submit information to be broadcasted, but also through our more formal channels that scientists are familiar with, which is our publications. And we have over 24 journals across all of our disciplines that we support, where scientists can continue to publish their work and get that information out for further collaborations and innovations in the promotion of science. And also we have that career piece that is important for, as I mentioned, early career scientists, even mid-career experts who are making a pivot. We have services. We also have information, and we provide that connection to other experts and collaborators around the world to help in the mentoring of early career, but also in the advancement of science through collaboration. So with the convenings, the communication pieces, and that career advancement, I believe that's how AGU is really showing up, and it continues to show up for its membership. So not sure if Ben has anything you wanted to add to that.
Yeah, thanks, Brent. I think that's great. And just to add, some of what you just alluded to, the fact that we are global. And I think that's really critical always for science. And we've seen this as live stream already, right? How important that is, especially right now, right? For those of us in the US who really are benefiting from the global community right now and that fellowship. I also want to emphasize that we're global and we're independent. AGU and other professional societies are independent from the federal government. And that's really critical because it's that independence that gives an organization like AGU's voice particular weight in a moment when federal science institutions are under, frankly, a lot of pressure. And we're not always sure when we hear messaging from those government institutions exactly how to take that messaging. And so because AGU answers to the scientific community and not to the administration or any particular political agenda, we can set standards, we can defend scientific integrity, we can serve as a watchdog, and we can call out times when we see the science enterprise being undermined, as we've repeatedly seen over the past year. And we can serve as this two-way channel of communication between membership and the broader communication strategy that we have as a scientific community to make sure that we are identifying and responding to critical issues as they arise.
Yeah, thank you both so much. And you just started to get into this, but this obviously is an unprecedented time for American science and, climate and weather science in general. So how do you see the role of AGU changing from where it has been in the past to potentially how it will adapt in this new reality?
Yeah, Haley, that's a great question, and I'm just personally, I think that professional societies in general, the importance of them is magnified now, as Ben was mentioning. Before, within the research ecosystem or the science ecosystem, you had higher ed, the federal government, private sector philanthropies, professional societies. But when you have injuries, as I would call them, on the federal side and maybe even in higher ed, where are these other pieces within the ecosystem going to kind of step up or show up in a different way? So I think that's really important for professional societies, and AGU has certainly had to make decisions on how to show up in different ways than it has before. And one of those ways is, this time last year, once we were kind of getting our feet under us with everything that was going on, we actually became part of some litigation that focused on the illegal firings of federal workers. We were standing up for science and scientists in a more active way, and we actually won because the judge, those who recall, said that those hirings were illegal. All right, so we had a win there, but that's something that we've never done before as professional societies. So and we know that all societies have their roles to play, and we're able to do some things that others aren't, and vice versa. So that's why we need to operate as a collective. The continued federal advocacy that we are leaning into, and the ways that we allow our members to also lean into is really important. So for example, when the administration came out and proposed to slash science budgets and again, eliminate different positions, and even more recently dismantle the National Center for Atmospheric Research, we mobilized our members through our policy arm and our through those mechanisms, and more than 54,000, almost going towards 55,000 emails were sent to Congress, and over 3,400 phone calls. And from what we've heard on the Hill, that made a huge difference, that scientists were leaning in as advocates for science and science funding. And the way that showed up is that in FY26, Congress, even though the president's budget for FY26 had these crazy slashes proposed for science funding and science agencies, Congress stepped in and pretty much saved that, right? But that doesn't mean the work is over. Now, we and others are pressing the administration to stand true and be faithful to what the appropriations say. And so we continue to push in that regard.
Yeah, maybe I could just build out with a couple other examples of how we're doing this. And I think what all these examples have in common, what Brandon just mentioned, is it is AGU as its members, right? So channeling the strength of the community is really inspiring for me. I feel really grateful to be in a position where I get to see that happening, in a world leadership AGU right now, because there's incredible strength, incredible broad support that then AGU can try to help focus in various needs. So a couple examples of how that's been done in addition to what we've already mentioned, the Intergovernmental Panel on Climate Change. So as I think most people who are tuning to this live stream know, we're in the 7th assessment report cycle, and that involves authors being named to do these reports. What maybe not everyone knows is that IPCC doesn't pick those authors out of the ether, right? The authors need to be nominated by governments. And so always the United States administration and other administrations around the world have nominated these experts. And that's how we get our roster of authors that make the IPCC as effective as it is. This administration became quite clear in 2025 was going to shirk that responsibility. So they were not going to go through the formal nominations process. But what we learned, and again, channeling the knowledge of our membership, is that, oh, well, there's another path here. And membership came to us and said, well, can AGU coordinate that other path? And indeed, we were able to do that. And working with academic partners, we launched the U.S. Academic Alliance for the IPCC, which then successfully ran a coordinated nominations process that actually got more nominations, recruited and vetted than in the previous cycle by the U.S. government. Got those experts into the system, and we're now working with various funders to support the other part of this that the government really should be supporting, which is how do you get the authors to the meetings? How do you get them the resources they need to be effective? And so now AGU is serving that role. And this was all before the government, the administration pulled the U.S. out of the IPCC, which happened back in January. And so, when that happened, it made the fact that we were able to mobilize this community all the more important. The domestic, not quite parallel, but a domestic side of this assessment challenge we've got right now is, of course, the national climate assessment. So again, back last year, the administration dismissed the authors and staff of the 6th National Climate Assessment when a lot of the work had already been done. Right, so this was hugely wasteful, if nothing else. And so it's also congressionally mandated work. So the administration actually is required to do this; they just aren't. And so what we have done is AGU partnered with the American Meteorologist Society to launch a special U.S. climate collection, so we can save the work that's been done, get it out through peer review, put it at, make sure that we are making use of this investment that has been made, right, in this science and the knowledge that these authors bring, and get this information out as much as we can to decision makers. That's a start. And now we're working more broadly with partners who have been involved in the NCA in the past. They will other functions of the NCA that local governments and citizens rely upon that are now have been taken away from them illegally. How do we restore that kind of energy?
Yeah, and just one more thing to add to Ben's excellent points. He started with this, the concept that AGU is truly global, right? And showing up in different ways with the IPCC nominations as well as the special collection is really important to allow scientists to participate, right? But also to allow a home for the information to sit. But so there's the information, there's the scientists, and then there is how do you protect that information? How do you keep that information? And we recognize that through the removal of funding and the reduction in agency capacity, et cetera, that many of our data sets are vulnerable now. And so that's another way that AGU is stepping up through our data resiliency effort. And we have some information out there about how we are supporting all those elements that are related to data accessibility and replication, et cetera, because if the data is not there, obviously that's going to impact how the science is conducted, and also who can access it, who needs it, et cetera, the redundancies that need to be built in, and so on and so forth. So the ways that Ben just shared and even how we are working to preserve data sets are these unique ways that AGU has started to show up.
Yeah, and on behalf of everyone watching the stream and all of the organizers, I just want to thank you both and everyone at AGU for all of the work that you're doing to step into this space and really, do what needs to be done. I think it has been so amazing to see AGU and AMS and all these other societies step in to take over these jobs that you shouldn't have to, but also to save the work and preserve the community and keep these things going and keep the connections happening while you have to. I hope that's not always true, but just thank you so much for all of the work that you guys are doing on that. And in that spirit, would you mind giving a Cliff Notes version of the statements that have been put out from the AGU talking about the cuts and the layoffs and how they're affecting the weather and climate community in the US? And I think AGU was one of the first to really step out when all of these things were happening, and we really appreciated it.
Great, yeah, thanks so much, Haley. So maybe I'll jump in first on this one. When it comes to the various statements that come out, again, it's been really an honor to be in the opportunity, to have the opportunity to be part of those statements. The AGU staff, the full team, is just incredible at staying on top of things and making sure that Brandon and I are in a position where we can really share with members the best possible information. When it comes to the Cliff Notes version, because you're right, there've been a lot of different statements. There's a lot happening all the time these days. One thing I would like to point to, and Brandon already mentioned EOS, right? So EOS is the AGU's kind of digital news magazine. So it highlights various kinds of research. It's at any time, EOS is a great thing to pick up because it's a really interesting science. I'd say in the past year and a half, it's become a vital source of information because of what we're able to accumulate there. And I encourage folks to look at the EOS in particular for the state of the science 1 year on. So the state of the science 1 year on, and AGU's EOS, which was published back in January, to look at that first year of what had happened under the Trump administration. Really comprehensive accounting of what the cuts have meant. And it is, sobering. And so we know that between January and November of 2025, which are the data that are in that assessment, the federal workforce shrunk by about 10% overall. So it's a huge number, but it's a low ball estimate of what's happened to weather and climate services. Because if you look at the agencies that matter for weather and climate, NOAA was down over 15%, USGS was down close to 20%, NSF over 18%. And what's behind those numbers? They're not just percentage points. These are our forecasters, our hydrologists, our radar technicians, our oceanographers, all the scientists that are providing the best possible breakthroughs, innovation, and services, right, for the country. And this is what keeps Americans safe when there's extreme weather, when there are other kinds of environmental hazards at stake. And we are now starting to see evidence that this is going to show up in the forecast quality, right, which is not great timing as we go into the hurricane season and all the extreme storms that summer brings across the United States. We know that the staffing cuts have forced the National Weather Service to scale back weather balloon launches, for example, as well as some of the satellite operations. This is leaving alone all of the proposed cuts from the administration for ongoing monitoring that's critical, like just dismantling systems that are already in place and frankly already paid for. And one of the counter arguments is that here is like, well, AI, and it's like, AI is great, absolutely, right? We have already been interesting talks, and we'll have a lot more interesting talks about all we can do with the power of AI in the hands of our scientific workforce. But AI depends on data, right? And so if you're getting rid of the data systems, then you're going to be going in blind, and there's only so much AI can do to make up that difference. And if you're going to go politically after something that's climate, well, keep in mind what is climate. It's weather over time, right? And as former NOAA scientists have gone over saying, it's like, yeah, in the climate services resides a lot of our weather capacity. And so to take a political attack on climate will end up resulting in a reduction in what we're able to do on weather that affects Americans every day.
Yeah. And just a tiny portion to add to that, not that it's not important, but the impact on the capacity not only means, as Ben was describing, what we can do research, tool, technology wise, and the data, et cetera, but also it's the people. So I know our live stream listeners right now are monitoring what's going on with the NCAR situation, right? It's still a demoralizing issue for the people that are there, right? So since last year, NCAR has probably lost close to 59 federal research awards. So everything Ben was talking about as far as that kind of support, that long-term vision for support of important science that is accessible, it also is important for life-saving measures and decisions. It's hard to describe the importance of that, right? And so one particular news outlet spoke to some folks in NCAR, and they're still talking about demoralized teams and how the projects have impacted how they show up at work and what it is that they can do, the frozen grants. But one of the main things, and we kind of hinted at this earlier, is the impact on our early career experts, early career researchers, some of those who had internships and other professional development experiences lined up for them, or maybe they were in the middle of them. And all of a sudden, the financial supports and nets were swept out from under them. And what does that mean as far as the workforce that is needed for the future here in the US, but also globally around science? So it's things that AGU are monitoring, certainly around the NCAR situation, but science in general.
Yeah, I was just thinking back to the last AGU annual meeting, which is when they announced the dismantling of NCAR. We were all, sitting in that convention center together, which in some ways was sort of a, shooting themselves in the foot, because we all were together, and it was a horrible, demoralizing moment for everyone, especially the NCAR staff and UCAR staff who were there. But but also we had the opportunity to be together and talk about what we were going to do. And I think HU handled it as well as you could, for such crazy news to drop in the middle of like this very big planned conference. But yeah, that's one of the big things that I think is so important that you all are doing right now, is just keeping the community together, and standing up in support of everyone. So to follow on with what you're saying about the early career scientists, what have you been seeing about these cuts and their impact on people in the early career stages? And then how do you think these cuts may affect people going forward and the scientific community in the US going forward?
Yeah, I'll start with this and quickly just hand it over to Ben. So the impact is, I hate to keep using the word dire, but there's going to be this cascade effect, right? Because it's across the system. So it's direct funding that was impacted for students, for instance, graduate fellowships or postdoc funding for those in that career phase, right? If they were assistant professors or in an analogous role in another organization, the startup funding, et cetera, that may have been there for them, if it's not there now through a grant or through some other means of support, what does that mean? Where do they go? How do they establish themselves as researchers and experts, and build that credible career base for them that not only is pushing the science forward, but also bringing others along with them, because obviously there will be undergraduates and others who are involved in that kind of research. So there's the impact from cutting of direct funding, but also cutting of programs, from NSF or other funding agencies where early career individuals and others relied on, again, that long-term pool of support that they could tap into to help them move along in their career. So, and those are just a couple of examples of where the systemic impacts are, showing up in different ways. And that means downstream, there are going to be systemic impacts. And one thing that I'm concerned about, really, as a former high school teacher, 5 years and years ago, is if high school students are interested in science and their parents, the science teachers, high school guidance counselors are looking towards the future for science, and they're seeing that it's being dismantled, it's in disarray. What does that mean for that pool of individuals that may have been interested in science, and they're looking and saying that it's maybe not a good career option right now? So how is that going to impact, again, as I mentioned before, the scientific workforce that we need for the future? This is something we really have to pay attention to.
Yeah, Brandon, thanks for bringing up high school, right? Because this is all along the entire career arc that this is having effects. And so, when we talk about things like the brain drain out of science, that happens when high school students don't see it as a good career to go into. It happens when students end up pursuing different majors or decide that this is not going to be the way that they can go. For recent graduates and our early career scientists, who now many have kind of had to at least take a pause and perhaps drop out permanently from a scientific career. I mean, they're very talented people, and they're using their scientific training for good things, and I have great confidence that people can land on their feet, but we're losing them from science, right? And they're losing their opportunity to pursue science. And the brain drain continues on through. When you look at then what's happening with the funding landscape, right? The fact that the administration is not only canceling grants in midstream, but also that we're seeing grants come out at a very low rate, NSF at about 20% of the level this time in past fiscal years. That's going to affect our ability to fund new positions for graduate students, for postdocs, as we all know. And then you're seeing that up the chain to people being more senior scientists, some being recruited to other countries, certainly, but also just need to kind of like scale back what they're able to support in the enterprise. Training systems as well, right? So we already talked about NCAR, and NCAR is, for decades, has been this premier training ground for graduates and scholars. I certainly benefited from it, as many of my colleagues did. And when you start taking apart that capacity, then you lose the ability to have the best possible scientific workforce out there. One last thing that I want to mention, which I know we're talking a lot about the funding of science, the attack on international graduate students is both honestly morally reprehensible, what it's doing to people, and also a terrible attack on our ability to operate as a US scientific system, because the US is a meeting place for global talent, to cultivate it, to contribute to our own economy and to humanity's advancing knowledge. And when you go after these folks, not just with funding, but with direct challenges to the legitimacy of their status, right, to the security of the life they're trying to create, again, morally reprehensible. And also, it really comes after some of the fundamentals of what we're about as science, the global community. I would like to say what we're about as a country. And also, I think it goes after, it ties the idea of science not only as science, but science as an important humanistic social enterprise, and something that's really important for us as human beings. And that when you start going after it this way, it starts to divide people. That's damaging across science, and I would also say beyond.
Yeah.
Absolutely. And yeah, I know I keep saying thank you, but just thank you again for the stances that you all are taking and the work that you're doing to, fight back against some of these things and make sure that we can continue to do the jobs that we all signed up for. We're not intending to go out here and do a live stream and make people call their representatives and stuff, but it's what we have to do right now. And I just thanks again for continuing to do that and support the community as we have to step into these new roles. So with that, I want to turn it over to some questions from the chat. If anyone watching has more questions, put them in there and we'll get to as many as we can. So the first question from Malorian, sorry if I said that wrong. Though you're nonpartisan, do you feel pressure from the current administration, or do they not even realize you're there?
That's a great question. I'm not sure that we feel pressure directly from the administration. It's because we are supporting science. We always stand up for science, and we're stand up for our members who happen to be scientists. That if the administration is proposing or acting in a way that's antagonistic towards science or scientists, then the pressure kind of shows up there. But I do want to say that it's not always, we're always advocating for science, even if there's a science-friendly administration. There's always more that can be done, even to Ben's point about bolstering the scientific enterprise. If we think about this 76-year-old model that we're living in now from the NSF Act of 1950, where there's notion that the government is going to, for the public good, support research and distribute resources through, mostly back then, the higher ed system. We have the private sector and others now, so that the innovations can occur, the training could occur. Also, if you look at the NSF Act, it was a national security purposes. There was a recognition that we needed science and the innovations and research and the products that came out of it to ensure that we could stave off threats as a nation. Well, where are we now? Where are we security-wise with the backtracking and all of these things that Ben and I have talked about, our global collaborations, our communications, our funding, support for early career? What does that mean? We're less secure now, and if it continues, we're going to be even more less secure because we're isolating ourselves. And if we think about something that's currently going on, which probably is more direct than indirect, is this new policy from OMB, this proposed policy that would insert politics into just about every portion of the funding pipeline for the federal government, and where political appointees would have the final say on from solicitations that are posted to grants that are awarded. And kind of shirking and dismissing the input from experts around the world in the particular disciplines where that science would be supported. I mean, peer review is a backbone of the scientific method and one of the strengths of the scientific enterprise. And this proposal from OMB, it would just shatter that. And so there is a public comment period. I'm sure the listeners know about that, even though it's relatively new. And I believe that comment period is over sometime in July. And so we would encourage as many members and as many people as possible to be engaged in that process. This is still a democracy and we still have voice. And so we are encouraging people to speak up.
Can I just add that so thanks, Brandon, for bringing up that, because it's the OMB issue is really front burner right now. The partisanship question is an interesting one, right? Something that one can honestly struggle with. I do think it's important to remind ourselves that, we say, oh, science is nonpartisan and it just kind of rolls off the tongue, but let's actually think about that when we say it, because it's true, right? Notwithstanding some of our concerns about, the public's understanding of certain scientific issues, the popularity of science, the public support for science, the fact that folks are proud of what the United States accomplishes in science and as we convene our global community, those numbers are through the roof, right, compared to anything else. And so though there are partisan lines that end up forming when certain policies or coalitions, political coalitions organize themselves, fundamentally, Americans support science. And we are here to help make that case and remind people of how important it is.
Yeah, thank you so much for drawing attention to the OMB issue. For listeners, if you haven't done your calls today, make sure you do. That link at the bottom of the screen has a script about that OMB proposed rules that they have, so you can call your representatives about it and then absolutely go and write a public comment as well. So we only have a couple minutes left, but there's another really interesting question from Kelsey Ward. Is the emotional impact of all these budget and staffing cuts affecting the quality of the work, do you think? And has it, for example, led to difficulties with focusing?
That's a great question. Personally, yes. The focus part. However, what I found, and even among for instance, the AGU staff and some of my colleagues in former federal agencies that I worked in, they are really burning the candle at both ends. I mean, they were already dedicated people. They were already about the mission. If it was AGU, if it was, NSF or some other agency, they were already focused on that, because as a federal employee, former federal employee, when I raised my hand and took that oath, it was to the Constitution, it was to the mission of that agency. And every part of what I did in the work was for the general public as the taxpayers, right? So when I see and have been impacted directly from an outside, well, really it's friendly fire, from an entity that is interrupting all of that, it does have an impact on you emotionally and, just kind of even at a spiritual level. But what I've seen time and time again over these past 16, 17 months is that people here at AGU and other organizations, other agencies have just decided, and we're going to fight. We're going to stand up. We may be tired, we may be wearied, we may be battled, but we're here because what we're doing is right. And as Ben mentioned, science is one of those unifying concepts and constructs that we can't let continue to be attacked.
Yeah, and maybe just to build on that last statement, Brandon, which I think resonates with me strongly, which is that it's more important than ever to celebrate our community and what we accomplish. Because, yeah, we need to buoy ourselves. Understandably, the stress is affecting people, and that's not going to have a positive impact, on their mental, on their own lives, let alone their productivity as researchers. But if we can just remind ourselves of how strong we are as a group and how bright the future really is, notwithstanding some current headwinds, I think that's going to be vital for us as we continue to do great work and also to be the people in the community that we want to be.
Absolutely. Just from a personal standpoint, I completely agree with everything that you both said. And it definitely does weigh on you. And I'm sure everyone in the chat feels the same way. But, if there's one thing that I would recommend people do coming out of this is to find, it doesn't have to be AGU, it totally could be AGU. I love being an AGU member, but finding a group where you can organize together and you can, commiserate and you can talk about all of these things that are going on and you can find ways to take action together. That is an absolutely invaluable, experience and way that we can work together and get through this as a group. So I just want to thank you both so much for all of the work that you've done, all of the work that you will do, and for sharing your expertise and your experience on the stream.
Oh, it's been great, Haley. Thank you so much for having us, and good luck with the last few hours of the stream. This has been awesome.
Yeah.
Thanks so much.
Thanks again. And there we go. I'll turn it back over to Mackenzie.
Awesome. Thank you so much. That was a really amazing panel. We've all learned so much, great answers to questions, really amazing work that's being done over there at AGU. And so now we're going to move on to our next keynote speaker. But before that, I want to just remind everyone why we are here. And that's because scientists in the US have been world leaders in weather and climate prediction. We had the first computerized weather forecast, as well as we host organizations that develop complex models of the weather and the climate that are used all throughout the world. We also have a very large observation network with satellites, planes, boats, Argo floats, as well as land surface measurements as well. And all this amazing research and scientific advancement is thanks to all of you, the public, because your taxpayer dollars is what helps fund our US federal grants and funding, and it's absolutely essential for our field. And one organization that I want to point out that's really the heart of weather and climate science, you maybe already heard of it if you have been on the live stream for a while, but if you haven't, welcome. And that is the National Center for Atmospheric Research, or NCAR. And so some of the weather and climate models that we all depend on for our daily lives, whether you realize it or not, when you open a weather app on your phone and there's a forecast, more than likely at the back end of that forecast was created by a model developed by NCAR. So NCAR is really important. I personally really love NCAR. I spent a summer there as a student visitor working on Colorado downslope windstorm research. And I gave a talk on that last night about some of that research, and the time that I spent at NCAR and with the amazing community that I built from there really made me want to continue pursuing this Colorado research that I've been doing, and absolutely impacted me and shaped me into who I am today as a scientist. And so we've already seen negative impacts from these funding cuts, such as short-staffed weather forecast offices, as well as shrinking and elimination of research and climate labs. Also, the elimination of some research experience for undergraduate internship programs that have been funded by the NSF that we talked about earlier on the stream as well. So I really just want to encourage you all to take a few minutes out of your day today to look at the link at the banner down here and visit our website, wclivestream.com/call, to contact your representatives and senators to help protect our climate and weather research. And so our next speaker is Flavio, who I'm very excited to talk to, who is an assistant professor at atmospheric science. And just as a reminder, all of our speakers' views are their own, and they are not representing their employers or any institution. So welcome, and we're really excited to hear your talk.
Thanks. And yeah, I hope you can hear me just fine. Thanks for having me, and thanks for putting this together. This is exciting. I was able to follow a few of the talks both this time and last year, and it's just such a nice effort. It would be a nice thing even if we didn't have to do it. But yeah, hopefully this has an impact, and I really appreciate it. I'm going to talk about a few things from sort of my research portfolio. I try to bring up something that is quite top of mind of a couple of climate scientists in the West. I know I'm not in the West anymore. I used to work at NCAR and could never really let go of questions around water in the West. It's just a very intriguing and important topic. So I'm going to talk about this 2026 Western US snow drought, about this year specifically, and then also a little bit about the context, and try to answer like how unusual it was and how we should expect to think about snow droughts going forward into the future. Obviously, this is not work done by me exclusively. This is in collaboration with various people. I try to call them out as we go. I started with this picture that I was able to actually snatch myself when I was in Colorado visiting colleagues this spring. It's just outside of Boulder, Niwot Ridge, where there's a couple of research stations and weather stations that, among other things, measure snow. And this was taken on March 29th, and normally you'd expect to see snow at an elevation of 9,000 plus feet at this time of year. And this year we didn't, and I'll try to show how unusual this was. But first I want to kind of like set the stage, especially for people who haven't maybe thought too much about the West. I don't know where everybody's sitting who's tuning in today. I always like to start out with this picture of the United States with its major rivers, where the width of the river corresponds to the volume of water that flows through it in a given year on average. And you can kind of see what you might already know from basic geography, that there's not many big rivers in the West, especially in the Southwest. There's really just the Colorado River that's of note. And indeed, about 40 million people inside and outside the watershed of the Colorado River depend on its water. It's a mostly snowmelt-driven river, so ultimately what we care about, and that's why we talk about it today, is how much snow falls into the mountain regions of this basin. A lot of this precipitation falls in winter, and so that's the season we most care about. And then the other thing to understand about generally the Western US, especially the Colorado River, all of this water that's available there is basically fully allocated. So there's what's called water rights, and basically every drop in this river is typically owned by somebody. So it's a highly sort of like over-allocated basin that changes to the water availability would quickly have impacts for society and also ecosystems. There's two major reservoirs sitting on this river that you might have heard of. It's Lake Powell and Lake Mead. Especially Lake Mead is dammed up by Hoover Dam, a famous big dam. Two big reservoirs that were put in place in the 20th century to basically protect a lot of the enterprise around this water resource and to make it more sustainable in years of drought. I'll show you in a second how this reservoir has evolved over time, but I wanted to kind of point out down here in the right-hand side that these are by far the largest reservoirs that exist in North America, and they're really vital in providing sort of a sustainable water enterprise in the Western US. If we look at what happened over the 20th century to those two reservoirs, we see that they were built, the first one in the 1930s and the second one in the 1960s, and it took until the early 1980s for both of these to fill up. And since then, obviously, we've seen a steep decline of the water that's stored in these reservoirs. And I want to just like highlight two numbers that I think are sort of worthwhile to think about, is that when the reservoir is full, which last happened in 1983, it can store about 4 years worth of annual stream flow on this Colorado River. So you could put it bluntly that like if it's full, you could like go for 4 years without water. In reality, that's a bit more complicated, but that's like a rough story there. And now looking at 2026, we're probably going to have less than a year's worth of stream flow stored in that reservoir. So that buffering capacity, in case we have back-to-back drought years, has really kind of melted away over time. This is a complex story. It has to do with climate change, but it also has to do with human water use. And we're mostly focusing on trying to understand the climate change part of this story. That kind of like starts with thinking about what actually drives, for example, reservoir storage in this region, but you can think about water resources more generally. And if we look at stream flow, so how much water has actually come down the Colorado River over the 20th and early 21st century, we see that there's been ups and downs, but it's generally been declining, especially again since this high point in the 1980s. And this is mostly driven by a decline in precipitation itself. So it simply rained and snowed less since the 1980s gradually, but also a strong increase in temperature throughout the entire period, but again, especially since the 1980s. And that kind of like tells the story, especially if this recent drop from basically storing 4 years worth of water to only 1 year worth of water. And the key question we get if we talk to anybody in the West in sort of the applied and practitioners world, can be water managers, different municipalities, federal agencies, is really what aspects of this recent trend that we've seen since the 1980s should we expect to continue into the future? And you might already have some thoughts on this yourself. And so along comes 2026, which is a very unusual year, especially in the entire West. So this is a graph an undergrad here at Cornell recently made showing the snowfall anomalies. So like how unusual snowfall was in this past winter across not just the Western US, but sort of like also including Western parts of Southern Canada. And what's striking and what you might even have seen in the news headlines is really this complete lack or like very negative anomaly of snow in essentially the entire Western United States. There was only pockets where snow was near normal or maybe slightly above. The other thing that's interesting that gets a little lost in a US-centric perspective, a lot of that snow actually ended up in Canada, if you will, where we had very positive anomalies. So it's not just that there is less snow everywhere. Yes, we'll talk about this as well, but it's also like a very big anomaly in terms of where the snow actually fell this past winter. And again, if we look at this map and we zoom in onto the upper Colorado River basin, this is the part of the Colorado River where really all the snow of note falls and where all the stream flow is produced. And we look at that basin over here and the snowpack deficit of this winter, we see that basically everywhere much below normal snowpack throughout the entire basin, especially these regions high up in the mountains where all the snow typically sits and where the stream flow is generated. And I just to kind of like loop back to the beginning, so this picture I took is just in the northwest corner basically of this watershed, a little north of Denver, Colorado. Another way to look at this, which is quite striking, is to look at sort of the total snow water equivalent. So how much water is stored in this snow, and we look at this as a function of the calendar year. So typically in winter, we start to look at this in October, November. We see the snowpack building up, and then sometime in spring, we get what's typically called the peak snow water equivalent. So like when this snowpack peaks and afterwards it starts to melt. And so this is really a natural storage of water. And indeed, like if you're thinking about what storage we have currently in the reservoir, I said like it's maybe a year's worth of or less of stream flow. We have another year usually stored in this natural reservoir of snowpack that we can count on to come down the mountain come summer. Now this year you can see the curve of 2026 compared to all the previous couple of decades of observations we have in this region. It was unusually low and peaked very early. And so by the time we come into spring, a lot of this snow has already melted, and we cannot expect a lot of stream flow to come down the mountain now to help us with agriculture or anything. So this will be a year where we have to draw down these reservoirs, which, as I showed, are already very low. So it's a pretty uncomfortable situation that we're in the Western US with regards to these big water resource allocations. Why did this happen? Kind of alluded to this already a little bit in terms of the long-term trends, but if we look at how unusual these winter conditions were, so we're talking November through March, temperature anomalies over the upper Colorado River basin, as well as precipitation anomalies. We see all the past couple of decades lined up here, and then ultimately colored by how low the snowpack was. Again, this SWE snow water equivalent. And we just see 2026 that I want to point out here. It's in the bottom right corner. It's dark red. So it is the warmest, the driest, and the year with the lowest snow on record. And so that's completely consistent with what I showed you before. So we had this confluence of not a lot of precipitation to begin with, and very warm temperatures, which all else equal will make precipitation fall maybe a little bit more as rainfall rather than snowfall, leading to a very, very low snowpack going into spring and summer. We're trying to understand both like why that happened from the atmospheric science side, but also try to look into the future and see how much more likely should these events become according to the data we have. And so this is a project, NSF-funded project, ultimately led by a postdoc Ankur Dixit and PhD student Sydney Carr at Cornell and at CU Boulder, where we take both reanalysis data, ERA 5, as well as a climate model, and we downscale it to a high spatial resolution over this particular watershed. The reason we do this, just to keep it brief, is to represent snowpack and the climate correctly over mountains, you really need to do it at high spatial resolution. So the global climate models are useful to provide a general context of what's happening to the weather in this region, historically and into the future. But to get the details right, we do need a higher resolution. And if we do this, this is kind of a type of curve we end up with if we're looking again at the upper Colorado River Basin where this important snowpack sits. So we have on the one hand our observations, so this goes up and down from year to year, so we have big variations in how much snowpack there is. And then we see 2026 here as a record low year in the recent past. And then this gray shading are these results from this climate model. This climate model was run both over the historical period as well as into the future under the assumption of continued strong emissions of greenhouse gases. So this is a pretty warm scenario, and I'm happy to talk about other scenarios in the Q&A if that's of interest. But fundamentally, we're like interested in, okay, if the warming continues into the future, what does that mean for the snowpack? And so we see two things. One, we see a gradual decline of snowpack into the future, very much in line with this trend we've seen over the historical period. We see still a large variation around this. This is internal variability to the system. We think weather variations, day-to-day variations that can always happen, right? We can always still have a very high snow year in the future, and we can have very low years. There's a lot of variability in that. But ultimately, what we're interested in is this long-term average, this long gray line that we see declining. And so the other thing we can do, the second thing, is we can ask this specific question. Okay, 2026, clearly the worst year on record. If we go out and talk to practitioners in the West, historically, they've always cited 2002 as a particularly bad year. This is way back here. It's not the lowest on record in the upper Colorado, but it had pretty devastating consequences for water resources. And so now 2026 is basically the new low standard. And so people start to ask, like, okay, this is a really bad year. How much more frequent should we expect this to become in the future? Using these climate models, we can start to answer these kind of questions. And some of the high level results here, to not get into too much detail, is that if we look at the historical periods over the last sort of 40 years, we see that this event is actually about a 1 in 40 year event according to this climate model simulation. So it's not a completely unusual event, but it is very exceptional. And you would have to observe 40 years on average to see another event like that. However, then if we look at the end of the century, this becomes on average a 1 in 8 year event under continued warming, so a much more frequent occurrence. And that's clearly, with the knowledge you already have now, starting to be a problem. If your reservoirs can at most store 4 years worth of water, but are already depleted, and we're moving into a future that has even less natural storage and less snow provided, it calls for a very different approach to managing and preparing water resources for use in agriculture and municipal areas. And so this is kind of the kind of information that is useful and actually actionable, because at the end of the day, a lot of engineering solutions to environmental problems, including changing climate, want to learn about return periods, but like, how often should I expect this to happen? Because once it happens too often, you really have to rethink and adapt to this changing baseline. The other part that we're still working on is basically trying to understand a little better, not just the temperatures, which I think we have a pretty good understanding why they've been going up, it's greenhouse gas driven, but also the decline in precipitation. There's a lot of literature, including work I've done as a postdoc, that assumes that a lot of this decline is just an unfortunate sort of swing of things, like a gradual decline from a wet period to a dry period, but it might turn around again and become wet again. So that this is largely just internal variability and not necessarily strongly affected by, say, greenhouse gas forcing or other things that humans have done. A lot of people are looking at this, especially because we keep not having the precipitation we used to have in the 80s and 90s. And so I just highlight this nice article here by Bob Hansen from last summer that summarizes a couple of new studies, including one we have published, and I'll summarize briefly here. But all to show that this is a hot topic, because yes, warming is a problem for water resources, but like the key question remains whether precipitation will return or whether we'll stay depressed. Like it's hard to start a drought if you have above normal precipitation. So the key to all of this is really what is happening to precipitation. And so this gives me a chance to feature some work by Yan-Ling Kuo, a PhD student who just graduated here at Cornell, who looked at this in great detail. And specifically, she looked at this question we asked at the very beginning, where we saw actually in 2026, yes, it was a very dry year in the Western US, but actually it's a very wet winter in Canada. So it's not necessarily that there's a complete lack of moisture, it's just like, where did the moisture end up? And so this is actually something we've observed very systematically since the 1980s. We had this tendency towards declining precipitation in the Southwest and a slight tendency towards increasing precipitation over Canada. And we can first order link this to changes in atmospheric circulation out over the Pacific Ocean. Specifically, we're talking here about what we call positive anomalies in sea level pressure, or in other words, we have a tendency for weather systems that spin clockwise in this direction. And what that does to any moisture that wants to get to the Southwest, it gets deflected either northward into Canada or southward into sort of central Mexico. But it kind of like avoids the Southwest if we have this kind of weather pattern. And indeed, this is the trend in this weather pattern over the last couple of decades towards more of this kind of situation. So now then the question is like, okay, is that just an unfortunate sequence of events, or is that something more systematic? And this is where we turn to climate models to better study this. To first order and based on theory, we expect this type of weather pattern actually to occur because the Pacific Ocean has been doing something that we call a La Nina-like sea surface temperature trend. In other words, the tropical Pacific Ocean has been cooling over this time period, which we know from a lot of research, and I'll show you in a second how well this works, that this would trigger this kind of weather pattern and a decline in precipitation over the Southwest. And indeed, if we do take this kind of sea surface temperature pattern and we put it into a climate model, so we give it sort of half of the answer, if you will, it closely produces this kind of pattern. So I think I have one more sort of slide here to better explain this. The way this works is like the tropical Pacific Ocean is generally very warm, but it does swing back between warm and cold phases. This is El Nino and La Nina, something you might have heard in the news before. And so what happens here, just at the example of an El Nino where the tropical Pacific is very warm, it triggers waves in the atmosphere called Rossby waves that can then affect the weather over the North Pacific and ultimately over North America. And that's kind of what we're interested in at the end of the day. It's not a perfect analogy, but you can think of this a little bit as like ripples in a pond, where something it is happening in one place and can like ripple out and have effects far away from where the initial action happened. That's kind of what the ENSO, the El Nino Sudden Oscillation teleconnections can do. And so if we take this sea surface temperature pattern, or like this the initial drop of a stone into the ocean, we see the rippling effects in a climate model are pretty much exactly what we see in reality, where we have this positive sea level pressure anomaly, the circulation anomaly in the atmosphere that really avoids moisture from getting into the southwestern US. So we have a good understanding that this is typically what happens in this kind of situation. The problem now is that this kind of pattern, climate models are not very good at reproducing this. And there's a lot of literature on that I'm not getting into here in detail, but it has for the last 5-6 years, I would say, undermined our confidence a little bit in what's happening in this region. It was then interesting for us to look at climate models. So CNIP6 is a whole collection of climate models, and CSM2 is one specific climate model developed at NCAR, but it's kind of the same caliber of climate model. And indeed, over this time period, from the 1980s to roughly today, neither of these sets of models can easily reproduce what we've seen in reality. However, if we look at the atmospheric circulation response and the precipitation response from those models, they actually do look a little similar to what we've seen in reality. So suddenly, something is happening in addition to the tropical ocean that drives the weather. Because with this tropical ocean or this tropical ocean, we wouldn't necessarily expect this kind of weather and this kind of precipitation trend, because it's kind of opposite to what we've actually observed in reality. So something is a little off over the last couple of decades. And it's interesting that other people in other fields, sort of adjacent to what we do, also notice this. This is the community that makes seasonal predictions of climate. So rather than looking over decades, they just look from one season to the next and try to predict what the weather is going to be. And they also noticed this, for example, in the 2023-24 winter, that even though the Pacific Ocean looked primed for an El Nino, we didn't really get or didn't see the classic response in the atmosphere and the classic response in precipitation over the Southwest that we would expect. So the question is, of course, what is driving this and what are the mechanisms? And we looked at this in a fair bit of detail. I try to keep it short here, not promising that I'll succeed, but it's really for us a search for like what's going wrong in the typical chain of events that drive the weather that comes from the tropical Pacific Ocean. And so for this, we looked first at a metric that looks at the coupling between the tropical ocean and the tropical upper atmosphere. So this is the 200 hectopascal, so higher up in the atmosphere, velocity potential gradient. We don't need to necessarily go into the details of this, but what we found is that the distribution of trends of that metric compared to sea surface temperatures in the tropical Pacific was not that different between a simulation that is assuming the climate before humans affected the climate, as well as this historical period, let's say from the 1980s to today. Yes, they're a little different, but not too different. So it's nothing is going wrong, so to say, between the tropical Pacific Ocean and the atmosphere above it. That still behaves as we know it. But then when we look at a metric that looks at the coupling between the tropical atmosphere and the mid-latitudes, so this is now where the North Pacific sits, where this weather system sits that dictates whether we get precipitation in the Southwest, there we see a strong relationship in the pre-industrial climate, so before humans had a significant impact on the atmosphere, and then a much weaker relationship in the historical period. So something is overriding what normally would be a strong connection between tropical upper atmosphere and the mid-latitudes where most of us live. I'm not going to go into too much more detail, but there's two mechanisms that we found might influence this. There's a bunch of others, and I would say science is still trying to figure out which are most important. One is aerosol forcing over from Asia. So over the last couple of decades, air pollution, broadly speaking, ramped up quite a bit in countries like China, and this can affect the atmospheric composition. It affects like how heat is trapped in the atmosphere or how sunlight gets blocked from incoming. And so this can like be another ripple effect in the pond. And what we found is that this tends to produce this kind of weather pattern over the North Pacific that leads to a decline in precipitation over the Southwest. So there's one ingredient. The other one is that generally what happened with climate change is that the tropics have been warming a fair bit, not just in the Pacific, but also in other parts. And that's, again, a well understood mechanism that should lead to a weather pattern, again, that tends to block moisture from coming into the Southwest. So we have these two ingredients that sort of act to override what we normally expect to happen between the tropics and the mid-latitudes. So we call this the tropic mid-latitudes coupling that is weakened by these mechanisms. This can act in any given year, but it certainly seems to act over these longer time scales that we've observed. And then just briefly on the implications of this, we're looking at the southwestern US at a bit of a complicated plot, but what we have on the y-axis here is winter-spring precipitation trend. On the x-axis, we have summer temperature trend, and the colors are soil moisture trend over the Southwest. And so generally, we see this logical relationship, I would say, that if you have a warm summer that follows a dry winter, you should expect soil moisture to be quite low. And so if you now look against this kind of mesh here, where recent decades, both in observations and all of these climate models fall, we see that a lot of them cluster in the bottom right of this plot. So there's just this preference for any, both observations, climate models of various kinds, to end up in the bottom right corner of this graph. And this is driven to a large extent by the warming, right? So all of these dots are to the right of the center here, but a lot of them are also having a precipitation decline. So there's these two factors that combine to make this a particularly dry period, both the very warm temperatures and the decline in precipitation. And so we concluded from this that forcing, I didn't get into too much detail which ones, but like certainly greenhouse gases and aerosol forcing made this particular drought or this tendency towards low precipitation over the Southwest more probable than we previously appreciated. The flip side of this is that if aerosol emissions from Asia actually had a significant influence, then as countries like China clean up their air, we should expect that effect to go away a little bit. That's a chance, at least, for precipitation to come back if it was indeed strongly influenced by Syl Foisy. At the same time, continued warming, as we should expect with the accumulation of greenhouse gases in the atmosphere, is expected to drive aridification of the Southwest. So there's a little hope for good news on the precipitation side, but as long as we warm, there's a good chance that this region will further dry out. The implications for the public are at first pretty straightforward, like any kind of water security concerns are likely to increase in the future and definitely need managing, and lots of people, agencies, literally the 7 states that border the Colorado River are on this task right now. They have to agree on new rules this year and how to manage this water. I think the key question for science to still answer is how quickly should we expect things to get bad? This year was very bad, but should we expect this next winter to also be bad? And so these are kind of questions that were really pressing for us to answer going forward. So I try to summarize or answer the question I posed at the beginning, how unusual this U.S. snow drought was. Is it just a fluke, or is it a harbinger of worse things to come? And so I think the answer is a little bit both. It was certainly exceptional. I mentioned this number, 1 in 40 years approximately kind of event. But we also see that in almost any kind of climate scenario going forward, such events will become more common. Ultimately, how bad it will get depends really on what's happening to precipitation. And that's the part where I think there's still the jury is a little bit out. Will precipitation stay depressed, or will it return to sort of, let's say, 1980s levels? And I want to just end with saying, like, just as one concrete example of how the current funding landscape and the political situation affects this specific research or my group specifically. I'm waiting for a large NSF grant that, as far as I understand, should get funded, but because everything is delayed, even the funding that NSF has, I haven't been able to get that funding. I couldn't recruit any students or postdocs this year on this grant to study this exact question. And this happening in a year where, like, all the states and the actors in the Southwest are coming together to try to develop new rules on how to manage this water. And so it's really a complete clash of, like, the urgency of a topic and how hard it is now to get funding to study a topic like that. And then for me personally, having worked at NCAR and having worked with people at NOAA, I just experienced that the insecurities at some of these very critical partner institutions that do measurements, that do the model development, that can trigger exodus. It certainly doesn't help everybody do good work, and it ultimately destabilizes the entire research enterprise. And so these are things that even for me at an Ivy League university are starting to have really concrete impacts. And I consider myself in a relatively stable position compared to a lot of my colleagues. And so these are just some of the examples I can provide, and I can only imagine how it is in some of the other situations. And literally some of our students that graduated while I was a professor here have since lost their job at a federal agency. And so it's really, it starts to really get at the foundation of the entire U.S. research enterprise. I think I'll stop there. I'd be happy to take any questions, both now or later. And thanks again to the organizers for putting this together. This is great.
Awesome. Thank you so much, Flavio. That was a really great talk. I live out in Colorado, so it's been a lot of the talk here is about how we don't have a lot of snowpack and things are very dry. So it was really, really interesting to see you dive more into that. And also, we appreciate you talking about your experience with funding slowdowns and things like that to give folks at home kind of an idea of what's going on here. So we have quite a few questions for you. We're going to start with one from Sydney. She says, I've seen a lot of discussion about certain communities completely running out of water, especially during this El Nino. Is that within the realm of possibility?
Yeah, that's a great question. I will say I don't know exactly any specific communities and how they're situated, but what is clear in the Southwest in particular, or in the Western US in general, as I mentioned at the beginning, all the water is allocated. So people have what's called water rights. So they have a right to draw a certain amount of water if it's on their property, or they have some other arrangements. But these water rights are sort of tiered. Like, some are so-called older, some are younger. And the younger ones are the first that will have to curtail their usage in case there is a declared emergency. So if you're in a community that has been built relatively recently, then good chance that the water rights are young or like are the first ones to be curtailed. And so that's something to watch out. And I know communities are starting to be concerned about that. Of course, that also gives a chance for water to be traded, but it's not always clear that there is money to buy water from somebody who doesn't need it. I will say that in the Southwest, again, historically, in an El Nino year, we would expect above normal precipitation. That's kind of like a hopeful outlook for this winter, where we expect a strong El Nino to happen. But again, there's two things that can like mess this up. First off, not every El Nino actually delivers what we sort of expect. That's just weather, right? Not every weather forecast is always right. And second, these factors I mentioned that like seem to, at least over the last couple of decades, tend to override what an El Nino can do to the Southwest a little bit. So I think it decreases the chance to get precipitation even in an El Nino year. So I think all put together, I think there's a real possibility that some communities are going to struggle.
Thank you for answering that question. Yeah, and also talking about the upcoming El Nino this winter too. I encourage listeners to stay on for the next talk. We're going to be talking more about El Nino as well. Our next question is going to come from Cambrian. This was earlier in your talk when you were talking about the different climate models that you were using and downscaling for your simulations. And they ask, what happens if emissions get worse? What's the worst realistic simulation you've done?
Yeah, so that's a bit of a debate among scientists, I will say. So I mentioned how like we think there is a role for the historical aerosol emissions to have contributed to the decline in precipitation. We expect a lot of countries to clean up their air over the next couple of decades, so that should alleviate that a little bit. Other studies think that more of this mechanism is tied to greenhouse gases, which means that it doesn't matter too much whether we clean up our air or not. The greenhouse gases are the thing that's driving this, and so it doesn't look like those are going to go away. So those scenarios are much more pessimistic. They kind of think precipitation will remain depressed for the next 20, 30 years, which will be really dramatic for a place like the Southwest that's already running out of water. And so that's, I think, the biggest uncertainty there. On top of that, of course, it's always a bit unclear what humans are actually going to do, right? I mean, we kind of say we expect them to clean up air. It's not a guarantee that they do that. We also hope that countries reduce emissions of greenhouse gases, but again, no guarantee that this will happen. So I think it remains important to look at the whole range of scenarios, as much as that is kind of sometimes a little overwhelming, especially for decision makers, if you present them everything from RCP 8.5 to RCP 1.126 or something. It remains important to provide that range of outcomes, because what you don't want is to be unprepared. If you're over-prepared and you thought through scenarios that are very unlikely, that's still good. That's like typically how engineers approach any problem. And so I encourage people to continue to make that case as long as we don't have clear evidence that one of these scenarios is really the one we're going to be on, both on the physics side of things as well as on the emission scenario side of things.
Yes, absolutely. And one thing I want to plug there too is with those different emission scenarios and larger climate model simulations, a lot of those are housed and run by NCAR as well, which are really important for us to keep funding.
Yeah, totally.
I think we have time for one more question, maybe two. Let's see. We're going to go on to Arianna's question. She says, is it possible that continuing Western U.S. snow drought might result in consistent and repeated extreme snow events in the Eastern U.S., like what happened earlier this year?
Yes, there is generally actually a bit of a connection there. At least this particular winter, we had basically a strong ridge and a strong trough. So these things are a little bit connected. I try to show how when there is no snow in the southwestern or in the western U.S., there is a higher chance of snow in Canada. Similarly, if there's a hot, dry winter in the southwest, there's a slight chance for the opposite to happen in the east. And then people have also looked at whether this type of weather pattern will become more frequent. There's a slight tendency towards that in the future. So I would say a soft yes to your question. But in any given year, a lot can happen in the weather. So we want to look at this over the next couple of decades to be sure what the actual signal is.
Yes, yeah, absolutely. The internal climate variability is very important to look into more. Yeah. Awesome. Well, we're at about time to switch over to our next keynote speaker. So thank you so much, Flavio, for giving an amazing talk and awesome questions. Everyone, please in the chat, thank him for coming here, and we will move on to our next speaker. So thank you. All right. So as we are now in our 48th hour, everyone, spam the chat with 48s. Very exciting. We are going to move on to our next speaker. But before that, as many of you know the drill, if you've been with us for many hours, I'm going to remind everyone why we are here. But if you're just now joining, please welcome. I'm Mackenzie. I'm going to be your host for this last talk here. And so we're here because U.S. science and scientists have been world leaders in weather and climate prediction. We had the first computerized weather forecasts here. We also have complex models of the weather and climate that we develop, especially here at NCAR. And we have a really awesome observation network of satellites, airborne measurements, boats, floats, land measurements, and all of those awesome observations that are used for a lot of the research that you've already seen over the past 47 hours or so. And all this amazing research and science advancement is thanks to you, the public, because your taxpayer dollars are what help fund us all with US federal funding. It's absolutely essential for all of our research. And so, however, the current proposal by the Office of Management and Budget, or the OMB, would drastically change how federal research is funded. We've heard a little bit about this earlier as well. And one note I just want to point about what's going on with that proposal is that when researchers or professors are writing proposals and applying for funding to look into a scientific question, each one of these proposals and programs needs to now align with the administration's political priorities rather than scientific need. And this has now become a big shift in previous federal funding proposal processes post-World War II, in that now things need to align more with political priorities rather than us needing the science. And we've already seen negative impacts from funding cuts, such as short-staffed weather forecast offices, as well as the shrinking and closing of research labs, including climate labs, as well as termination of NSF internships, such as research experience for undergraduates or RU programs that have been very essential to many scientists that you've heard talk over these past hours. So I encourage you all to look at the link at this banner below down here to visit our website, wclivestream.com/call, to contact your representatives and senators to help us protect our weather and climate research. So next, we're going to go on to our next keynote speaker, who is Emily Becker, and she is a research associate professor and going to be talking about the super El Nino that will be happening this upcoming season. And just as a final reminder, I just want to tell everyone that our speakers' views are their own and they're not representing their employer or any other institution. And with that, Emily, everyone's really hyped up for some ENSO talk from the last talk. So just go for it. Yeah.
All right. Thank you, Mackenzie. Yeah, Flavio's talk was a really nice lead-in. So I'm always happy to talk about ENSO. My students know that I can talk about ENSO for months on end. So I'm going to try to keep it to 20, 25 minutes. So we have some time for questions. But first, I really want to thank the organizers for this invitation. This is a great opportunity. It's a great event, and I'm really happy to be part of it. So here's my goofy title. It's a bird. It's playing Super El Nino. Put a little cape on him. Super is not really a technical definition that we use, but I don't know, a week or so ago, I just decided I'm just going to lean in. If you can't beat them, join them. Super, bring it on. So today I'm going to go over El Nino, ENSO, what it is, crucially, why we care so much about it, and then also what we're going to, what we expect to see later this year. I'm really sorry if you can hear sirens in the background. Of course, just happened this moment, but I'm not closing my windows. If any of you are in the mid-Atlantic, it's that rare open window season. So hopefully they'll drive away. All righty. So what is ENSO? ENSO is the El Nino Southern Oscillation. We mostly refer to it as ENSO, but I often will just call the entire system El Nino. It's the entire El Nino, La Nina system. And it's a recurring pattern of warmer than average. So that's El Nino, that image on the top there, and cooler than average La Nina surface water in the tropical Pacific. Just to note that a lot of my figures and a lot of my experiences from the ENSO blog, which ran from 2014 to July of 2025, when climate.gov was disbanded. So I owe a debt of gratitude for most of these figures here. And I'm happy to say that climate.us is standing up as an independent source that will provide a lot of the data, figures, and information that was previously provided, and they will be launching sometime later this month. So stay tuned. It's just an independent endorsement of them. I'm not part of climate.us. All righty, so we got our warmer than average water, we got our cooler than average water. Where do we go from there? So critically, ENSO is a coupled ocean atmosphere system. So it involves the ocean, it involves the atmosphere. It's not just that warmer water, although that is the easiest to forecast part and the sort of the first step of what we require to declare an El Nino event. The average tropical atmospheric circulation pattern is called the Walker circulation, and that's driven by strong convection, which is rising air, clouds, and storms that grow over the very warm water of the far western Pacific. So you can see in this figure here, these winds that blow steadily from the east to the west, those are the trade winds, so-called because they carried sailing ships along on trade routes hundreds of years ago. And those winds are there because of the rotation of the Earth. So it's a pretty fundamental component. And all the time they are blowing along the equator, pushing that warmer water towards the west and accumulating it here in the far western Pacific. And over warm water, you see convection. And this is a very, very strong and consistent pattern. And in fact, drives the entire global circulation. The tropical circulation is so powerful that it drives the entire globe. So this is your average setup here. So ENSO neutral. And hopefully this animation, it's a little bit slow. Yep, here we go. All right. So here's your neutral conditions again, your Walker circulation during La Nina. You actually see a strengthening, but during El Nino, and I'll let it cycle through again, but in El Nino, you have that warmer than average water that grows here in the tropical Pacific, and your circulation center sets up over that warmer area. So you essentially see a movement of this engine of global atmospheric circulation towards the center and the eastern tropical Pacific. It's a big change, and it has global ramifications. So what are some of those global ramifications? The bottom figure tries to take all of our anticipated ENSO impacts and cram them all on one figure. It's a little bit challenging, but also it's important to remember that these impacts are aggregated over many different ENSO events. And so they are just sort of a broad strokes guide to what we might expect to see. So up here, we've got, again, a different view of our circulation patterns during El Nino. And, oops, sorry, didn't mean to skip that. So here we've got maps showing what we can expect during December to February. Even though El Nino develops over the summer and into the fall, the strongest impacts in terms of temperature and rainfall and snowfall are during the winter, especially in the Northern Hemisphere. So what we see in the US is this cooler and wetter through here, and generally a warmer and drier pattern. through the Pacific Northwest. And this horseshoe of dryness setting up with some extra warmth over in the region of in the region of Indonesia. We tend to see some wildfires occurring during El Niños. So something to be on the lookout for. And then there are impacts as far away from us as Africa and South America. You see drier conditions through Southern Africa. And this is a pretty consistent wet signal here in Africa. So those remote impacts are called teleconnections. And as I said, they affect precip and temperature. They also affect hurricanes, drought, and even tornadoes and severe weather. It's funny, the longer I spend studying, and so the more surprised I am at all of the different impacts we see. And so affects Antarctica, it affects the Indian monsoon, all kinds of things. So it really has its fingers in all sorts of things. So the expected impacts, so this map we've got here, and then whenever we talk about expected impacts, they are largely, that information is largely based on what happened during past ENSO events. And I have a little bit more nuance about that in a minute. But I wanted to explain how we see a lot of impacts over the US and North America in general. We see an extended Pacific jet stream. So Flavio, if you were watching earlier, Flavio showed the Rossby waves, that atmospheric wave that emanates out of the tropical Pacific, and those downstream shifts on the jet stream. The jet stream carries storms along it. So we tend to see this extended further south jet stream amplified storm track, bringing very consistent rain and yeah, not so much snow in the south there, but rain patterns through the southern tier of the US. So yeah, I promised a little bit more nuance on the expected impacts. Those expected impacts are based on we have an El Nino record, ENSO record that stretches back about 75 years. It's not that long. We have about 25 El Ninos, 25 La Ninas, and they range from weak to very strong to super. So there's a lot of variability that is hidden in these averages that we show in the typical maps here. And all these little postage stamp maps are the rain precip patterns during every El Nino since 1950. This does not include the 2023-24 ENSO event, El Nino event, but it includes every other one. And you can see, if you squint your eyes a little bit, that there's consistency through especially the Southeast US, but there is a lot of variability that can get hidden. Generally, what we say is that the stronger the ENSO event, the more likely that we will see those consistent impacts, those expected patterns. And maybe you can take away from the stronger events, which are the top two rows here, somewhat more consistent wet patterns through the south and southern tier of the US, and drier in the interior. But you can tell that while El Nino does tilt the odds, just like Flavio said, there's a lot going on that can influence how the outcomes actually transpire. So, however, that being said, ENSO itself, El Nino itself, is predictable. We can predict it 6 months, even a year in advance. And that gives us a way to anticipate what is coming up: temperature, precip, hurricanes, all those things. If you think about it, there aren't a lot of sources of information about what might be happening 6 months into the future. On the weather and climate timescales, we have the seasonal cycle. So winter will be colder than summer. That's a pretty solid forecast. We have the global warming trend, and we have ENSO. So you add those three together, and we have some more information, especially since the seasonal cycle we don't use it in a predictive sense other than as an example to say, oh, it's going to be cooler. And in fact, it's a good example because while I can say that winter is cooler than summer, I can't say that every single day in the winter is going to be cooler than every single day in the summer. In fact, just a few years ago, January 1st here, New Year's Day, was actually warmer than the 4th of July was that same year. It was 74 on New Year's Day, 73 on the 4th of July. So just an example of variability within a season. How does El Nino affect hurricanes? That altered Walker circulation that I talked about changes the global atmospheric circulation. And one of the ways it changes it is it actually strengthens the upper level winds over the Atlantic, which increases shear. And shear is just the shift in the winds from the surface level to the upper levels, from the lower levels to the upper levels. And it makes it harder for hurricanes to form if there's more shear. So I think many of you have likely seen NOAA's recent hurricane outlook, which factored in this El Nino forecast into its below average probability. But of course, I have to mention, especially since I'm based at the University of Miami, it only takes one. Hurricane Andrew was during an El Nino year. So never let your guard down. How do we measure El Nino and La Nina? This box here, this little key monitoring region, is the Nino 3.4 region. We look at the sea surface temperature anomaly. So I said El Nino is warmer than average water. La Nina is cooler than average. We look at the average in that box and its difference from the long-term average. So that's called an anomaly. We also compare that to the temperature of the entire tropical oceans. This is a recent adoption we have made of the relative Nino index. And the reason we did that is that El Nino and La Nina, while this region wasn't really showing a very strong temperature trend, the oceans across the entire tropics were getting warmer and warmer. And that was sort of confusing that atmospheric signal that I talked about because the atmosphere responds to warm water. So what we want to know is relative to the entire tropics, is this region warmer or cooler? So that's our relative Nino 3.4 index. And the figure on the bottom just shows you recent relative Nino 3.4 index, our 2024 El Nino and a couple of years of La Nina that followed. All right, it's super time to talk about the potential super El Nino. I did an interview recently where the reporter did not seem interested at all in the fact that we don't use super as a category. Hence why I've decided just to stop worrying and learn to love the super here. So on the left, we've got the forecast actually made in December of last year. So just as the La Nina that we had last year was developing. And each of these lines here is a prediction for that Nino 3.4 index. This, in fact, is not the relative one. It's our older metric. But the reason that I'm showing this is because the consensus of these lines, which is this black dashed line here, that's the average of over 100 different model forecasts. That is showing that the models as far back as December, and in fact, you can go back farther and see hints of this too, we're expecting us to pull out of that La Nina and just start developing into an El Nino event. And in fact, we are, this forecast is verifying nicely. So the climate models saw this coming. And this is the corresponding consensus team forecast as of December 2025. So essentially these blue bars are the probability of La Nina and the red bars are the probability of El Nino. So back at the end of last year, we had an almost 50% chance, which is a pretty confident chance for something almost a year away, that we would see El Nino. So to put this in the context of the relative index, which we adopted only a few months ago, NOAA wanted to test this pretty thoroughly before we changed to it, which was a great idea. And in fact, we have found that this relative index gives us a much more trustworthy view of the expected impacts. So along with an accurate monitoring of the strength of ENSO, it gives us that perspective on what we might be seeing for the impacts. So here we're comparing, again, this is this North American multi-model ensemble. So each color is a different climate model and each thin line is a different run of that model. These were started in the 1st of May, last month. We will have new ones shortly. The timing of this live stream is we're just a week away from an updated forecast. So stay tuned, not to the live stream, but to the forecast. So here's our relative Nino 3.4 forecast. And we see that the model consensus is around a 2-degree anomaly in the relative Nino 3.4 index. And that is on the border of strong to very strong. And hence we do have a fairly confident forecast for a stronger event. So here are the consensus forecasts that were released in May, and we have, as I said, the upcoming forecast next week. These probabilities, this is just for the advent, this is just for the advent of El Nino altogether. And over here, this is a recently released graphic showing the probability of what strength categories we will see. So this darker pink here is a strong El Nino. And then once we get past 2 degrees, we get into very strong El Nino, or super, whichever way you want to look at it. And we do see by the winter in this forecast that was issued last month, as about a 60% chance that we'll be in strong or very strong, with about 1/3 of the total chance that we'll be in a very strong El Nino event. So why are we so confident in that? This animation is showing the subsurface temperature. So what we see is a lot of warm water underneath the surface of the tropical Pacific, and it's moving eastward as it does in what's called a downwelling Kelvin wave. This provides a source to the surface and provides us confidence that we will see a continued warming of the surface. Also, critically, all these arrows are showing you the pink regions of this figure are showing the weakening of the trade winds. So we call them westerly wind bursts. So the trade winds are easterly winds. When they weaken, we see a westerly anomaly. And we've seen quite a lot of those. When the winds weaken, those trade winds, they allow that warm water to slosh back to the east, and also allow the surface to warm further. And they're a sign of the coupling between the ocean and the atmosphere. So we are seeing some of these winds. We wouldn't necessarily say that the ocean atmosphere system was coupled yet, but we're seeing signs that are giving us some confidence that may be coming up. And also I wanted to show, this is the Nino 3.0, or the relative Nino sea surface temperatures, relative sea surface temperatures in the tropical Pacific right now. And we do already see a good amount of warmer than average water, including particularly over here in the far eastern part of the basin, which can spread to the west. Okay. a lot of people want to know about El Nino and global temperature, so the global mean temperature. This is an older figure. It stops in 2022, so it doesn't show the very, very warm global temperature anomalies that we saw in 23 and 24. But essentially, if you spend some time staring at this figure, you will note that the El Nino years are the warmest global average temperature of their recent years. So El Nino tends to be the warmest year of its own decade. But you can also see that La Nina events currently are much warmer than El Nino events in the past. So what El Nino does is it does provide a temporary spike in the global temperature anomaly, but it's not actually accelerating global warming. It's a jump that will be it's a jump that can be when La Nina develops after El Nino, we will usually see that global temperature dropping back down again. It's just a stair step along the way. It's not actually changing global warming. Sometimes I see some confused messaging about that. El Nino is accelerating global warming. It's just a change, a temporary change on top of the overall global warming signal. That being said, here is our North American multi-model ensemble forecast for the global mean temperature. And there's a lot of spread here, but you can see that the consensus forecast is for a steady increase over the course of 2026 and into 2027. Typically, the year that starts with El Nino, so in this case, it would be 2027, tends to be the warmest year that we see. So will 2026 be a record? Maybe, maybe not. Will 2027 be a record? I would guess it would be in the top two at least, but time will tell. All right, so I wanted to end on this lovely AI generated image that actually uses some quotes from a real article that was written a few weeks ago, I guess, a few months ago. So go big or go home. Here's our super El Nino, and I would be happy to take questions.
Awesome. Thank you so much. This is a cool graphic.
Yeah, isn't it fun?
Yeah.
I didn't make it, a friend made it.
No, it's awesome. A lot of awesome stuff going on in the chat. Everyone's been enjoying your talk. I know I did as well. We'll just start off with some questions. Sydney started by asking, have you looked into comparisons with this upcoming event and the 1877 El Nino?
You know, I haven't. I do think I saw something about that in the news. So it's really difficult to compare those things because 1877, while we did have decent measurements of the sea surface temperature along in bits and pieces, I guess, we really don't have very many atmospheric observations. And so it'd be really difficult to do a good comparison of those two. Honestly, my favorite thing about to say, if anybody asks me what I wish I had done, is built a time machine so I could go back 5,000 years in the past and build an amazing observation network so that we had a 5,000 year record of data instead of 75 years.
Yeah. No, that would be awesome.
Yeah.
I think kind of going off of that too, Dylan has a question in the chat here about how was ENSO measured before the days of floats?
Oh, what a great idea. Or what a great question. Yeah. Ships would go along and they would literally drop down a bucket of water and pull it up and stick a thermometer in it. In some cases, there was a thermometer actually stuck to the bottom of the boat, but most of our observations prior to the floats were from just trade ships traveling across the Pacific.
Yeah. Okay, cool. Next question from Mallory Ann. What's a misconception about ENSO that the media gets wrong that really grinds your gears?
Well, I said I've gotten over the super thing, right? So, yeah. So I'm grateful for this question because it's something that I didn't talk about in my talk, but there's a lot of, oh my God, El Nino is coming, prepare for the end times. And they talk about it like it's an asteroid that's going to hit the Earth. Whereas El Nino is something that's been happening we are extremely confident it's been happening for thousands and thousands and probably millions and potentially hundreds of millions of years. So as long as the Pacific Basin has had its close to its current configuration, there's been El Nino. And what it does is, yes, it does cause some extreme events, but it also tells us that those extreme events might happen ahead of time. So in many regards, it's treated as something to be dreaded, but in fact, it's more information than we ever have. Droughts and floods and famines happen all the time, but when we have El Nino, we know ahead of time where they might happen and we can prepare for them. So I would say it's that kind of characterization of El Nino as a cataclysmic event that is to be dreaded.
Yeah, I mean, very, very well said.
Thank you.
Next, we have a couple more questions from Sydney. Is it possible to get a triple dip El Ninos like it is with La Ninas? Or maybe if you could also explain what triple dip La Ninas are as well?
Yeah. So El Nino and La Nina do behave differently. In one way of looking at it, you can think of the warmer than average water that is required for an El Nino. That takes time to develop. So the ocean charges up with that. And during that time, which can take a few years, we will have neutral or La Nina events. And so, in fact, La Nina more often than not occurs multiple years in a row. So there's some debate about which of us came up with the double dip and the triple dip La Nina, but we've seen several of those. They tend not to be as strong. So with El Nino, I don't believe we don't have more than 2 years in a row. And when we have 2 El Nino years in a row, one of them is usually very weak, like 2014, 2015 sometimes barely qualifies as an El Nino, and then 2015-16 was quite strong. So the very short answer to your question is not really. And the longer answer I just gave.
Awesome, thank you. I have personally not heard the term triple dip La Nina, so I just learned a lot from that, so thank you. Another question from Sydney. With climate change, will El Ninos become more frequent, stronger, or both?
Yeah, another thing I didn't talk about, but I'm very happy to. So we don't know. The short answer is we don't know. As I mentioned, so we've seen warming trends almost everywhere around the world. But the tropical Pacific has not exhibited a strong warming trend over the last 40 plus years. And so I mentioned that because, of course, El Nino, La Nina, they occur in the tropical Pacific. So the question is that are we just waiting to see that warmer area? Or, I mean, is 40, 45 years, is it likely that something else is at work there that means that maybe that region won't experience a warming trend? So from that perspective, we're really not sure. There's might be some evidence that the variability, so the swings between El Nino and La Nina, are increasing and will continue to increase with climate change. That is also a very active area of study. We do have pretty confident outlooks that the impacts of El Nino will change. Again, we're not completely sure how, but you've got your whole warmer atmosphere holds more moisture, so the rain impacts could become more intense with climate change. But this is actually a topic that I spend a lot of time researching, so I'm grateful for that question.
Awesome, thank you. Yeah, it just shows how important it is for all of us to, call our representatives to get some of that federal funding to keep researching this. I was wondering if you wanted to maybe take a minute or two to talk about how, ENSO, research and funding has maybe changed a little bit with kind of evolving political climate and things like that, if you want to.
So one thing I would really like to underline is the importance of the monitoring. I mean, my joke is that I wish I'd built a time machine, and so we had 5,000 years of good monitoring, but we do have 75 years of good monitoring. But if we discontinue that, and there have been some efforts to change and diminish the monitoring that we do, particularly in the tropical Pacific, that is very critical. If we can't reliably understand what is happening in the tropical Pacific, if we have to go back to boats with buckets, we won't be able to forecast El Nino as effectively as we can, and we won't be able to anticipate those impacts. The mosquito outbreaks that occur in rain-sensitive regions, the droughts that occur in drought-sensitive regions, all kinds of things. Even the financial markets respond to the ENSO forecast. So, yeah, I would really like to say, and monitoring and observations, they're not a particularly exciting or catchy kind of subject, but they are critically important. Forecast is only as good as the data that goes into it. So yeah, if you want to talk to your representatives about that. If you have any questions, please, you can drop me an email anytime, whoever you are, and I would be happy to give you any pointers you want.
Awesome. Thank you so much. I think I actually did find one more question if you'd like to do one more. This is actually during Flavio's talk, and we didn't get to this question. This is a question from Hannah, a big teleconnection question. Is ENSO teleconnection / Rossby wave part of what's disrupting the polar vortex?
Ooh. Mm-hmm. So yeah, that's their short answer. It depends on which polar vortex you're asking about. If you're asking about what is occasionally called the polar vortex, the cold, we had a cold winter here in the east, just like Flavio was talking about. Yes, there are, that is a La Nina sort of impact that is entangled in a whole lot of other things that are happening. But yes, those Rossby wave trains that set up during La Nina and El Nino, they're different from each other, but they do contribute to those shifts in the jet stream that can cause the cold air outbreaks.
Awesome. Thank you so much. I thought that was a really, really fun question.
Yeah, me too.
We ran out of time earlier, so thank you for answering that.
Yeah.
And then we all wanted to thank you here at the live stream, as well as everyone in the chat, so much for your amazing talk. Everyone really loved it and had a lot of fun talking about it. You could even
thank you.
Go through the comments, and people were renaming Super El Nino to other fun things and trying to see how many adjectives they could put before it. So I would definitely encourage you to look at that. I was definitely laughing reading those. So
yeah, I love that.
But yes, thank you so much again for your time and for sharing your science.
All right. Thank you so much, Mackenzie.
Yeah.
Bye-bye.
Bye. All right, everyone. As we're wrapping up the 48th hour of the live stream, we're getting into the final stretch, which is really, really exciting. So it's now time for me to kind of pass on my hosting duties over to Jonah, who's one of the organizers. Welcome, Jonah. And are you ready? Start hour 49?
I am so pumped. There have been so many wonderful talks, especially in the last few hours. Hearing about El Nino, hearing about the snowpack, the AGU panel was so wonderful. But we have some great things in store. Mackenzie, thank you so much for being such a great host during the last few hours. It has been a pleasure to watch. Lots of amazing comments happening out there. But yes. Okay. Hi, chat. Hi, everyone. Thank you for tuning in. We are coming into the final hours of the live stream. And I just want to thank you folks who've been, whether you're just tuning in now or you've been tuning in for a long time throughout the stream. It's so wonderful to have you here with us to cap off this amazing event. We have a lot of stuff coming up in the next few hours. We're going to be, for those who might not know, we have part of the event this year is a walk from New York City to Washington, D.C. to Capitol Hill. And we're going to get an update on that, especially our main walker, Syl Foisy. So we're going to be, stay tuned for that. But before that, we have some wonderful talks coming up. And before that, I just want to stop and remind us all why we're here, why we're together, why we're doing this, why we're talking for 49 hours or 50 hours. And that is because we all care about maintaining weather and climate science here, U.S. federally funded weather and climate science. This is something that we all care about and use in our lives. We want to know, is it going to rain tomorrow? We want to know, where are the coastlines going to be in 50 years, if we're trying to figure out where to live and how to set up our communities. And without good weather and climate information, it's hard to do that work. Luckily, we have this wonderful community of people that you've been seeing who, going back decades, the first numerical weather predictions were done here thanks to U.S. federal funding. The first climate modeling on all sides of this field. This has been sort of the height of this sort of work has been happening here. And now many of those things are under threat. And like last year, there's the fear the administration is asking for these large cuts to the budget for many agencies, including NSF, NASA, and completely eliminating NOAA's research arm. There's the specific threat of the National Center for Atmospheric Research, which probably you've been hearing over and over again in the talks, how many ways NCAR helps us as a community do the work to help you be safe and help you flourish in the world. And so we really want to get protection for NCAR, because it's clear that it's not just enough to fund these places. The administration is looking for reasons and ways to cut things on political grounds. And that is this third thing that we're here about, which is these proposed rule changes from the Office of Management and Budget that would move away from merit-based, peer review-based dispersal of funds and move towards a model where a political appointee is choosing things based on what's the agenda of the administration. And so we're already seeing bad consequences from some of the cuts, poor tornado forecasts, among others. This is the time to act. This week, representatives are working on appropriations for next year, but also they know the importance of NCAR. They know the danger of these OMB rules, but they need to know that their constituents want them to do this work, want them to stick their neck out to push for this, because this is a time with, it feels like there's so much happening. Please just know this is a really an important issue. That's why we're all here. So with that all said, I'm really excited to turn to our next talk. We have June 1st was the beginning of Atlantic hurricane season, and we have a fantastic scientist here, Professor Kim Wood. Professor Wood is the Associate Professor in Hydrology and Atmospheric Sciences at the University of Arizona, and they are going to be talking to us today about the upcoming hurricane season. Kim, thank you so much for being here.
Thank you so much for having me. I honestly was floored when I got the invitation, and I am just really, really thrilled to be able to speak to not just the data provided and all the behind-the-scenes efforts to offer these incredible monitoring resources, but also tools that are developed by NOAA and others to let us do what we do as scientists. So here I have a snapshot from September 2020. I know that feels like forever ago, but that was a ridiculous hurricane season where in this one snapshot, we have multiple active tropical cyclones, including 2 that were named practically within hours of each other during one of the most active periods on record in the North Atlantic Basin. And we're able to see this in real time thanks to NOAA monitoring systems in space, such as the GOES series, as well as all the partnerships that make that kind of satellite technology possible, as well as getting it to us within minutes of it being observed from outer space. Now, one of the things I really want to highlight here is there are so many different providers within and beyond NOAA connected to NOAA. They are federal in nature that make this possible, including NCAR, as Jonah just talked about. So the Geoscience Data Exchange enables all kinds of access to taxpayer-funded data sets, these rich resources that enable so much of the work that we do, both in researching what has happened in the past, in driving the models that help us predict the future, and in seeing what's happening right now. Also, the analysis tools. I know this is like a ton of stuff all on one screen, but what's wild is this is far from a comprehensive list. Also, little shout out to ArgoPy, because I hear Argo's kind of popular around here, but that's a Python package that allows you to immediately interface with Argo data. And I'm actually going to show a couple images later on that I made today looking at observations from these amazing Argo floats. But again, this is just a snapshot of the available tools and the communities behind them. So all of these logos have all kinds of people invisible that contributed to these packages being possible and continuing to advance as our capabilities advance, both in computing and in knowing what we need to do with our data. So all of these things are related to this concept of open science. That's something that's been pushed by NASA and others, such that when our taxpayer funds contribute to these things being possible, they actually become open. They're available. They're accessible. We can reproduce what other people have found because we can access the same data they did. We can use the same tools that they did because of the nature of the ecosystem of open science. And so a lot of what I'm going to talk about today, rather than being kind of a research focus, is going to be highlighting what's possible when you have these open source tools available and these readily accessible data sets that are funded through congressional appropriations. So I'm here to talk about specifically the Atlantic hurricane season, but I want to give some context. Emily before this did such a great job. I'm so happy and honestly a little imposter syndrome to follow on from such a great presentation. But I really wanted to give some context, because without the context, are you going to know what it is I'm talking about? I don't want to assume everybody sitting here is also a hurricane expert. So I will also never pass up a chance to use a dropout GIF. So in general, when we're talking about tropical cyclones, that's the generic term for a tropical depression, tropical storm, hurricane, typhoon. A lot of these names depend on which tropical basin we're in. So this is a map showing our tropical regions, and where you see any sort of colored pixel like this, that highlights an area where tropical cyclones have formed in the past, at least from 1990 through 2024, so a 35-year period. When we're talking about the North Atlantic and the Eastern Central North Pacific, that at least the Eastern Pacific and the North Atlantic are under the purview of the National Hurricane Center. Then the Central Pacific Hurricane Center monitors the Central Pacific. And then when you get over to other basins, the agency that uses the same approach that the National Hurricane Center does, that Saffir-Simpson Hurricane Wind Scale, the 1 minute maximum sustained winds to categorize what a TC is, that would be the Joint Typhoon Warning Center, which is under the military. Different basins have their own WMO, World Meteorological Organization, designated centers for advisories. But if you're trying to study the nature of these systems and want a consistent approach to categorizing them, these are the places that use the same categorization system. So we see that in contrast to the East North Pacific, where everything forms really, really close together, as the darker the colors get, that implies more TCs are forming in those areas over that time frame. It's much more spread out in the Atlantic. And there's a lot of land that is in close proximity to where these storms form. So these seasonal outlooks are important for looking way ahead of time. What kinds of things should places be concerned about, whether it's city planning, whether it's emergency management, all of these different elements that depend on understanding what could be coming. Like Emily was talking about with respect to even the financial sector paying attention to ENSO forecasts, hurricane activity is one of the reasons that they do, because depending on the nature of an ENSO event, that can affect how many TCs form and where they end up going once they do. Something I'm going to refer to here, and you may have heard it referred to elsewhere when talking about the Atlantic Basin, is the MDR, which is the main development region, which is between 85 and 20 west and 10 and 20 degrees north. And that's where many tropical cyclones form, though as you can see from this map, that's not exclusively the area where they develop. One area that is of great interest to anybody who may live along this coast would be the Gulf of Mexico, especially the western Gulf of Mexico, where if a storm were to form in this area, it's likely to hit land and possibly with not a lot of lead time. Once they form, though, they aren't confined to those little boxes. They could go anywhere. And this is a little bit of a tough map to read because it's so many years, you can barely see many of the islands. So if we cut it down to a 30-year time frame, it's still actually pretty messy because we get a lot of tracks, we get a lot of long distance motion, so storms can stick around a while in the North Atlantic. And if they end up recurving, they can impact the North Atlantic, these higher latitudes that rarely get this type of storm, whether it be the eastern part of Canada or even potentially reaching Europe, usually as extratropical cyclones because they've gone through a process called extratropical transition. So the circulation patterns that set up, such as the high pressure system out here, as well as where the jet stream is located, those things are affected, as Emily discussed, by what ENSO phase we're in and how ENSO is transitioning. As far as the timing throughout the hurricane season, yes, hurricane season technically started on June 1st, but you may have noticed there's no storms out there. That's because June 1st through November 30th outlines the typical dates in which tropical cyclones form. That said, this chart highlights that most of the activity tends to be confined into a shorter time frame, usually early to mid-August through mid to later in October. So this green shading is highlighting when most of the activity takes place. The lines here are showing accumulated cyclone energy counted up throughout the season. And so if a season's really active, especially earlier on, then you'll see higher values at those earlier dates. And then as the season progresses, if there's kind of a lull, that's where you'd see more of a flat line because there's been no additional ACE to accumulate in this kind of diagram. So on average, we see this more steeper slope happening here in this kind of peak part of the hurricane season, but the lines show that we can get them throughout the June 1st through November 30th timeframe, and even sometimes a little ahead of June 1st, what we would call early season type of activity. ACE is a metric that's often used to help capture seasonal elements of just how active has a basin been, because it's computed by squaring every 6 hours estimated wind speed. So if a storm is stronger, that will be a higher value, or if it sticks around longer, it will generate a higher value. So it kind of helps capture more than just how many TCs were there, but how long did they stick around and how strong did they get. Note that this map I showed earlier was all the months, so June through November. But if we look at June, we just don't have as much activity, kind of shown on that previous graph where there were pretty low values early on in the season. And so that main development region, not so much is happening this time of year. If we do get a tropical cyclone, it tends to form relatively close to North America, particularly in the Gulf of Mexico or potentially off the Atlantic coast. So a lot of the time, if a storm does form this time of year, it has a relatively high chance to impact a populated area due to the location in which it develops. In comparison, if we jump ahead to September, which is one of the peak months, as I mentioned before, you'll see a pattern of tracks that looks a lot like all the months put together, because that's when you tend to see a lot of the TCs. And once they develop, if they are in this main development region, they likely came from a seed disturbance, an African easterly wave from Africa here. And so that's why you see a lot of tracks starting or moving westward away from that region. And then some of them will end up making landfall somewhere in North America, or they will recurve and stay out at sea, sometimes referred to as a fish storm. Though the fish probably don't appreciate all the winds if they hang out close to the surface, and ships definitely don't like those winds either. So where does a TC come from? There are 6 quote unquote ingredients that we often consider when we're thinking about, is this thing out there possibly going to turn into a tropical cyclone? And one of the big things that we look for is how warm is the water. The warmer the ocean water is, especially if it's a deep layer of warm water, the more energy is available to a tropical cyclone, because latent heat release is what's contributing to a tropical cyclone forming. So you get all that energy from the rich, moist air that's nice and warm, that's come from the close to the surface, and then it has all that energy and releases it as it rises through the troposphere, and that contributes to tropical cyclones being able to do what they do, since they're powered by thunderstorms. We also need some humidity, because if you get a billowing thunderstorm and it runs into a bunch of dry air, it's not going to stick around very long. So if that air that the warm water is next to is nice and juicy, so to speak, then the clouds that form can persist for longer and get more intense through there being plenty of humidity in that atmosphere. Also, low vertical wind shear, so that's not much of a change in winds with height, both speed and direction. So if the winds aren't changing a lot as you ascend through the troposphere, that's referred to as low vertical wind shear. That enables the towering thunderstorms that develop to go straight up, so they're more efficient, traveling a shorter path to bring their energy through the troposphere, and thus contributing more of that energy to the storm itself. That air has to rise, because the energy from the ocean, the air at the ocean surface, has to propagate through the atmosphere to release that energy in a way that a TC can use. And since these are large rotating systems, as we gain distance from the equator, we have increasing Coriolis, so that background planetary vorticity spin, and that you'll notice here with these tracks that there's really not much happening in those near equatorial regions, and that's because there isn't enough background vorticity for a tropical cyclone to develop. And finally, we need a starting point. These don't just randomly generate out in the atmosphere. There needs to be some sort of source disturbance, such as an African easterly wave coming out of the West African monsoon, to start up a tropical cyclone. Something I want to highlight here is you could have all 6 of these ingredients present and a TC still might not form. So we often refer to this as necessary but not sufficient. And when we think about it from the big picture, like the seasonal outlook perspective, what we're looking for is, what are these ingredients that could be in place throughout much of the season, and are they in place in ways that tend to support tropical cyclone development or hinder it? So let's tie it back to El Nino. Emily touched on this a little bit, but I want to dive into a few more details related to it and bring it back to these 6 ingredients that we just talked about. So which ENSO phase we're in, by affecting the nature of the Walker circulation, affects what kinds of ingredients are present. So when we're in an El Nino, with this shift in the Walker circulation as shown through my favorite NOAA climate graphics. Oh, I missed that site. The rising branch of the Pacific Walker circulation has shifted over to be closer to where Eastern Pacific tropical cyclones tend to form and develop, and intensify, I should say. So there's this enhancement along the equator of, there's more warmth because we have higher than normal SSTs. We have more convection, which leads to more precipitation. And then in this region, there will be an increase in TC activity through more moisture lots of warm water, and a reduction in vertical wind shear, as well as more support for rising motion that will offer that instability that supports deep convection in a TC. When we hop over to the Atlantic side, though, we get the opposite. So over here, the Walker circulation having shifted now means there's sinking air, where before there would have been rising air. So sinking air works against the deep convection associated with TCs and can limit the formation of storms, as well as what they can do once they, if they are able to develop. Also, there's an increase in vertical wind shear and an increase in trade winds. So typically, the influence of El Nino in the Atlantic, specifically on hurricane activity, is through modulation of these ingredients, the shear and the rising air, in ways that tend to be detrimental to TC activity, but also these stronger trade winds. Not only are they enhancing the vertical wind shear, but they're also speeding up the motion of these seed disturbances, and they tend to struggle to spin up if they're moving too fast, because they aren't able to really coalesce in a way that would enable them to take advantage of latent heat release in a way that would let them develop. So when we compare activity in El Nino years versus La Nina years, these are years categorized using the relative oceanic Nino index that Emily talked about previously and may have been talked about elsewhere in the live stream, but I haven't been able to be on the whole time, sorry. And so we see that there's 137 TCs across 18 El Nino years between 1970 and 2025, but 222 in the same number of years during that same time frame. So both these represent 18 years of either El Nino or La Nina. And so that's an average of 7.6 per year versus an average of 12.3 per year. Now, you may notice that these numbers are both kind of low compared to what you get if you look at the averages from NOAA for what a typical hurricane season looks like. That's in part because we've been in a more active period since 1995, and so more recent hurricane seasons just tend to have more TCs than seasons much earlier, such as in the 1970s and 1980s. So yeah, let's get into the hurricane season outlook here. What did NOAA say when they released their first check on what they think is likely to happen this upcoming year? So they're looking at a more than 50% chance that will be below normal. So for context, the average is 14 named storms, so that's reaching tropical storm strength at minimum, 7 hurricanes, so that's reaching at least 75 miles an hour, and then 3 major hurricanes, which is reaching 115 miles an hour. I always think about it in knots, which is 100. And so the numbers that they're calling for are up to, definitely below to up to that average for named storms, below to not quite the average for hurricanes, and then below to maybe the average for major hurricanes. And it's a little complicated, as it tends to be these days, because there are these competing factors. So emphasis mine here regarding the competition involved. So if we think back to those ingredients that I talked about, one of the competing factors is that the ocean's expected to be warm. So even if El Nino ends up imposing this increased wind shear, this increased stability, if the water's warm enough, that might counteract that on a day-to-day basis when a given disturbance is in place. And something else I thought was interesting in this discussion is that they mentioned that the trade winds will likely be weaker than average. So recall that a typical El Nino influence is to intensify those trade winds, but that might not be the case this particular year because of other factors that are at play that affect what the trade winds are doing. And so that particular component may not be as strong as in a typical El Nino year. So whenever we think about a given upcoming season, we got to think about the flavors that are at play. Even if it is a super El Nino, there might be other things involved that affect the overall resulting TC activity in the Atlantic basin. But I wanted to do a couple of comparisons to past years where we have had a strong El Nino that is already kind of shaping up as we approach hurricane season. So the timing of the shift to El Nino can change throughout the year. Sometimes we're getting that strong signal at this point in the calendar year, sometimes it's not really kicking off until later into the summer. And so that does have some effect on how the teleconnection impacts end up playing out. So in 1997 and 2015, which were both very strong El Nino events, we had well below average activity in 97 and also below average activity in 2015. But note the timing of these storms. So in 97, there was kind of this long gap, like practically nothing, if not anything at all, in the whole month of August. And then there was a major hurricane in the form of Erica. In 2015, it was more quiet earlier in the season, but then we had this period of relatively high activity, though most of the systems ended up being on the weaker side, so tropical storm to hurricane strength. Now, something Emily already pointed out is that it only takes one. So regardless of how a given season plays out on overall activity, it only takes one storm for it to be really bad for one location. And it doesn't have to be a major hurricane. Hurricane Andrew was a Category 5 that hit South Florida, but there's also events like Danny in 97, which I believe set the rainfall record in Alabama at 3 feet. I mean, that's a lot of rain. So again, the devastation that can be wreaked by a given event doesn't necessarily have to be tied to its intensity, especially if the highest impact happens to come from heavy rainfall and the associated freshwater flooding. Now, I also wanted to point out 2023. So 2023 was an El Nino, but also a warm Atlantic, and it was a bit active. It was near normal for hurricanes and major hurricanes by those NOAA values that I mentioned, but it had 20 named storms, and a lot of them happened in short succession or even at the same time. And so this helps highlight what those competing factors can be when you have an El Nino setting up, especially a strong one, but you also have other things to consider more locally within the basin, such as warm water. So some differences, because there may be many comparisons in the coming weeks to what happened in 2023, is that the timing of El Nino is earlier this year compared to what happened in 2023. And there were already signals that there was going to be an above average active monsoon from West Africa, which is the source of those seed disturbances that often can become TCs in the North Atlantic, those African easterly waves. And then as far as the warmth in the North Atlantic, where the waters are warm matters. Right now, those waters off of Africa, extending kind of into the central tropical Atlantic, are below normal. So that could also play a role in the coming months as to what kind of season we end up getting. So I want to highlight that many factors affect which seeds become TCs and how those TCs evolve after forming. Here, I'll just go ahead and show them all at once. So there's nuances here. So what we're seeing is right now, like because the SST data just came out for May, we can compare May 2015 to May 2023 to May 2026 to kind of get a sense of what were the SST patterns like ahead of these particular seasons. The boxed areas up here are showing the North Atlantic and the East North Pacific main development regions. And then the two other boxes are highlighting the Nino 1+2 and the Nino 3.4 monitoring regions. And all of this is made possible through the efforts at NOAA and elsewhere to take these observations, to collate the data, to develop these rigorously quality controlled data sets, and then make them available to people like me to be able to look at through these open source tools. So all of the plots you see here were made by contacting a remote server, using Python tools, and making these plots. In fact, this particular plot I made about 3 hours ago, so some of it can be done very quickly. So we see here that in 2015, that the Pacific was very, very warm, both close to the equator and off of Baja California, whereas 2023, what had below normal SSTs out in that same region, but the Atlantic was quite warm. And then, so here in May 2026, we're kind of almost in between them, where we've got this warm Pacific, both along the equator and at higher latitudes, but the main development region of the North Atlantic is close to normal as opposed to being warm like 2023 was. So continued monitoring is essential so we can assess how this year will go. And for that monitoring to be maintained, we need funding to support that. Monitoring tools like these are how we diagnose what's happening. So we can drive predictions from these observations. We can explore what happened in the past with these observations, and we can see what's going on today through tools like these. And so one of the things that I've been running for a few years now is these daily updates to these charts that show what the average SSTs are in a given area, and a little inset map highlighting what the distribution of anomalies are for that particular region. So, this is, again, hot off the presses as of a few hours ago. And not only can we do this for sea surface temperature data, we can also do it with Argo data. So what this is highlighting is over the past couple days, where have there been completed Argo profiles taken? And if it's a square, it's a dashed line. If it's a circle, it's a solid line. And so this up here is highlighting what are the temperatures like in those top 120 meters. So it helps highlight the isothermal mix layer near the top, which sometimes can be rather deep. And if a tropical cyclone were to move over that, that would give it a deep reservoir of energy from which to draw from as its winds upwell water from below the surface. We can also take a look at what this is for different areas. Just like we were doing for SSTs, we can look at it for out in the tropical Atlantic, west of where our sea disturbances would come from, which is Africa. I forgot to mention earlier that this color scale is specific to that threshold we often look at for tropical cyclones. So generally speaking, if it's below 26 degrees Celsius, there's not enough energy available to help sustain those deep thunderstorms that comprise a tropical cyclone. And then over here, we've got anomalies. So we're looking at the 3.4 Nino region, which is the typical ENSO monitoring region that we use, especially for the relative ONI. And then this is that Nino 1+2 region, highlighting kind of where ENSO monitoring started in the first place, which is from fishermen noticing that the behavior of fish was changing as the temperature of the water changed off the coast of South America. And this map highlights where in the world we are for looking at what these values are doing. And so all of this, again, made possible through all of these NOAA tools. NOAA has a lot of different ways to do outlooks. If you're not familiar with the Global Tropics Hazards Outlook, it is a wonderful resource if you can get through some of the jargon. They talk about so many things, and it's updated every 2 weeks, or no, every week, to give you a heads up. This was just off the presses yesterday. And so what this is highlighting is over the upcoming couple of weeks, below average rainfall is expected out here, likely a result of the shifts in the Walker circulation associated with the developing El Nino. And then we've got enhanced rainfall out here. Again, that's that area where you get that enhanced low-level convergence, more rising motion, the warm and wet blob that was highlighted on that NOAA climate graphic shown earlier. And then they'll also point out places that are being monitored for potential tropical cyclone development, such as these two areas in the Western North Pacific look like it will be kind of active too. This suppressed activity for rainfall for the ITCZ, the Intertropical Convergence Zone, likely also indicates not a lot's going to be happening in the North Atlantic for TC activity either. The last thing I just want to briefly point out is that the East North Pacific season, which technically started May 15th, has kicked off its first tropical cyclone named Amanda as of this morning. And it's formed in an oddly westward position for this time of year. And so those abnormally warm waters could be affecting where a disturbance is able to kick off already at this point early in the season. I just want to point out a couple of other things related to NOAA, specifically the cooperative institutes, which is what you can do to look at a TC in real time because these entities exist through federal funding. So the SIMS, the Cooperative Institute for Meteorological Satellite Studies is probably one of my all-time favorite ones because I've studied tropical cyclones for my entire career, and I do it using big data sets such as satellite observations. This is if you click on an active storm, you can get a whole bunch of information such as ocean heat content, which is here shaded, and then what the shear is doing, which is here in the contours. And you get to pick and choose what's overlaid in case this kind of color scheme doesn't work for you. But it's over some ocean heat content, so there's energy available to it, and then it's in a region of relatively low shear. There's also CIRA at Colorado State University. Again, lots of real-time information as well as active research to help improve forecasts going on at places like this. And then, let's see if this works. There's also just NOAA itself. The GOES image viewer shows what's going on right now, and that's through NOAA NESDIS. And then this animation I finished running about half an hour ago, or actually half an hour before I got on here, which is straight from Amazon Web Services plus Python. I didn't download any data. I just used Python tools to make this happen. So hopefully that gave you a little bit of a sense of why we need to keep supporting NOAA and the research done through NOAA data sets and observations, because without being able to see what's going on, we won't know what's coming down the line.
Well, that was such a wonderful talk, Kim. I feel like I learned so much about hurricanes, and I learned so much about the incredible tools and resources that are available to help, make these great plots just sort of almost instantaneously, thanks to the resources provided by U.S. federal funding. And it was a very popular talk in the chat. One of our most loyal viewers is called Fish, and also sometimes called Storm. And so Fish Storm definitely caused a ripple of excitement in the chat. And of course, anything Argo related is definitely beloved out there. We have some wonderful questions for you. And our first one actually, I think, is from Fish. Early on in your talk, when you were showing the MDR, there was also a kind of a blue blob west of Mexico, where there was also, it seemed like, a lot of sources of tropical cyclones. And I was curious, what's going on, or Fish is curious, what's going on in the blue blob west of Mexico? And there.
So I don't have time to get into this because you just asked about my favorite lonely forgotten basin, the Eastern North Pacific. So the Eastern North Pacific is the region with the most dense cyclogenesis in the globe, as shown by this map. And we get, so those African easterly waves that I mentioned that can come and serve as seeds in the Atlantic basin, if they don't develop there, they can emerge into the Eastern Pacific and serve as seeds here instead. There are mesoscale convective systems that can develop during the North American monsoon that can move offshore and serve as seeds to tropical cyclones in this region. And this is also an area where the intertropical convergence zone can break down as a Rossby or Kelvin wave moves through, causing all these, you can get like a little conga line of tropical cyclones forming one after the other when a breakdown event occurs, because this particular area is got those ingredients all co-located. You got the warm water, you've got the unstable air, you've got the moisture, and often low shear. So once there's a seed disturbance available, we're far enough from the equator, it can just take off. That's where Hurricane Patricia formed in October 2015 and is the strongest hurricane that people have flown through.
Wow. That is a very helpful explanation. And I think I remember seeing, actually, now that you mention it, I like to put together time-lapse images of some satellite footage, and sometimes you see those sort of trains of cyclones in that region. So that's really helpful. And there's a kind of a follow-up question from Sydney. I'm going to ask, would a severe El Nino make a California landfalling hurricane possible? Because I noticed that you were showing that basin,
So one of the things that I'll mention here is we have there, we see these blobs. So especially in 2015 and 2026, these blobs of abnormally warm water. But the actual temperature of that water is quite cold. When it comes to a tropical cyclone, I grew up in Oregon. Going to the beach meant being cold if you got in the water. And then I first visited the Gulf of Mexico and was like, what is this? I see why hurricanes like it here. This region tends to be too cold to support TCs moving up there. That said, we can get an event like Hillary in 2023, which managed to gain quite a bit of latitude because the surrounding flow with a ridge to its east and a low pressure to its west caused there to be just the right direction for steering it to bring it right into Southern California. It didn't quite make it to Southern California as a tropical system, got real close, but it doesn't still have to be tropical to cause widespread impacts, especially in the form of rainfall. Now, when we do have warmer water extending farther north, it does tend to help storms gain more latitude and have a higher chance of making it into the southwestern North America. Hurricane Lester managed to cross Tucson, Arizona as a tropical storm, but it happened in August 1992, and we were a little distracted by Andrew in Florida and Iniki in Hawaii. So as far as would a super or severe El Nino make it more likely, it makes influence or potential impacts from whatever the form the storm has when it gets there. But a hurricane reaching this part of the world is very, very difficult, especially if it's to do it from the ocean, such as a hurricane hitting San Diego. It's happened, but it is extremely, extremely uncommon.
Well, maybe a Hollywood movie someday will tackle that one. I feel like they love destroying LA in various ways. But this was such a wonderful talk. There is one more question, but maybe you can take a look in the chat because we're going to move on to our next speaker. But Kim, that was wonderful. Let's thank Kim again. And we have another wonderful talk, also from another wonderful Kim. But I just want to take a chance to remind us why we are here. Here in hour 49, we are reaching the end of this incredible event. And there have been so many great talks, but we're here for a serious purpose. And that purpose is to work together to keep weather and climate science funding working the way it should here in the United States. You can see the incredible things we can do together as people when there is these resources. Kim being able to make those plots almost instantaneously from this fleet of Argo floats out in the different ocean basins. This is a real miracle that we've been able to put together something like this, and all of this is currently under threat. The proposed funding cuts that are in the budget this year, the administration's proposed budget for fiscal year 2027 include cutting NSF and NASA's Earth science budgets in half, completely eliminating NOAA's research arm, and perhaps most sort of sad considering what we've been seeing, slashing programs for training the next generation of young scientists. This is something that so many of the people who have been speaking have come up through the fellowships, through the undergraduate research opportunities of various sorts. So to lose these is to cut us off from having more of this sort of work in the future. Last year, we were able to push back against this and keep the funding for these programs, but it turns out that on its own is not enough. The administration is finding ways to not spend that money on the things that it is being asked to spend it on. And a most dire version of this is the National Center for Atmospheric Research, a place that was at the beginning of Kim's talk earlier, a place that is close to many of us. Many of us have gotten to spend time, is currently under threat of being dismantled. The NSF soliciting plans for people taking the MESA lab, for getting rid of all of these different components or pulling them apart. It's clear that we need to stand up for NCAR, and we need to call on our representatives to stand up for NCAR. So, and we need to stand up for the many future NCARs that might be coming down the line if these new OMB rules are put into place. OMB is proposing to make the sort of decision-making that they made around NCAR, where they said this is an institution that produces science that can be used to justify policies we don't like. Not even that to say it's advocating for policies they don't like, just to say it's producing science that can be used to justify those policies. Science should not be politicized. We should get to try to understand the world that we live in and get to share that information so we can live good lives here. And so this is something that is at risk in these new OMB rules. We ask that you please call your representatives. You can see the URL at the bottom of the screen. Let them know that we want to protect good science, and we want to protect our funding here. And with that, I want to introduce our next speaker, Kim Cobb. Kim is a professor and a climate scientist at Brown University. It's wonderful to see you, Kim. I'm so glad that you can join us here for this final talk. We're thrilled and honored that you would join us. And I'm just going to let you take it away and share what you have to say.
Great. Thanks so much. Confirm you guys can hear me. I had some audio issues before.
Absolutely. Hear you loud and clear.
Perfect. Okay, perfect. And my slides, are they now sharing as well?
Absolutely. I can see
Okay,
them.
all right.
I can see the red, white, and blue.
Awesome. Yes, that's what we're about today. We're all about red, white, and blue. So just wanted to thank the organizers for doing this incredible event for the second time. I'm honored to be back for year 2. And maybe there'll be a year 3. Maybe it won't be necessary. Who knows? But I'm really honored to be here. I just wanted to thank everybody and wish America happy birthday on this amazing summer that we're leaning into the 250th. And we have a long, enduring legacy as a leader at the forefront of science and technology in general, and specifically in climate and weather. And as much as I would love to review that entire 250-year history, and you might like to hear that, that would be a talk for another venue. This is going to be short and sweet and focus on something that is very important right now, which is El Nino and what we know about it and how we can use corals, which are the X-ray pictured here on your right, to look back in time to tell us a little bit more about the exceptional nature of today's events and how that might be linked to climate change. So that's the focus of the work that I do that I'm going to share with you. We're going to talk about some federal funding initiatives along the way. So I am a climate scientist by training, and I use past climate information or paleoclimate information to constrain future climate projections with a strong focus on El Nino, which makes today's information, I know, very salient. I was just listening to Kim Wood talk about the effect of this potential super El Nino on tropical cyclone genesis and hurricanes, very relevant and very important, but El Nino touches everything. But I wanted to start at the beginning in noting that I started as a high school researcher way back in the day in 1991, looking into distributions of copepods in salt marshes in New England. And that was part of an NSF-funded project. So that was my start in science. Going on into the mid-90s, I was a college intern in my sophomore year studying El Nino in sediment from Santa Barbara Basin. Again, NSF-funded summer research intern. Fast forward to my graduate career, which started in 1996, and 1997 was at the time the largest El Nino event on record. And I was studying that as an NSF graduate research fellow, something that is critical to the pipeline of talent in this country and something that many of my own students have relied on in past decades as well. But we're here to talk about El Nino. So this is a picture of the 1997-1998 El Nino as seen from space, a visualization of the sea surface temperatures that are elevated across the central to eastern basin and disrupt atmospheric circulation across the world. And this was the site that I was focused on studying in a cruise in 1997 that I was lucky enough to be a part of. And this event was, I would say, relatively poorly forecasted. And it just hit with a huge wallop, and we found ourselves down at the equator for 2 months during the peak of the event. Storms, all kinds of different currents, corals bleaching. It really made an impact on me, and it really drove me to think about how we could use coral archives to look into the past of El Nino's activities and understand just how exceptional an event like the 1997-1998 El Nino truly was. Turns out it was quite exceptional. We'll get back to that. But first, just to reiterate some points that many of you have no doubt heard before on this live stream, and you can't avoid them in the headlines right now. I'm really fond of saying there's almost no weather extreme that is not impacted by El Nino and its cool sibling La Nina events. And so these are some of the impacts that are most important for the United States. It has a huge impact on hydrology across the Western United States, and is increasingly tied into the kind of whiplash of vegetation boom-bust cycles that have caused some of these incredibly devastating wildfires out west. Of course, in combination with desertification and increasing temperatures across the Western US. So El Nino plus climate change ends up being oftentimes implicated in so many of these impacts. Hurricanes are something that are statistically linked to El Ninos. We're already looking at projections for a weaker than average hurricane season coming up. And of course, one of my favorite pastimes here in New England, impacted by El Nino and La Nina cycles. It was an incredible year for skiing here in New England this last winter, looking at a pretty devastating season coming up. And this is a seesaw that changes in large part with the West and the East. Of course, a devastating season out west this last year as well. So, and many other agricultural impacts, water resource impacts that I could go on and list, but I think you get the point. And one of the central questions in my research is this natural climate phenomenon becoming more extreme with climate change? And this has been the driving question of my research for the last 25 years or so since I was first on that cruise in the tropical Pacific. And you no doubt have seen some of these headlines, but I particularly like this graph of the forecast for the 2026-2027 El Nino event. This is from Jeff Baradelli, a meteorologist with a sizable climate portfolio in training and communication. So shout out to him here. If you don't follow him on BlueSky, you should do so. This is cribbed from his BlueSky account. But you can see the 2026 forecast here. This is the Central Tropical Pacific sea surface temperatures, an index that we call the Nino 3.4 index, and forecast to be somewhere potentially over 3 degrees, maybe over 2.5. Whatever it is, it very likely is going to exceed some of the projections, the historic maxes for this particular index over time. We can see many incredible events on this plot. 2015-16 was one of the last biggest events. 2023-24 is on here as well. We can go back in time. You can see 1877 here with an estimated temperature spike of 2.5 degrees Celsius. I'm not going to list all of these out, but I list them here on the left in text form, if you will, because it's important to see that the kind of the recurrence time of major El Nino events seems to be getting somewhat shorter, although we have only a handful of events to look at when we talk about it in that way, of course, because prior to 1950, and especially prior to the satellite era in the late 70s, we really have but an extremely dim view of past El Nino activities. And that's why it's so important to bring these other sources of quantitative information to bear, from corals, tree rings, ice cores, and sometimes we're going to talk about corals today. Notably, of course, the last time we had an El Nino event, we did shatter a global temperature record in 2024, and we most certainly will shatter another temperature record in 2026 or 2027, depending on how this event matures and what its peak is and how it falls in the calendar break between December and January. But I wanted to stress this point about all these events that occurred prior to 1950 that we have just very dim views of. And the further back in time we go, the dimmer these views get. And so the bulk of my work has been focused on reconstructing even into the early 20th century, but as far back as we can, centuries, in some cases millennia, to get a really great baseline of natural variability in a extreme that only occurs once every few years. And so we simply don't have the statistics to look at the climate change role without that. So this is one of my favorite portions of my job, which is going into the field to collect corals that can help us reconstruct El Niños back into the past. And this is a photo on the left from a living coral. This is the kind of a massive reef building coral that we use to reconstruct climate. They grow about 1 centimeter per year. So if you hold out your finger, that's about how fast they grow, which is very fast, much faster than trees, and a perfect archive to look for the signal of an event that only occurs for 6 to 9 months. And El Nino is here and gone in that amount of time. So really important to have an archive that is growing quickly enough to capture that. So we use the living archive on the left to push back 50 to 100 years on the living reef. And then we push into what I'll call fossil corals, although they're not like the museum fossils you grew up with, in that they have not been chemically replaced. They've just been sitting on beaches for hundreds or thousands of years, waiting for us to come drill them. And we use uranium thorium dating techniques to understand when they grew. And then we use the same kind of chemistry that we use in the modern day reefs to look at the temperature histories of El Niños and La Niñas locked into those records. So when we cut open a coral core, this is what we see. On the left, you see the actual coral core. The coral skeletal material is calcium carbonate. And then on the right, you can see the X-ray that kind of guides us down year by year. You can faintly see those coral growth bands there. And the coral lays down this calcium carbonate skeleton with oxygen, of course, as part of the carbonate. And the oxygen that is locked into the coral skeleton varies as a function of the temperature that the coral skeleton was growing in, as well as what the oxygen isotopic ratio of the seawater was, which is kind of, we can think of like salinity. So this is an archive that is exquisitely sensitive to temperature, which is critical to tracking El Niños. And it's also secondarily sensitive to salinity, which is great because we can capture some of the rainfall signals that shift so dramatically with El Niños. And it creates a powerful pile-on effect to magnify signal to noise ratios in corals so we can reconstruct El Niños and La Niñas with incredible fidelity. I'm going to show you just how well in a second. When we drill down every 1 millimeter, we're actually capturing an estimate of how this chemistry is changing every 2 or 3 weeks. That's really how quickly these corals are growing. And we can see the detailed evolution of El Niños and La Niñas as they come and go over 6 to 9 months. So this is the kind of plot that we get after many decades of work and with a mass spectrometer that can measure about 30 samples a day. So you're looking at, hundreds, if not thousands of data points on this plot here. And so the colors are coral chemical signatures that are locked into the calcium carbonate skeleton. And you can see El Niños are up and La Niñas are down in this chemistry. And what you can barely see on this plot are the gray curve of sea surface temperature at the site that's coming from satellites, of course, only available since 1980 or so. And so these are really overlapping, they're interchangeable. During this calibration period, we're seeing that the corals are accurately capturing the coming and going of even the largest El Nino events like 1997, 1998, 2015, 2016, et cetera. And so when we push this kind of archive back much further in time, we're getting the first ever view of some events that occurred in the early industrial period, in the prehistorical period. And we're going to use that baseline to look at how exceptional this recent spate of large El Niños really is. And so this is the kind of material that we work with. We go to a place like this is Christmas Island, smack dab in the middle of the Pacific Ocean, right in the center of action for El Nino. And we'll take some corals, pick them up like this. These are much smaller than the one I showed you before. These will contain 10, 15, 20 years of material, let it go. But we've been playing this game for a long time. So we've amassed about 2,000 years of pre-industrial El Nino estimates from the corals that we've been working with from these ENSO El Nino hotspots. So after 20 years of working at this island in the middle of the Pacific Ocean, we actually have found that when measured against this long pre-industrial baseline, the last several decades of El Nino activity are in fact stronger than that pre-industrial average by about 30%. So that's a significant shift that we see. And that's not really because they're getting more frequent. They're actually, we know they're getting stronger on average. So that's what the metric that we're using is telling us. The 2015-2016 El Nino was a part of this bucket of recent decades activity, if you will. And we're looking forward to extending this record into the 2023-24 El Nino. And then in a year or so, we'll be back to Christmas Island to try to recover the last increment of coral growth that might capture this event. But there is a ripple in our archive here that has to do with the effects of El Niños on coral warming themselves. And so this, I wanted to just step back a minute and recognize that, well, corals are amazing recorders of El Nino and La Nina activity. They're also subject to huge, large-scale coral bleaching and mortality related to El Nino-related ocean warming at the surface, in this case at Christmas Island, combined with that ever-warming baseline of temperatures that are creeping up in the tropics decade by decade. And so on the left, you're seeing the reef in 2014, which was in incredible shape. This is one of the most remote reefs in the world, untouched by many of the other impacts that many other reefs have experienced, for example, in the Caribbean. And in 2016, you can see after the 2015-16 El Nino, just a devastated reef. All of that coral has been killed, 95% mortality or so at the site. And that's just kind of blue, brown, red algae wafting around on this graveyard of corals. The corals have been recovering since. They're, of course, very small size cohorts right now with so little time elapsed. It would take the reef 30 to 50 years to recover to the picture that you see on the left there. But obviously, we're facing a devastating bleaching prognosis for this winter. And, I'm not the coral ecologist of the group. My collaborator, Julia Baum at University of Victoria, will be out there surveying these reefs again. But this is not just something to be concerned about in the center of action for El Niños, because the last El Nino that we had really was a global scale coral bleaching and mortality event that was documented across every tropical reef in the world. So this is something that many coral researchers have our eyes on right now, extremely concerning for the function and ecology of the ocean system as a whole, with reefs playing such an important role there. Of course, that has implications for people who rely on the ocean for food, not just us, but subsistence people who live across the tropical belt, relying on that food source, tourism, of course, other economic assets tied up with El Niños and the impacts on corals. So that's an important point. But it's not just corals. This event will touch, of course, weather and climate extremes all over the world. And in particular, one of the things that I'm very focused on right now is the public health impacts of this kind of event on Pacific islands. And so on the island that I've been working on for many decades, Christmas Island, working with their governmental agencies to try to figure out what happened in 2015 and 2016 with respect to vector-borne illness, waterborne illness. I myself was a victim of vector-borne illness on the island during 2015-16. So I know that this is a thing, as was my student. So this is a major impact. And so these are not really communities that can benefit from the kind of early warning systems and operational pivots that many of the more wealthy nations and communities can, even when equipped with a strong forecast like this. So trying to think about how we can translate this kind of information using past events as precedent. What can we do to help lift up some of these concerns with the lead time that we have, which is pretty staggering in this case. And then, of course, also in my backyard here in New England, we're very, very far from El Nino, but we know that we will be suffering from its impacts this winter in the form of, statistically speaking, warmer conditions and drier conditions across New England. So that will have ecological impact, agricultural impacts, as well as discrete economic impacts, especially on wintertime economies. So these are things that I'm actively working on and thinking about the impact side of the equation. But I wanted to focus on how we have this great forecast today that is equipping us with such incredible lead time. And no matter how strong this event gets, it seems almost virtually certain that we will have an El Nino event of some kind by fall, and it will be a sizable one, whether it's moderate, strong, very strong, or super. How do we know that? So we know that because we have an array of buoys across the tropical Pacific belt called the Toga Tau array. And this has been in place since the 1990s. And it allows us to put our finger on the pulse of this climate cycle. And every single 5 days, we are digesting this full data stream. These are the buoys that are moored across this array. You can see a schematic here on the left. This is, by the way, an amazing paper by Mike McFadden in Oceanography in 2023. If you're interested in more of the history and how it works and what we've learned, I direct you to that amazing paper, extremely accessible. This is an image from that paper. So you can see that these are moored to the bottom of the ocean, which is very deep in that region of the world, and at all times transmitting incredibly important information in real time back to scientists at NOAA regarding temperature, wind speeds, which are the most important variables here. And the array extends down below the surface of the ocean. I'm going to tell you why that's important in a minute. Well, this seems expensive. Why can't we just use satellites? Well, we actually need to get a finger on the pulse of the subsurface of the Pacific Ocean, because that's where the heat shifts are most predictive. That's where we understand the physics extremely well in order to give us this amazing lead time that we have on a forecast like this. So thanks to the Toga Tau array and this real-time stream of buoys that does so much better than satellites at helping us to forecast events and dissect the physics of events that have occurred in the past. Thanks to this array and its long decades of data that have been maintained with strong advocacy from the scientific community, this array has been under threat for several administrations now. And so it's really the scientists who've continually said this is one of the most valuable pieces of our ocean infrastructure in the world. And it is the way that communities all across the world are able to rely on these forecasts. So that's an incredible asset to this forecast. Why do we need the subsurface? We need the subsurface, as illustrated here, because this is a cut through the tropical Pacific now, a vertical slice. And this was from April, just a couple months ago. And you can see these warm colors there spiking into the brown. These are temperature differences that are up to 6 degrees warmer than average at that location. And they look like that diagonal cut because this is actually a propagating wave in the subsurface of the tropical Pacific called a Kelvin wave, which is the most important predecessor of a fully mature El Nino event several months later. And so when this wave fully matures and arrives to the Eastern Pacific, it will start to perturb the atmosphere, winds will start to shift, and that will further this destabilization in the Eastern Pacific. And we're off to the races in a feedback loop that we've seen many, many times because we have subsurface information streaming at us from the tropical Pacific for this to capture this kind of wave activity. So this is a great blog here from severeweather.eu where I grabbed this image which illustrates and discusses this Kelvin wave that was happening at the time. Okay, so to sum this portion of the talk up, and I'd love to take your questions. This array has been in place since the 1990s. It's an amazing asset for forecasting. So this is exclusively funded by NOAA. This is your tax dollars at work. This is one of the most important inputs into what we call seasonal forecasting in climate science. This kind of forecast allows us to take the pulse of El Niños and La Niñas, one of the most critical drivers of seasonal differences that we experience year to year, one winter versus the other winter. What's it going to look like? This is where this information is most critically coming from. And so this gives us about 3 to 6 months. Now we're almost, we've been talking about this for a while, almost 9 months, perhaps you might say, to look into how it's going to tip the scales on a whole range of impacts here in the United States. So these impacts, this information, this lead time really helps us think about how information is leveraged for agricultural planting seasons, water resource management, critical infrastructure management, public health campaigns. This saves lives in terms of extreme weather forecasts, for example, with the hurricane season dynamics, and saves a huge amount of money in losses and damages that we can avoid. So this is an incredible investment with a huge return on it. So these investments across the board, whether it's the ocean observing systems that are currently under threat in the North Atlantic, the Atlantic Ocean, Eastern Atlantic and the Pacific Ocean that have been discussed in the news lately, or this array that I'm talking about, or the vast array of satellites that's up there giving us streaming information back to us about greenhouse gases, weather patterns, water vapor, wind speeds, ocean chlorophyll, you name it. These observing systems are critical for our public health and safety. They are critical for protecting critical infrastructure, including water resources, the grid management and resilience. It's critical for economic prosperity with so much of our economy tied up in coastal economies and agriculture and other kinds of all kinds of tourism applications, and it's very critical for our national security. We think about this with respect to our homeland, but we also think about this with respect to the many geopolitical risks that we face in a warmer world characterized by greater and greater extremes. So these are the lenses that I take in trying to communicate the urgency of maintaining our supremacy in weather and climate and maintaining the observing systems most critically that the entire world depends on. This is a team sport. Nobody can go this alone, and we have played and continue to play a critical role in maintaining that kind of infrastructure and that talented workforce that has basically leveraged all of these incredible data sets into products and forecasts that are driving these skills. So I just wanted to end with a shout out to my lab members, past, present, and future, wherever you are, to acknowledge the role that federal science funding has played in supporting this group of people to do the amazing work that they do. They are often to jobs in the government, in industry, in academia, all over the world. They inspire me, and they are incredibly skilled thanks to the access to data streams we've talked about today, and thanks to federal science funding, which has in many cases supported them in their training. So with that, I will end it there. Thanks.
Thank you so much, Kim. That was a wonderful talk. So great to see all of these connections being made across the corals to paleoclimate to the conditions that
Hello?
we're facing today. Oh, can people hear me okay? Oh dear.
Okay, I can hear you now.
Now you can hear me?
I'm
Okay.
kind of, yes, I can. Maybe I could stop
Okay.
sharing here.
Okay, well, it's great. Yeah, well, that was a wonderful talk. I was just saying it's incredible to see all these connections made between corals and the deep past and what we're facing today, and to see how federally funded science is helping you make all of those connections and helping us to understand the world that we're in. It was a wonderful talk. So thank you for that, Kim. Do you have a moment to take some questions from?
Yes, sure.
We have some great questions from the chat. You mentioned about some of the risks that coral are facing, and we saw that devastating picture of the effects on the coral. One of our viewers is asking, does ocean acidification and coral bleaching impact this ability to do reconstructions, this ability to compare what we're seeing now to what might have existed in the past?
Absolutely. So when the corals bleach and when they die, of course, they stop building their skeletons. And so that's not an archive that we can rely on to be continuous going into the future. And so when we have this wholesale loss of the corals, for example, at Christmas Island, it will be very, very hard, if not impossible, to find a coral that continues through the 2015, 2016 event. And so we kind of pieced it together because we were in the field many, many, many times during that event. And so we were able to find some of the small corals that survived and be able to piece together that event. But going forward, this archive and this way of looking into the past will have a hard time finding this kind of modern analog or calibration window to exist. Thankfully, federally funded science has enabled many researchers to recover long cores from many of these very remote and incredibly important places for climate science. And so the archive that, for example, I have amassed is archived with the federal officials, and anybody who would like to work on that material going forward will have access to it because it simply won't exist at these sites in coming decades. Great question.
Wow, that's a great question. And we have another question here from Fish. Are there any specific types of corals that are more useful for this type of research?
Yeah, so we really rely on the ones that grow in the most boring way. So they grow about a centimeter like a blob in all directions. And so, we think of corals, we think of diversity of shapes and colors and all kinds of things on the reef. And the picture that I showed you had a huge diversity of corals in that healthy reef photo. But in fact, it's very hard to predict whether corals grow up, out, sideways when they are very complex shapes. And the more boring for us, the better, because when we drill from the top straight down, we know that we're drilling straight through time. And we can see those bands laid down like a tree ring that helps us know that we're locked into the time axis of growth there. So that's almost exclusively what you'll see employed in coral paleoclimate work like the work I showed today.
Wonderful. And I'm going to ask maybe one more question from here. How much of your research involves doing work out in the field, collecting data, versus more kind of analysis or working on preparing manuscripts, writing, et cetera?
Yeah, so I like to show my pretty pictures to all the recruits that I'm trying to bring into the lab, but that's a vanishingly small part of the work that we do. Most of the work is lab-based work. So we run a variety of different instruments in service to these reconstructions. It takes an incredibly long time to make the measurements that we're making. We also need to work on the dating the material, right, which is a whole other very labor-intensive component of the work. So I would say the most of it is lab work, but definitely the second largest portion of time is data analysis. So as I showed you, we're working constantly with instrumental records of temperature, climate model output, all kinds of gridded data from all over the world. And so we're analyzing that for relationships to El Niños, La Niñas. We're looking at how well models perform with respect to observations. We're looking at how we can bring together multiple paleoclimate records into a single robust reconstruction of El Niño. So that's a statistical exercise there. So a lot of this is kind of, large scale data analysis that we grind forward in coding platforms like my colleagues in the dynamic weather and dynamics fields.
It really seems like you're covering all aspects of this pipeline of information going from the field all the way out through all of this analysis. It's
we try our best.
Try our best. Do you have time for one last question?
Yes,
maybe?
absolutely, Jonah. Of course, yes.
I just personally want to know, do you personally have a favorite coral? I'm just curious, in your experience going out in the field and seeing, if I could use host prerogative for a second to ask.
Yeah, that's a great question. Never been asked that question. I think my favorite coral was the first paper that I ever published and the first coral that I had the privilege of working with. And that's what it is. It's an immense privilege to work with this one-of-a-kind, priceless, irreplaceable material at this point. And the coral that I had the privilege of working on as a graduate student and publishing for my first paper in 2001 was a 3-meter tall monster coral. That's 10 feet for those of you who work in US metrics, but this was a monster coral growing on the reef at the time. And we were very, very lucky to recover it in 1998 at the tail end of that El Nino event, because the next time we went back in 2000, it was gone. So it had probably toppled over and been washed away by the currents. And so that is the longest record from that entire region that was ever recovered. And when you look at its growth, I mean, this is where we get into flowery language that, just tells you how nerdy I am. Just the fabric of its growth was so regular and so beautiful and so vertically oriented and like open fabric. And it's just inviting you to reconstruct its coral chemistry for climate reconstruction. It was just incredibly beautiful specimen. I just got really lucky in that as well. So I'll never forget that coral and the gift that it gave me as a young researcher and falling in love with this whole business. And here I am, but also to the world and giving us our first glimpse of what climate looked like in 1886 when that coral was born.
Well, I really appreciate the gift of you coming and sharing that story with us and all of your work with us. This was a wonderful way to have our final talk of the live stream. Thank you so much, Kim. And chat,
thank you for doing this. Thanks everybody for watching too. Bye.
Well, folks, we are in the final hour, and that was a great way to close out our regularly scheduled programming. But we have please stick around because we now have something special to close with. We're going to talk about the culmination of the entire stream, including Syl's epic walk, 250 miles, all the way from Central Park to Capitol Hill. But before we do that, we're going to do one last call sign. One last collective effort to try to get Congress to act to protect weather and climate science. By now, you have heard from speaker after speaker, over 100 speakers, showing you the incredible work that they're able to do because of the tax dollars that the U.S. public has given to weather and climate science, the amazing agencies and NOAA and NSF and NASA and all of these different wonderful organizations and groups, and this culture, this whole methodology of having peer-reviewed granting of scientific awards so that people can go and find new information, make data available that then someone can go and instantaneously use to prepare these wonderful visualizations, this wonderful analysis, this way that we can understand the world that we're in and the world that's to come. And as we've been saying all along, this is under threat, not just the threat that we had last year that this funding could be taken away, but that even these agencies that were set up to serve the public, to help the public to get the information it needs about the world it lives in, that these agencies might start to control how this money is being spent, not in the spirit that it was intended to be spent. Coming in and saying, we don't like that this science can be used to justify policies that we don't agree with, and therefore we're going to pull the funding. So we are urging, if you haven't called yet, to please call your representatives and tell them that you can use that link at the bottom of the screen. Tell them to sustain funding coming into the next fiscal year for weather and climate science, to put protection for the National Center for Atmospheric Research into law so that we can keep this wonderful center that you've been hearing about all stream, and act to stop this absurd proposal from the Office of Management and Budget to politicize the process of funding scientific research and research in general in the United States. And I just want to share one little thing here, which is we're asking you to call, and that is very important. But there's another opportunity that I talked about for those who were here in the wee hours of the morning. I think it was 3 or 4 in the morning. We were talking about this opportunity to submit comments to this new rule. So there's a great write-up done by Elizabeth Genexi. You can also find write-ups from AGU and from Science, but this one I think gets across an important point, which is that anyone, you don't have to be a scientist, and you don't even have to be a citizen here in the United States. You can just be someone who's affected by this proposed rule change for the OMB. You can go, and we have a link here. This is the link that you can go to submit comments for this proposed rule change until, I think it's July 13th, 2026. If you go here and make it personal, because apparently what helps with these comments is if it's not just a form thing, if there's individual comments that specifically reference some of these sections of the proposed rule change, and I think you can find this in a number of different places, but here, these are some of the specific ideas for how to change science. If you reference those specific rule changes and talk about how you might be impacted by them, they have to respond. They have to engage with you on this, and that engagement can be used in the future to challenge these rules. So please, this is another thing that you can really do to help us to keep the wonderful sort of work you've been seeing going in the future, to keep our 3-meter coral growing. So let's keep this going. And with that, I want to turn towards the end of the stream here. It's been such a great event. I want to bring on another organizer here, Andrew Williams. Andrew.
Hey, Jonah.
How are you doing, Andrew?
I'm doing all right. I can't believe we're almost at the end.
It's unbelievable.
49 hours, 26 minutes in. We did it. Well, we're almost done. We're almost done.
There's still just a little bit left. How are you?
I feel like we started this. I feel like we should end this as we started it. And it was us two, and I feel like someone's missing right now.
Oh, yes.
Right? I don't know who. Do you remember who it was? Can the director, can you help us out here? I don't remember who. Who started the stream with us?
Who was it?
Virginia Beauty? No? Okay.
I have the script in front of me, and I know you're going to say, who is it? But you're saying, who is it? And I'm like, oh, it's me. We started it together, us three. Nice to see y'all both here at the end, 50 hours later.
Somehow we're still standing, barely.
So I have a few questions for you on behalf of everyone in the chat. I want to know the gossip. So I want to know from each of you. Andrew, we're going to start with you because I just decided to. What's your favorite thing that we've been talking about backstage as organizers, from the chat comments, from each other? What's your favorite thing that we've got going on in our chat as organizers?
I mean, I don't want to give too much away, but we do have a channel dedicated exclusively to basically the memes that the audience is making. So I don't know if Shane is watching now. Shane, you were the subject of some excellent memeage, making Lamont proud. I think that was there was some pretty solid memery there. We've got a lot of great ideas for t-shirts regarding Argo as well. So
Jonah, how about you? What's been your favorite part of our little behind the scenes chat?
I always love hearing, in addition to the memes, people share people's reactions to the event. And I think we all care a lot about the work that we do, but we don't always do the work to share it. And it's so wonderful to hear the excitement that people have around these beautiful systems and ideas that people are sharing. So I think for me, that's my favorite part.
I will just add by saying that we were ready to pivot to a pets of the live stream and commenters on YouTube section if any of the last minute speakers had dropped out. And so chat, I know you've been asking for a year 3 already. If everything is perfect for science next year, we could always just gather and share pictures of each other's pets. But I'd like to pivot now. I think, Andrew, you wanted to bring other people in. You wanted to call out some specific
I just think we're almost at the end of the 2026 stream, and I want to give it a proper send off. I think the only way to do that is really to take a few minutes to thank the people who helped us get to where we are, the people who made it possible. And the first people that we need to thank are the organizers. This event exists because of a truly incredible group of people who have been giving it everything that they had for weeks now. And their names, if we can bring them on stage, it's Ash, Berenice, Brianna, Claire, Haley, Heather, Jen, Jonah. This is going to fill up at some point. I'm still going to keep saying the names: Mark, Maria, Miriam, Paulina, Phoebe, Stella, Syl, Virginia. Oh, I think do we not have space for old Syl? Oh no, Syl's not here. Oh well, Syl will get there eventually. Yes, round of applause in the chat. Round of applause for each other. Oh, Syl has entered. Add to stage. It's a surprise, Syl. Woo! But round of applause for all of you guys, just for the incredible work you've done. Some of you guys were part of the organizing team last year and were crazy enough to come back. Again, insane. But many of you joined this year for the first time, and you brought your talent, your energy, your positivity, and you brought passion, which has just taken to this event to places we probably couldn't have imagined before starting it. And I just really want to thank you for that. And I also want to acknowledge those people who helped us last year, who for various reasons were not able to take part in the same way this year. There are so many things that you helped us with last year, and your positive influence is still being felt a year on. For example, the TV in the corner was created by someone who is an organizer last year and has become a beloved part of our messaging, our t-shirts, and our stream. And so just thank you to everyone who has been a part of this event this year and last year. These incredible volunteers have been contacting and coordinating hundreds of speakers, hosts, directors, chat moderators throughout this event to fill out the full 50 hours. And this has been no easy task. We have, as our speakers will attest to, we have a fairly complex and convoluted setup for getting you from volunteering to speaking. And some of the good people here have been really at the forefront of just moving you through this system. We've also been developing a political message that makes sense and is a clear call to action in the midst of fairly rapid developments. As Jonah was saying, it was only last week on Friday, or I think, that OMB dropped these extreme proposals. And we've also had people promoting the event tirelessly on traditional and social media. And so to all those folks who were on stage just then, I cannot thank you all enough for being willing to sacrifice your sleep, to sidelining your day jobs, being away from your friends, your family, or maybe material comforts for days on end to make this event a success. So thank you all so much. And just chat, just like, we need so much love for these guys. This has been, none of this would have happened without everyone who is just on screen. So make sure that you're giving them lots of love. Also, to our hosts and our chat moderators, I just want to say thank you for helping to build a connection between us and the audience. There are so many of you, far too many to name right now, but you know exactly who you are. And whether you were grinding through a graveyard slot at 4 a.m, or hyping up the chat before a stream reset, or improvising live on camera when things were on fire behind the scenes, you really carried this stream. And the fact that everything to the audience, if you didn't notice anything wrong, it's because things were going wrong. And the hosts and the chat moderators were just like keeping everything super smooth and professional. So thank you guys so much. To the hosts as well, I also want to thank you for standing up and speaking out so strongly for weather and climate science, for helping to get the message out, inspiring people to write letters, to call their representatives. Again, we couldn't have done this without you. Another thank you is to our speakers. I'm sure that to everyone who's been a part of this field, I'm sure that we'll all admit it's been a hard year. Our field has been under attack now for 17 months, and it's taken a toll on all of us. And so, when we put out the call for speakers, I wasn't really sure what to expect, but honestly, I was blown away when we got nothing but energy and generosity and an eagerness to share your work with the public. You guys really stepped up, and more than 140 of you shared your work over these 50 hours. And so I just, it's really touching, and I think it's a testament to the resilience of our field. Who were these 140 people? Their names were, no, I'm not gonna do that, but these 140 people, you came to us and gave talks. You were grad students, you were postdocs, research scientists, professors, professional science communicators, consultants, private sector workers, broadcast meteorologists, federal scientists, journalists, 2 presidents of the AMS, 2 presidents of the AGU, and 1 documentarian. Thank you, Annika, if you're watching. The talks you gave are truly a treasure trove, and I am sad that I didn't get to watch the full 50 hours, but I'm so happy that this stream is going to live on after the event. And it's going to be a monument to, I think, the strength, the resilience, and the joy that characterizes our field, even in moments like this where we're maybe on the back foot. To all of our speakers, I think it comes from all of us organizers when I say that you inspire all of us, and we're thankful for all the work that you do. And finally, to you, the audience, the real discovery of this whole thing this year and last year has been you guys. The people watching at home, you guys jumping into the chat, staying up with us at every hour of the day and night. People from all over the world. I think it's just been it's been really touching to see people really valuing our science and being excited about it as well. And the whole time that you were watching us, we were watching you back. And the joy that you were putting in the chat was really infectious, and I think just lifted us all up. This year was extra special because so many of you came back from the first year. We had reunions in the chat. Sage, Squid, Fish from New Zealand. Fish returned to help us with the late night slots. To those of you who don't know those names, you should have spent more time in the chat, honestly, or you'll need to come back next year. Just saying.
So rude.
And as I said, we had a little behind the scenes secret the whole time. We had this channel where we were just keeping screenshots of the kindest, funniest, most wholesome things that you guys put in the chat. And it was just bolstering the organizers behind the scenes. We had Argo floats, we had heist content, we had Bigfoot content. You had to be there. You had to be there for the Bigfoot content. We laughed a lot, and you guys turned a marathon live stream about a really serious topic into a joyful expression of what it is to love and to do science, and that was no small thing. But beyond joy, to the audience and the speakers, you also gave us organizers confidence to do something bigger than just this live stream this year. This year we took on a new challenge, a new way of trying to raise attention for these issues. And that was a group of the organizers took part in a 12-day walk from New York City to the steps of Capitol Hill in DC to draw attention to the cuts to weather and climate science. And I don't want to have any stolen valor here, because I didn't actually do the walk, but I want to hand it over to the people who did. So Virginia, Syl, if you can come back on, Miriam, if Miriam's on the chat at the moment, we'd love to just hand it over to you guys and for you guys to tell us about this amazing part of the event.
Thank you, Andrew. So I think that Miriam is working on something that will be a surprise for all of us. So chat, I'm going to talk with Syl about the walk. And so if you have questions for Syl, please put them in the chat. I will bring them in. But Syl, I just wanted to get you to describe your own thing that you did. You went on a very long walk, yes? Can you tell us? You're muted, but make sure you unmute. And can you tell us why you did it, what you did, and then we'll get to the results.
Yeah, absolutely. First of all, hello, live streams. Great to see everyone. I'm glad to be sedentary now, sitting down in a bed somewhere. I think we're in Bethesda, Maryland. Yeah, so I thought it would be a cool thing to try to get on the ground and talk to scientists in person and hear about the work they do, and try to bring some awareness to the importance of weather and climate research through some sort of like public, physical manifestation of what this stream is all about, which is calling your reps and using your voice. So incredibly, it worked. We made it today, this afternoon. There were 7 representatives there to greet us at the Capitol steps. I ended up walking 270 miles, which was a lot. And along the way, stopping with over 20 scientists at 10 different institutions. I learned so much about the research that goes on, and the hope is to share that with you all. And we're working on some of the first media that will air live right now to kind of close out the stream. But yes, so that's a little bit of the background of the motivation. And Virginia was there the whole way. Miriam Nielsen was there the whole way, supporting, which was just such a pleasure. And we did something crazy and we pulled it off, and it's so great to be here and now seeing all the speakers fueling the mileage of these last 2 days, and now to finally be here on the stream is just an honor. So it's awesome to be here.
So I want to make sure you viewers know, the live stream, we spent every spare minute asking you to call your representatives, but you can also write to your representatives, and everything we know about what moves members of Congress to act, what actually makes a difference in what happens on Capitol Hill, is that letters and calls can matter in different ways. Letters are such tangible ways for people, you can pass them around, you can gesture to them, you can bring them to the floor and wave them around when you make some kind of legislative decision based on a quote from something somebody wrote in a letter. So we've been along with the walk urging people to submit letters, and we printed them out and actually handed them to the members of Congress today who were there to greet us. We had 250 printed out. We have some more that we are going to print and get to Capitol Hill on y'all's behalf. And so again, I want to emphasize that the impact of this community from last year to this year grew in part because we knew that y'all would jump in and would be here to meet that goal with us. Syl, all that stuff said, a little bit more serious tone, I want to turn it back to you in the walk. Did you prepare beforehand for your 12 days of walking? Can you prepare beforehand for your 12 days of walking?
Oh, that's a great question. My whole vibe with the whole walk was it would be like a public performance. So was I the most trained for it? Probably not. But I feel like tennis ball was crucial to keep my feet loose every night. I did a 20-mile walk around Manhattan the weekend prior, and that was pretty fun. So I'm like, okay, maybe I can do this. But I think the hardest part actually was turned out to be logistically coordinating with all these folks to set up interviews and handing out stickers. I was on my sticker grind set, handing out all these weather and climate stickers, striking up conversations with folks about, the research that I do, that my colleagues do, and also hearing about the work that they do and the types of weather and climate research that actually matters to them. So I guess to answer your question, physically, I thought of it as like a public performance, and that's the public art or public theater. There's a chance of things going wrong, which is kind of exciting. And I think logistically coordinating with speakers, that was very difficult. But luckily we had so many brilliant people we were able to coordinate with and meet up with. So it was just I'm exhilarated. Yeah.
Syl, someone says, I hope your joints are okay after that. I know we joked a lot about how you could not get injured because Congress was waiting for us to arrive on a particular date and time, also timed to match up with this live stream. Are you okay physically?
Yeah, shocking. I actually felt better every day. And actually the second to last day ended up doing a double marathon. So I did 52 miles 2 days ago. Which was my longest day by far. So shocking. I think I kind of built up to it, and then I think a little bit of luck as well. But yeah, I'm feeling great. I probably feel terrible tomorrow. It's up till like 3:30 editing videos. So I'm like, yeah, it's gonna be a long sleep for me coming up.
And I know you said you were handing out stickers. Who were you handing out stickers to? What was that like?
Yeah, so I think I took a class actually about the art of trading with people, and I feel like it'd be like obviously my interactions, I was trying to extract something from folks as like I want to hear what you care about weather and climate. So for me, I felt like it was really handy to have a sticker I could hand out to. Someone commented, "Please take a break." All right, I will. Anyways, the point is, I felt like it was really good to have an item to thank people in return for stopping to chat. So I think my strategy was to try to, open up with like, "Oh, do you have a glass of water or something? Or can I buy a Gatorade or something?" And then from there, it was kind of a small talk. I crashed like an American Legion because I saw they were like all eating food outside, and I was like, in the doorway, and I was like, "Oh, hey, just wondering, does anyone have any water?" And then exchanged some stickers, got talking about ice nucleating bacteria, which I love. And then, we're talking about the types of storms that hit that area. They ended up giving me a full meal to take on the way and some water. So that was just, that was a really cool interaction. Kind of stochastic random interactions, which were really, really meaningful along the way, in addition to the planned interactions with people. So the scientists that we coordinated with. Yeah, exactly. So I think hopefully that answers the question.
I think it does. I'm sorry. I feel like I've been having a little bit of connectivity problems here, but I heard the answer to your question. You've got another one. What was your favorite day?
Ooh, that's such a hard question. I think every day was so unique and chaotic. I mean, Virginia, as well as anyone, how chaotic and adventurous every day was. One that stood out, it was Jonah, who you've probably seen on the screen a lot, joined me for a day and brought a ukulele. That was really fun to jam out to a lot of tunes on the side of the road. And then also we had a really nice moment at the end of the day where we stopped by a park and put our feet in the cold stream water. There's like this beautiful little river. I can't remember where we were. I think we were in Delaware. And that was like a really fun moment. It was like, okay, we're in the shade after a hot day with our feet in the stream, playing all sorts of tunes. That was really, really fun.
Yeah, I love that. Let's see. Other questions we have. So I think you were tracking in Strava. Is that right?
Oh, yeah. Sorry, I'm reading the comment about Jonah, and yeah, I love it.
So someone asked, do you know how many steps you took, like a day? Or do you just know the mileage?
Yeah, I mean, I can estimate, because I think it seemed to be around 50,000 per marathon. So it'd be 50,000 times 10. So like maybe 500,000 roughly, I think. Yeah, steps. There's quite a few. And yeah, I'd also, one of my friends who kind of is a good influence on me, in my opinion, who also does long walks, just coincidentally happened to walk 63 miles in a day, the same day I did 50. And I called him about it at the end of the day. I'm like, what are the odds we both just decided to walk all day? So he also, our step totals combined were probably insane for that day. Yeah.
Cool.
Shout out JLD. That's my friend.
Someone asked where you can see videos about the walk. We've been putting them up on the live stream Instagram and as YouTube shorts, less on BlueSky because that was me and I was running around trying to make sure the walk and the press conference today went off well. So check out our YouTube shorts and our Instagram channel. Okay, let's see. And then I see that someone asked in the chat, is there a way to get a list of all the contributors and speakers who are on BlueSky? I could probably put together a starter pack for you about with everyone who spoke on the live stream last year, this year. So let me think about that after I've had some sleep. But the technical answer is yes, it can technically be done. Okay. So let's see. So someone asked, what's your favorite part about New Jersey specifically? I'm wondering if you have like a kind of, this is what, because you went through New York, New Jersey, Pennsylvania, Delaware, Maryland. Do you have like a, this is what each state felt like in one sentence? I know that's such a challenge, but can you do like a 5-point vibe for me of what the states were like?
Yeah, I would love to. That sounds fun. Let's see. So I guess starting off in New York, right? You have, we walked through Times Square, very energetic, the city that never sleeps. And then down into Staten Island. That was like really great walking in my opinion, because there's a lot of sidewalks and there was a lot of pedestrian friendly areas and places that are built with intention of walkers. So very much shout out there. When I crossed into New Jersey, I was very pleasantly surprised to see a lot of the similar vibe, and also a lot of greenery that I feel like I hadn't known about in like my very not rigorous understanding of the New Jersey landscape. So for example, there was like a stretch of Jersey as I approached into the Princeton Geophysical Fluid Dynamics Laboratory. That was just like this gorgeous vegetation, lush forest everywhere. There were some beautiful parks. And then right after that, just this awesome canal trail. I don't know, I'm trying to remember the exact name of it, but actually that's when Andrew Williams joined me for a day, and we walked on that. And it was also Tim Merlis kind of showed from Princeton, showed around that path, which is just beautiful and pristine. So I'd say that was probably my favorite part. And then some of the interviews with like Nader Givenchy near the Institute Pond in Princeton is gorgeous. And then as I made my way down towards Trenton, crossing the river, a couple rivers around there were really, really pretty. And then, yeah, okay, you asked about all these states. There's so many states to remember.
That's okay. So we can actually pause on this because I'm looking at the time, and we are getting late breaking news that we are going to be able to show y'all a video about the walk and a little bit about kind of the results of everything with the press conference that we did this afternoon. And so I'm so sorry to cut you off, Syl, but I do want to make sure that everyone knows that we're working on getting that for y'all to share. I want to bring us back to, again, the impact of this walk for everybody that's watching, waiting for this video like we are. We're so excited. Last year, when we did the live stream, 180,000 people watched, and we logged 30,000 calls to Congress. This year, the addition of the walk really let us pull in members of Congress. And we had the head of the Ocean Caucus in the House. We had the only meteorologist who's ever been a member of Congress. We had the ranking member of a science committee in the House with us, and they were fired up. I think that we gave them some fuel to take back, to use to fight. And so the impact right now of what y'all have helped us do this year is a little harder to just rattle off in numbers, because we're hoping that it can be something that we can point to that happens on Capitol Hill, which would be amazing. So I just want to make sure y'all know that it's harder for us to express just the simple numbers at the moment, but we would like to express them, and we are excited to see what happens. We do, before, oh yes, sorry, someone is requesting backstage maybe that some things come on. And so I just want to say, yes, sorry, there are so many messages on my computer. If anyone's trying to get in, you can totally jump on. I do want to share with y'all in the chat, I think we have a QR code ready for you to tell us your opinions for next year. In case there's anything you really want to see, in case we feel compelled to do this again next year. If we can all just hang out with each other, that would be great. But if we feel like we are still pushing for change next year, is there anything that you want to see that we could do to make this more interesting for y'all? So I think if we could bring up that QR code with our with our graphics team. It should be somewhat obvious where to point your camera for your phone. So y'all can let us know what you think. Thank y'all so much. We have referenced what you said last year with the exit survey, and it helps us make this. Oh, I'm seeing I'm seeing a chat backstage. That little heart at the bottom is supposed to open, and you can see an Argo float inside.
That's so cute.
I know. So yes, please do take the survey. We designed it to be very, very, very quick for y'all. I do want to invite Andrew back up onto the stage so you can help orient me with what is going on, because I don't want to keep. Oh, there it is. Oh, look at that Argo. What does it say? Argo float, my beloved. Amazing.
One of our organizers found one of the beautiful Argo memes that was made either I think this year or last year, but
fantastic. Okay, Andrew, how are we doing on the video? Are we not quite ready still?
I think we're not quite ready on the video, but someone can just let's put that sorry, give me 1 second.
Yeah, sorry there. So
Okay.
For y'all on the stream, this is usually we try to cover for these moments where there are so many, all those organizers that were on your screen earlier, we are talking to each other in several different places, and everyone, we call it decentralized lovely chaos. Everyone's got their own pieces that they specialize in, and somehow we all come together and make it work, which is great. And except that sometimes it's hard to keep track of all the messages. Claire, would you like to come up and join us?
Yes.
I'd love to add Claire, just because Claire was one of the people who was a really key organizer for this event as well, and was not able to be on in the big mass thing earlier.
Thank you for having me up here now.
Claire, you weren't able to join us on your own schedule because you were giving a keynote at a talk or at a conference, right?
I am at a conference this week doing science.
Yeah. Have you given your keynote yet?
I have.
Was it amazing? Do you feel like a queen?
It went well. Thank you.
Yeah, I'm so excited. This is so great. Okay. Everyone is growing right before y'all's eyes in the comments. Okay. Claire, you are getting many shout outs in the chat. I hope you see these.
I know. I see them. I don't have the cloud again on me right now, but the cloud again sends love to all of you in the chat.
All right. It looks like we are pivoting to trying to get
Who for day one joined me, but now I'm kind of out here roughing it in the rain.
Sorry, just This is the video. Sorry.
You can take all of us down so everyone can just watch together.
All right.
Enjoy the video, live stream viewers.
Hey everybody, my name is Syl, and I'm walking 250 miles from New York City to DC, starting right now with these steps. Along the way, I'll be talking with climate and weather scientists along the East Coast, hearing about the research they do and urging that it be prioritized. I had a great crew for day one join me, but now I'm kind of out here roughing it in the rain. I'm in my final mile here of New York, out on Staten Island, and I gotta say, New York, you kind of did me dirty. It's been raining this whole time, but we knew it was gonna rain because we have these great forecasts. And we have these great forecasts because the US federal government has invested in science since before we even knew forecasting was possible.
We've come so far in our ability to warn people of what's coming their way. And we know that if we can continue or even increase funding for that data and research, we will get even better and keep people more safe and more prepared. Any loss of funding is a risk to that.
Climate science is so important, and the US and public funds have been at the forefront of climate science for decades, and we need to continue delivering so that we can ensure that communities are protected.
So what we're talking about here is decades of stable government-funded research that allowed the construction of these comprehensive models of climate and of the Earth, and that allowed for these climate forecasts made over decades and decades before they were able to be confirmed, and that predicted salient aspects of the world that we see now.
Oh man, the hardest part is seems to be just to keep walking. I'm starting here day 3, day 5, 6. Welcome to day 8, day 11 coming to a close. Excited to be approaching into Washington now. Feeling a lot of gratitude for everyone who's made this project happen. In my own personal time, I took 12 days off to walk and talk with scientists. At every stop, I met scientists passionate about the work that they do, but also concerned about their and our future.
What's really affected me in my research effort is the lack of ability to respond to new funding opportunities. So most of my funding is from NASA or NOAA. They have called for proposals. We submit, we win some, we lose some, but those calls, those opportunities have just disappeared.
Right now, I'm taking my final steps to deliver over 200 letters we collected from concerned scientists throughout the walk, directly to members of Congress, sharing why places like the National Center for Atmospheric Research are so important.
I think a lot of people don't realize that NCAR's supercomputer is available not just to NCAR scientists or the government, but this is a resource that's open to all institutions across the US and is used to better understand weather and climate for all Americans and actually all across the globe.
We rely on these federal organizations, particularly NCAR, GFDL, GIST, to do a lot of the model development. So making sure we have access to those climate model simulations, that those simulations are being developed and analyzed is critical to the work that we do and pushing the science forward. And a lot of that work is done at universities, but it relies on access to those federal resources.
We need to maintain strong and stable funding.
Historically, we had 200 employees at GFDL developing these models, and recently we've lost about 20% of our staff. So we're down to about 160 employees within our building. We've lost really important expertise in a number of different areas, which means that we're spread thin and we can't do the same quality of science that we used to be able to do.
Now, after walking 250 miles from Central Park to Capitol Hill, I would like to invite to the podium Syl to walk just a few more yards. Please come up and officially conclude your walk for science.
On my walk, I talked with Boy Scouts, firefighters, cashiers, hairdressers, driveway basketball enthusiasts, you name it. I walked not only to celebrate this remarkable scientific achievement, but also to bring awareness to the risks that the agencies that make this research possible face in light of budget and staffing cuts. So I'm speaking from my own personal opinion here. Americans know the value of U.S. weather and climate science, and it's time that these values are reflected in our government. Thank you.
Hey everyone. I may have cried then. I think that was really beautiful. And I think that, yeah, I just want to say thank you to Miriam for being the genius who was behind all of this video editing throughout the whole process. Any shorts you've seen, a lot of that has been Miriam's heart, blood, sweat, and tears behind the scenes. And so, Miriam, we love you. That was beautiful. I had to prep these things, what I'm going to say next, because this has been the part that I've been dreading for the past couple of weeks, is just how do we say goodbye to something like this? I don't think any of us are truly ready for this to be over, but it's time for us to say goodbye. And as I've been sitting around, like during the prep, during the live stream itself, in the conversations behind the scenes with the organizers, one of the words we keep going back to is community. And I'm so proud of the communities that have showed up in this stream and have formed as a result of this stream. The organizers, the speakers, the walkers, the audience, and the community that we built together by doing this and by coming together like this. Together, we've not only elevated the field of weather and climate science and drawn important attention to these cuts, but I think almost more importantly, we've elevated and we've strengthened each other at a time where I think that community is really one of the most important things that we can build right now. And this renewed strength, this belief in the power of our communities and our actions together to make real change happen is what I'm going to be taking with me as we step away from this stream. I have so much love, so much gratitude in my heart for everyone here, all the people behind the scenes. I see staring back at me, all of the people who are on the StreamYard throughout this whole thing. And I hope that we can come together again next year under better circumstances to build each other up and share in this collective wonder of our remarkable and our precious planet together. Thank you so much for watching. Thank you once again to all the organizers, the hosts, the speakers, the chat mods, the audience. I think it's fair to say that we all need a nap right now, and I need a stiff drink. Thank you again for everyone for joining us for these 50 hours. Let's keep fighting to save America's forecast together. And remember that we only got one planet. Let's protect it. Thank you so much. I'm going to put the beautiful Blorbo thing back up. If you can fill out our QR code, we'd love that. Thank you. 50 hours.